Now, already I've actually shown you how the CBOW actually works, continuous bag of words. And I've also showed you that how the neural network gets trained, right? Now, what is the difference between CBOW and skipgram? What is the difference between the architecture? It's very simple, guys. Right now, just focus. I'm going to take the same data set over here. Let's say that Tiny company is related to data science. I've written over here, right? And with respect to this, you can see that I've created my input and output. Now, if I am using skipgram, then the thing that is going to change is that everything will be same. Let's say that I've taken the window size as this. So if I probably go ahead and show you, now what will happen is that before the input was this specific test and the output was this specific test. Now with the help of skipgram over here, the initially let's say that if this was input, now this is going to become the input, and this will basically be the output, right? And this is with respect to window size is equal to 5, right? Window size is equal to 5. All the steps will be same. Only what we are doing is that we're changing the input and we're changing the output. Before the input was this all text and the output was this. Now what will happen is that entirely when we are creating this neural network, now in the input, let's say that I have this is word, related word, to word, right? So in the input, I'm going to basically have input layer with 7 vectors that will be going. Why 7? Because if we probably see this, our vectors, how many number of vocabulary, what is the vocabulary size? 1, 2, 3, 4, 5, 6, 7, right? So initially in the input layer, I'll be giving input, which will be basically having 7 vectors, 7 dimension vectors. And then in the middle, I will basically be having my window size vectors. So window size is nothing but 5, 1, 2, 3, 4, 5. Just understand this, these are just nodes, okay? And in the output, you can see that I'm having 4 words, right? So everything that is present with respect to this, right? Similarly, this will get constructed over here at this point of time. So over here in the output layer, you'll be able to see that I will be having 1 word, 2 word, 3 word, and the 4th word. So this is what is the kind of output we will be getting. And again, here it is very much simple because every one will be like 7 dimension over here again, right? So I hope you're able to understand. We just change the direction with respect to this, right? So this will be my input layer. So here you can see that we will basically be having a 7 cross 5 matrix with respect to the weights, because weights initially be randomly initialized, right? And then we need to train this, right? And then we will be having with respect to this all, I'll be connecting here to here, here to here, and this will basically be a 5 cross 7 matrix with respect to weights, and then this will be 5 cross 7. Similarly, over here you'll be seeing that this will be 5 cross 7, and below one will also be a 5 cross 7. But in with respect to that, you can see that initially when I give the input is will be the is vectors will be going over here, and as you know that is the third word, so this will be going like this, right? So 0 0 1 0 0 0 0. So this is the vectors that will be going over here, and again since my window size is 5, over here you'll be able to see other vectors that will get initialized. Randomly, this all will be connected with weights. So 7 cross 5 weight matrix will be created, and with respect to this, how forward propagation will happen. And obviously, you know that if you probably know ANN, right, what all things happens in between the hidden layer. The input weights is getting multiplied by the weights itself, and then a bias is added and an activation function is applied on top of it. In the output layer, we basically apply a softmax function. Softmax function, so that we compute it with y and y hat. Y hat is the predicted one. Y is the real data. In this particular case, this is my y. Sorry, this is my y. Like in the first case, y is ineuron. So ineuron, whatever things will be there, whatever vectors will be there, here you'll be initializing it, right? So here I basically apply a softmax function. Let's say with respect to ineuron, my y is nothing but 1 0 0 0 0 0 0 0 7 zeros, and then y hat will be computed since we apply a softmax over here, right? So y hat will be something, right? Some values over here, and then what we do, we calculate our loss function, and we make sure that we keep on doing the forward and the backward propagation unless and until all the loss function decreases, right? The loss value decreases, and finally you'll be seeing that whatever is connected, like this particular word will be shown in the form of 5 vectors. This word will be shown in the form of 5 vectors once the loss is completely minimized. So same process. You should definitely know how the ANN actually works, how the optimizers actually work, and this was just a brief idea about skipgram, right? Now, how can we improve this? Or the basic question is that when should we apply CBOW? CBOW. So the question is, when should we apply CBOW or skipgram, right? The simple thing is that according to the research, right, whenever you have a small data set, small corpus, we can definitely go with something like CBOW, that is continuous bag of word. If you have a huge data set, you should definitely go with skipgram, and that is proven in many research papers. I'm just giving you the direct observation out of it so that you'll be able to do this. Now, let's say if you want to increase CBOW or skipgram, how can you basically do it? One thing is that you should increase your training data set. Increase the training data. That basically means the more the training data, the better the accuracy, right? Increase the training data. The second thing is that you can also increase the window size, which in turn leads to increase of dimensions, increase of vector dimensions. This is super important. Okay, so here I'm saying how to improve CBOW or skipgram. So this is what you can basically do. Increase the window size. Okay, this is super important. Increase the window size. I'm again going to take this separately or forget it out. So over here again, let me write this. We have to increase. We can also increase the window size. Instead of having 5, I can make this as 100. You know, so obviously with the increase in the window size, increase the window size. If you are increasing the window size, that basically means the vector dimension is also increasing, right? The vector dimension is also increasing. So when we keep on increasing and try it, you'll be able to see that we'll be getting better performance. So this is also you can basically use. You can increase it. Now when we see in the next example, right, we'll be using a pre-trained model with respect to Google. So Google word to vec, right? Now this is basically trained in 3 billion words. I guess it is 3 billion words. 3 billion words. And it is going to give me a feature representation of 300 vectors. Sorry, 300 dimensions. That basically means, suppose if I have a word cricket, okay, since cricket is always there in the news, this 3 billion word is from the Google News, right? And Google is a very big company, guys. But then this amount of data is very much easy. So what they're going to do is that if we give a word called as cricket, then it is going to basically convert this into a 300 dimension vectors. Okay, vectors. This is super important. 300 dimension vectors. Okay. So I'm just going to write it as 300 dimension vectors. And this all example I will try to show you when we use this. What we'll do is that in the upcoming session, we'll try to use a pre-trained model also, and we'll try to also make sure that we train a new data set from scratch with the help of word to vec. And that we are going to basically do with a GenSim library. Okay. So yes, this we will be doing in the next video. So I hope you have understood both the architecture. One is CBOW and one is the skipgram. Only the thing that you really need to know is that you need to have the knowledge of ANN or a fully connected layer neural network. If you know that, it'll be very easy to understand. So yes, this was it from my side. I will see you all in the next video where we discuss about how to implement word to vec. Okay. So yes, I will see you all in the next video. Hello guys, so we're going to continue the discussion with respect to word2vec. In this video, we're going to discuss about the advantages of word2vec. Now, already from our previous techniques, like bag of words, TF, IDF, we have already seen that what were the main problems. See, initially, before we used to get a sparse matrix, right? Sparse matrix basically means we used to get a lot of zeros and ones or decimals or zeros. This kind of matrix we used to get, right? And obviously, what is the problem with sparse matrix? It leads to overfitting. But now, with the help of word2vec, you are actually being able to get a dense matrix, right? So now you'll be able to get a dense matrix, and this is only possible because of word2vec. That basically means you will not have many zeros or ones, you know. So this was the first amazing advantage with respect to word2vec. And again, if you have a dense matrix, again, machine learning models will be able to train in a better way, right? Coming to the second point, right? Because we have already seen with respect to every word, we are getting a separate dimension of vectors, and we're also able to find out the similar vectors also. Now, the second thing is that based on the similar vectors, before semantic information was not getting captured. Now, semantic information is getting captured, right? Info is getting captured. Now you will be able to find out the similar words with the vectors itself, comparing the vectors itself. So semantic info is getting captured now, right? Before, with the help of techniques like bag of words or TF, IDF, there was some amount of semantic information getting captured, but not much. That basically means if you really want to find out a word, let's say there is a word like honest, right? And you want to find out a similar word, or you want to find out how similar this specific word is, so that you will be able to do with the help of word2vec. Now, honest and good, I think it is almost a similar word. We'll also be able to find out the cosine similarity with respect to this, and that is what I will be probably showing you as we go ahead, by seeing the practicals of word2vec by using pre-trained models, and again from scratch also we'll try to see it. So coming to the third one over here, now you don't have to actually worry about vectors becoming bigger, because before, with the help of bag of words and TF-IDF, we are completely dependent on the vocabulary size, right? Vocabulary size. But now we are not dependent on the vocabulary size. So over here you'll be having a fixed set of dimensions. Fixed set of dimensions. Now, if I probably take an example of Google pre-trained word2vec, right? Google word2vec, pre-trained word2vec, there you'll be able to see that we'll be having only 300 dimensions, and it has been trained in huge data, huge data. So obviously, this again solves a very big issue. Before, again, we used to get a very, like if the vocabulary size is huge, that many number of vectors we used to get. Now, no, fixed set of dimensions with respect to vectors, we are able to get it. Okay, so this is also a very important thing. Coming to the next one, which is called as out of vocabulary. Now, out of vocabulary, there is hardly any scenario that you will be able to see that some words may be outside the dictionary or outside the corpus itself. With respect to out of vocabulary is also solved. Why? Because now we are capturing all this information like semantic info and all, right? We're also making sure that because we represent every word with some feature representation, right? So that is also out of vocabulary is also solved with respect to this. So these are some of the advantages of word2vec, and again, right, it will definitely perform well when compared to the bag of words or TF-IDF model. But yes, this is a good, good way. Basically, we'll also show you that how we can actually solve a text classification with the help of word2vec and all as we go ahead, right? So this was in short the advantages of word2vec. In our next topic, I'm just going to show. I'll try to show you one more very important topic, which is called as average word2vec. Super important topic, because if you really want to solve any text classification problem statement, we really need to also use average word2vec, and that is what we are going to see in the next video. So yes, this was it from my side. I'll see you in the next video. Hello guys, so we are going to continue the discussion with respect to NLP, and in this video we're going to discuss about average word2vec, a super important topic again, because just with the help of word2vec you'll not be able to solve the classification problem. You really need to perform something called as average word2vec. Let's take a simple example, and I'll try to show you. Right now we'll just discuss with respect to theoretical intuition, but as we go ahead we'll be discussing about practical part also and how we can implement average word2vec also. So over here I have my text data, the foot is good, and output is 1, 0, and 1, and you can see all this on my documents. Now, as you know that with the help of word2vec, what we do is that we take every word and we convert that into vectors. Let's say that I'm using a Google pre-trained model. Okay, I'm using a Google pre-trained word2vec model. Pre-trained word2vec model. Now in this Google pre-trained word2vec model, what I'm actually doing is that over here you can definitely see that. Okay, so if this is my sentence, the foot is good, right? Now the will get converted into some vectors. Okay, and when I've already shown you that with respect to feature representation, we will be getting a vector of 300 dimensions. So let's say this is the vector of 300 dimensions. Okay, so this the will get converted into 300 dimensions with respect to this. Okay, the will be there. Now come to the next word, that is food, right? Food will also get converted into 300 dimensions.
नमस्कार दोस्तों, स्वागत है आपका अपने YouTube.
Every word that is present over here, like is, will also get formed in 300 dimensions, and here also all these words will get converted into vectors with respect to this many number of dimensions. Okay, perfect. So till here I think you're superbly clear, because we have already discussed about all these things in our previous session. But now you need to understand one thing, is that when we have this kind of sentences, and if we are basically writing this many number of dimensions, basically this many number of vectors are there. Let's say this is my 300 dimension vector, which is basically getting converted for the food and this. In the real world scenario, I should be converting this entire sentence into vectors, right? But here you can see I'm getting vectors for the also 300 vectors. For food I'm getting separately 300 vectors. For is I'm getting 300 vectors, and for good I'm getting 300 vectors, right? 300 dimension vectors. Now this is the problem. At the end of the day, for this entire sentence, let's say if I'm getting a 300 dimension, for this entire sentence, let's say this is my sentence 1 or document 1, my main aim should be that I should be getting only one 300 dimension with respect to this, so that I can take this as an input, and this will basically be my output, and I can basically train my model, right? But here you can see that since we're applying word2vec, every word is basically getting converted into a separate 300 dimension vectors. So in order to solve this, what we do is that we take all these vectors. And we find the average of it. Once we find the average of it, then we try to write that particular vector over here for this entire sentence. And then this vector will be considered for this entire document or sentence. Similarly, the second vector also is there. We'll go ahead and calculate the average of it, and we'll write it over here. Similarly, like this, every vector will basically happen, right? For every vector, all the word vectors, averaging is basically happening. And that is the reason we say average word2vec. Okay? And why this will work? Because see, at the end of the day, you'll be seeing that we just require the vectors for this entire sentence. And right now, we have for every word a separate 300 dimension vectors. So if you're trying to take out the average of all this particular vector, and if we try to write down as one vector, and this will also be, the length will obviously be 300 itself, right? This will be 300 dimension itself. But now, with respect to this particular vector, I will be having my output. I can pass it to my model and get trained with respect to this. So at the end of the day, what happens is that if I'm having a sentence like this, after applying average word2vec, I'm just going to get, let's say if I'm using the pre-trained model, I'm going to get a 300 dimension vector, which will be all this particular average of all these particular vectors itself, and all this will be over here, and I will be getting my output variable, which is already over here. And similarly, this will happen for the second word set document, third document also. So average word to vec basically says that, okay, we're not doing anything. Whatever vector is getting converted, I'm just trying to average out each and every vector with respect to that, right? So here, let's say the is having 300 dimension vector, put is having 300 dimension vector, is having 300 dimension, what is having 300. For every line by line, all the vectors, I'm just averaging that out, and I'm actually finding out a value. And why we are doing this? Because we really want only one specific set of vectors for the entire sentence, right? So this is what average word to vec is basically. And for any text classification, we basically need to solve through this specific way only. Now, in upcoming tutorials, what I'm actually going to show is that I'm going to basically use a library which is called as gensim, okay? And there is also a library separately which is called as Glove. But if you probably understand gensim, you'll be able to do everything. So first of all, we will go ahead and we will see with respect to a pre-trained Google word to vec. And then in the second instance, what we are going to do is that we're going to train a word to vec from scratch. From scratch. That basically will take a data set and we'll try to train a word to vec model. And again, with the help of gensim library, we'll be doing it. So I hope you got an idea about average word to vec. At the end of the day, why we are doing this, because for the entire sentence we want some vectors. And since we're combining all this particular word, the semantic information will also be maintained, right? So yes, I will see you all in the next video. Hello guys, so in this video we are going to basically see the word to vec practical implementation. I really want to show you some Google pre-trained models and basically give you an idea like how word to vec creates a vector, right? So for this tutorial I'm going to use a library which is called as gensim. So let's go ahead and let's install this particular library. So you just need to write pip install gensim. So here you can see that requirement is already satisfied. And what I'm actually going to do is that I'm going to import this, import gensim, and from gensim.model I'm going to import word to vec and keyed vectors, okay? And I'll talk about this, why these two libraries are specifically required. Now one very important thing for this, as I said that to show you the practical implementation of word to vec, here I'm going to take a Google pre-trained model. In the upcoming video I will try to show you a different model which can be trained from scratch, but here I'm going to show you a Google word to vec pre-trained model and what this particular model is all about. So I'm basically taking a word to vec Google News 300, okay? And this is basically a pre-trained vector trained on Google News dataset about 100 billion words. The model contains 300 dimensional vectors for 3 million words and phrases, right? These phrases were obtained using a sample data driven approach and distributed representation of this and all the research paper and everything is basically given over here, okay? So this same model we are going to use and we're going to see that how it can easily create a vectors whenever we give any kind of words. So in gensim, you have something called as API, right? So there is a library called as API. So you just need to write import gensim.downloader as API, and you just need to write API.load and basically the model name, right? So the model name is nothing but word to vec Google News dash 300, okay? Now once you do this, all you have to do is that when you provide any word inside this WV variable, which is nothing but this is an instance of the specific model, it will try to give you the vector. I'm not going to execute this line of code because I've already done it because the model size is 1662.8 MB, right? So it will probably take some time for you all to download. So I have already downloaded this so that I can record the video directly. You can just go ahead and download it. Now let me go ahead and see that how the king vector look like, okay? So this is basically the king vectors, how the words basically converted into vectors, and the dimensions that you'll be seeing, right? How many vectors are there? As said from here, right? We have 300 dimensions. So this is what we're getting. This entire vectors you'll be able to see will be having 300 dimensions. So if I probably use this vector underscore king dot shape, right? So if I execute this here, you'll be able to see 300 dimensions, right? So with respect to this, you use any kind of word, you will be able to get some kind of vectors. Now let me give you some of the example, okay? Suppose I make over here, and for this particular vector, what all things I use this WV variable, which is a word to vec object, right? All I have to do, I have to give this and give any word of your choice. Let's say I want to give cricket, right? So if I give probably cricket, you'll be able to see that the vector is automatically generated. So here is again the vector which you are basically getting with respect to this particular shape, that is 300 dimension. Now this WV variable, right, which is a word vector, it also has some of the functions. You can actually use something called as most underscore similar. Now let's say that I've given this most underscore similar. I'm saying that from if I'm giving this cricket word, right, which is the most similar word present in this entire corpus, right, and I'm actually going to use the same word to vec object, and I'm going to find out all the words. So if I execute this here, you'll be able to see the most similar with respect to cricket. It will first of all try to convert into a vector, and then it will probably check whether that vector is being able to see any similar kind of words or not. So these are all the words that is similar to cricket in that specific corpus. So you have cricketing, it is having like 0.83 similarity, 0.83% similarity. Then cricketers 81% similarity. Then you have test cricket. Here you can see 80% similarity. 20 cricket, right? You have 80% similarity. Then you have cricket. Then you have cricketer. All these things are they are showing some kind of similarities with respect to this Google News feed, right? Now similarly, if I really want to find out which is the most similar word with respect to happy, you'll also be able to see I'll be having words like glad, pleased, ecstatic, overjoyed, thrilled, satisfied, proud, delighted. And understand that these all are similar words when I compare to happy, right? So it is also being able to say that okay, these are the similar words when compared to the happy word, and they also being able to show with respect to how much distance. And I've already shown you how this distance is basically calculated, right? So we have a concept of cosine similarity and all. Similarly, I can also provide two words, and I can basically say that okay, how much these two words are basically similar. So if I probably execute this, here you'll be able to see WV.similarity. I'm getting hockey and sports are somewhere around 53% similar, right? Now this is very interesting, okay? I'm going to take the vector of king, and I'm going to subtract with the vector of man, and I'm going to add the vector of woman. Now let's see what will be the kind of output vectors that I'll be getting, okay? So once I do this, in short, what I'm doing, I'm subtracting king minus man plus woman. Now, obviously the answer should be queen, but I really want to prove you through the vectors itself whether we are able to get the queen or not. So here I'm going to execute this. I got my vector. So this is my entire vector. So this is my entire vector, and again this vector is of 300 dimensions, okay? So this is my entire vector. Now what I'm going to do, I'm going to use WV dot most underscore similar, and I'm just going to pass this entire vector over here. So once I execute this, here you'll be able to see that. See, king is the first. Obviously, king should be the most similar vector, but here I'm getting queen, monarch, princess, crown prince, king, sultan, queen resort. But here you can see that the most similar word after king is queen. So the kind of vector we are getting after doing all this particular subtraction matches more towards the vector with respect to queen, right? And this is what we are able to get with the help of word to vec. Try to use this, guys. This is an amazing model altogether. You'll be able to see that you can actually use this model itself. You can actually use word to vec Google News 300, which will be able to solve many problem of yours. And this is just a brief idea about a pre-trained model. How a word to vec pre-trained model looks like. You can also take your own text and train it from scratch. But again, there's a different process for altogether. And this entire thing I've executed in Google Colab because the model size is quite huge. Okay. So in the upcoming videos, what I'm actually going to do, I'm also going to show you a word to vec technique by using gensim where you can train the model from scratch. Okay. So yes, this was it for this particular video. I will see you all in the next video. Thank you. Hello all. So guys, we are going to continue our discussion with respect to natural language processing, and this is our first classification project that we are basically going to do with the help of NLTK and with all the techniques that we have already learned, right? Like bag of words, TF, IDF and all. And we'll also, like after converting the word into vectors or sentences into vectors, we're also going to train with the model. So what are the things we are going to do over here? Let me just give you a brief idea about it so that everybody will be in the same page. So here we are basically going to apply bag of words, TF, IDF, and then we are basically going to apply a machine learning algorithm to do the classification of the spam and ham, right? So all these things we are going to do. And remember, the data set is same, and I'll be showing more examples with respect to different data sets also, and there will be also many assignments that will be given to you so that you can also practice. So over here, you can see that I'm having this particular data set that is called as spam classifier, spam collection and all. So what I'm actually going to do over here is that I'm just going to give that same path, spam classifier, SMS spam collection, and this is the file that I have. And these all things I've already repeated. Again, I'm repeating it over here. So these are my entire messages. You can see I have label and messages over here. So in label, you have ham and spam, whereas in message, this is basically your email body, right? We really need to predict that which email text actually is a ham or a spam. Now, initially, we have already shown you that what all things we'll do. We'll do data cleaning and pre-processing, and for that, we require regular expression and LTK. And stopwords. Stopwords we really need to remove because some of the words will not play a very important role, right? So this is already downloaded. Then I hope everybody knows what is port stemmer. Port stemmer is basically used for the bag of words itself. So I'm just going to execute this, and this is all the repeated code which I've already taught, right? And this is the entire cleaning process of the text. Apart from small a to z and capital A to z, I'm removing all the special characters by a blank, right? And this I'm applying to every messages over here. I'm loading the messages, and then I'm splitting it, and then I'm applying stopwords. If the word is not present in the stopword, then only I have to do the step. And then finally, I'm joining all the reviews, and it will be available in my corpus. So these things already have done it, right? But after this, what we're going to do is that we're going to apply a machine learning algorithm. And the same steps I will also try to show you with the help of a TF-IDF. So this will take some time based on the size of the text. And let's say if your data set is quite huge, I would suggest try to do it in cloud format or cloud in the cloud itself. Like Google Colab is there as an example, or if you have some virtual machines, that also you can basically use. Now this is my corpus. So entire corpus is basically present over here. Perfect. Now let's go ahead and create the bag of words. For creating the bag of words, I just need to import from sklearn.featureextraction.text import count vectorizer. And over here with respect to the count vectorizer, I'm saying that let's take the maximum features to 2500. And here I also want to make sure that I give my n-gram range 1, 2 so that I take a combination of two words. Okay. So this will probably help us to improve the accuracy and all. But I'm just trying these things right over here. Now this is my count vectorizer. And I will be doing cv.fit_transform corpus, and I'll store that in my x. Okay. So this is got executed, and this is basically my x. Okay. X, and probably if you want to see the vocabulary, so you can basically write cv.vocabulary also, and here you'll be able to see the vocabulary, and wherever there are two words, that index will also be there within that 2500 words. Perfect. So till here, what we have done is that we focused more on the independent feature. If I say X, this is basically my independent feature, right? So this is my independent features. Now, whenever we try to solve a machine learning problem statement, we also need to focus on the output features or the dependent feature. So dependent feature or the output feature, we already know what it is, right? It is basically our label text, right? So this label. So what we are basically going to do is that I am going to take this label, and right now this is still in categories. I'll convert this into zeros or ones or ones or zeros. Okay. So let's go ahead and let's see how to convert it. So here I'm just going to write y. I'm just putting it as a variable. Y is equal to get underscore dummies, and in get underscore dummies, I'm just going to write messages of label, right? So all these things will basically be there, and here you'll be able to see once I execute it, you'll be seeing if there are two labels, then I'm actually going to get 0 as one column or first as another column. So here you can see ham and spam. These are basically two categories. Wherever there is a ham, I'll have 1. Wherever there is a spam, I'll have 0. Now, as you know that either of these two columns can be used as an output feature. Now let's just consider ham over here, right? Wherever ham is present, it will be 1. Wherever spam is present, that will be 0. So here what I'm going to do is that I'm going to basically write y.iloc, and I'm just going to write this colon comma 1, and let me just go ahead and take this all values. Okay. So in short, what I'm doing is that I'm just probably picking up this particular column. Wherever spam is 0, basically wherever spam is there, that will be 0, and wherever ham is there, that will be 1. Or I can also go ahead and basically take 0 column value. So if I probably execute it, so I'm going to just take the ham value over here, right? And this I'm storing it in my y variable. So I have my independent features. The independent features are nothing but this x values, all the x values, and I have my dependent feature that is my y value. Perfect. Now the next step that we specifically do in machine learning is basically our train test split. So here I'm just going to say train test split. Okay. And in this particular train test split, what I'm doing, I'm saying writing from sklearn dot model selection import train test split. Okay. And finally, I'll be having x train, x test, y train, comma y test. Okay. And then I will basically be showing train test split with x comma y comma. I'll just put my test size. Okay. And let's say the test size is just 0.20, that is 20%. And I'll just execute with any random state. That is not a problem. So I'm getting an error. Let's see what is the error. So test size I have to write like this. Perfect. So now I have my x train, I have my y train, x test and y test. Understand why we are doing this train and test split is that my model will basically be trained with the training data set. So x train and y train I'm going to take as my independent and dependent features. And to verify how my model is basically performing, I'll just use the test data set. Okay. Now the kind of algorithm that I'm basically going to apply over here is that I'll from sklearn dot model selection. I'm just going to import one. Sorry, I'll not use this one. So let me just go ahead and import name bias, which works very well with the sparse matrix data, right? I'm just basically going to use multinomial name bias, and I'm just going to create a variable. Okay, so the variable will be spam detect model. Okay, so this will be my spam detect model, and here I'm just going to initialize multinomial name bias. Along with that, I'm also going to fit with my x train, comma y train. I can separately write this in the next line, but I just want to perform it here itself, so that it will become easy. I don't have to write much more line. So this is my model over here, spam detect model. So this is a multinomial name bias model, and it has been already trained on x train and y train. Okay, now all I have to do is that do the prediction for my x test data and try to compare my predicted output along with the truth output, which is basically present in the y test. Okay, so here I will write dot predict. And when I predict on my x test, this is how I'll get the output. Either I'll be getting ones and zeros. This I will save it in y underscore pred. Okay. Now, in order to compare y test and y underscore pred, we are going to use some of the performance metrics, right? So I'll write from sklearn dot metrics import accuracy score, comma classification report. Okay. Now, one more thing that if I probably try to see, right? If I write y dot unique, let's see whether unique will work or not. Okay, it does not have a unique. If I say y dot shape, so it is basically having 5572 records. Okay. So let me do one thing. Let me just use this classification report and accuracy score to just see that how my model is giving my accuracy score. And here I'm just going to give my y test from a y prime. I'm going to compare this, right? So this is basically my accuracy score, which I'm actually getting somewhere around 98%, which is good. Okay. Just to verify, because we may also have an imbalanced data set. So we'll also try to verify with the help of classification report by seeing precision, recall, and all. If we see that there's a huge fluctuation, then definitely there is a problem with respect to imbalanced data set. But I've already checked it beforehand. It is not an imbalanced data set. So I'll say from sklearn.metrics, import classification report. Okay. And I'm just going to print this classification report with my y test and y print. I'm basically comparing the prediction with respect to the new data. So here you can see that I'm getting somewhere around 96, 94, 98, which is good enough, which is a good one. With respect to precision also, it is almost in the same stage. And all the accuracy looks pretty much good. So we feel that yes, this model can definitely play an amazing role altogether, right? So I hope you have seen that how we were able to train this entire model with the help of with the help of a machine learning algorithm, and we are able to see this particular accuracy, right? So yes, this was it. In the next video, we are basically going to solve the same problem with the help of word-to-vec and average word-to-vec, and we're going to train this entire model from scratch. Okay, so this is just to give you an idea. Still, there are some end-to-end projects also going to come up where we'll focus on deploying the project in some kind of clouds. Okay, so yes, I hope you like this. Just you can take up any data set, but anyhow, I'll be giving you the assignments what all data sets you need to focus on. But you can take up any data set and just try to do it. And yes, this was it from my side. I will see you all in the next video. Thank you. Hello guys, so we're going to continue discussion with respect to spam ham classification. Now in our previous video, we have already done bag of words and we have applied machine learning algorithms, right? So in this video, what we're going to do for the same project, we're also going to apply a TF-IDF model and then apply a machine learning algorithm. So let's go ahead without wasting any time and let's see that. Already we have seen all these things, we have basically created a bag of words, we have implemented this, we have seen the vocabulary, then we got the output feature, and then we did a train test split, and then finally we trained the model with the multinomial naive Bayes algorithm, and then finally we did the prediction for the X-test data, and finally we have the accuracy score, and over here we have also seen the classification report. Now let's go ahead and create the TF-IDF model, and with the help of this, we are basically going to create the entire thing, okay? So basically, we're going to create the model which will be able to train this TF-IDF itself. Okay. So first of all, as you know, that in order to create the TF-IDF model, we just need to import what. So again, this is all repeated things. So I'm just trying to show you with the help of some project. So I'm basically going to use feature extraction dot text import TF-IDF vectorizer. Okay, and then I'm just going to write TV is equal to TF-IDF vectorizer. And here also I'm going to make sure that I use max features as 2500. Okay, and say 2500 maximum features basically means what? The maximum number of features that are having the maximum frequency, right? So top 2500 words are having the maximum frequency. And I can also take the n-gram range, and obviously that is a hyperparameter. I can play with it. Okay, I'll just do 1,2, and then finally this will be my independent feature now. So here I will write TV dot fit transform on my corpus, and I'll convert this into to array, right? The same thing like how we did it over there. And this is finally my x value. So here you'll be able to see the x value itself, and some or the other way you'll be seeing some values in decimals. So here you can see 0.344, and there are many variables you should be able to see. Okay, and if you probably want to see tv.vocabulary underscore, you'll be able to see over here also, right? All the vocabulary is basically there. Perfect. Now again, with respect to this x, I'm just going to again do a train test split like this. Okay, 20% I'll be taking in the test data, and I'm just going to execute this, and this will create my new x train and x test data. And again, the same code basically to import the multinomial naive Bayes and train it with my x train and y train. And here I'm just going to write spam TF-IDF model, okay, since we are going to use this. And finally, we can do the predictions. And the predictions will be using the same code that is what we have actually earlier done it, right? So instead of writing spam detect model, I'm just going to write spam TF-IDF model on X test. Perfect. And then finally, I'm going to get my accuracy score with respect to this. So it is coming somewhere around 97% with the help of TF-IDF. And again, if I probably try to see with respect to classification report, I'm actually getting a good, it is somewhere around similar kind of thing, right? Here, precision is getting decreased to 84, but almost if I see as an weighted average, it is coming as 98%, right? Very simple with the help of TF-IDF. Again, with the help of TF-IDF, one thing that I will probably see over here is that you can also play with different parameters with respect to TF-IDF also, right? And one more thing, guys, here I have actually performed, I have actually performed only ps.stem. You can also perform lemmatization. It is up to you. And try to do it. This will be a task that will be given to you itself. You can actually do it with the help of lemmatizer, and just let me know how much accuracy you are able to get it, right? So yes, in this video, we are focused on showing you the implementation with respect to TF-IDF model and training a machine learning model like multinomial naive Bayes with respect to that same data. And finally, you'll be able to see all the accuracy that we are getting. So in the next video, we are going to do the same project with the help of word-to-vec also. Yeah, this was it. I'll see you in the next video. Hello all. We are going to continue discussion with respect to natural language processing, and in my previous video, we have already seen how we can actually perform spam ham classification with the help of bag of words and TF-IDF. And this is the entire materials that you'll be able to see. We basically applied a bag of words with respect to count vectorizer. Then we got all the vectors over here with respect to the vocabulary. Then I got the output feature. Then we did the train test split. Now this is super important. After applying a bag of words, we did train test split, and then we further saw the accuracy and with respect to the classification metrics also we got. Here similarly we did the TF-IDF model, we got the vectors, and finally we applied all the train test split and we got the accuracy. Now one super important thing about some of the very important best practices. And I will tell you guys, deliberately, I have made some mistakes, and that mistakes you needed to definitely know. So I'm not told in the previous video. So let me tell you what mistake that we did. In the first step, usually, right, and this is super important for any machine learning algorithm. First of all, we focused on doing pre-processing and cleaning, right, of the text data, right? And we also say this as feature engineering, right? So this process is called as feature engineering. In the second step, what we did with the help of bag of words and TF-IDF, we converted all the sentences into vectors, right? This is what we did, right? We converted all the sentences into vectors, right? Now this is the second step that we specifically did. Coming to the third step, after this, what did we do? We did train test split, okay? And finally, on the fourth step, we basically trained our model, right? Train our models. Now, this is what we did in the previous steps. And deliberately, I have done this because there is some major problem between this second step and third step. Now, what is the problem? Understand, pre-processing and cleaning is usually done for all the data set itself. But when we say bag of words and TF-IDF, now this is super important. Bag of words and TF-IDF is a concept wherein we convert the sentences into vectors, right? Now, this is done on the entire data set. And then we do the train test split, and then we apply the model, basically the model trainings, right? Over here in the second and third step, just take a pause and just think, what mistake did we do? The real thing should be that, first of all, we should do train test split. Okay, so I'm just going to make this point. First of all, we need to do the train test split, and afterwards, we should apply bag of words or TF-IDF to convert our sentence into vectors. Now, you need to understand why we are specifically doing this, because understand, when the model is getting this, if I talk about training and test data is only used for training the models, whereas test data is used to evaluate the models itself, the machine learning models. And by interchanging this step, we are making sure that the model has no bit of information regarding the test data. If we do it in the reverse order, wherein we focus first on doing TF and then IDF, TF or IDF, and then doing the train test split, what will happen in the train test split? The train and the test data will be almost similar, right? So we should try to invert this particular step. The second step should be train test split, and then we should try to apply bag of words. And by doing this, we are actually preventing data leakage. Super interview question, preventing data leakage. That basically means, just imagine that you're going to write the exam, right? In the exam, you should not even get a hint of the question paper, what questions are going to come, right? You should just prepare with respect to all the syllabus that you have. So your syllabus that is present is your training data, right? And your test data is whatever question paper is going to come in the exam, right? So that is what. So this particular concept you really need to look after it, right? Now what I'll do, I will reverse this step. Okay, and this is the best practice that we should follow, guys. I have deliberately not performed this because you should know this, right? And I'm making a dedicated video just to make you understand what mistake we made. So here everything is fine. So here you can see I got corpus. So till here all the cleaning process is there. Now before this bag of words, now what I'm actually going to do before applying bag of words, I'm just going to perform this train test split. So here I will perform the train test split. Now instead of giving X, I will give corpus because that is my input data. Okay, corpus, and I will apply this, right? So I've applied the train test split over here with respect to the corpus, and I've given corpus. Y will be same. Test size is 20%. Okay, because before only we have basically selected the Y variable. Let's see where is the Y variable. Okay, Y variable is somewhere here. Okay, so it's okay. I'm just going to copy this, paste it over here. So I'm just going to Control C, and before this, I will have my Y variable. So let me just execute this, and this is what I'm getting. Okay, now see this is super important because after doing train test split, now we'll apply the bag of word model. Now bag of word obviously will initialize the max features. This is fine. Okay, now with respect to X, now see this. Now I don't have X, I have X train, X test. Okay, now first of all, I will apply X train, and I will say cv.fit underscore transform on my training data. So that basically means if I probably see right now also my X-train data, what will be my X-train data before this? If you see over here, my X-train data is still having text, right? So these are all the text it is having. If I probably try to see what is the length of my X-train data, you'll be able to see that I'm getting this much 4457. And similarly, if I go and see what is my length of Y, I'm also going to Y underscore train. You'll also be able to see that I'm actually getting how much 4457, right? So this is my train. This is my training data, right? And I'm going to train this particular data with my model, right? So since in my X-train still I have text, I need to convert that into vectors. Now I'll try to apply bag of words, right? So I will say fit underscore transform on my X-train and I'll convert that into an array. But with respect to X-test, what you'll do with respect to X-test, this is super important. Instead of writing fit underscore transform, I will go ahead and write transform on my X-test data. And finally, I'll convert this into array. Okay. Now see, I did not perform fit underscore transform here, right? I just performed transform. So whatever techniques is basically used or whatever vocabulary is basically created with the X-train data itself, we are going to use that same technique for the test data, even though some words are missing. So now in this way, I'm making sure that my training data and my test data are not at all similar. It is at least something different because in the X-test data, I may have something different, right? And this is the simple change that you basically have to do. And once we do this, what we are basically doing in the next step is that I'm actually converting this into my X-train. Like I'm basically converting this into my X-train. So this is what is my X-train looks like. All my data points is over here. Now with respect to vocabulary, also you can check it out. I'm having all this particular vocabulary. Now remaining all are very simple. Let me just delete this. Because we don't require anything as such. And this is my y dot shape. It's fine. I'm just going to remove this. I don't want it. Now I don't have to do all these things because I've already done the train test split. Now go ahead and apply your multinomial bias, and we will try to find out the accuracy metrics, and then finally we will do this. Right? So here you can see that I'm getting 98%, and again, this is also a very good 98%. Now with respect to the TF-IDF model, also we'll do the same thing. First of all, we really need to perform the train test split. Okay. So what we're going to do, I'm just going to copy and paste the same thing over here. So this is my output, and this is my train test split, and I will again use the same corpus over here. Okay, done. Very simple. Now I'm doing fit underscore transform on my X-train, and this will basically be not my corpus, it will be my X-train data. Understand this, guys. What are the changes specifically I'm making? This is super important to understand. And then X-test, where I'm writing tv.fit. Instead of fit transform, I have to write transform. And this will basically be my X-test data. And I will try to convert this into an array. Okay, and this is done. So this is my X-train with respect to this, and this is my vocabulary. Here you can see all the values I've got updated. tv.vocabulary is this one, and finally I don't have to perform this, so let me delete it. No need of this. Then I will try to do it with this fit predict, and here you can see I'm getting 97%, and this is at an average I'm getting 98%. So this is the best practices that we should definitely do. This in short was just to help you out how things need to be done with respect to this, so that you don't have any confusion. But please make sure that you follow these best practices, and this is not with respect to only this problem statement, any machine learning problem statement. After doing the feature engineering, then probably if you're handling the missing values also, then try to do a train test fit, and then you try to apply in this particular way, right? So these are the best practices that we should follow. I hope you are able to understand. Yes, this was it from my side. I will see you all in the next video. Thank you. So, guys, so we're going to continue discussion with respect to natural language processing. In this video, we're going to solve the spam ham classification project using word to vec and average word to vec. I'll just change the spelling. Okay, so this will be an important one, guys, because with this, the accuracy level will be quite good, But the main thing is that how we can train this entire project from scratch using word to vec. That is what we're going to see. And for this, we are going to use gensim as a library. So again, you know that how to install this. So you just need to write pip install gensim if you don't have already. Then I'm going to import two things from gensim.models. Import word to vec key vectors, and I already have shown you that how you can load word to vec Google News 300 model. That is a word to vec model, which is a pre-trained model. And here I've already shown you that by default, this particular word to vec model will give you vectors with respect to that. If I probably see the shape, it will be giving you a 300 dimension vectors. So if I probably want to see the vector, the king vectors itself, this specific word vector, these are the vectors that I'm actually getting. But now our plan is to take this entire data set, which is all the sentences, and then probably create a word to vec from scratch. So this will be an amazing one, and probably with the help of this, you'll be able to do a lot of tasks as such. Okay, and in this, we are again going to use different techniques. So let me just go ahead and let me do one by one. So first of all, this time what I'm actually doing, I'm also going to make some changes. In NLTK, I will not apply porter stemmer, but I'll apply lematizer. Okay, so just this simple change because I really want to give you the different types in a specific project how you can solve the similar things. So I'm just going to import the word net lematizer, and then I'm going to basically say lematizer, okay, is equal to word net lematizer. So I'm going to initialize this with the word net lematizer itself. Now the next thing is that all the things will be same over here. You'll be able to see that I'm basically removing all the special characters from the messages itself, right? And this is basically my messages itself, right? Then I'm lowering it, I'm splitting it, And let me do one thing. I just don't want this all things to happen, I don't even want the stop words to apply because I want to see that how for each and every word this vector will get created. Okay, that basically means I'm taking every word in this review and I'm just applying the lemmatization and I'm appending that in the corpus. This is the change that I'm doing. I'm not removing every stop word because I also need to check that how it is basically creating a vector for each and every simple words. Okay, so this is what I have actually done over here, and right now I'm getting an error. Okay, I think I did not import RE, no problem. So I'm going to import regular expression, and what all things I need to import if I go over here and see, okay, NLTK, and import NLTK, and also have to make sure that I download all the stop words, right? And now if I probably go ahead and execute it, so this is my entire corpus, perfect. So the corpus is over here, right? So this is the corpus, and in this particular corpus, I have basically applied word-let lemmatizer. Okay. Now there are also multiple ways how you can also do this. Every time you don't have to probably do this. Today I'm going to show you some more. In this particular video, I'm going to show you some more techniques. Let's say that I want to create all the words. So this is basically my words. And I'm going to show you a special function which is called as simple underscore processes. Okay, and for that I just want to import two more things. Let me just import it. So two more things I'm going to import over here. One is sent underscore tokenize. You know what is sent underscore tokenize, and this is a super important one, which is nothing but from gensim.util. I'm going to import a simple underscore process. Now probably if I show you the definition of simple underscore process, here you'll be getting an idea about what simple underscore process will basically do. If I press shift tab, it converts a document into a list of lowercase tokens, ignoring tokens that are too short or too long. So if you also want to make sure that you want to lower any kind of tokens, you can directly use the simple process. And I'll just show you one way where I'll have all the words and all the things. So I'll say for sentences in corpus, because in the corpus I'll have a list of sentences, right? I'll just write sent underscore token. I'll first of all create all the tokens itself with respect to sentences, and I'll write sent underscore tokenize, okay, with respect to all the sentences. So the sentence may have 4 to 5 sentences, it can also be a paragraph, each and everything it can be different. And then I will say from sent in sent underscore token, right? And I'm just going to apply this. I'm just going to apply the simple process, okay, on all the sentences. Now see what will be the output. This is super important. Okay, first of all, let me just write down the code so that you'll be able to see the output. And this I'm basically going to append in my words list, right? So this is what I have done. Okay, now if I probably execute it, now see what will be the output. Initially I had the corpus. Corpus is something like this. Now if I probably go and see my words, so this is, see, for every sentences I'm getting all the list of words. So this is my sentence 1, this is my sentence 2, this is my sentence 3, right? And this is my sentence 4. So like this, I can get each and every sentences. That's what I'm actually meaning. Okay, so over here you'll be able to see with respect to every sentences I'm getting all separate words. And this lowering process is also done by the simple underscore process, which is very good. So every time you probably don't have to do this, you can also take this specific path. And again, there are various ways. I'm just using the most efficient way, most easy way, so that you will be able to follow the same thing. Okay, so this is with respect to all the words that I have probably got. You can explore this with respect to all the sentences, all the words I'm able to get, which is very, very good. Now is a super important thing, because see, at the end of the day, I need to train all this particular word with the help of word to vec, and then with the help of average word to vec, I'm just going to do the concatenation, which is super, super important. So let me go ahead and let me show you that now how you can basically train everything from scratch. And again, you know that what is the sentence size, you know what are the different things in this, right? Perfect. You have got all the sentences with respect to all the words. Okay. Now the next step that I'm probably going to do is that I'm going to import gensim. Okay. And now let's train this model. Let's train this word to vec model from scratch. Let's train word to vec from scratch, like how that Google has basically trained, right? With the help of gensim only, we'll try to do it. Now over here, I'm going to import gensim.models.word to vec, and here just let's press shift tab. Now over here, gensim.models.word to vec, here you'll be able to see that the first parameter that I'm giving is sentences. Now already I have my sentences, that is basically my words. Okay. Now coming to the other parameters, which are the important parameters. Here you can see vector size. Now this is what I'm saying. Now Google word to vec, which we have seen in the pre-trained model, it is giving you 300 dimensions. But here you can see that you can set your own dimensions. You can set 100, 200, 300. So I'm going to by default set vector underscore size equal to 100, and you can play with all the other parameters like minimum count. Minimum count is basically like if you probably see this, right? Somewhere this entire information is given over here. But here I'm just going to focus on very important features. But definitely you can try and you can see all the features what it is basically doing. See what is minimum underscore count. It ignores all the word with total frequency lower than this. This is basically to create the vocabulary size itself. So over here, what I'm actually going to do, I'm going to give my words. Along with that, let me keep this vector size as 100 because I really need to get every words will get converted into 100 dimension. I'll keep the windows and minimum count as the same size. Okay. So let me just go ahead and probably execute this, and probably I will just store this entirely in the model variable. And this will be my model itself, right? Now if I go ahead and basically write model.wv, that is word to vector, and there is something called as index underscore dot 2 underscore k, and this particular line of code is to get all the vocabulary. Okay, so if I probably execute now, here you can basically see these are all the vocabularies over here. If you really want to check what is the vocabulary size over here, so you can basically write model.corpus count. Let's see, corpus count. If I execute it here, you can see 5569 is basically my vocabulary size, and you can also see that for how many epochs it has basically been trained, and by default it will be taking 5 epochs. The more number of epochs, the more better it is. But just to give you an idea about how the training will happen, because if you give 100 epochs, probably this entire training will take a good amount of time with respect to that, right? Right now I've just done it for 5 epochs because that is what is the default value that is given over there. You can keep it to 10, 20, whatever values you want, right? And now if I probably try to see similar similar by word. So there's a function called as similar by word. Let's say if I'm taking a feature called as skid, right? And if I execute it, now here you can see with respect to the skid, what all values you are able to get, or what all similar words you are able to get along with the cosine similarity score, right? This is very, very good. Suppose if I say good, right? So here also you can see morning, what, not, happy. See, happy is also coming. I know the training has just been done for 5 epochs, so you're probably being able to get like this. But here you'll be able to see that yes, you are able to get some of the words which are super similar, right? Now, one more very important thing is that whatever vector, see, what is the vector that is getting created over here? So if I write model.wv of good, right? And if I see this vector size, you'll be able to see it is 100 itself, right? So these are the 100 dimension that is getting created. So probably if I write dot shape, you'll be able to get this. So I'm getting 100 different vectors with respect to every word that is good. Okay. Now this is a super, super important step. As I said, why do we use average word to vec? I've told you that. See, let's say, let me just go and show you. Okay. This is my words, right? Suppose if I say words of 0, this is my first sentence. Go until Jurong point this. Now, if I probably consider this word to vec, for every word, it will give you 100 dimensions, right? For every word, for go, it will be 100 dimension vectors. For until, it will be 100 dimension vectors. For all these things, it will be 100 dimension vector. But what we really need to do is that for every one sentence, we need to get 100 dimension vectors, right? That is what we really need to get it, right? In order to train our model. So what we can do is that for go, for until, for Jurong, what we can do, we can basically do the averaging of all the vectors of this specific word, and then we will only be able to get the 100 dimensions. So let me just explain you what I'm actually trying to say, right? So over here, you'll be able to see that. Let me enable the writing over here so that you'll be able to see. So what I'm actually saying is that, suppose, let's say, let me first of all rub this. And this is super important because without this, the average word to vec you'll not be able to train. So let's say I have this go word, I have this until word, I have this Jurong word, and I have a lot of words like this, right, in the sentences. So go will have a separate vector like this, until will have a separate vector like this, Jurong will have a separate vector like this, and every word will have a separate vector like this, right? Now, this is my entire sentence, and for this entire sentence, I want a vector of 100 size. So what I will do, I will average up all these numbers. Let's say I'm going to average up all these values, and I'm going to get one specific vector. So this will be for my entire sentence, and this particular vector size will also be of 300 dimensions. And that is what I've already told you about how the average word to vec intuition is all about. Then this sentence will be treated as this input, and the output, whatever output is there with respect to that, either it is 1 and 0s will be taking that. So this is what we basically do in average word to vec. So in short, I have to find out the average of all this, okay? And that is what I'll show you in the code itself, right? So here I've actually created a function which is called as average word to vec. Here I'm saying that model, see, return np.mean. Mean basically means average. For word in doc, for every word in doc over here that I've given, if the word is not in this index.2 key, then only I will probably try to create my model vector, right? And then this will basically happen on axis equal to 0. So this is a very simple function. I'm just making sure that row wise I have to probably do the mean. That is only what we are doing over here. So let me just execute this, okay? And before I go ahead and probably do the other work over here itself, I also want to make sure that I install one progression tab, right? So just to understand the progress, so I'll be using tqdm, okay? And this will probably take some time with respect to this because this tqdm, and why I'm doing this, I'll just tell you in some time, okay? So from tqdm, I'm going to import tqdm, okay? And here it is. So here what we are going to do is that I'm just going to import this, just a second. Okay, now this is done. Now what I'm actually going to do, I'm applying this entire thing. I'm trying to apply this word to vec on every sentences, on every sentences. Okay, this is super important. I will try to apply the word to vec on every sentence, average word to vec. So whatever things I'm basically doing this for every sentence, it will take up and it will apply this particular thing and it will do the average of all the vectors. Okay, and that is what we are doing over here. Just to see the progress, I've written hello, but I think that is also not required since we have the tqdm. So I'm just going to remove this and just go ahead and execute it. So here I see some error. Okay, numpy is not there because I did not import it. Not a problem. So I'll say import numpy as np and we'll start the process. Now here you can see that I think we did not get any kind of errors. And now let's go and see our x. Okay, so this is what I am able to get. See how quickly it has happened. So this is with respect to the first sentence vector. This is my second sentence vector, which is quite amazing. And this is my third sentence vector. And here we have just done average word to vec, right? Amazing, right? So this is what I'm actually getting. And if I probably try to see my x dot shape, you'll be able to see x dot shape x. Okay, x is a list, not a problem. So if I probably go and see length of x, you'll be seeing that this will basically be my 5569, which is the input size of the messages, right? So this is what is my input size of the messages with respect to that. And this is how we have basically done the entire word to vec, which is quite good. Now the next thing that we just need to do is that try to convert this into an array. So here I'll just write x underscore new is equal to np.array on x, right? So this becomes my independent features, right? So this is what I'm doing. But here you just try to understand what we have done. We have just done average word to vec on every sentences after finding out the vector, right? And this you can see how quickly it has happened for all the sentences over here. And this is my final sentence over here, right? All the vectors. This is the vectors 100. And remember, all these are 100 dimension. So if I probably now see this x dot shape, see if I write x underscore new dot shape, you'll be able to see I'm having 5569, right? This is super amazing. And this is what we have actually done it. So let's say if I'm writing x underscore new of 0, I'm actually getting my first array, right? Which is very good, right? And now if I probably try to see the shape of this, you'll be able to see that I'm getting 100 dimension, right? So super cool. We have done an amazing work with respect to this. And obviously you know what is my dependent feature is. So dependent feature is my output feature. Okay, so I'm just going to write my dependent feature over here. So already I've shown you in the previous like how you can take the dependent feature. I will apply this as my output feature over here and take the first label right over here, and that is done. So this is my Y dependent output feature, and this is my independent feature. Now in the upcoming video, what we're going to do is that we're just going to apply the machine learning algorithm because I have now my input features and this is my output feature. All I have to do is that train my model, right? So this part, the second part, we'll be seeing in the next video. I hope you're able to understand. Now this is the thing that you really need to do with respect to all the problems. Very easily, all the code is available over here. You can try it out, you can see, and what all things you can basically do. Hello guys, so we're going to continue the discussion with respect to the SpamHam project with the help of word to vec and average word to vec. Already we have converted everything into the vectors, and we also saw that our x underscore new, that is the data, right? It is basically having 5569 rows. Now there are multiple things which I really want to talk about right now, and this will probably be giving you a sense like what is necessary before we start providing this entire data set to the training algorithm, right? Now first of all, here you can see that whenever I see with respect to any vector, any sentences, there will be 100 dimension. This is perfectly fine. But if I probably see the shape of the messages, so if I see the messages right now, this is what is my messages, right? And probably if I see the shape of it, here you'll be able to see 5572 rows and 2 columns, right? But the number of rows that is coming in x underscore new, it is 5569. So obviously there's a problem because initially we had 5572 rows, now we just have 5569 rows, right? So this is not matching, and x underscore new is after all the sentences are converted into vectors with the help of average word to vec. So one important thing is that we have to make, and probably if I also see the y value, right? So y shape is also, if I just go ahead and execute this, now here you can basically see with respect to this, let's say I'm going to basically use messages of level, right? So if I also see y shape, that is the output feature, is also 5572, but my independent feature is 5569 rows. So this is a big issue. That basically means our training data set is just having 5569 data points, but my output data is 5572. So after pre-processing, right, we have lost 3 records. Now we really need to find out why these 3 records have been lost. And this is an amazing use case, guys, because when I was also solving this problem, it took me a lot of time to understand where that 3 rows went. And how did this 3 rows get removed from this particular data set? That is also a thing. Now let me go back up over here, right, before the corpus. So here was the corpus. Let me show you the corpus. So here I was getting my corpus, right, after this code. Now I have added one line of code. I'm saying that I, comma j, comma k, 3 information I'm taking it out, and I will be nothing but I'm zipping it length, comma corpus. So I'm basically going to have one information about the length of the corpus. So it'll be in this mapping condition, and then I have this corpus, and then I'm displaying the messages. Okay, and I'm only displaying when if I is less than 1. Now what is I? I is nothing but this is the length of the corpus, right? If the corpus length is less than 1, I am basically displaying all the data, right? So once I execute this, and probably you can see this is a very simple Python code. I'm using zip list of map length, comma corpus. Then I'm getting the corpus value, and then I'm getting the message value, right? And over here you can see that initially there was some message like 645, and it has got removed and it has become blank. Why? Because I've told that only A to Z and capital A to Z should be there, and everything should be removed. I could have also put up like 1 to 9 also, then also it would work, right? But now in this particular scenario, it is just going to remove everything, even words, even this kind of characters, right? So everything is getting removed and it is becoming blank. So that is the reason I'm getting 0. And if I probably execute this, how many values I'm getting? I'm getting 3, right? 1, 2, 3. And this is like if I probably subtract from my entire data set, then I'm like initially my data set was 5572. If I'm subtracting 3, I will definitely get 5569, right? So that is the reason my 3 is missing. Now we need to find out with respect to y also where that length is less than 1. So what I've done is that over here, when I'm creating y, I've just written this messages of list of map of lambda, length of x is greater than 0, comma corpus. When I've written this, I just have to replace this messages with y, and now you'll be able to see that I'll be getting the y dot shape as same. Nothing I've done. I've just found out that which all length of the data or the paragraph or the sentence is greater than 0 in this specific corpus. I'm just taking that particular messages and probably doing get underscore dummies, and I'm getting my output feature, right? Now one other thing. Now first issue is basically solved, right? Now even though my message is 5572, now my x underscore new is 5569, and if I probably just see x underscore new, let's see x underscore new. So x underscore new is basically, so if I execute this once again, let me just execute it, okay? Or forget about x underscore new because I've converted x into x underscore new. So here it is got converted, and this is my x, and this is my x underscore new. Now if I probably consider x also, forget about x underscore new. Let's see x, okay? X is list of arrays, okay? List of arrays. Now if I probably see the length of x, right now it is, the type is, what is the type of x? It is nothing but list. The length of list is 5569. And if I probably write x of 0, so this will be my first sentence vector. Then if I write x of 1, this will be my second sentence vector. Similarly, if I write x of 2, this will be my third sentence vector, okay? So all these things are there. Okay, now this is perfectly there. Okay, now what we are basically going to do is that, now see, this is super important. I need to add each and every vector that I present over here as a row in a data frame because it will become my independent features, right? So for that, what I'm doing is that, again I'm repeating it, guys. See, x of 0 is basically my vector of the first row, right? First sentence. So I need to add all this particular thing inside a data frame within the first row itself, right? Because these are all the dimensions. Similarly, x of 1 should be added as my second data point in the data frame. And for that, I'm writing this specific code. My y variable is already ready. What I've done is that this is my final independent feature. I've created pd.dataframe, and then I'm writing for I in range of 0, length of x, okay? And then I write df.append pd.dataframe of x of I dot reshape of 1, minus 1. Now this is super important. Understand this, okay? So if I say x of 0, okay, and if I probably just see the shape, this is a single dimension array, right? 100, because it has 100 vectors. Now what I need to do is that I need to add this as a row in the data frame. So I will be using reshape, and here once I write 1, minus 1, here I'll be able to see that this entire row will now have a dimension of dot shape like 1 row and 100 columns. And that is what we really need to do, right? The first sentence is nothing but it should be a 1 row data point with 100 different vectors. That is nothing but 100 columns. Now similarly, what I'm actually going to do, I'm going to add like this for every data point that is present inside x of I, right? Basically the x value. Suppose if I want to do it for x1, x2, x3, all these data points need to be appended over here. So that is the reason why I have written for loop, and I'm writing this, and I've used ignore underscore index is equal to true. So one assignment, just try to find out what is the meaning of this. And it is very simple. You just go ahead, press shift tab, you'll be getting the information over here itself. Okay, so once I execute this, now you'll be able to see that this execution will take some time. Now if I write df.shape, now here you can see that 5569 data points is there, and now we have 100 dimensions, 100 features, right? And that is what it is there. Now if I probably go ahead and write df.head, you will be able to see these are all my data points. I don't worry about what is the columns. So this is my first sentence data points. This is my second sentence data points, right? And these are all my independent features, and it is all 100 dimension, right? Now what I can do is that I can basically write my independent feature is nothing but x is equal to df, right? So I can basically write like this, and my y already I know. I'll just print the y also. Okay, so this is my x and this is my y. The next step, what I will do again, very simple. I will do the train test split. So train test split, and here I'll be giving my x, y, this is there, and automatically everything will start getting executed. So this is my x train dot head, right? And here you can basically see all my data set with respect to this. What is my y underscore train? That also you can basically see. And let me write dot head. So I think in a series dot head will not work. Okay, there's a number array, no problem. So this is my y train, right? So everything is there. We have our independent feature. We have our dependent feature. Now we can apply any machine learning algorithm. For this case, let me just say, because at the end of the day, these all vectors are a dense vector. So I'm going to basically apply sklearn random forest. Okay, and it should be a classification problem. It should be a classification problem. So here you can see from sklearn.ensemble. Okay, from sklearn.ensemble, I'm going to import random forest classifier. Okay, so this will be my classifier, and I will just initialize it to random forest classifier, and this is done. And after that, I will just write classifier dot fit on my x train, y train. Okay, now I'm getting an error. Let's see what is the error. Input contains nan infinity or a value too large for data type. Now this is the error that we are specifically getting. So let's see how we can actually fix this. So guys, now here you can see that I'm getting a specific error over here, right? It is saying that input contains nan infinity and all. So we did not do a check. So that is the reason we are getting this. So once I get my x value, let's see that whether I have any nan values or not. So here if I write x dot is null, okay, dot sum, And if I probably see this, how many null values that I have? Okay, function has no attribute sum. Okay, not a problem. Is null dot sum. So here you can basically see that okay, there are 12 null values in every feature, right? Every columns in chart, right? So obviously we have done so much in for pre-processing and all, so we can directly remove this vector. So before that, what I'm actually going to do is that I'm just going to make sure that I have my output feature also over here and append it to this, so I can basically do it in my df itself. So I'm just going to make a cell up and let me write df of output. Okay, first I will initialize it to y value. So this is done. So this is my entire df dot head. Now here you can see I'm just adding my y variable also over here, and finally you'll be able to see this is my output. Okay, now first thing first, I will just remove the null value. So I'll say df dot how to remove the null value. Fill or I can say drop na. Okay, drop na, and over here I have features like access equal to 0, access equal to 1. So I would definitely like with access equal to 0 because I want to remove all the rows itself. And let me make sure that let me just write it as in place is equal to true. So this is got executed. Now if I probably go ahead and see df dot is null dot sum, now I think we are fixing all the problems. Again, is null is there. So dot sum, now I have zeros. Now all I have to do is that put over here, right, as df. And again, if I probably see this is null, okay, in my x value. In my y value, I can basically use df of output. Okay, and this will be there. Let me see what is the output variable. Yeah, capital O. Okay, so this will basically be my output feature. Done. So I have my x and y. Now all I have to do the train test split, then again head, then this is my y train. Okay, and then I'll apply my random forest classifier. Again, I don't need to check this. And let's go ahead and do the fit. Finally, the fit has been successfully done. Now you just understand that just to do this, how many different issues are coming. And I'm deliberately not deleting all these issues. I'm trying to show you what all situations, what all different things may come. And then what I can do is that I can just do the prediction. So here I'm just writing classifier dot predict. And this will basically be my text test data, and this will basically be my y print. Okay, and again on random forest classifier also you can perform a lot of hyperparameter tuning. Now let me just go ahead and write the accuracy score and classification report. So here I'm going to print accuracy score with respect to y underscore test comma y underscore print. So this is the accuracy that I'm getting, which is good. Okay, and similarly I can print my classification report with y underscore test just to make sure that everything is fine. So here also I'm getting a good accuracy. And sometimes this can also lead to overfitting, but if you don't want to do overfitting, you just need to perform some hyperparameter tuning in random forest. So I hope you got an idea about how we can perform this. And finally, we have done this in an amazing way. Line by line, we have written so many codes. We have understood different things. You just need to practice things and you will be able to do this. So with the help of average word to vec also, we are able to do this, right? And yes, finally we are done. All now you have to do is practice with different problem statements. A lot of data sets, take up, do it, and just try to do it in a better way, right? So from this also, I'm just going to remove this 2 lines of code because I don't want you to get stuck over here. Just to explain you, I've just put up this. You need not execute this line of code itself. So yes, this was it from my side. I will see you all in the next. Hello guys, so we're going to continue discussion with respect to natural language processing. In this video, I'm going to start a new project. It's called as Kindle Review Sentiment Analysis. An amazing use case altogether, so you can do many things over here. So let's talk about the dataset first of all. What is the dataset all about? So this is a small subset of dataset of book reviews from Amazon Kindle Store category. Contain 5 core dataset of product reviews from Amazon Kindle Story category from May 1996 to 2014. Contains a total of this many number of entries. Each reviewer has at least 5 reviews, and each product has at least 5 reviews in the dataset. So these are some of the features that we have, and we also have one very important feature, which is the output feature, which is called as rating. Okay. So just want to give an acknowledgement about this particular dataset. This dataset is taken from the Amazon product data from this Julian Macaulay UC SD website. So this particular website over here, you can see this. You can find out different datasets also if you really want to train it from scratch, right? So this is just a small data set, even though I'm saying small data set, but this has this many number of entries also. So license to the data set belong to them, so the entire credit is given to them with respect to this. Okay, now what are things we can basically do over here? So we can you can see do sentiment analysis, we can probably do fake reviews or outliers or any other interesting analysis we can basically use. Even we can use word to vec with respect to this. Now just to talk about this particular data set looks something like this, and right now we will not be able to understand it. So let me quickly import pandas and probably read this particular data set, and we will start doing this particular project again. The main intention of the project is to follow all the best practices. So let me just go ahead and write it out. So what are best practices? We are going to use it, and probably you also have to follow this. So the first thing is that we will be doing pre-processing and cleaning, which we can also say it as feature engineering. Okay, so this part we should definitely do it. The second thing is that I will go ahead and do train test split, right? And then we can probably apply bag of words, TF-IDF, or you want word to vec, anything you can basically apply. But I will just show you a couple of things, and remaining all things you can basically do it. Okay. Fourth one, then we'll probably train with some machine learning algorithms, train ML algorithms with respect to this. Okay. So here it is, best practices. We're going to follow this, and I've also told you what is data leakage altogether, right? So we always need to, after doing the pre-processing and cleaning, we should definitely go ahead with train test split. So let's go ahead and load the data set over here. So the loading of the data set is pretty much simple. We basically use the data. So let's say this is my data itself. I will be using pd.read_csv. Oh, before that I'll import pandas, right? I need to import pandas as pd read_csv, and I will also try to show you everything with respect to this. Okay, so over here you'll be able to see that my dataset is present inside Kindle reviews. So I'll be using this folder Kindle reviews, and then all let me just check out the dataset name. So this is my dataset name. We'll just use this one over here, right? So then the dataset will be able to load it. Now let's go ahead and see what is data.head. So this is how my data set looks like right now. I'm not ignoring the columns, so by default some indexes are coming, but the most important features out of here are review text and rating. I'll not be using other for this particular use case. For this use case, I just require the review text and rating itself. So let's go ahead and read that specific thing. And in order to read it, I will just use data of 2 features, and I'll just give my feature name. One is review text, and the second one is something like ratings. Okay, rating. And probably if I just execute this, I'll be able to get it. So I will just try to replace entirely with the data itself. And now I can probably see the data.head. Okay, so easy with respect to reading the data set. And over here, let's see some of the unique values, how much null are there, and all. We'll try to see it out, and we'll try to check it out. Okay, so first of all, let's see the data.shape. So here you can see I'm having 12,000 records. Okay, let's check out the missing values. Okay, so to check out the missing values, it is very much simple. Here I'm just going to use data loss is null dot sum. Okay, so it is 0, no missing values as such. Let's see how many unique ratings I have. So if I say unique unique. So I will probably be able to see that how many unique ratings are there. Let's see. So here are 3, 4, 5, 6, 3, 4, 1, 2, 3, 4, 5. So 5 different ratings are there. Okay. I'm just going to use this. Let me remove this part. Okay. And if I probably want to see the data ratings, value underscore count, just to find out that how many, whether this is an imbalanced data set or value underscore counts. So here are like 5 ratings at 3,000 reviews are with 5 ratings, 4,000 with 3, 2,000 with this, 2,000, 2,000, right? So I have overall a good number of ratings and almost all of them are almost similar, right? So this is perfect. I have our data set in a very good way. So we should definitely go ahead and try to solve this. Now, focusing on the first point, as said, we are going to do the pre-processing and cleaning, right? So this is super important. And cleaning. So what are things we need to clean? See, it is not like possible that you go ahead and check each and every sentence and what are the things are not. But what is the main thing that we are interested in? Much more information about the text if it is available, that is actually good for us, right? First of all, the first thing that I need to really fix about is the rating, right? I can use this many number of ratings and probably do the classification. But here, when you're saying review sentiment analysis, I just want to see that with respect to a specific sentence, whether the review is positive or negative, right? Or I can make also 3 categories. Let's say now in this particular use case, I'm just going to focus on 3 categories. Let's say any reviews that are less than 3, okay, less than 3, I will say it as a negative sentiment or a negative review itself. If I see any review that is greater than 3, then I may say it as a positive review. So this is what I'm actually going to do. And for this, I will just use data of rating. And if you know something about Python, so here we have a function called as apply. Okay, and now inside this apply, what I will be doing is that I will just write one condition. If my x is less than 3, okay, that basically means I'm saying that I'm going to take each and every rating and I'm going to basically perform this particular condition, right? If my x is 3 here, then my output should be actually 1, and this I can only apply if I have a lambda variable. Okay, so here if you know the basic functionalities of lambda, I can basically write lambda x if x is less than 3. Else I will say it as 0. Let me see. Okay, for any ratings that are less than 3, I'm basically saying that negative will be 0 and positive will be 1. Okay, or you can do vice versa. It is up to you. At the end of the day, you're going to get any kind of output itself, right? So here I'm just going to write it as over here, just to give a simple thing. Positive review is 0, sorry 1, and negative review is 0, right? Is 0. Perfect. So this is done. Let's see. I'm getting an error which says that dot apply this is there. Let's see whether everything is right or not. Data of rating dot apply. Oh, lambda b. Okay, so this is the problem that we faced it. So with respect to that, I can see that I'm actually getting converted to 1 or 2, right? So what I'm actually going to do, I'm just going to say data of rating. Okay, so here I'm just going to apply this. Insert is equal to this is there, and let me write it as data of rating. Every time I write data, right, it is really confusing. So let me do one thing. Okay, let me write this as df. Okay, df, because data frame, it'll give a good reason to say me as a data frame, right? So data frame is null, data frame df. Okay, and this is the thing that we use, right? Most of the time we can actually use this df and df. Okay, so here I'm going to execute it, and finally if I probably go and see my df.head, you'll be able to see that I'm getting this ones and zeros. So if you don't believe me, just go ahead and probably write df of rating dot unique. You'll be able to see this, right? So it is ones and zeros. So this is the first thing. I had so many number of categories. I just made it as ones and zeros. Okay. So these are the basic thing that we did. Now, again, we can also check with respect to value underscore counts and how good that is or how bad that is. So total number of ones are 8,000 and total number of zeros are 4,000. So I will not say this as an imbalanced data set. It is good enough, right? It is good enough with respect to the data set because 50% is there, and I think most of the machine learning algorithms will be able to handle. Okay. Now this is the first thing that we specifically did. Now I will go ahead and write some pre-processing steps that we usually face with respect to any kind of text data. The first thing is that we try to lower all the cases, right? That is important step as I've already told you. And again, we can also do this with the help of a simple thing like I will be taking df of, okay, and this will basically be rating dot str dot lower, and I can basically write this. So let's see what is the error. Can only use str access with string values. Okay, sorry, I'm using it on rating, right? So it will be rating text, okay, or it will be review text. I have my review text. Okay, and once I execute this, now here you can see all these 12,000 words are becoming smaller, right? So here I will just save this in my review underscore text, review text, right? So perfect. This is what I'm actually got it. Now df.head, you'll be able to see that I'm actually having a lowering of things. Now let's go with the second step. Okay, so this was the first step. Now with the second step, what I'm actually going to focus on is a very simple thing that I'm actually going to do is that I'm just going to clean the data with respect to different things. Now I don't want any special characters out of it, right? So in order to remove all the special characters, what all things I can basically do? It's very simple, right? Removing special characters. So removing special characters, and then we can probably go ahead with removing stop words. We can go ahead and removing punctuations, different things. And already I've actually shown you how about lowering all the cases. So what I will do is that I have probably written a code over here, and all step by step we will try to do this. Okay. Now first one that you're probably being able to see, right? If I probably say it, first step is basically removing special characters. Now see this, how I'm actually applying it, and by using lambda function, you can perform all these operations in the data frame itself, which is very good, right? So here you can see df of review of text dot apply lambda, and suppose if I say over here removing special character, what I'm putting as a regular expression over here, A to Z, capital A to Z, and 0 to 9. Only this letter should be there in the text itself, right? Other than this, everything should be removed with a blank, right? So that is what we have done with respect to special characters. Then I'm basically removing all the stop words. Now in order to remove all the stop words, I take up all the sentences. First of all, I will find out all the words in those sentences, and I'll see that even if that particular word is present in the stop words or not. If it is not present, then I will probably apply. I'll just remove all the stop words and then combine all those words and probably join them as a sentence. That is basically done in the second step. Okay, so here you can see if y not in stop words, then I'm going to take that y and join back that into a sentence. Now, third step is that. Now, see, guys, generally within a text, you may find all these things. You may find special characters, you may find URLs, right? URLs are also not that important because in the text, they may put some product review URL and all. Right? So I should also try to remove the URL. And again, I'm applying a regular expression over here, which is this regular expression. And I had to put a lot of efforts in writing this particular regular expression from one website. I checked it out. Now, see, this URL basically means any Gmail ID, any specific URL, any email ID, that all things will be getting removed. So I've added at the rate and all. And this all things you can basically perform it. And this is again a regular expression, which will basically start with if there is an HTTP, HTTPS, FTP, or SSH, just try to remove that. Okay. And then finally, I'm also removing the HTML tags. Now, to remove the HTML tags, we can use a beautiful soup library. So here again, lambda function is getting applied x, LXML, and I'll be getting the text where all the HTML tags will get just removed, and we'll just have the text itself. And finally, I'm joining them over here. I'm removing all the additional spaces. So these are kind of pre-processing. Just see with respect to text data, right? You may find out these all scenarios over here, and it is always better that we write this kind of a generic code. Now over here, you should see that what all libraries we require. First is import re. Okay. import RE, import the regular expression, and then I'm basically going to import NLTK because I'm also going to use stopwords. So I'll say from NLTK dot corpus import stopwords. Okay, so this is done, and then what I'm going to do, I'm going to basically write NLTK dot download, and I'm going to download all the stopwords. Okay, I'm going to basically download all the stopwords NLTK dot download or stopwords, and you know that in stopwords also we have something else, right? So import NLTK, no module named NLTK from NLTK dot corpus import stopwords. So let's see. Okay, here it is, NLTK, right? So I've done this. This is true. As I said, for HTML tags we are using beautiful soup. So what I'm actually going to do is that I'm also going to import the beautiful soup library, and again the installation is very much simple for this. All I have to do is that take up all the beautiful soup library and add it as an import statement. So I'll add a text above, code above, and I will just say from BS4 import beautiful soup. And if this particular library is not there, just try to import it. Okay. So beautiful soup is also done, RE is also done, everything is done with respect to stopwords. Now let me go ahead and apply it on my DF. Now this is probably going to take some of the time because there's so many regular expressions that will get applied. It depends on system to system, right? So finally, if I go ahead and now see my df.head, now this is what my data set looks like, and over here still there is some problem. See over here, when I was trying to join this, right, there is a problem over here. Like it has removed all the white spaces, right? And this is also again a problem. Let's fix this. Let's go ahead and fix this particular part also. Now guys, you can see over here all the spaces has been removed. So let's go ahead and debug this. So what I will do is that I'll just try to one problem that I see over here, right? When we are replacing, like other than this, right, I will probably just try to give a spaces over here. Okay. Now see, because of this particular spaces, right, what will happen is that spaces will get maintained in all the text, right? So this is one of the mistakes that I specifically did over here. So what I'm actually going to do again, I'm just going to execute from let's say from this particular part where I have all my data. So now you can see everything may be working fine. So here is my rating. It has got applied. Now this is number of ones and zeros, and don't worry about all these warnings. The first warnings are coming. So this is my df.head. Now I'll download the stopwords. Now apply this. Now let's go ahead and apply this all things. Now if I probably go and see my df.head, let's see how much time. It will take some amount of time with respect to this. Only the thing that I've updated is that I've given some additional spaces because of the issues that was coming, and now it is just going to apply for all the regular expression that is available over here. And this will probably take some time. So I will wait till all the execution will get over. Okay. So guys, so finally you can see the df.head, and probably took 2 minutes for this entire processing to happen. This kind of warnings that are coming, don't worry about it. It will not create a major impact in this kind of problem statements. But you can basically use .lock instead of directly assigning a value with respect to data frame. Okay, so this is how my df.head looks like, and the previous issue is now fixed. I'm having spaces all in small letters. This is perfectly fine. Now the next step that I'm actually going to perform is basically applying a wordlet limitizer. Okay, so let's go ahead and apply a wordlet limitizer. That basically means, in short, I'm going to apply the limitization in this entire text. Okay, so let me go ahead and write this limitizer. So for limitizer, it is very simple. I will say from NLTK.stem import word net limitizer, and here is my initialization with respect to word net limitizer. Now let me create a function. So okay, sorry, I don't have to initialize like this. So let me do one thing. Let me just create a limitizer, which will be the word net limitizer initialization. And all I will be doing is that I've created a function which is called as limitize words. So that basically means whatever text I'm going to give over here, it is going to split all those texts and it is just going to apply the limitation. Okay, so limitizer.limitize, and it is just going to give us the output. Okay, so finally I can apply this back to my data set. So what I'm actually going to do, I'm just going to copy this entire thing, the last statement, again apply the limitation over here, and again I'll be using a lambda function. Inside this I will just be changing it, and I'll apply lambda function. It is very very useful. That is the reason why I'm showing you over here. And this I will give it to my limitizer words with respect to x, right? So once we do this, again this will take some time because limitization usually takes time with respect to all the process, right? So finally I have my df.head, right? This is perfect. I have all the things that are available right now over here. Now let's go to the second step regarding the train test split, and then we will go ahead with the things, right? So for train test split, all I will be doing is that I'll be importing from sklearn.model selection import train test split, and then I'm just going to put x underscore train, x underscore test, y underscore train, comma y underscore go test, and this will be train test split. Here, the first thing that I'm going to give as my x-axis will be my df of review text, okay, and the y-axis will be, let me make some more cells. Okay, this goes down. Then I'll copy and paste it over here, and over here this will basically be my df of ratings, right? And I hope ratings is 1 and 0s, and perfect. So in my next line I'll say what is my test size. Test size is equal to 0.20, and this is done with a random stick. So far, perfect. We have done the second step. So that basically means if you see the best practices that we are going and following, right? Pre-processing and cleaning is done. Train test split will be done. Now I will just go ahead and apply the bag of words and then train the machine learning algorithm. So this part we will do in the part. Hello guys, we're going to continue discussion with respect to the Kindle review sentiment analysis project, and we are in the part 2. In part 1, we have already done all the pre-processing and cleaning. Now we have also done about the train test split. Now, according to the methodologies that we are following, the best practices we are following now only bag of words, DF, IDF, basically the technique of converting words into or sentences into vectors is remaining, and then probably we'll apply the ML algorithm. With respect to word to vec, I'll give you this as an assignment, but with respect to bag of words and DF, IDF, I'll try to show you over here. Again, word to vec is almost similar like whatever things we have discussed. Also make sure that you use average word to vec so that you'll be able to convert all the sentences into vectors. Now, in order to apply word to vec, bag of words and all, what I'm actually going to do, I'm going to import some libraries. So let's say from sklearn.feature extraction.text, I'm going to import count vectorizer, okay, and then finally I will say vectorizer, or I will say count vectorizer is nothing but bag of words. So I'll say BOW is equal to count vectorizer, and we can now convert x underscore train underscore BOW. So I'll say BOW, that is like a bag of words, and I can write BOW dot fit underscore transform, okay. And here I'm just going to give my extra data, right? Understand, for the training data set, we need to give extra fit underscore transform. For the test data, what I'm actually going to do, we're going to just apply BOW dot transform. And I've told you already why we need to do this, so that data leakage should not be there, right? So this should happen on next test. Perfect. So these two things are there. I'll just go ahead and execute it. And similarly, I can also do the same steps for TF-IDF. TF-IDF vectorizer. So here I will just write it as TF-IDF, and already we know how to do this, right? So I'm just going to write TF-IDF, TF-IDF vectorizer, and with respect to this, I'm just going to create TF-IDF variable like this, so that we'll have both the variables, right? And instead of writing BOW, I will write it over here, this one and this one, right? So we are doing fit underscore transform on xtrain and transform on xtest. So here we are also able to get the vectorizer. So if I probably see x underscore train, right? Or okay, let's x underscore train, right? Underscore BOW. So you'll be able to see all the vectors that is getting converted. Still, this is not getting converted to an array. So in order to convert this to an array, what I can actually do is that I can just write to array over here, and same thing I can copy everywhere, right? Over here also, dot to array, dot to array, dot to array. Perfect. So these are all my independent features, right? So now if I probably see x underscore train underscore bow, you'll be able to see all these things. And somewhere decimals, values, ones, zeros will be there. Okay. And similarly, if I can also see x train TF-IDF, I'll be able to get it. Now the next step, what I'm actually going to do is that I'm going to apply a naive bias algorithm because it usually fits well with the sparse matrix dataset, right? So I have something like epsilon.naive bias import. I can use multinomial also, I can use Gaussian naive bias also. So I'll go ahead and use the Gaussian naive bias. So I'll say NB model, naive bias model, and let me just write Gaussian naive bias. And then what I'm going to do, I'm going to basically do the fit on my x train underscore back of words, comma, y underscore train, which is my output feature, right? And I can also do the prediction, but later on I'll do it. And similarly, this is my model with respect to BOW for the BOW dataset. And similarly, I'll copy this entire thing and I'll make it to TF-IDF over here. Okay, and this will be a naive bias, and instead of giving BOW, I'll give TF. Let's see. So this is TF-IDF, right? I guess. Perfect. So let me just execute it. So this way, two models have been created. One is NB underscore model underscore BOW, and NB underscore model underscore TF-IDF. This is probably going to take some time because there are 12,000 records. Till then, what I'm actually going to do, okay, the execution is done. So I'm going to basically import some of the metrics. So I'm going to import confusion metrics, accuracy score, and classification reports, right? So these are all metrics. I'm going to basically use it. So I'm going to make some cells and paste it over here. Perfect. So go ahead. I've imported all the things. And now what I'll do is that I'll just write y underscore pred underscore BOW. This is with respect to BOW. So here I'm going to basically use NB underscore model of BOW dot predict on my x test data. Okay. So x test underscore BOW. Okay. So this y pred will basically happen. And similarly, I can do it for TF-IDF also. These are all my prediction that I'm going to get. And here also I'm going to give x underscore test of TF-IDF. Okay. So this is done. Now all I have to do is that print accuracy score, right? So print accuracy score. And this I'm going to print it for bag of words. BOW accuracy, okay, is equal to with this value accuracy score with respect to y test y underscore test comma y underscore pred or BOW. Okay, so here it is. I'm executing it. Oh, there is an error. Let's see where is an error over here. Accuracy score. Okay, I can write comma over here. So I'm getting basically bag of words as 58% accuracy, which is good. Not good, but it is obviously a little bit bad because the data set is quite huge, and for this word to vec will definitely work. I'm also going to make sure that I'm going to show you the confusion metrics with respect to y test comma y pred. And that will be BOW, right? So once I execute this, you can see that how many are wrong and how many are correct. Okay, so obviously not getting good accuracy, so you should definitely try this with word to vec because the data set is quite huge. Okay, and now this is with respect to a TF-IDF accuracy, right? And I'm just going to make a cell above, and let me just go ahead and write this one and paste it over here, right? So this is my TF-IDF accuracy, 58.1%. Again, not that good, but with respect to confusion matrix, I'm again going to print it. And that is the reason why for a bigger data set, word to vec works actually good. Okay, so this is the thing with respect to the confusion metrics, TF-IDF and all. Obviously, the accuracy is not that good, so you should definitely go ahead and try with word to vec also to get a better accuracy at the end of the day. Okay, so yes, this was it from my side regarding this particular project. One important assignment for you is that just try to do it with word to vec. And yes, I will see you all in the next video. Hello guys, so we are going to start the deep learning series. In this video, I'm just going to give you a brief idea about what exactly is deep learning, and we'll also be able to understand the differences between AI versus ML versus deep learning. So to begin with, first let's go with the first thing, that is AI. That is nothing but artificial intelligence. The main aim behind artificial intelligence is to create applications that will be able to perform its own task. Now, probably some of the examples like Netflix recommendation system. Now, in that recommendation system is an AI module because based on some user inputs, it is automatically able to perform and provide recommendations of different movies. Other applications are like self-driving cars, Amazon website, wherein you do shopping. It also provides you some amazing recommendation. Now, coming to the second type, that is with respect to machine learning. Machine learning is a subset of AI, and it provides you stats tool to analyze the data, visualize the data, even to perform various operations such as forecasting, predictions. So all this kind of tasks you'll be able to do with the help of machine learning, right? In machine learning also you have two different types like supervised and unsupervised machine learning technique. Now let's come to the most important part in which this entire series is based on. That is deep learning. Now deep learning is a subset of machine learning, and you need to understand why deep learning came into existence and why it is super popular right now. The main task of the deep learning is to mimic the human brain. So what did researchers do is that can we make a machine learn like how we human being learn different things? So it is about mimicking the human brain, the technique like how we learn various things. We also want to make the application of machine to learn in the same way, right? So that is where deep learning came into existence. And in deep learning, we will be specifically working with neural networks. I'll not just say neural networks, but I'll say multi-layered neural networks. And we will be able to solve various tasks. I'll also be discussing why neural networks are very powerful and all and what all things we are able to do. Now, with respect to deep learning, if I talk about deep learning, in deep learning, also you have supervised and unsupervised techniques, okay? But mainly what all neural networks we will be discussing about, we will start with something called as artificial neural network. Artificial neural network. So here, with the help of artificial neural network, we will be able to solve both classification and regression problem statements, because these are the two important things with respect to a supervised machine learning problem statement, right? So this too will be able to solve with the help of ANN, that is artificial neural network. Second thing that we are probably going to cover is something called as CNN. Now CNN is nothing but convolution neural network, right? Again, this also helps us to solve classification problem statements, and there are a lot of tasks we will be performing with the help of CNN. Now, what is so special about CNN? Here, your input data will be in the form of images and video frames, right? And it performs exceptionally well whenever you have this kind of input data, right? So whenever your input data is in the form of images, video frames, you'll be able to perform a variety of tasks with the help of CNN. Now we'll not just stop in CNN because we have other techniques also which will actually help us to perform object detection. Like you have RCNN techniques, you have masked RCNN techniques, right? Which will also help you to do object detection along with that image segmentation. You have techniques like Detectron, right? You have most famous things like YOLO. You have various versions like version 5, V5, V6, V7. So with the help of this, after learning CNN, probably you also need to learn about object detection. Okay, object detection. And this probably comes as a part with respect to computer vision. Super important, right? Because here we are specifically focusing on input input as in the form of images and video frames. Now, coming to the third main technique with respect to deep learning is something called as RNN. Now, what exactly is RNN? We basically say it as recurrent neural network. Now, why recurrent neural network is super important? Because if our use cases are related to NLP basically means natural language processing. That basically means if our input is in the form of text or any time series data. Time series data basically means forecasting sales, what will be the logistic forecasting, how much raw materials I need to probably procure in the upcoming 6 months. So in this kind of use cases, which involves sequence of data, wherein tomorrow's sequence is dependent on the previous sequences, right? So in that particular case, we will probably be learning about RNN. So specifically, if I talk about the two domain problems that we'll be solving over here, it will be with respect to NLP and time series. Okay. Now we will not be stopping just over here, guys, because there are many things in RNN also, right? We first start with RNN, then we get to know about something called as word embeddings. Then we learn techniques like LSTM RNN, right? Then we learn about GRU RNN. All super amazing techniques which will be super useful in solving various use cases. Then we have something called as bidirectional LSTM RNN, right? Bidirectional LSTM RNN. We have encoder decoder, right? We have encoder decoder, and it will be used for different use cases, which I'm also going to discuss about it. Then we have something called as transformers, super important. And right now, transformers are like you are able to solve any kind of problems. And then you also have BERT, right? Now all these things we will be discussing in this particular series. We'll be solving multiple use cases, and we'll also be using framework like TensorFlow. Right, so framework here we are going to use basically like TensorFlow. Now, if you don't know about TensorFlow, TensorFlow was made as an open source by Google. Google Brains were using this, and we're going to solve many use cases by using these all techniques. Right, along with this, you'll also be seeing that we'll also focus more on end-to-end project in this particular series also. Right, now with respect to maximum research, you'll be seeing that maximum research are basically happening in this particular section, wherein object detection are basically happening, and data sets that are related to NLP. Right, that is text data. Maximum number of researchers, even PhDs, are people are doing. Google is doing immense amount of research with respect to all the text data, how sarcasm can be included, how the model will be able to understand the sarcasm and all. Right, we will be solving good amount of use cases so that you will be able to crack any kind of jobs. But to minimal get a job, what is the main basic thing that you really need to focus on is these three techniques, right? Still, in most of the interviews, they will probably ask with respect to this three and variants of this three, right? And most of the interviews, if you're able to answer them properly, then probably you'll be able to clear the interviews and jobs also. So yes, we will be learning all this particular technique. In the next video, we are going to discuss why deep learning is becoming very popular, right? So I hope you like this particular video. I will see you all in the next video. Hello guys, so we are going to continue the deep learning series. In this video, we are going to discuss about why deep learning is becoming popular. And in order to understand that, let's go back somewhere in 2005, right? So in 2005, if you don't know, Facebook was launched, right? Facebook, many people started using Facebook over there. And with the Facebook, right, many people started posting different stories, let's say photos, images, videos. And then later on, you also saw YouTube coming into the market. Then you probably saw WhatsApp, right? Probably saw LinkedIn, right? Twitter, right? Over here, continuously people are posting something there. In short, data is getting generated, right? So these are nothing but social media platform. Right, and with the help of this particular social media platform, you could see that huge amount of data was getting created. Right, so this was in 2005 it basically started, but as it went time till 2011, 12, most of the social media platform was launched. Right, and because of this, data was getting generated exponentially. This is super important to understand. Data was getting generated exponentially. Right, exponentially. That basically means it was increasing. Right, now at that point of time, companies usually thought of how they can store this particular data very much efficiently. Right, and this data were in the form of images, text, right, documents, videos, right, videos, and many more. Right, and at that point of time, the entire company was thinking of storing this data efficiently so that it can be accessible in a quicker way. Right, so at that point of time, big data was becoming very famous. At that point of time, only big data came into existence, and then in big data, if you know about Hadoop, right? Now you know about Hadoop, HBase, Hive, and all, right? At that point of time, they started storing all this particular data efficiently in this kind of structure wherein you're efficiently able to store the data, and whenever you want it, you can probably access it. And this data is like this database is like kind of thing are not just restricted to structured data. It also includes unstructured data also, right? Unstructured data images can also be unstructured data. At the end of the day, they were finding out a way to store this data efficiently, and they solved this, right? When I was probably about to pass out my engineering in 2011, this big data frameworks were clearly created, right, by companies like Cloudera and all, right? Cloudera, Hortonworks. So if you know this particular companies, they provide you all kind of Hadoop VMs and all, where you can efficiently store data in a better way, right? So that you will be able to access the data from anywhere you want. And nowadays, many companies, many banks are moving to the big data concept because why? Because they will be able to access the data quick and efficiently. But in 2011, 12, 2011, 12, and I'm not saying that deep learning was not famous in 2006 and 7, but there are some reasons why it really became popular. Now, one thing was that, let me give you some of the reasons why it was becoming very popular. First of all, the hardware requirements, right? Hardware requirements. Specifically, if I talk about GPUs, right? Because to train the deep learning models, right? Specifically, you require GPUs. And nowadays, GPUs cost are decreasing. Why? Because there is one amazing company named by NVIDIA, which are coming up with this high configuration GPUs, right? And they're making sure that based on the research, the price is decreasing for all these GPUs and high configuration. Now you'll have GPUs even in cloud, which is cheap to use, so that you'll be able to train the models, right? You'll be able to train the models, the deep learning models, right? Bigger models. So this was one of the reasons. This is also one of the reasons why deep learning is being used nowadays, right? And second thing that I talked about, right? There are huge amount of data, right? So huge amount of data is already generated, right? Huge amount of data is getting generated, right? And this is a very good thing for deep learning models, right? Because deep learning models usually require huge data, right? So deep learning models, deep learning models usually perform well with huge data. Right? So deep learning models perform well. Now, since the data is getting generated, now the companies, they found out a way of storing the data efficiently, but they just can't keep that data in storage itself. They really want to use this data for some important things. How? They can probably make their product more seamless to the front-end user, to the user who are basically using them. Let me give you some of the examples. I hope everybody has heard about this company called as Netflix. Now, initially, Netflix was a movie streaming platform, right? Movie streaming platform. And if I just ask you a simple question, what is the main aim of Netflix? Yeah, you'll say that obviously they need to have a lot of subscription. People should join the subscription plan and probably start watching movies. Along with that, Netflix, one more important thing is that they really want to keep the users engaged in the platform, right? You've seen, like I have some of my friends who can binge watch Netflix for a week time. Like from morning to evening, they can just watch. And how that things are happening, right? Obviously good quality movies, good quality series. But along with that, one important thing, what they did is that based on the data they had, they created a recommendation system. Now, what exactly is this recommendation system? Understand this, guys. This recommendation system is nothing but, let's say I'm seeing an action movie, and obviously Netflix has huge amount of data, like huge amount of movies also, right? Now, if I'm seeing an action movie, if I also get a recommendation of another action movie which may be interesting, then I may probably watch that movie. And this way, I will be engaged with the Netflix platform. And this way, it may happen is that I may also increase my subscription again month by month, right? So this is what Netflix actually want, right? And based on this recommendation system, how this recommendation system is basically getting created, it is from the data from the interaction we basically did that is stored somewhere. Now they really want to use that model, use that data and create some efficient models so that they can bring innovation in their product, and which in turn increases the revenue, right? These all things are basically done to increase revenue, right? So, because of the huge amount of data that is getting generated, deep learning models usually perform well with the bigger data itself, right? Now, coming to this third one, which is again very, very much important, okay? And I'll tell you, I can probably show you this specific graph. And this is what is the relationship between the huge amount of data with respect to performance. If you know about machine learning algorithms, right? Machine learning algorithms. Let me just pull this up a little bit so that it will be put up in line by line. But this is super important to understand, guys. Now, here you have this machine learning algorithms, right? You can see the graph. As the data increases, but after some level, the machine learning algorithm model performance will not improve, right? That basically means the accuracy may not improve, even though I keep on increasing the data. But with respect to deep learning, here you can see that as the data is getting generated more and more, as the data is getting increased more and more, deep learning algorithms perform well in terms of accuracy. And that is what we are going to see, why it performs well. But this is what is the relationship with respect to the amount of data and the performance with respect to deep learning models, right? So this is super important, guys. You really need to understand. And this way, nowadays, a lot of research, since there is a huge amount of data, deep learning models are being used in various use cases. Now, coming to the third one, deep learning models have been used now in many domains, okay? Deep learning is being used in many domains. Now, why I'm saying this, because I've seen use cases. Let me talk about different use cases, even in domains like medical application, medical imaging, all these things are used. It is being used in e-commerce, right? It is being used in retails, right? It is being used in marketing domain. And they are like a lot of domain. The list will never end. In short, in any domain, you probably find out a use case, you can definitely use deep learning. And there are many, right? Because they have different use cases altogether, right? The application by using deep learning models is quite extensive because you have all the different kind of deep learning techniques which will help you to solve different problem statements, right? So deep learning is being used in many domains, and that is the reason why people trust more on deep learning techniques to solve some amazing use cases, right? Now, coming to the fourth and the most important one with respect to why deep learning is becoming popular, and that is because of the amazing open source frameworks, which is open source, right? As you know, two important frameworks. If I talk about two important frameworks, one is TensorFlow, and the other one is something called as PyTorch. Now, if you don't know about TensorFlow was made as an open source from Google. Google used to use this before, right? By the Google Brains team. And PyTorch was basically invented by Facebook, right? And again, both these particular frameworks, you can do amazing tasks with respect to deep learning, let it be RNN, LSTM, RNN, BERT, transformers, you will be able to do this. And because of this open source, what has happened is that many people, the community size has really increased, right? The community size has really increased. Now, when the community size increases, more research usually happens. And because of this, every day you'll be able to see something new is coming in deep learning by using the techniques that I've mentioned over here, all these particular techniques, right? So these are some of the reasons why deep learning is becoming popular. Initially, the main aim, in 2004 and 5, companies were finding problems to store the data efficiently. They came up with Hadoop architecture, they came up with HBase, Hive, Flumes, and all, right? Later on, this company just started thinking they just can't store the data over there and keep it for them, like in the storage device itself, in the server, in the databases like that, right? Instead, they really need to use the data to make their product better so that they will be able to earn more and more revenue. And these are some of the examples: self-driving cars, Netflix, which has been able to automate more tasks, and they're able to solve the problems and use cases what they're actually thinking for, which may inversely affect or which may directly impact the product in a better way, right? So this is the reasons why deep learning is basically becoming popular. Now, in my next video, I'm going to talk about the first basic neural network classifier, which is called as perceptron, a basic unit, and we'll try to understand that how deep learning actually works in a neural network itself. So yes, this was it. I hope you like this particular session. I will see you all in the next session. Hello guys, so in this video we are going to discuss about perceptron. Now, if you don't know about perceptron, guys, it is also a very simple neural network unit. We also say perceptron as a single layered neural network. Okay, we'll try to understand what exactly this is, and in the upcoming videos we'll also try to understand what are the advantages and disadvantages with respect to perceptron, and why do we move towards multi-layered neural network, which is again we call it as artificial neural network. But if I talk with respect to artificial neural network, the difference between perceptron and ANN, I can say perceptron is a basic unit of ANN. Okay, so in this video we are going to cover what is exactly input layer, hidden layer, weights, activation function, right? So let's take a very simple example, and if I talk with respect to perceptron, this perceptron, which is a single layer neural network, it is used in solving binary classifier. Okay, that basically means if my data set has a problem statement which is of kind of binary classification, we can definitely use this perceptron to solve it. Now over here, let me give a very quick example by taking a simple data set. So let's say I have a data set over here, okay, and in my data set I have features like IQ and number of study hours, okay, and the output is either pass or fail. So I need to create a perceptron which will be able to predict based on IQ and number of study hours whether the person is going to pass or fail. So let's say in my data set I already have this particular data set where the IQ is 95, the study hours is 3, the person is going to fail. Let's say the IQ is 110 and if the study hours is 4, the person is going to pass. And let's say if the IQ is 100 and probably the study hour is 5, the person is going to pass. So let's say that I have these 3 data sets, 3 rows of data set with me. Okay. Now how this particular data set will be taken in a perceptron and how it will be trained, that is what I'm actually going to show you. Okay. And with respect to that, we're going to discuss about all these things with respect to a perceptron. Now this is super important, guys. Please try to understand this entire flow, the entire architecture of a perceptron. To begin with, the perceptron will first of all have something called as input layer. Okay, so this is my one input and two input. Okay, now this we usually say it as input layer because the number of inputs that I have is two. So let's say over here I have x1, over here I have x2, and this is my output feature. That is the reason why I have actually created only two inputs in this input layer. Okay, let me again rub it and probably create it once again for you. So in my input layer I have two specific inputs. Okay, super important. Okay, now this specific input, this is my x1 and this is my x2, will get passed to this. Now from here it will get connected to a simple unit of neural network. Okay, and we specifically say this layer as hidden layer. Hidden layer. This is specifically hidden layer 1. Okay, and from here you'll be seeing that this input will be connected to this hidden layer 1. Okay, I'm basically showing you how a perceptron is, what is the architecture, what is the diagram of a perceptron, and I'll talk about what is this x1 or x1 or x2. I've already told you these are my inputs, so it will be going one by one over here. Now in this hidden layer I will specifically tell you that this is a neuron. Okay, neuron. I'll talk about the importance of neuron and all, and in this neuron we specifically perform two tasks and then we give the output. Okay, now this is the diagram of a perceptron, a very simple neural network unit. Okay, why we say this as a single layer? This is obviously an input layer, right? We do not count an input layer as a separate layer. We just count the hidden layer, and in this hidden layer I just have one neuron. Okay, one neuron. So this we specifically say it as a single layer neural network. Now what all operations usually happen in this? First of all, I hope you got an idea about input. Since I have two inputs, x1 and x2, that is IQ and number of study hours, those input will be passing it from here, right? Then the next thing that we really need to understand is about weights. Now what is weights? Let's say that when this input is getting connected to this neuron, this input is getting connected to this neuron, we initialize some weights like w1, w2. Now what is the importance of this particular weight? Understand guys. Let's say this is my left hand, okay? And I'll give you a practical example to make you understand. If I keep a hot object over here, then what will happen is that those signal will get processed through my neurons and it will go to the brain saying that something hot is placed over here. So I have to remove my hand, otherwise it will harm, right? So this processing of the signal and telling my brain that something harm is going to happen, how these things are actually happening, it is all because of the neurons, which is signaling, which is processing that information, and it is telling us that yeah, something harmful is going to happen. Now this hot object when I place over here, the weights are getting activated, the weights are high, and that is the reason I'm removing this particular hand, right? I'm not moving my other hand, right? I'm moving this hand because the hot object is placed over here. And this is all possible because as a human beings, right, our neurons are well trained to handle those things. So the weights will be quite higher when such kind of events happen, and those weights will make sure that our neurons gets activated in that. Okay, so this weights play a very important role, and the entire mechanism of this neural network is that we need to train this weights well, which will be able to identify different tasks for us. As a human being, if I'm seeing a camera, I'm able to identify that I'm talking in front of a camera. If I see a cat, I will be able to identify that okay, I can see a cat. If I probably see an animal for the first time, I will not know it, but somebody will train me. Oh, this is a dog, this is a hen, right? Like that. A kid, when he or she is born, they will not know about any animals from the start. The parents will teach him, okay, this is a dog, this is a dog. Then only he'll come to know, he or she will come to know, right? So this weights will play a very important role, right? So we have discussed about weights, input layer and all, and we have also spoken about hidden layer. Now in this hidden layer, I have one hidden neuron, right? Now inside this hidden neuron, two simple processing will happen. As I said, right? I keep a hot object, some processing will happen, and that signal will go to my brain, right? Which will then I will do a response to stimuli, right? Now over here, two simple steps will happen. This is step 1 and this is step 2. Okay. Now in the step 1, what will happen is that I will do the summation of x of I, w of I. That basically means I'm going to multiply the inputs and the weights, and I'm going to do the summation of all the inputs and the weights, right? So in short, if I try to denote this by z, my step 1 will be denoted by z. I'm going to perform an operation which will be like x1 w1, or let me write this as w1 x1, w1 x1 plus w2 x2. Now since I just have two inputs, that is the reason I've written x1 and x2. Like this, I can have any number of inputs. That basically means I can have any number of features. Input is never restricted, but with respect to hidden layer, I'll just have one neuron in the perceptron. That is the reason we say it as single layer neural network, right? So in short, what we're doing the summation of inputs multiplied by the weights. Okay, super important, right? Now along with this, we will also add one more parameter which is called as bias. Okay, now what is exactly is this bias? Along with this inputs, I will be giving my b, that is my bias. It is denoted by b. Okay, and let's say that I'm going to give a constant over here as 1. Now what is the importance of this bias? So let me just add bias over here, which is like plus b. Okay, so in short, what I'll do, I will write z is equal to summation of w of I, x of I plus b, right? So very simple operation over here, what I've actually written. Okay, or I can also write this as x of I or w of I, same thing, right? So I will basically write summation of I is equal to 1 to n x of I, w of I plus b, right? So this is the step 1 operation. Okay, now what is the importance of bias? There are multiple very important things regarding bias. Let's say if my weights are randomly, usually the weights are initialized randomly initially. Let's say if the weights are initialized as 0, so no processing is going to happen. So this bias needs to have some kind of value, right? So that this entire processing will not become 0 and this hidden neuron will not become deactivated, right? Because all the output will be 0. So what we do is that we add a small bias, and this bias is treated as a noise. And this is super important because we really need to create a generalized model. Noise basically means a data that may be completely different, and our model is also able to handle those, right? In a linear regression term, we also say this as intercept. Okay, and I'll discuss about it as we go ahead. Okay, so this is basically the bias that we specifically have. Now this is what happens in the step 1. Now in the step 2, what happens is that we get the z value. On top of z, we apply an activation function. Now what exactly is activation function? The main aim of the activation function is to transform the value. So here let me write it activation function. We'll be learning about different activation function. Activation function basically transforms the output between some values. Let's say between 0 to 1 or between -1 to +1, right? If I really want something to be between 0 to 1, I may use a sigmoid activation function. So sigmoid activation function diagram also I'll try to show it to you, like how it is drawn. -1 to +1, let's say if I want to make it between 0 to 1. So here I can actually use something called as a step function. Okay, so let me just draw this over here. Now how does a step function look like? So step function is also an activation function. A step function usually diagram looks like this. Okay, so step function which looks like this. So here I have all my values between 0 to 1. Let's say this is 0, this is 1. The another one that can be applied as an activation function. There are many activation functions like ReLU and all. We'll try to understand. We'll try to understand the importance of each of this, right? So here also you can see that I'm having this sigmoid activation function which looks something like this. So my sigmoid activation function will be looking something like this. Okay, so this is between 0 to 1, right? So Again, understand what is the main aim of the activation function. Since we are solving a binary classification problem, at the end of the day, right, after performing this operation, either I should be getting 0 or 1, right? So in case of step function, what we do is that we get two conditions. Okay, let's say this is my z value. If my z value is less than or equal to 0, I'm going to make it as 0. And if my z value is greater than 0, I'm going to make it as 1. So in step function, my threshold value is basically 0. Right? Either I need to get 0 or 1, right? So whatever z value I'm getting, after I apply a step function on top of that, if the z value is less than or equal to 0, it is going to become 0. Otherwise, if it is greater than 0, it is going to become 1. Right? Similarly, in the case of sigmoid activation function, if my z value is greater than 0.5, it will become 1. If it is less than or equal to 0.5, it is going to become 0 because this is 0.5. Right? But at the end of the day, you'll be seeing that I'm able to get a value between 0 to 1. I'm able to transform the value of z between 0 to 1 on both the cases. But here, what is changing? Over here, threshold value is changing. Because here, the threshold is nothing but it is 0.5. Right? So I hope you're getting an idea about why do we apply an activation function, because to solve any binary classification problem in short, right? So we cannot just keep it like this, but we really need to apply an activation function on top of it. So these are the two basic operations that we get. So after this, whatever output we get, right? Let's say whatever output we are getting. Let's say I'm passing this 95.3. Okay, I initialize some weights. This will get multiplied. Then an activation function will get applied. And let's say that I got the output after this is somewhere around, let's say I got it as 0. Right? If I'm getting the 0 for the first record, my real output is also 0. Then that basically means my error is 0. If my error is 0, then the weight that is initialized is very good. But let's say if my error is a little bit high, if my error is 1, then 1 minus 0 is 1, right? So over here, this is my real output for the first record, but I'm getting 1. So what I need to do, I need to update this weights, right? So this error that is getting created, I need to reduce it. So what will happen? We have to update this W1 and W2, right? And this process will continuously go on unless and until we get a suitable weights which will be satisfied for all these particular records and will give us a better accuracy with respect to this particular data, right? So these are the basic operations that we have actually performed. Now let me go back again and show you. The step 1 operation is very simple. We have applied a Z, which is nothing but summation of W of I, X of I plus B, right? Now see, if I probably extend this from I is equal to 1 to n, let's consider that I have n inputs. Then how will this operation look like? W1 x1 plus W2 x2 plus W3 x3, right? Plus like this up to Wn xn. And then I have a bias added, right? Bias added. This equation is similar to the equation that we have with respect to y is equal to mx plus c. In y, we also, if you know linear regression, we also write something like this: beta 1 x1 plus beta 2 x2 plus beta 3 x3, right? Like this up to beta n xn. These two are almost same. And we are trying to solve this. And this is basically used to solve a linear problem statement, right? Linear problem statement. Now, what we are able to do with this step 1 and step 2, let's say if I have a classification problem where I have 2 points like this, where I have 2 specific points like this, then with the help of perceptron, what we are able to do, we are basically able to create a linear line which will be able to separate both the specific points, right? That basically means perceptron is a linear classifier. Right, linear classifier, and that is what we are able to do with the combination of step 1 and step 2. At the end of the day, I need to find out the best fit line to solve the classification problem, right? So this was about a perceptron, and I hope you got an idea about what exactly is input layer, hidden layer, weights, activation function, and like this, there are many activation functions, and each and every activation function has some different functionalities at the end of the day, right? So we will try to understand this more in depth from the next video itself, because we'll try to understand what are the advantages and disadvantages of perceptron, right? So this we will try to discuss in the next video, and then we will go from the single neural network to the multi-neural network, and then we'll try to understand that how does neural network actually work, right? And then we'll try to get the entire clips and idea about it, right? So why single neural network will not be able to use the single neural network to solve complex problems, right? This error that we are also getting, right? We also say this as loss function. Or if we take all the records by once, we basically say it as cost function. And we really need to update this weight by just going forward and backward, which we also say it as forward propagation and backward propagation. Anyhow, we'll be discussing that in the multi-layer neural network. So I hope you like this particular video. This is just a beginning, guys. We are going to learn many things as we go ahead. So yes, I will see you all in the next video. Thank you. Hello guys, so we are going to continue discussion with respect to perceptron. Now, usually in perceptron models, which I did not discuss earlier, we usually have single layer perceptron models and multi-layer perceptron models. Whatever things we have discussed before in the previous video, it is nothing but a single layer perceptron model. Now, we really need to understand the advantages and disadvantages with respect to the single layer perceptron model, and why do we specifically go towards multi-layer perceptron model, which we also specifically say it as ANN, right? So artificial neural network, or we also say it as multi-layered neural network, right? So that is what we're going to discuss. But we really need to understand what are the disadvantages with respect to a single layer perceptron model. Now, over here we have already seen that we pass our inputs, and then what we do, we assign a weights. This weights can be randomly assigned, and then we perform 2 steps. That is summation of these inputs with the weights, and then we add a bias, and we apply an activation function. Then after applying an activation function, if I probably get something greater than the threshold value, I'm going to get either as 1 or I'm going to get it as 0. So I'm going to get 1 or 0, let's say. Okay, but let's consider that for my initial input, I had my real output as 1. Okay, and let's say that after performing all these operations, and whenever I say performing all these operations, I'm talking about from going from left to right. That basically means performing this step 1 and step 2, which we also say it as feed forward neural network, because we are performing this step 1 and step 2, right? Let's say after performing these all operations, if I get a threshold value less than 0.5 or less than 0, less than or equal to 0, I'm going to get an output as 0. But my real output was 1, right? This is my y, but this is my y hat. Obviously, there is an error over here. So what we do, again, we go ahead, change the weights, and again we do the feed forward neural network, right? We perform this particular operation, and then we keep on doing it unless and until we get this particular value similar, right? Again, this is not a very efficient technique, but yes, if I probably consider with respect to advantages, linear separable problems can be easily solved. Separable problems will be solved with the help of this perceptron. Now, what is linear separable problem? Let's say that I have a classification problem, right? Let's say I have 2 data points over here. So these are my first data points, and these are my second data points. Let's say these are my other data points. Now, in this particular use case, what will happen is that with the help of perceptron, we will be probably able to create a best fit line. We'll be able to solve these problems with respect to the classification, and that is the reason we say it as binary classifier. Okay, but again, the technique that is basically used with feed forward neural network, and again, let's say if the error is high, then again we go and change our weights randomly, and probably again do the feed forward. It is not a very efficient technique, right? So in multi-layer neural network, we have techniques called as loss function, back propagation. This was the biggest invention regarding the backward propagation, which we'll be discussing about it. And because of the backward propagation, this weight updation will be happening very seamlessly, right? Over here, with the help of single layer perceptron model, we're just focusing on feed-forward neural network operation. That is step 1 and step 2. But what after getting the error? There's a concept of something called as loss functions, optimizers, which we are basically going to learn in the multi-layer neural network. So if I talk about a single layer perceptron model, it is just good for basically solving binary classifier, which are linearly separable. Okay, super important, which are linearly separable. Let's say that if I have a data set which looks something like this. Let's say if I have a data set which looks something like this, and over here, let's say some of my data points are like this, and these are not linearly separable, right? So my other data points are like this. So I cannot just create just a single line to basically split this particular data points or classify these data points. So this is non-linear separable, right? Non-linear separable. And for this, we definitely require a multi-layered neural network. Multi-layered neural network, because a single layered neural network like perceptron will not be able to solve these complex problems, right? So this was the advantages and disadvantages with respect to single layered perceptron model. In the case of multi-layered perceptron model, we are going to learn about forward propagation. Forward propagation. We are also going to learn about something called as backward propagation. These are some very important topics which I'm going to cover as we go ahead, right? Backward propagation, right? The next technique, we will also be learning about something called as loss functions, right? Let me just write it in another color. So backward propagation, forward propagation is there. Then we're going to learn about backward propagation, as I said, backward propagation. Third techniques, we're going to basically learn about loss functions, right? We'll also be using various activation functions. This will basically be covered in the multi-layer neural network. Super important, various kinds of activation function, which activation function to use when. And then we're going to also cover about optimizers, which is super important, right? Because here we can just go towards the feed for neural network technique, right? We can just perform this step 1 and step 2. We cannot just update the weights based on some mechanism. And this is just not an efficient way of updating the weights in the single layer perceptron model, right? So we'll be using these all techniques in the multi-layer perceptron model, which we also say it as multi-layer neural network, like ANN, artificial neural network. Okay, and this is super amazing, guys, because all these techniques, right, regarding when I probably say with respect to backward optimizers and all backward propagation, these are super cool inventions, right? And with the help of this deep neural network, which we say, with the help of this multi-layered perceptron model, right, we'll be able to create deep layer neural networks which will be able to solve more complex problems, right? And that is what we're going to learn about in the next section about the multi-layered neural networks. This was it with respect to the perceptrons, and yes, I will see you all in the next video. And initially, we'll be having a lot of theory videos, and then we'll move into practicals, guys, right? So this was it. I'll see you all in the next video. Thank you. Bye bye. Hello guys, so we are going to continue the discussion with respect to deep learning. In our previous video, we have already seen about single layer perceptron model. We have seen that what are the disadvantages with respect to this, and why we should actually focus on multi-layered perceptron model, which is nothing but ANN, artificial neural network. And this is where we are going to basically understand like how multi-layered perceptron model works. And in this video, we are going to focus on, or we want to get a very high level understanding of what is forward propagation, what is backward propagation. And this backward propagation has like this entire thing was invented by Jeffrey Hinton. He's an amazing scientist. He is basically called as the godfather of entire deep learning community. The deep learning work that he has specifically done. This is Jeffrey Hinton, an amazing personality. You should definitely read his research, whatever research that he has probably done. But the main research was based on this backward propagation techniques, you know. And because of this, now we are able to actually create very deep neural networks also. And then we'll also get basic understanding of loss functions, optimizers, and activation functions, right? And as we go ahead, we'll be deep diving into each and every topics, and we'll try to understand this. Okay, so let's go ahead and let's try to see this. And again, guys, when I say multi-layered perceptron model, I'm basically talking about multi-layered neural networks. Okay, so let me write it down over here: multi-layered neural network. Okay, multi-layered neural network. This is super important. Okay, now let me give you a 1,000-feet overview about like how a multi-layered neural network works. Because in a single perceptron model, we just had a feed-forward neural network. That's it, right? And then we had some threshold value. If some value is greater, whatever output that I'm getting from this activation or step function or whatever threshold function that we're using over here, if it is greater than the threshold value, we either have 1 or 0, right? And based on that, like let's say if it is not matching, we again go ahead and update the weight. And we just have feed-forward neural network. But we understood what is the problem with respect to that, right? So in this multi-layered perceptron model, what we focus on is we focus on something called as forward propagation and backward propagation. Because of these two steps, you know, the efficient change of weights will actually happen, through which, you know, we will be able to get the model, we'll be able to train our model very much quickly. Okay, so let's go ahead and understand. Whenever I say multi-layered neural network, now let's take this as an example, and this is my data set, right? My data set has basically IQ and IQ of the students, study hours, like in a day, how many hours a student is studying, and then how many hours a student is playing, and based on that, I have a specific output saying that whether the student has passed or failed, right? Whenever we have one value, that basically means passed, otherwise it is 0. Okay, so here you can see that I am having 3 specific features, right? X1, X2, X3. Now these 3 features will get passed one by one to my input layer. So this is specifically my input layer. Now, whenever I say single layer neural network, that basically means I just have one hidden layer, right? In multi-layered neural network, what may happen is that I may have more than one hidden layer, right? So in this particular case here, you can see that I actually have over here. So this is one of my hidden layer. So this is hidden layer 1. Okay. In this hidden layer 1, I have 1 neuron. But in real, we can have any number of neurons. We can also have any number of hidden layers in a multi-neural network. Okay. Multi-layered neural network. And this particular layer is basically called as my output layer. Okay. So over here, you can see that I am specifically having 2 layers of neurons, right? One neuron is over here and one neuron is over here. And I'm saying this as an output layer since this is the last layer of this particular neural network. So in this particular case, I actually have a 2-layered neural network. Okay, we basically say it as 2-layered neural network. Like this, we can have any number of hidden layers. We can also have any number of hidden neurons. So this specifically is my neurons. Okay, neurons. Now let's understand whatever things we have discussed till now with respect to the previous example. Now the first thing, whenever I say forward propagation, this is super important to understand, guys. Whenever I say forward propagation, that basically means we are performing some steps. Now along with this, I've already told you we will also add a bias weight. So let's say this is B1 with 1, and here also since I have 2 neurons, here also bias will get added. So here also I'll be having B2, and again the constant will be 1. Okay, we provide some kind of constant, it can be 1 or -1. B1 and B2 are also initialized randomly. Now as we know, in the forward propagation, in the feed forward neural network, what all things will happen? We will first of all assign weights, W1, W2, W3, right? So these weights are initially assigned randomly, and I'll also be talking about what are the different techniques of initializing these weights as we go ahead. And here you can see B1 is also initialized over here randomly, and B2 is initialized over here. Now from here to here, after this hidden layer is basically connected to this output layer. So I'm just going to have another weight which will be my W4. Okay, so I hope you are able to understand this. Now the first thing is that the first step that I really want to talk about is about the forward propagation. Now as you know, forward propagation basically means what? In this neuron, there are two steps that is going to happen. The first step is that, and again understand, whatever output I'm going to get from this neuron, let me write it as O1, and whatever output I'm going to get after from this particular neuron, I'm going to write it as O2. Now in the first step, what usually happens, we have already discussed, right? Over here, what will happen? It is summation of I is equal to 1 to n, x of I, w of I plus b, right? So that is bias. So in the first step over here, we are basically going to do the summation of x1, w1, plus x2, w2, plus x3, w3. Now I can definitely write, and this will be plus b1, right? I can definitely write this as summation of I is equal to 1 to n, w transpose x, right? Plus b. Now this is what I'm basically using it, right? And this will be I, and this will be I. So this is the first step that is basically happening. And after that, what we do? We apply an activation function on top of z. So this is my step 1. Very simple. And this is my step 2, right? We have discussed about this, right? So over here, let's say that we are also going to do this, and this particular technique, whenever we go and do this, we perform this operation, this is basically called as forward propagation. Okay? So this is basically called as forward propagation. So in forward propagation, we specifically apply this step 1 and step 2 in every hidden neurons. Okay? This is super important to understand, guys. Again, I'm repeating it. Whatever I'm actually doing with respect to this two calculation, it happens in every neuron, right? Now let me go ahead and let me show you what will happen over here. Okay? So let's consider that my W1, W2, W3 is initialized with some values. Okay? So here I'm just going to say my W1 is basically initialized to 0.01. Let's say randomly I'm initializing this. Okay? You can initialize any value. Okay? So this is my W1, this is my W2, this is my W3. Okay. Now in the forward propagation, what will happen? First of all, I will go ahead and compute my Z. So over here, in the first case, I will pass my first record. What is my first record? The IQ is 95, so X1 will have 95. Study hour is 4, so X2 is going to have 4. And play hours is 4. I'm going to have X3 as 4. Okay. So what I'm going to do? I'm going to multiply 95 by W1. So here it will be 95 multiplied by 0.01 because the W1 is 0.01. Okay. And let's say the next one is nothing but 4. 4 multiplied by the weight 2, right? Because this both will get multiplied. So this weight 2 is nothing but 0.02. And W3, which is nothing but this 4, right? This is X3, right? X3 is nothing but 4. Then again, it will get multiplied by 4 multiplied by W3, which is nothing but 0.03. And then I'm going to add this bias. Let's say that the bias initialized over here in this particular case, I can consider it anything. So here let's consider that I'm going to initialize it to 0.001. Okay. So this is what is the bias that I'm considering. Again, it can be randomly initialized. We'll talk about all the initialization technique and which initialization technique we should definitely use. So this bias will get multiplied by 1. So it is 0.01. So this is what is my entire Z value. I'm just doing the summation of weights and the inputs, summation of inputs and the weights plus bias. Okay. And this is the same thing that we have written over here. If you probably do the output calculation, I got somewhere around 1.151. Okay. So this is the output that I'm getting. And this is obviously the step 1 in any neuron. In any hidden neuron, right? In this hidden neuron, this is the first step that is going to happen. Now in the step 2, what is going to basically happen? We are going to pass through an activation function and we are going to pass this particular Z value. In this video, let's discuss about one simple activation function which is super important, which is called as sigmoid. Now what is the main aim of sigmoid is that sigmoid curve is basically created like this. Whatever Z value we give, right, it is going to convert this Z value between 0 to 1. Okay, so what it is going to do, it is basically going to convert this Z value into 0 to 1. Right? I'll talk about this. Why it is basically why we specifically use this. Let's say this is 0.5. That basically means whenever I pass this Z value to this function, and this function mathematically is denoted like this. Okay, so we basically write sigmoid is equal to 1 plus e to the power of minus Z. So whatever Z value that I'm getting over here, if I pass it over here, right, to this equation, I'm always going to get the value between 0 to 1. Now understand what is the importance of this. Let's say I'm keeping a hot object on my hand, right? Now when I keep my hot object on my hand, my weights will get triggered. And based on the activation function like 0 or 1, my neuron should get activated, right? My neurons should get activated because saying that, okay, in this neuron, my hot object is placed, I have to remove this hand, right? So what is exactly happening over here? As soon as I keep my hot object, if this neuron is getting activated, that basically means through this sigmoid function it is becoming 1. Okay? And it is saying that, okay, something is placed over here. I have to do some response to stimuli. I have to probably remove my hand. That is what exactly is happening. So this activation function plays a very important role in activating the neuron and deactivating the neuron. Now when I say deactivating the neuron, just understand this. If I place a hot object in my hand, I'm not removing my left hand. I'm removing my right hand. That basically means the neuron in the right hand has got activated. The neuron on the left hand is deactivated because it does not have any role. This is feeling the pain and this is sending the signal. And this is all possible because of the correct weights. Right now, we have just initialized the weights. We need to train this entire model in such a way that we should get the exact weights. Okay? So here you can see that in the step 2, what I did over here, and this is with respect to hidden layer 1. Okay? This is with respect to hidden layer 1. So in the hidden layer 1, I performed step 1 and step 2. After this, I passed my activation function. Let's say this is f of z, and here I'm just going to pass 1 plus e to the power of minus whatever value this is, 1.151. Okay. Now once I get this value here, you'll be able to see that I will be getting some value, and this value, if you probably do it with the help of calculator, you'll be getting somewhere around 0.759. Okay. That basically means the output of the hidden layer 1, that is O1. Here O1 is nothing but it is 0.759. Okay. 0.759 with respect to the hidden layer 1. Okay. Very simple, very easy to understand what has happened, and mathematically I've shown you. Okay. Now in the hidden layer 2, and this is we're still in the first record. Later on we'll go to the second record when I will tell you. Okay. Now let's go to the hidden layer 2 because this O1 will now get passed to hidden layer 2. Right? Hidden layer 2. That is what is happening over here. See, this O1 will get passed to hidden layer 2, that is O2. Now in here also, we have initialized a weight W4 in this layer, and another bias B2 is getting added along with this. So in the next operation, what will happen? Let's say I'm again going to consider Z. O1 is going to get multiplied by W4, and then this will be plus B2. Now let's say that we have initialized W4 randomly. Again, let's say the initialization of W4 is 0.02. I've just initialized it randomly. You can initialize any value because I really want to show you how things happen in forward propagation. Then let's say bias 2 is basically initialized to 0.03. You can add up any values, okay, as such. So what is O1 over here? O1 is nothing but 0.759 multiplied by 0.02 plus 0.03. Okay, so this becomes my Z value. So what is my Z value over here? My Z value is nothing but it is 0.04518. Okay. Now this is my step 1, again hidden layer 2. In the step 2, what we do, we pass through the activation function. As I said, again I'm going to pass this Z value to my activation function. Okay. I'm just giving this Z as a notation. And what is the activation function? It is nothing but 1 plus e to the power of minus whatever value I'm getting over here, 0.04518. So what will be the output over here? It will be nothing but 0.51129. Okay. So this is the output that I'm getting. That basically means here my O2 will basically have this output. Right. So O2 is nothing but 0.51129. Perfect. So since I had two hidden layers, both these hidden layers are able to perform the operation, and now we are in the output layer with this particular value 0.51121. Okay. Now it is super important to understand. After we get the output, the most important thing that we get now is something called as loss function. Now, what exactly is loss function? Loss function, what it does is that whatever output that I've got in O2, that is the predicted output of this particular model. Okay, that is the predicted output of this particular model. Now, what is the predicted output for this particular model? Let's say I'm getting 0.51129. So over here, this O2 or this output, I will just denote this as y hat. Y hat is just like predicted. Okay, so my predicted output, I will just use like this brackets. So it is nothing but 0.511.51129. Okay, 29. Okay, so this is my predicted output. But I also need to find out what is my real output for this record. My real output is this much. That is 1. So what is 1 minus 0.5111129? It will be approximately equal to 0.41. Now this loss function is basically talking about the error we got. Super important, right? The error we got over here. And the error is high. Because if I get my predicted output as 1, then only my actual output and my predicted output will match. But here it is not matching. So I'm getting a loss function of 0.49, which is my error. And my main aim, whenever I'm training this model, is to reduce this error. And right now, I'm having a good amount of error, that's 0.49, right? Now, based on this error, we need to minimize it. And how can we minimize it? The only way to minimize is to update this all weights, to update all these weights, right? So the updation process will be going from the back end process, from here to here. First, we need to go ahead and update W4, then we'll go and update W1, W2, W3. And this process is basically called as backward propagation. Very simple, right? I made you understand what exactly is happening. And in the backward propagation, what we do, we try to update every weights. I'll talk about what is the weight updation formula in my next video, but this is just to give you a 1,000 feet overview, right? So once the backward propagation happens and all the weights are updated, then what will happen? Then the next input will be sent. Once the next input will be sent, again, in this hidden layer 1 and 2, all the steps will happen again. Again, we'll go in the output layer. Again, the loss value will be calculated with respect to this output. And if the loss is not less, we'll try to reduce again the weights value. Again, this process of forward and backward propagation will happen unless and until we reduce our loss function. Okay, loss function. Now, there is one very important thing. What is the difference? And this topic we will be learning. What is the difference between loss function versus cost function? Okay, and there are different loss function and cost function also. I'll discuss about it. Now, just see that, guys. When I did y minus y hat whole square, I was doing this for every points. Understand this? I was doing it for every points, right? But now, with respect to cost function, just imagine that this loss function. As soon as I was passing every single point, I was calculating y minus y hat. Okay, so this is super important. For every point, I was calculating y minus y hat whole square, right? The difference between the truth and the predicted. But with respect to cost function, here we calculate this error for I is equal to 1 to all the endpoints, y minus y hat whole square. That basically means we don't calculate the error in every point and update the weights. We just calculate the error at once and then we update the weight only at once, right? So if you're still getting confused, don't worry. What I will do is that I'll again repeat this. What is the difference between loss function and cost function? Not right now, but exactly I will try to show you when I'm discussing about the loss function, the different type of loss function. But from the overall 1,000 feet height, I think you've got an idea about what is the difference between forward and backward propagation. And we have also learned about this one. If I talk about the backward propagation, how this loss function is getting reduced, how these weights are getting optimized. For this, we use something called as optimizers. Okay, we use something called as optimizers. Now, this optimizers is super important because it helps us to do backward propagation. It helps us to reduce this loss function, and then we update the specific weights, right? And obviously, in this video, I've also discussed about sigmoid activation function. There are also different activation functions like ReLU and all are there, which I will be discussing about all the different activation functions and when we have to use which activation function. But I hope you got this idea about how a multi-layered neural network actually works. That was the main aim, to just make you understand what all happens in the forward and the backward propagation. In the next video, we'll deep dive into this backward propagation and we'll try to understand how things basically happen. So this was it from my side. I will see you all in the next video. Thank you. Hello guys, so we're going to continue the discussion with respect to deep learning. In our previous video, you've seen the high level overview, right? 1,000 feet high level overview regarding forward propagation, backward propagation and all. Now we'll deep dive into backward propagation and we'll try to understand what is the main use and importance of it. Now, yet over here, this is a 2-layered neural network because I have my hidden layer 1 and the output layer, okay? And again, as I said that in a hidden layer, I can have any number of neurons and I can also add any number of hidden layers, right? So here what I've done is that I've taken this input layer and I'm giving 3 inputs, which based on my data set like this, x1, x2, x3. These inputs are basically my independent features. This is super important to understand, guys. These are my independent features, right? And this is my dependent feature, okay? Dependent. That basically means this value will change based on this inputs getting changed, okay? Now, here you can see that for solving this problem, I've taken an input layer which has 3 inputs, that is IQ, study hours, and play hours. In the hidden layer, I've taken 2 neurons, right? And bias is also getting added over here. Bias, next bias is also getting added. Here you can see this all inputs will be connected to all the hidden neurons also. And here you can see W1, W2, W3, W4, W5, W6. These are the weights that are getting initialized, right? And then from the hidden layer to the output layer, I'm connecting it with 2 lines, which is having W7 and W8 as a weight initialized, okay? And this is basically my output layer. Now, you may be thinking, why I've used just 1 output neuron over here, right? This is very important to understand. Why can I add 2? Understand the type of problem statement that we are solving right now. It is with respect to output 0 or 1. So this particular neuron is going to give the output as 0 or 1. So that is the reason I'm just use 1. Let's say if this is a multi-class classification problem, suppose let's say there are 3 outputs over here, I can basically use 2 neurons, right? So it can either give 0, 1, 2, like that kind of outputs, right? So with respect to that, I can give 2 or 3, right? Based on the multi-class classification, I can add that many number of neurons in the output layer. Now, this is clear. I hope everybody's clear with the forward propagation. As I said, in the forward propagation, what we do, we take this inputs multiplied by the weights, and then we add a bias, and then we apply an activation function. Now, since I have used 2 neurons over here, now the matrix multiplication that is going to happen will have a shape of 3 cross 2. Why? Because I have 3 input layers and 2 hidden layers. So x1, w1, x1, w2, x2, w3, x2, w4 will get multiplied and it will keep on getting added, right? x3, w5, x3, w6. So I'm going to get this kind of neurons. That basically means from here, I'm going to get x1, x2, x3, right? And from here, I'm basically going to get 2 layers, w1, w2, w3, w4, something like this. Let me just write it down again. So Here it is. So let's consider this one. So I have 3 neurons. So here what I will be getting, sorry, 3 inputs. So here I'll be having x1, x2, x3, right? And in the other side, the other matrix will have w1, w2, w3, w4, w5, w6. Okay, so something like this, right? So if I probably consider this, now see, with respect to this x1, I'll be multiplying with w1, w2, then x2 will get multiplied to w3 and w4, and it will get added, obviously, and x3 will get multiplied with w4, w5 and w6. So in short, if I probably combine these two matrices, I'm going to get a final shape of 3 cross 2, right? 3 cross 2 matrix. So just to understand this, just understand in a simpler way, we're just multiplying two matrices, okay? Then what we do, we apply an activation function, we go ahead, we find out the output, and finally we go to the output layer. Then after this, what we do, we calculate a loss function. Now, since this is a binary classification problem, and there are multiple different types of loss function. Some of the loss function, I'll just like to mention it over here, so that, and we'll discuss about this loss function. For regression and for classification, we have different loss function, okay? And for regression, let's say I have something called as mean square error. For regression, I have something called as mean absolute error. Third one that I can basically use is something called as Huber loss, right? Similarly, in classification, I have different loss function like binary cross entropy, and then I also have something called as categorical cross entropy. We'll discuss about this, don't worry, okay? Categorical cross entropy. We'll discuss about all these loss function in depth in the upcoming videos. Okay. So in short, these all are some formulas which will basically, if I really want to use a simple loss function, I will just say y minus y hat whole square. That basically means whatever is the predicted output, whatever output that I'm getting from here, that will basically means the difference between the real output will be calculated. And our main aim is to reduce the loss function. Let's say if we get a very big loss function, then what we do, we have to update all these weights. And updation of the weights usually happens in the backward propagation. Okay. So this backward propagation will happen. Okay. And how the weights updation formula will be there, I will talk about it. Okay. So backward propagation will happen, wherein we will focus on subtracting these weights and updating it. Okay. Now this is the idea, and this is what we discussed in the last class also, right? Now let me go ahead and let me show you with respect to the weight updation formula. This is super important. Okay, weight updation formula. Now in the weight updation formula, here you can see that when I am doing the backward propagation from here, from the loss, I'm going to do the backward propagation. The first weight that I will be probably getting is something called as W7 and then W8. Okay. Now this W7 will get updated something like this. So W7 is equal to, and I would just like to write W7 new because this will be the new weight, is equal to W7 old minus this notation. I will explain you what exactly this notation is, and then along with this, we will try to take derivative of loss, whatever loss I'm getting, okay, derivative of loss with respect to derivative of W7 old. Okay. Now this is super important to understand what this derivative of loss with respect to derivative of W7 old is. This in short is that we are trying to calculate the slope of the graph which we plot with respect to the weights and the loss function. Usually, with respect to different loss that we have like MSE, MAE, or binary cross entropy and all, right, we usually get something called as gradient descent. Okay, so this is what a gradient descent is. This kind of curve usually is created by a gradient descent. And if you know machine learning, if you just know linear regression, if you've seen my video with respect to linear regression, so here you'll be able to see that this is the global minimum. This is where we have to come, or we have to arrive. Our entire weights should come to this particular location because here the slope is exactly 0. And when the slope is exactly 0 over here, that basically means we don't need to update the weights. Okay. So derivative of loss with respect to derivative of W7, let's say it is this specific point. So when I do derivative of loss, in short, I'm just trying to find out the slope. And I'm saying that whether this is a positive slope or negative slope. Okay. And by this, we try to update this specific weight. Okay. And this is the formula. For W7 new, this will be the formula. For W8 new, this will be W8 old minus this value with respect to derivative of loss with respect to derivative of W8 old. I will talk about this. What is this parameter also? Okay. So this parameter is basically called as learning rate. Okay. I'll talk about the importance of learning rate also. Okay. In this video only I'll be talking about. Now, why this formula will work. Okay. And like this, we have all the weights, and probably if I really want to write a generic way of writing, it is nothing but W new is equal to W old minus the learning rate of derivative of loss with respect to derivative of W old. So this entirely is my weight updation formula. This entirely is my weight updation formula. So this is my weight updation formula. Okay, so it is very simple. Now, why this formula will definitely work? Let us understand this. Okay, let's say I have this gradient descent, because with the help of this loss function, with the help of this whatever loss function we are trying to use, we will be getting this kind of gradient descent most of the time. And we'll try to understand whether there is a chances of any local minimum or not as we go ahead. But just understand the importance of this loss function is that we will be almost getting this kind of gradient descent when we plot with respect to weights and the loss function. Okay, so let me just go and draw this. So this will be my gradient descent. Let's say. Okay, now my main aim is to basically update all these weights with the help of backpropagation. Whenever we get this kind of loss function, if we want to minimize this loss function, we use a concept called as optimizer. And this is what an optimizer will do. This optimizer is called as a gradient descent optimizer. And there are different types of optimizers also, which we are going to discuss. Let's consider a simple gradient descent optimizer. Okay, gradient descent optimizer. And like this, we'll have many optimizers. The optimizer's role, again, let me repeat it. What are the optimizer's role? This optimizer's role, I'm going to write each and everything. So just be patient and just try to understand these things. Okay, so what are the optimizer's role? Optimizer role is to reduce the loss value. Super important. Okay, that is our main aim, and we will be only able to reduce this loss value. We'll be able to reduce this loss value only by updating this weights, because in the backward propagation we are updating all these weights. Now let's say how the weight updation will happen. Now you know that our aim is basically to come in this. Why? I'll talk about it. Why? Let's say this is my initial weights, and with respect to this weight, let's say I've got this loss function. Now this is super important. Okay, I've used the formula which is W new is equal to W old minus learning rate of derivative of loss with respect to derivative of W old. Whenever I say derivative of W old, right, I need to update this weight. That basically means I am trying to find out a tangent over here, or I'm trying to find out the slope with respect to this line. Okay. Now the first thing is that with respect to the slope basically means with the unit movement in the x-axis, what is the unit movement in the y-axis? That is what is the slope that we really need to compute. Okay. Now the first thing is that we need to understand whether the slope is positive or negative. And the best way to understand this is that see the right side of the line. The right side of the line. The right side of the line is pointing downwards. Whenever this right side of the line is pointing downwards, understand again what I'm repeating it. Whenever the right side of the line is pointing downwards, okay, then what kind of slope we will be getting? Just think over it. We will be getting a negative slope, and this can be proved mathematically also. You just go and see. right? If it is pointing downwards, it is basically saying it as a negative slope. That basically means W and loss are inversely proportional, right? So if I, with respect to this, whenever I try to calculate the derivative of loss with respect to this particular value of weight, you'll be seeing that I'm getting a negative slope. Negative slope basically means negative value. Now my W new will be nothing but W old minus learning rate with some negative to negative value, right? So that basically means what is basically happening, and this is basically 0, and as we go ahead and increase, W is increasing in this direction. Now, this is a negative value, right? So if I try to add this up, W old plus, it will be learning rate with a positive value now, right? So here we are increasing the W value. So finally, you'll be seeing W new will be greater than W old, right? Because negative into negative is positive. So what we are doing over here, we are probably trying to increase the weight. And understand, we need to come to this location. Why? Because in this location, this point is basically called as global minima. Super important, okay? This point is basically called as global minima, okay? And now main aim is to come over here. And you can see with the help of this weight addition formula, we are doing the same thing, right? First of all, with this W, I got it at a negative slope. So if I'm getting a negative slope, that basically means I have to increase the weights to this particular point, and that is basically happening. The W new value that we're going to get is going to increase. So this is definitely going to work. Let's say with respect to the other scenario, let's say if the W value is over here, then with respect to this, I'm getting the loss value over here. Now let's go and calculate the slope over here also. So here, let's say the slope is this one, okay? Now in this case, you can see the right side of the line is pointing upwards, okay? Let me write it down much more in a better way. Let's use the green color. So this is my slope. Now when I try to calculate the slope, this right side of the line is pointing upwards. When it is pointing upwards, this becomes a positive slope. Now when I have a positive slope, that basically means I have to decrease my W value to come to this, right? So if I try to apply the same formula, what will happen? W new is equal to W old minus learning rate of derivative of loss. Derivative of loss, derivative of W old is nothing but this is a positive value. So minus into positive is positive. So W old minus learning rate with some positive value. In this scenario, the W new will be less than W old. Do you agree? Because we are reducing something. It will obviously be less than this one, right? We are reducing something. So based on this two condition, we are able to get this, right? And at the end of the day, my main aim is to come to this point, right? So definitely this weight addition formula will work. Okay, this is super important. Then what will happen? Let's say the next point. Let's talk about this one, the learning rate. This is super important. Learning rate. What is the importance of learning rate? Let's say if I initialize this learning rate to a smaller value, let's say the smaller value is 0.001, and usually we initialize the smaller value. Then what will happen? Let's say for this scenario, I will just add this W old by a smaller value. So my next point, what will happen? The weight will get updated to here, right? And with respect to this, my new loss function will come over here. So this learning rate decides the step size towards this global minimum, how fast it really want to converge, right? Because it will be a continuously iteration process, right? We need to continuously update the weights because we're doing the backward propagation, then again we'll do the forward propagation like that, right? What happens if we initialize this to a large value? This is also very super important to understand. Then what will happen? From this point, you'll see that we'll not be having a small step size. We will be jumping here and there, right? Because the value is quite big. And sometimes it may happen is that we may go outside this gradient descent and it will never converge. So in this scenario, it may never converge. So it is always a good practice that we take this learning rate to a small value. Super important, right? So I hope you got an idea about what we're discussing over here. At the end of the day, we need to come to this global minima. So when the optimizer will understand that, okay, finally the weight updation is done. See, once the W comes over here, right? Over here, when we try to calculate the slope will be 0. So this entire value will be 0. Right? When this value will be 0, this into this will be 0. So W new is equal to W old. So when W reaches, so I'm going to put a very important point. When W reaches global minima, my W new is equal to W old. That basically means I've reached my global minima. I don't have to update more weights, and my loss function will also keep on reducing. Because over here you can see the loss is near to 0, right? If we go downwards, over here also the loss is decreasing. Initially the loss was high, and when we are coming downwards, it is becoming 0, right? So this was the idea about gradient descent optimizer. Similarly, there are many types of optimizers which we are going to learn, and we'll try to understand what are the importance of each and every optimizer as we go ahead. But I hope you got a clear idea about the weight addition formula and what exactly is happening in the backward propagation. But still, we just discussed about W7 and W8. We also need to know that how does W1, W2, W3, W4, W5 weights will also get updated, because this W1 is dependent on W7 also. I mean, this W7 is also dependent on W1. W8 is also dependent on W2 because this is connected. And that is what we are going to learn in the next video, which is called a chain rule of derivative, right? And we'll try to understand how chain rule of derivative is useful in calculating the weights of W1 and all, right? So yes, this was it from my side. I hope you're able to understand this. This is super important, guys. If you understand the theory well, trust me, implementation wise it will be very, very easy. So in this video, we have covered about backward propagation and weight addition formula. Now you have probably got more inside it. Yes, don't worry, we'll be talking about all the loss functions also. We'll go step by step and we'll try to understand that, okay? So yes, I will see you all in the next video. Thank you. Hello guys, so we are going to continue discussion with respect to deep learning. In this particular video, we are going to understand about something called as chain rule of derivatives, a super important topic because this is something related to the weight addition formula itself. So till now, already you've seen, we have discussed about the weight addition formula. We know the formula over here. The generic formula is basically written, right? So if I probably talk about the weight addition formula, again, let me write it down over here. W new is equal to W old minus learning rate of derivative of loss with respect to derivative of W old. So this is the entire formula that is basically used for the weight addition. Now let's go ahead and understand what exactly chain rule is, okay? So as you can see this, right? This is my input layer, this is my hidden layer where I have just one neuron, this is my output layer. So let me just write it down so that you don't get confused. This is my HL1 and this is my output layer. And finally, I get my output, and then we calculate the loss function, and then we do the this was initially the forward propagation, and then we do the backward propagation. Backward propagation, we update the weight. Now let's imagine if I really want to update W4, right? And obviously, see guys, in the forward propagation, after the processing that happens, let's say that this input is O11 and this input is O21. Or I can also write it as O1 output and O2 output. So basically, after doing all the processing and applying the activation function, I'm getting the O1 output after this neuron, and this is basically my O2 output after this neuron. Okay. Now, if I really want to update W4, then the formula is quite simple. What I write, so it is nothing but W4 new is equal to W4 old minus learning rate of derivative of loss with respect to derivative of W4 old, right? And obviously, you know that if I take this term this term, right? And if I expand it, how will this expansion look like? Now see this guys, this is super important. So if I just take this term and basically write derivative of loss with respect to derivative of W4 old, it is nothing but derivative of loss. See, loss is entirely dependent on O2, right? So I will be writing derivative of loss with respect to derivative of O2, and O2 is dependent on W4, right? So here we can split this equation of derivative of O2 with respect to derivative of W4. So once we write like this, here you'll be able to see that the same derivative has been expanded in this way. And at the end of the day, if I cut this 2, right? If I cancel out this 2, it is going to remain the same thing, right? Derivative of W4. So this splitting of this derivative is basically called as chain rule. Okay, chain rule of derivatives, super important. Okay, and that is how we will be able to compute each and every component with respect to finding the updated weights, right? So whatever value we'll be getting, whether it is a positive or negative value, then we will multiply with our learning rate and then we'll updating the W4 weights. Now let's go ahead. With respect to W4, it is fine, but let's go ahead and try to update W1 or W2 or W3. Now with respect to W1, what my formula will be? It will be nothing but W1 new is equal to W1 old minus learning rate of derivative of loss with respect to derivative of W1 old. Now let's consider this. And let's go back and let's expand this with the help of this chain rule. Now here you can see the output from this neuron is O1, right? So this W1, O1 is dependent on W1, right? This O2 is dependent on W4. And in short, you'll also be able to see this O2 is also dependent on O1. So how we can actually expand this with the help of chain rule? Now this is super important to understand. You can pause the video, you can just try it by yourself. Anyhow, I'm just going to show you. So let's go ahead and let's show you this particular method. So here, what I can do is that I will write derivative of loss with respect to derivative of W1 old is nothing but here, first of all, derivative of loss is dependent on O2. So here you can find out this loss is dependent on O2. Then O2 is dependent on W4, right? Then W4 is dependent on O1 and then O1 is dependent on W1. So I hope you're able to understand this, what we are basically doing with respect to updating this W1 and the other values, right? So here you can see that loss is dependent on O2. This W4 is basically getting combined with O1 and W4, right? So that is the reason O2 is dependent on O1 also, right? So here I can basically go ahead and write derivative of L with respect to derivative of O2 multiplied by derivative of O2 multiplied by derivative of O1. Sorry, divided by derivative of O1. Understand this. Loss is dependent on O2. O2 is dependent on O1 because O1 is getting multiplied by W4 and an activation function is getting applied to get O2. And then this O1 is dependent on this one, right? So this is how it basically goes, right? So similarly, the chain rule will be like derivative of loss with respect to derivative of O2, multiplied by derivative of O2 with respect to derivative of O1, and finally we'll be having derivative of O1 multiplied by derivative of W1 old. So if you deduct all these things at the end of the day, I'm going to get this, right? So this is how a chain rule basically happens, okay? Now there are two assignments that I really want to give it to you. Just try it for updation of W2 new also and W3 new also, okay? Now one more thing, let's say that this is another neural network. In this neural network, what all things are there? And this is also an assignment for you. But anyhow, I'll give you the answer, okay? This is my input layer, okay? Just understand this. This is my hidden layer 1. This is my hidden layer 2. And this is my output layer. Okay. Now here, first time I'm using two hidden layer. In the hidden layer 1, I have one neuron. In the hidden layer 2, I have two neurons. In the hidden layer 3, I have basically the output layer, I'm just having one. So that is basically nothing but a binary classification problem. So the assignment question is, how do you update W1 new? Okay, so this is W1. So here I need to find out this one. Okay. Now this is very important. Loss is dependent on O31. O31 is dependent on O21 also. O22 also. O22 is dependent on O12. O21 is dependent on O11. And these both are dependent on W1. So how do you think? Obviously, this equation is very simple, right? I will write W1 new is equal to W1 old multiplied by learning rate derivative of loss with respect to derivative of W1 old, right? So this is the formula. But now the main thing is that I want you all to expand this equation according to the chain rule. Okay. So let's go ahead. You just try it by yourself and then I will show you. So this is nothing but derivative of loss with respect to derivative of W1 old. This is nothing but, first of all, I want to find out derivative of loss with respect to W1, right? So first, loss is dependent on O31. So I will go ahead and write it. Let's see this. Okay. So I will go ahead and write it. Derivative of loss with respect to derivative of O31. Okay. I'm just going to make this bracket. Now O31 is dependent on O21 also, O22 also. First of all, let's go with this side. Okay. So O31 is dependent on O21. So here I will write multiplied by derivative of O31 divided by derivative of O21 multiplied by derivative of O21 divided by derivative of O11. So here you have derivative of O21 divided by derivative of O11. Okay. And then finally you'll be able to see derivative of O11 will be dependent on W1 old, right? So here I will write derivative of O11 divided by derivative of W1 old. Okay. So this is the first side, right? I hope you're able to understand this is the first side. But we did not still pass this, right? We went through this rule, right? From here to here we went and we went here to here and finally we updated this. But what about this? This part is also dependent, right? Here you can see O31 is also dependent on O2, O2 is also dependent on O1. So what I'm going to do, I'm just going to do an addition, and this addition will now have another layer which will say derivative of loss with respect to derivative of O31 plus derivative of O31 divided by, it should not be plus, it should be multiplied. Because chain rule it says that derivative of O31 divided by derivative of O22. Why O22? Because this is O22 output, right? Right? O31 is nothing but O22 multiplied by W5, and then an activation function we specifically apply like sigma. Okay. And then you can also see that I will be writing derivative of O22 with respect to derivative of O12, I guess, right? So this is nothing but derivative of O12, and then O12 is directly dependent on W1. So finally, this is how my derivative of W1 old. So this is how my chain rule will look like with respect to the updation of derivative of loss with respect to derivative of W1. So if you really want to update this will entirely get converted to this equation. And that is how a chain rule actually works, a chain rule of derivative. I think you may have studied this in 12th standard and 11th, 12th standard, right? So this you will definitely be able to understand. Okay. So this is what is a chain rule of derivative, and this always happens with the help of, because see, at the end of the day, if I'm trying to find out derivative of loss with respect to O31, here we're just trying to find out the slope, right? And because of the optimizers, we'll be able to find out the slope efficiently. And that is how we get the entire values. Okay. So yes, this was it. I will see you all in the next video. In the next video, we're going to see more exciting things. We have completed the chain rule of derivative. Still, there's so many theories to come up. We have loss functions, we have activation functions, we have optimizers. We need to see what are the different types of activation functions. Why only sigmoid? Can I use some other activation function? What is the advantages and disadvantages? Everything I'm going to cover up. So yes, this was it from my side. I will see you all in the next video. Hello guys, so we are going to continue the deep learning series. In this video, we are going to discuss about vanishing gradient problem. And going forward, we are also going to discuss about various kind of activation functions. Now, till now, if you see that, we have also seen the chain rule of derivatives. We saw that how the weights are getting updated. In the backpropagation, the most important thing is that the weight updation is very, very much important, and it usually happens with respect to the chain rule of derivative. So let's take one more example over here, and let's understand what exactly is vanishing gradient problem. So over here, you can see that I have one input layer, two hidden layer, and one output layer. So if I probably want to talk about this artificial neural network, I'll basically say two-layered neural network, right? So two-layered, one layer is this one, hidden layer two, and output layer. And over here, you can see that in every hidden layer, I just have one neuron, just to keep it much more simpler, so that I can explain you the topic much more efficiently. Now, from this input layer, you can see x1 input is going over here. W1 weights are getting assigned. Then you can see B1 bias is getting added along with this. And as you know that inside this particular neuron, what happens? The input will get multiplied with the weights, and then a bias will get added. And then we apply an activation function, which is called a sigmoid. So till now, I think we have understood what exactly sigmoid is. So let's say that the sigmoid activation function, what it does is that it basically, if I probably consider, first this is my z, right? It does summation of I is equal to 1 to n, w of I, x of I plus bias, right? And then after this sigmoid activation function, whenever we talk about sigmoid activation function, we basically apply after this. So let me just again write it down over here. So that will be very much simple. So the first step, usually in every hidden neuron, what happens? Summation of I is equal to 1 to n, w of I, x of I plus bias, right? And after this, what we do? We apply a sigmoid activation function. This is my step 1. And in the step 2, I just apply a sigmoid activation function. Here I'm giving a notation for sigmoid, and we'll continue discussing the specific notations. Why I'm using this notation? There's also some other notation which looks like this, okay? And in research paper, I've seen this notation also, in this notation also, right? For sigmoid, right? Over here, this is basically sigmoid, this is basically sigmoid, okay? Sigmoid. So here, going forward, I'm just going to use this particular notation to make sure that to just indicate that how does the sigmoid actually look like, okay? So this usually happens in the step 1, and then you have this in step 2. Whenever I talk about sigmoid, you have to always remember what kind of diagram I usually get, the main aim of sigmoid, okay? And probably I will explain you this one very much properly, because in this video, we're also going to discuss about sigmoid activation function. So sigmoid activation function, okay? Now, sigmoid activation function, as I said, the main aim of this activation function is to take the z and transform its value between 0 to 1, right? And this is specifically used in binary classifications, where I probably need to have either 0 or 1 as the output, okay? So if I talk about how the mathematical equation is with respect to sigmoid, so suppose if I say this is my notation of sigmoid, this is nothing but here is the mathematical notation that we specifically use. That is 1 divided by 1 plus e to the power of minus z. And if you really want to know with respect to in graphical representation how this looks, so let's say this is my entire z axis. So this is my z value, and this is basically my sigmoid of z, okay? So let's say over here I have 1, 2, 3, 4 like this. I can extend it to any number, and I have -1, -2, -3, -4. So whenever we take any z value, and whenever we apply the sigmoid activation function, this I'm just going to consider it as 0.5. I'm always going to get a graph which looks like this. So at the end of the day, the sigmoid will be transforming the value between 0 to 1. Okay, it will not be exactly 0, but very much near to 0, and this will also be very much near to 1. Right. So whatever z value, after we do it in the forward propagation, right, and once we pass through the sigmoid, we are always going to get the value between 0 to 1. Okay. Now along with this, here you can see that in the forward propagation, all this operation will happen. O11 is the output of this particular first hidden layer neuron. Okay, and then this will get multiplied by W2, and then a bias will get added. Then again, activation function will get applied, and then I basically have my O21 as the output, and then again another weight is basically assigned between the output layer. This will get multiplied. Again, a bias can get added over here. Okay, like D3, and then finally we get an O31. And here you can see loss function will get calculated, which we discussed earlier. Loss, let's say there are different kind of loss functions we're going to discuss. But in short, what I'm doing over here with respect to this loss, I'm just trying to subtract y minus y hat whole square. Let's say, okay, and then what we do, we try to reduce the loss value. Okay, just let me make my face a little bit smaller so that you can see it. And then what we do is that we try to reduce this loss function. And to reduce this loss function, we use something called as optimizers. The main work of the optimizers is to do the back propagation and update this weights like W3, W2, W1, and the forward propagation is basically denoted by, I can give this one as the forward propagation. In forward propagation, we do this step 1 and step 2. Okay, and here specifically remember that we have used sigmoid activation function, because I'm just going to talk about the disadvantages of the sigmoid activation function. Now let's say I want to update the weight W1. So with respect to W1, if I want to update the weight, then what will be my formula? W1 new is equal to W1 old minus learning rate of derivative of loss with respect to derivative of W old. Okay, now W1 old. Okay, so I'm just going to consider this, and probably we are going to expand this with the help of chain rule. Remaining all are very much easy because those values are already there. This will get initialized initially. Let's say the initialized value is like 0.001, or it can be it is a small value, right? And I've also told you that why this should be a small value, because this actually helps us with respect to the speed of convergence, right? In our previous session we have seen that. So revise it if you don't know it. Okay, now what I'm actually going to do, I'm going to basically take this derivative of loss with respect to derivative of W1 old, and I'm going to first of all use a chain rule of derivative. So if I really want to update W1, how will I be using the chain rule of derivative? First of all, you need to understand, go from the back end side, because see, back propagation over here, this is basically back propagation. Back propagation basically means we have to go from the behind, that is from this loss, and keep on updating every weight. Why? Because see, loss is dependent on O31. O31 is dependent on O21, right? So O21, and then O21 is dependent on O11, and finally O11 will be dependent on W11. So we're going to go in this particular pattern, and we're going to basically find out the chain rule derivative, right? So first of all, derivative of our loss, I'll just write it as derivative of loss with respect to derivative of O31 multiplied by, now as I've already told, O31 will be dependent on what? O21, right? So here I have derivative of O31 with respect to derivative of O21, and then finally derivative of O21 with respect to derivative of O11, I guess. So O11, and finally derivative of O11 with respect to derivative of W1. This is fine, right? We have previously used this. We know what exactly this is. This is basic chain rule of derivatives with respect to finding the specific weight. But here, I'm going to go one more step ahead. Let's consider only one, and let's try to solve this. Okay? Let's try to solve this further. So guys, now focus on this, okay? Derivative of O31 divided by derivative of O21, okay? First of all, I will try to find out what exactly is O31. O31 is nothing but this specific output. And here you can see that in O31, to get O31, what all I have to do? I have to multiply O21, multiplied by 3, and then a bias, and then on top of that, I have to add an activation function, right? This all things I have to do. So if I really want to write O31, I will basically apply an activation function on O21. Instead of writing O21, I'll write W3 multiplied by O21 plus bias, right? This is the same thing that we have done over here. See, O21 multiplied by W3 plus bias. Bias is nothing but D3. And I have basically applied an activation function, right? This is super, super important. Understand this, because this O31 can be broken up in this specific way, okay? This specific way, okay? Now, tell me one thing, that if I probably take this entire equation as Z, okay? Let's consider this as Z. So here what I'm saying, let's Z be W3 multiplied by O21 plus B3. So how I can write O31? O31 will be nothing but sigmoid of Z right? This is what is the notation that I have written. Now see, if I am trying to divide with respect to derivative of O31 with respect to derivative of O21, now what exactly this Z is? See, can I say Z is nothing but O21 multiplied by W3 plus B3? So can I say the input that is going to the activation function is basically Z? Yes, in a very simple way. I can basically say that whatever input is going before the activation function or before the activation function getting applied, that is basically Z. And that is what I've got from this specific notation. Now consider this one, okay? This equation, this is very simple. O31 with respect to O21 can be written as derivative of O31. Over here you can write it as derivative of Z. So here you can basically see, sorry, not derivative of Z. So this you can basically write derivative of sigmoid of Z with respect to derivative of Z, then multiplied by derivative of Z, and Z is dependent on what? Z is basically dependent on O21, right? So here what happened? See, over here Z is there, right? And Z is already dependent on O21, right? So O21 multiplied by W3 plus bias G3 is nothing but Z, right? So here what I've done, I've just made another chain rule to split derivative of O31 divided by derivative of O21 is nothing but derivative of sigmoid of Z with respect to derivative of Z multiplied by derivative of Z with respect to derivative of O21. So I am just used chain rule to bring the dependency. I've added this Z and basically brought this dependency of this to this, okay? Instead of directly going. That is what I've actually done, okay? And again, this is from the chain rule. And there's a reason why I'm doing this, okay? There is a reason that I'm doing this. So this is basically my chain rule, okay? Now over here you can see that what is the derivative that I'm trying to find? I'm trying to find out the derivative of sigmoid. Okay, this is super important. I'm trying to find out the derivative of sigmoid. Now one very important thing, guys. See this, whenever we apply an activation function on any values with respect to Z, I'm always going to get it between 0 to 1. That basically means I can also give this notation. 0 is nothing but less than or equal to sigmoid of Z is less than or equal to 1. That basically means I'm always going to get this specific value whenever I try to apply an activation function like sigmoid. But with respect to derivative, if I try to find out a derivative of a sigmoid function, that is sigma of Z, I'm always going to get a value between 0 to 0.25. Now this is super important point, guys, and this is mathematically proved. I will not be providing any proofs as such because that is not as important, because over here we are trying to understand something with respect to a specific problem statement. Okay, we basically apply all these concepts in business problem. Unless and until you are not a researcher, I think you do not have to go behind the proof over here. Okay, so over here you can see that the derivative of sigmoid function is always ranging between 0 to 0.25. That basically means if I probably try to create this, and let's say if this is 0.25, then I am going to get a curve which will look like this. Okay, so this is with respect to derivative. This is super important, guys. Whenever we apply a sigmoid activation function, I get a value between 0 to 1. But whenever I apply a derivative of a sigmoid activation function, like how we are applying over here, derivative of sigmoid activation function, this value is always going to be between 0 to 0.25. And this is what is my derivative of a sigmoid. This is super important to understand. Okay? Because understand, I'm not going behind the proof over here because this will be required as a researcher, not as a data scientist specifically. But I think if you know this much, and it is mathematically proven, you can pick up the research paper and actually have a look. Okay? So in this case, whatever I'm going to get between this 0 to 0.25. Okay? Now see this. Now I'll go ahead and multiply this. Now it will be Z, you know what it is. So I'll write derivative of W3 multiplied by derivative of O21 plus B3. Right? Now see this. This is super important. And this will be divided by derivative of O21. Now if you know derivative, guys, what will happen in this? Say derivative of O21 is here. So W3, O21 will get cancelled. It will become 1. The B3 is a constant. So this will become 0. So in short, what you will be getting is that here, obviously, you'll be getting 0 to less than 0.25 because this is the derivative. Multiplied by here, you'll be getting W3. So this will be exactly your derivative of O31, derivative of O31, derivative of O31 divided by derivative of O21. So this is what you are basically going to get. And this W3, what you are getting is basically the W3 old value. Okay. Now see, what I've done, I've taken this value, I've split it across, and I've basically shown you the entire information what is coming, right? Now here, the reason I'm showing you this, because understand, all the time you're getting 0 to 0.25, and weights that are initialized initially, right? That will also be between 0 to 1 only, right? So initialization techniques also I'll talk about, like how many different types of weight initialization techniques are there, but usually weights are also initialized in a smaller value between 0 to 1, right? And there are also different kind of distribution, like uniform distribution, again, which I'll be talking ahead when I discuss about different types of initialization technique. But in short, what you're having a smaller value between 0 to 0.25 and multiplied by the weights. And obviously, if you're having some values between 0 to 0.25, then this entire value will also be very small. So over here you can see that with respect to every derivative, right? This will be ranging between 0 to 0.25. Right? Let's say this will also be ranging between 0 to 0.25, right? 0 to 0.25. This may also be ranging between 0 to 0.25, unless and until the weights are very high, right? So here you can see that what will happen with respect to this. Now see, here all we are getting smaller values, right? These are all smaller values. Right? Here also we'll be getting smaller values because here also in the output level we use sigmoid activation function. Now when we get all the smaller values, when we multiply it, we also get a smaller value. Now if we are getting this entire value as small, see, understand this. If you're getting this entire value as small, then what will happen? This will also become a small value. Right? Now when this is a small value, you're multiplying with 0.01, and usually initialization of learning rate is also small. It will be between 0 to 1, but we usually initialize 0.001. Right? Now when this will get multiplied with this, you will be able to find out that there will be hardly any update with respect to W1 old. Right? Because this is entirely a very small value. This entirely becomes a very small value. Right? So in short, W1 new will be approximately equal to W1 old. Now if this thing is happening, that basically means your weights is never getting updated. I hope you're able to understand the weights are never getting updated. Now if the weights are never getting updated, that basically means you're not moving towards the convergence. So over here, this was the convergence, right? Your weights are not getting updated, it is stuck in this position. Right? This is your loss function. This is your weight. Right? It is not coming down because the W new and W old are approximately equal, which is basically over here. They're almost equal. The weights are not getting updated, and because of that, you're not moving towards the convergence point. That basically means you're stagnant. And this is all happening because of this sigmoid activation function. Right? Because of this. And this scenario, wherein your weights will not get updated, this problem is basically called as vanishing gradient problem. Very important thing. Vanishing gradient problem. Now, vanishing gradient problem is a problem wherein your W1 new and W1 old is not at all getting, W1 new is not at all getting updated, and these all are both equal. Right? So at the end of the day, this is not getting updated. We are not going to come to the global minima. And this scenario, and this scenario is basically happening because of sigmoid activation function, because the derivative of sigmoid is 0 to 0.25. And in a deep neural network, let's say if I have more layer, wherein if we keep on increasing these values, right? If we keep on seeing this chain rule, right? All the values will be a very negligible smaller value when we keep on multiplying it. right? So I hope you're able to understand what exactly vanishing gradient problem is. In a deep neural network, if we keep on using sigmoid activation function, because of the concept of the derivative of sigmoid ranging between 0 to 0.25, in this chain rule, we will always try to get a value very, very smaller. So if we keep on multiplying it, okay, if you keep on multiplying it, then you'll be seeing that this will entirely be a small value. It can be like 0.00000001. And when I take this value in this derivative of loss with respect to derivative of W1, if I keep on updating it over here, again it will be a smaller value. In short, I will be getting W1 new is approximately equal to W1. So I hope you got an idea about this. And that is the reason to fix this problem. To fix this problem, researchers, what they did to fix this problem, researchers started exploring other activation function. Some of the activation function I'm going to write it down over here, which we're going to learn. One is ReLU. Then you have before that I have an activation function which is called as TANH. Then you have something called as ReLU. Then you have something called as pre-ReLU. Right? Then you have something called as Swiss. And all these activation functions we'll be discussing. And at the end of the day, we'll be making a conclusion that which activation function should be used in the hidden layer and with respect to the output layer. So I hope you got an idea about vanishing gradient problem and activation functions. I hope you understood why sigmoid activation function is bad, because at the end of the day, whenever you try to find out a derivative of a sigmoid activation function, you're going to get a value between 0 to 0.25. But this is fine. See, if you have a smaller neural network, it is fine. But if you have a deep neural network where you have 100 hidden layers, at that point of time, this will not work, because at the end of the day, you'll get a smaller value, which in turn will keep this W1 new approximately equal to W1 old. Right? So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so we're going to continue the discussion with respect to deep learning. In this video, we are going to start with the activation function, and we're going to discuss about various activation functions as we go ahead. And already in our previous video, we have discussed about vanishing gradient problem. We also saw that what is the disadvantage with respect to the sigmoid activation function. Now let's go ahead and deep dive into this. And here is one amazing Jupyter notebook which I have actually created for you entirely. Okay, and obviously this is basically the operation with respect to perceptron. Here what we do is that we basically take all the inputs multiplied by the weights, and then we add a bias, and they apply an activation function, and then we finally get an output. Right. So let's go with the first activation function. Right, that is sigmoid. So as suggested, what is the main importance of sigmoid over here that you'll be seeing? That whenever we talk anything about sigmoid, like let's say that this is my z value, the sigmoid is responsible for transforming the z value between 0 to 1. Okay, and this is the formula that is basically used. Okay, 1 divided by 1 plus e to the power of minus x. Okay, this x is nothing but weights multiplied by the inputs. This is what is the output of the sigmoid activation function. We have already discussed about this. Where the sigmoid activation function is used in the hidden neurons, right? After the weights and the inputs are multiplied and then the bias is added. After that, the activation function that is applied is basically that is the same activation function what we are saying about, right? So this is again a kind of activation function. This was one of the points. The second point that you really need to understand is that the derivative of the sigmoid is always ranging between 0 to 0.25. So the derivative is always ranging between 0 to 0.25. And because of this, we also understood that in sigmoid activation function, what is basically happening, there is something called as vanishing gradient problem. Vanishing gradient problem basically means during the back propagation when the weights are getting updated. Usually, whenever we find out the derivatives, the value is small. So whenever we have a very deep neural network like this, you know, and as the weights keeps on getting updated, right, then what will happen is that the weight updation will become smaller and smaller, right, because of the sigmoid activation function, because the output is being ranged between 0 to 0.25. So what happens over here? Let's say over here one of the derivatives starts with 0.25, and as we go with chain rule, right, then it will keep on increasing like this, right, 0.001. I've just put some random value like this will keep on increasing it, right. So what will happen based on if it is a very deep neural network based on this chain rule, this becomes a very small number, and because of that the weights will never get updated, and because of that we face a vanishing gradient problem. So I already have discussed all these things in my previous video. My suggestion would be that please go through that particular video, but we really want to understand. Okay, this is the problem with respect to vanishing gradient problem. Sorry, the sigmoid activation function, and that is the reason we use different activation function. Now here I want to give some of the points with respect to sigmoid activation function. Now first of all, here is a simple definition. The sigmoid function is the most frequently used activation function at the beginning of the deep learning. So initially they were using it when the neural network was small, right? But when the neural network becomes bigger, deep, you know, with many hidden layers, at that point of time it becomes a problem. It is a smoothing function that is easy to derive because we'll also be able to derive based on the loss function. And here you can see the output of this is between 0 to 1. Okay, and we can think of probability, but in strict sense, don't treat this as a probability. The sigmoid function was once very popular. It can be thought of firing a rate of a neuron, right? It can show that how much a neuron needs to be activated or how much it should be deactivated. Okay, so this is there. Now along with that, the function itself has certain defects. Now there is some problems with this. Okay, now first of all, let's discuss about one by one. Okay, over here, this particular point that we are talking about, I'll just read it out and then we'll try to understand. Okay, when the input is slightly away from the coordinate region, the gradient of the function becomes very small, right? Almost zero. In the process of neural network backpropagation, we will use the chain rule of differential calculus to calculate the differential of each weight. When backpropagation passes through the sigmoid, the differential on the chain is very small. So this is the same thing what we discussed about the vanishing gradient problem. Because of this, the derivative of the sigmoid is between 0 to 0.25. What happens in the backward propagation, right? This value keeps on becoming smaller and smaller. And because of that, some of the weights will never get updated because the W new will be approximately equal to W. Okay. Now the second point that I really want to discuss about is the function output is not centered on 0. Now this is super important to understand. Right now, this is how my function looks like, right? This is how my diagram looks like. Now let's say what is 0-centered output basically means. Let's say if this specific line was looking something like this. Okay, let's say if this curve was looking something like this, wherein it is passing through the origin. So this becomes a 0-centered. Right, 0-centered. That basically means I'm basically saying that you know, let's consider with respect to the mean. The mean is basically there. The mean is nothing but 0. Okay, in 0-centered. The mean is nothing but 0. Okay, and probably if you know about machine learning, guys, let's say that if I have some of the data points, right? If I have some of the data points like this, let's say if I have some of the data points like this, in some of the machine learning algorithm, what we do, we apply something called a standard scalar. Right now, in standard scalar, what we do, we basically apply a z-score. With the help of standard scalar, one amazing thing usually happens. What is that? All these points will basically be brought up in this center, where my mean will be 0 and my standard deviation will be 1. Right, so this entire points will be brought it over here. So this is basically called as centering, right? And here you can see that it's passing through 0.5. So this is not 0-centered. Now, why it needs to be 0-centered? Because practically it has been proved that if my points are 0-centered, and probably if this function had a 0-centered, there will be an efficient update in weights. Efficient update in weights. Super important point. Okay, efficient update elements. That basically means probably will help us to find out the derivative in a quick way, right? And again, I'm not going back to the proof because I feel that as a researcher, probably if you're researching, that'll be it'll be good that you know at that point of time. Other than that, I think with respect to solving use cases, I think this much is more than sufficient. So here you can see the function of the output is not centered on 0, which will reduce the efficiency of wait update. Okay, then the sigmoid function performs exponential operations which is slower for computers. Now, this is also a disadvantage because we have an operation that is 1 divided by 1 plus e to the power of minus x, and this is an exponential operation. And since this is an exponential operation, it usually takes time, so it is very slower with respect to computers. But again, we also have to talk about the advantages of sigmoid activation function. One is smooth gradient, prevent jumping in output value. Output value is between 0 to 1, so normalizing the output of each neuron. Error prediction that is very close to 0 and 1 because either we are going to get 0 or 1. And again, if you keep a threshold value greater than 0.5, it will become 1, less than 0.5, it will become 0. Sigmoid has three major disadvantages. Prone to gradient vanishing, and we have discussed what is gradient vanishing. Function output is not 0 centered, and power operation are relatively time consuming. That is e to the power of that kind of operation will usually be taking more time. Now, since there are a lot of disadvantages, so instead of using sigmoid activation function, we use the next activation function that is called as tanh. And then in our next video, we'll try to understand what all tanh is basically fixing and what are the disadvantages with respect to tanh also. So yes, this was it for this particular video. I'll see you in the next video. Thank you. Hello guys, so we're going to continue the discussion with respect to activation functions, and yes, I've already given you the brief idea about what is the problem with sigmoid activation function, that is vanishing gradient problem. Now let me just go ahead and explain you detailing about sigmoid activation function and what are the advantages and disadvantages with respect to it. So to begin with, you really need to know three important information about the activation function. So the first thing is that what happens during the forward propagation. So that basically means the first formula that you really need to remember is this one. The sigmoid activation function is given by the formula 1 divided by 1 plus e to the power of minus x or minus z, anything it can be. And this usually formula is applied in the activation function whenever we do the forward propagation, because the step 2 basically says after you multiply the inputs along with the weights, and then probably you add a bias, and then on top of that you apply an activation function. Again, the main aim of sigmoid activation function is to transform the value between 0 to 1. So in the left hand side graph that you see, right, if this is your z value, and z usually we denote it as summation of I is equal to 1 to n w transpose x plus b, right? So after this particular operation, whenever we apply a sigmoid activation function, and this is the symbol of sigmoid, in other research paper it is also given something like this, so don't worry about the notation so much. At the end of the day, the sigmoid activation function is transforming the values between 0 to 1. This is basically happening in the forward propagation. Now along with this, the third most important point that you really need to remember is about the derivative of the sigmoid. Now the derivative of the sigmoid, whenever you try to find out the derivative with respect to this particular sigmoid and with respect to z, you are always going to get it between 0 to 0.25, and that is what this specific graph basically specifies. Always, whenever you try to find out the derivative with respect to sigmoid activation function, you're going to get it between 0 to 0.25. Now, why this specifically causes a vanishing gradient problem, I've already explained you, but I'm again going to revise. And why researchers started using other activation function, you'll get an idea about it. So here again, I've taken the same deep neural network. Here you can see I have hidden layer 1, hidden layer 2, hidden layer 3, and this is finally your output layer. And then you calculate the loss, and based on that, you use an optimizer and backpropagate. And while backpropagating, you update all your weights until your loss function decreases, right? So this is what we basically do. Now let's imagine I want to update the weight of W2. Okay, so in the case of updation of the weight of W2, what you do? You write a formula W2 new is equal to W2 old minus learning rate derivative of loss with respect to derivative of W2 old. Now this is a super important thing because I will split this more information. Okay, so now I can write derivative of loss with respect to derivative of W2 old is equal to, now let's see. Now here you can see loss is dependent on O3. O3 is basically dependent on O2. Okay, and we really need to update this. So finally you will be able to see O2 is also dependent on W2. So this is how the chain rule will basically work. So here I've written derivative of loss with respect to derivative of O3 multiplied by derivative of O3 multiplied by divided by derivative of O2, and then finally you have derivative of O2 divided by derivative of W2. Okay, now this is the case, right? Now let me deep dive more into this and let me solve this one also, and which we did it in the previous video, but I'm again repeating it because I really need to show you some more things over here. Now this O3, let's say I want to solve this. Over here, with respect to O3, let's consider that I have some Z input over here. And this Z input is nothing but O2 multiplied by W3 plus B1. And after that only the activation function will say, right? So the first step that we are computing Z. Okay. Here we are going to apply the activation function on top of Z. Okay. This is the simple thing that I'm trying to say. So let me denote Z is equal to O2 multiplied by W3. So this is nothing but O2 multiplied by W3 plus B3. So plus B3. So this will be my Z. So if I really take this up and split it again with the chain rule, what will happen? Derivative of O3 divided by derivative of O2 is nothing but derivative of activation function on top of Z. Because what is O3? O3 is nothing but this one, right? Activation function of top of Z divided by derivative of Z, right? Multiplied by derivative of Z with respect to derivative of O2. So I hope you are able to understand what exactly Z is, right? And O3 is nothing but it is just applying sigmoid activation function on top of Z. Okay. Now once you do this is nothing but the derivative of sigmoid, and you know that from this particular graph. And again, you don't have to go ahead and look for the proof like why the derivative is between 0 to 0.25. It's not that important, but as a researcher it may be important. But here we are just trying to understand with respect to data science so that we can solve multiple business use cases. So here you'll be able to see that my value of this particular derivative will be ranging between 0 to 0.25. And then what I've done for derivative of Z with respect to derivative of O2, I've just expanded Z. So here you have O2 multiplied by W3 plus B3. And whenever I try to find out derivative, you can see this entire thing with respect to O2 will become 1. So I'll have W3, and this is a constant, so it will become 0. So here you can see 0 to 0.25, whatever value is there, multiplied by W3. So here in short, what I'm actually going to get small value, based on some decimals, right? And why I'm saying decimals, because W3 also, initialization techniques will be that we will be using between 0 to 1, and it will be a smaller value. In the upcoming videos, we'll see what are different types of weight initialization techniques are also there. So in short, we're getting a smaller value. When we get this small value, right, that basically means we're going to get a small value here. Let's say that the small value is nothing but 0.002. Okay, so this is with respect to the small value. Or let me just increase a bit, okay, because this is in the back propagation. I'm just putting some random value. Okay, 0.01. Now here also you'll be able to see that, and since we're doing from the back propagation, derivative of loss with respect to derivative of O3, let's consider that this is also somewhere around 0.20. And then as we go ahead and increase this chain, right? When does this chain increase? When we're trying to find out when we're trying to update the weight for W1. And the updation of the weight will go ahead, right? It will keep on increasing this. And now here you can see that the smaller values will keep on appending. And once you multiply all these things, it will be a very, very small value, right? Now when it is becoming a very, very small value, we will replace this value over here. And usually the learning rate is also very small. Let's say that for this example I've taken 0.001. When I multiply with this small value, it will again be a very small value. Let's consider like it will be like this many number of zeros and ones. Now when I'm trying to update the W2 old W2 new, here you can see that W2 new will be approximately equal to W2 old. Now this basically what it is doing is that we are not updating the weights. If you are not updating the weights, it's basically that we are not doing anything, right? We are just back propagating it like that without updating any weights, right? So this problem wherein the weights are not getting updated, so what will happen? Your convergence will not happen in the gradient descent. In the optimizer, the convergence will not happen. It will get stuck here only, right? Let's say it will get stuck here or it will get stuck here, and the weights is not getting updated because in the x-axis you have weights. So in short, the convergence is not at all happening, right? So this is the problem with respect to sigmoid. Because why? Because the derivative of sigmoid is 0.0 to 0.25. Now let's talk about some of the disadvantages with respect to this. Obviously, I will talk about the advantages also. Advantages is very, very much simple. Let me just talk about all the advantages first, and then we'll talk about the disadvantage. And if since there is a disadvantage, we really need to use a different activation function, and that is how researcher came with different techniques. So I'm going to write the advantage and disadvantage. Let me write down the first advantages. Now here you can basically see that at the end of the day, this is suitable for binary classification problem. Why? Because you have the outputs like 0 and 1. Suitable, right? It is suitable for binary classification problem. Now one more important thing is that with respect to the binary classification, right, it actually helps us to get a clear predictions, right? That is very close to 1 and 0, 1 or 0. Okay, so these are the two main points. Okay, two main points with respect to advantage. And obviously, it helps us to train a medium size or I'll say a smaller size of neural network. But let's consider with respect to the disadvantage, and this is super important. Okay, the first thing is that it is prone to vanishing gradient problem, and already we have discussed about it. Vanishing gradient problem. It is prone, right? Because you are going to face if you have a deep neural network, deep neural network. Okay, the second one is something called as the function output is not zero centered. Now, super important point. What is this not zero centered? And why we are discussing about this? Okay, so this is what we'll be discussing. What exactly is zero centered or not zero centered? Okay, now here you can see that whenever I say zero centered, what does zero centered basically mean? Zero centered basically means let's consider a zero centered function. Zero centered. Okay, let's say if my function was something like this, wherein I start from here, I go from my origin, and then I go like this. Okay, let's say if this was my function. Okay, here it is passing through the origin. That basically means my mean is zero with respect to all this distribution. What I'm actually going to get, right? So this is exactly called as zero centered. Zero centered. Why zero centered is important? Because it is useful for weight updation. That basically means if it is zero centered, efficient weight updation will basically happen. Okay, so here I'm going to write for this is important for what? Or let me remove it over here. Centered. Okay, or let me just change the spelling. Centered. This is super important for efficient weight updation. Efficient weight updation because we use gradient descent most of the time to update the weights, right? So efficient weight updation it will basically help us to happen. Okay, understand one thing like why zero centered? Zero centered basically means the mean is zero, and that is the reason, right? If you know about linear regression also, right? Linear regression or logistic regression, right? Whenever our data points, right? Let's say if our data points are here. What we do for these data points, we do something called standardization. Now, standardization, what it is going to do is that it is basically going to bring all the points towards the centered region. So this is basically called as zero centered, where your mean is zero and all the points are over here. And this, when it is done, right, whenever we do we train our linear regression with the help of gradient descent, right, efficient weight updation will happen. Efficient weight updation will happen here. In case of linear regression, many people know about coefficients. Efficient coefficient updation will happen, right? So that is what we're doing. We're basically doing standardization. I'll not say standardization, but we are trying to bring this into central, as in a way that we are just trying to make it centered, all the data points. Okay, so this process in machine learning is basically called as standardization. What I specifically spoke about, right? The mean is zero. Okay, and the standard deviation can be 1 also. Okay, so this process, standardization is one process of making zero centered, like that you can consider. Okay, now coming to the third advantage, right? Now here, third disadvantage. Here you can see the formula is 1 divided by 1 plus e to the power of minus x. Right? For this particular formula, right? Whenever the computer wants to solve this problem, right, through processes that happens and all, this operations or this mathematical operation, I'll say this mathematical operation are relatively time consuming. Super important. Okay, super important. So these are the major disadvantages. Now, again, the researcher will not keep quiet. They'll come something new, right? With some new activation function altogether. And that is where we will learn about our second activation function, which is called as tanh activation function. So that is what we are going to learn about it. But I hope you have understood why sigmoid activation, what are the disadvantages of sigmoid activation function, and why we should not use in all the hidden layers in a deep neural network, right? Deep neural network, right? So this was the first activation function, and I've explained you detailedly what is the problem over here. And again, the problem is that you will be facing a vanishing gradient problem. Okay. So yes, in the next video, I'm going to talk about the next activation function that is called as tanh activation function. Thank you. Hello guys, so we're going to continue the discussion with respect to the activation function. In this video, we're going to discuss about tanh activation function. Already we have seen about the sigmoid activation function. We understood, usually sigmoid, whatever value it transforms between 0 to 1, and the derivative of sigmoid was between 0 to 0.25. And since the derivative value was between 0 to 0.25, usually in the back propagation, we used to face a problem which is called as vanishing gradient problem. And then we also found out some of the disadvantages with respect to this, that the function output is not zero centered, and the power operations are relatively time consuming because it has e to the power in the formula itself, right? So usually it is time consuming task. Now the second activation function we will be discussing is called as tanh, and tanh also solves some of the problems with respect to gradient descent. So let's understand this. The first thing that you really need to know is that what is the tanh formula. So tanh formula is basically the specific formula over here, right? So whenever we say tanh is nothing but e to the power of x minus e to the power of minus x, e to the power divided by e to the power of x plus e to the power of minus x. Until now, whatever things we have learned, I will just write this notation something like this because z is nothing but z is just let me write it like this over here. So e to the power of z plus e to the power of minus z. Okay, and z is nothing but summation of I is equal to 1 to n w transpose x of I plus b of I. Okay, so this is what is the entire z operations. Okay, and whatever z value you are getting, we are passing through this tanh, and tanh what it does is that it transforms all your value between -1 to +1. This is super important to understand. Okay, -1 to +1. So whatever value, like how sigmoid was transforming a value between 0 to 1, similarly with the help of this particular equation, it transforms this particular z value between -1 to +1. Okay, and the other thing that you really need to understand with respect to activation function is the derivative. Now the derivative of a tanh always ranges between 0 to 1. Now in sigmoid, you know it ranges between 0 to 0.25. But here you have basically having the derivative of tanh. Whenever you try to find out the derivative of this, it will be ranging between 0 to 1. Right. So these are the changes. And again, what all problems is basically getting solved with the help of tanh functions that we are going to understand now. Okay, but I hope you got an idea. And with respect to every activation function, you need to know the formula. You need to know what is the derivative of that particular value of that particular activation function and what that particular activation function is transforming the values to. Okay. So once you do all these things, you'll be able to understand this. Okay. So let's go ahead and let's try to understand about the advantages and disadvantages over here. Okay. So here you can see that this is a hyperbolic. I'll just show you over here. So and tangent is nothing but it is a hyperbolic tangent function. The curve of the tangent function and sigmoid are relatively smaller. Let's compare them. The output of the interval is 1. Is basically it ranges between -1 to +1. So I can basically update this value. And the whole function is zero centric, which is better than sigmoid. Now see, when I say zero centric, I told you right previously in sigmoid it was not zero centric. The values were not near to 0. Whenever I say zero centric, that basically means your mean should be 0, right? So over here you can see that it is basically zero centric. Okay, it is basically passing through 0. And your values between 0 to 1, that is the derivative of this tangent function is between 0 to 1. So you for a medium-sized deep neural network, you may not face a vanishing gradient problem, but even though for a deep neural network, right, deep layered neural network, you may face some gradient descent problem, vanishing gradient descent problem. Why? Because again your derivative range is between 0 to 1. But whenever you have a deep neural network, right, initially let's say one of the derivative over here with respect to this loss, right, if I'm trying to find out the derivative of tangent, it may come to 0.5, then it may come to 0.23, then it may come to 0.01, 0.005, like that. All these values will be coming. So at the end of the day, when we multiply this, again this will become a smaller value. And because of that, what will happen? Your weights will not get updated. So I hope you're able to understand this. Yes, with the help of this particular derivative that is ranging between 0 to 1, it may not have with respect to medium-sized deep neural network itself. But if I have a very long deep neural network, at that point of time, it may cause vanishing gradient problem. Okay, so this is the most important thing that you really need to understand. Again, the other thing is that in general binary classification, the tangent function is used for hidden layer and all. With respect to one more important thing, since this has e to the power of s, again there is a problem with respect to computation. Okay, so if I really want to talk about disadvantage over here, the first disadvantage is that vanishing gradient problem exists for deep neural network. The second problem that you probably find out over here is that with respect to this particular disadvantage, since the formula has e to the power of x, so computation time is more. But it is solving all the other problems like zero centric, and again, if it is zero centric, then the weight updation happens efficiently, right? So now you can just compare. Before they were using sigmoid, then they came up with tangent, but still there are some disadvantages with tangent. Now how do we fix this particular problem with tangent? And for that, we will be seeing our third activation function, which is called as ReLU activation function. Now the major problem is with respect to vanishing gradient, and here you can see that sigmoid was also not able to solve the vanishing gradient problem. Not tangent was also able to solve the vanishing gradient problem because again, still your derivative is ranging between 0 to 1, right? And as in a deep neural network, this value keeps on decreasing, and when you multiply that smaller value, it becomes a smaller value. At the end of the day, your W new and your W old will be approximately equal in a deep neural network, right? So now the third thing that we are going to discuss about is ReLU function, and this is also an amazing activation function, and this solves the problem. And this is the most popular activation function, which we are probably going to discuss in my next video. So I hope you're able to understand till here, understand each and every activation function, why it came. As a researcher also, if you start thinking, right, there were some problems in the previous one, and now they're coming up with a better one, right? So in the next video, I'll be talking about the ReLU activation function. Thank you. Hello, also guys, we're going to continue discussion with respect to the activation function, and in this video, we are going to discuss about ReLU activation function, and this is the most common activation function getting used right now. We saw in the previous videos with respect to sigmoid and tangent, there is still a vanishing gradient problem issue, but with respect to this ReLU activation function, you can basically see that the vanishing gradient will go away. Okay, but still there is one more problem in ReLU activation function which we'll discuss. Now, first of all, you really need to know the formula. The formula is very simple. You basically apply this max of 0, x. So in forward propagation, right, whatever value you get, that is the output of the ReLU. If you're getting less than 0, then you're probably getting 0 out here, right? So with respect to all the transformation, it's very simple. The transformation happens with respect to max of 0, x. Okay, so if the x is a positive number, it'll come as a positive number. If the x is 0, it'll come as 0. If x is negative, it'll come as 0. Okay, so this is with respect to the forward propagation. With respect to the backward propagation, where we specifically find out the derivative, the answer is either 0 or 1. That basically means on the x-axis, if it is positive number, I'm going to get 1. If it is a negative number, I'm going to get 0. And whatever values that I come over here is going to be 1 itself. So your output is either 0 or 1. Okay, with respect to the derivative. And already we have seen with respect to tangent, the derivative output is between 0 to 1. With respect to sigmoid, it is between 0 to 0.25. Now, since we have either 0 or 1, so in short, it is solving the vanishing gradient problem. Why? Let me again show you by creating this diagrams. So let's say I have this cells under there. Okay, so this is my input, hidden, and finally I get my output over here. This is my input layer. Okay, and then here we add a bias. Here also we add a bias. Here also we add a bias. So this will be B1, B2, B3. I think you are very much familiar with these things. Okay, let's say the weights that are getting assigned are W1, W2, W3, and finally this is my output, and then we calculate the loss. And with respect to this loss, we do the back propagation. Okay, and here let me just go ahead and write the output also. So this is O1, O2, O3. Okay, now let's say that I want to update this W2, then what will happen? The same equations will happen, right? Whatever we discussed over here. So let me again copy this so that it will become easy for me to write everything, right? So here I'm just going to copy this and paste it over here, right? Now what will happen? Instead of this derivative of tangent, now we are going to change this to ReLU, right? So now I'm going to basically have this one as ReLU of z, right? With respect to z. And you know that my value will be either 0 or 1, right? So it will be over here. I'm just going to write it down to make it very simple. The derivative will be 0 or 1. So here also it will be 0 or 1. If it is 1, then obviously we are not reducing the value. The weight updation will happen properly. So again, if ReLU output is 1, okay, if ReLU output is 1, that basically means weight updation will happen. Weight updation will happen because this is not becoming smaller, right? In the previous cases, we had values between 0 to 0.25, right? Over here, we have value between 0 to 0.25. So this is going to reduce. But with respect to 0 or 1, if I have 1, obviously, weight updation is going to happen. It will happen by a good amount, where the W new will at least be greater or lesser than W old. Okay? But if the ReLU output, or I should say, if the derivative of ReLU output, okay, this is super important. Derivative. If I don't write derivative, then we'll think of it as if the derivative of, then here, if the ReLU output, derivative of ReLU output is 0, then this creates a dead neuron. Why? Because if this is 0, 0 multiplied by this entire thing will be 0. Now when this entire thing is 0, over here what is happening? Then if I probably see the weight updation formula, that entire this derivative will become 0. So when this derivative, just see this, okay? If this entire derivative is becoming 0, because the weight updation formula is what? See, weight updation with respect to derivative of W2. Let me just write it down over here. So over here you can see that I'm trying to find out the weights for W2, right? W2. So how do I write this W2? So W2 new is equal to W2 old minus learning rate of derivative of loss with respect to derivative of W2 old, right? So this is the formula. Now when understand that if this entire when we are finding this derivative of loss with respect to this entire thing is becoming 0, right? If this is becoming 0, so this entirely changes to 0. So learning rate this into this will also become 0. So in short, if it is 0, if the derivative ReLU output is 0, I'll write over here, if derivative of ReLU output or ReLU of Z, I can write, is 0, then what will happen? W2 new will be approximately equal to W2 old. Now, if these two are equal, in short, again, weight addition is not happening, this will basically create a dead neuron, a neuron without any functionality, right? So let's say out of this one node has just, in the derivative, this became 0. So this entire neuron is going to be dead neuron, right? Dead neuron. It is not going to work. It is just going to pass the whatever inputs it is getting, it's just going to pass to the next layer. Like whatever information is just going to pass. Because this entire thing is 0, no processing is basically happening. Because of that, no weight addition is basically happening. So this leads to dead neuron only when the ReLU output is 0. Now let's understand when the derivative of this ReLU of Z will become 0, right? Because here, when the Z is, okay, I'll just give a condition, okay? If Z is positive, what is Z? You obviously know what is Z. So Z is nothing but this specific thing. O2 multiplied by W3 plus B3, right? In this particular case, right? If this entire value is positive, then obviously the derivative of the ReLU with respect to Z will be 1, right? If Z is equal to negative, then what will happen? Then the derivative of ReLU with respect to Z is going to become 0, right? So in short, let's consider that if the Z value that we are trying to compute over here, if this is positive, I'm going to get it as 1. If it is negative, I'm going to get it as 0. So here I'm just going to give a notation. So if the Z value is there, positive, it is going to get as 1. If it is negative, it is going to come as 0. Okay, and if it comes as 0, it is basically a dead neuron, a neuron which does not function anything as such. But this is solving a vanishing gradient problem. If the value output of the derivative is 0, at that time you get a dead neuron. Okay, other than that, it is solving the vanishing gradient problem. So I hope you have understood about this, but let me just go ahead and talk about the advantages and disadvantages with respect to this. Okay, so first of all, the advantages, if I talk about advantages, it is solving vanishing gradient problem. It is solving vanishing gradient problem. If I talk about disadvantages, okay, it leads to something called as dead neuron. And then again, more advantages with respect to this. Here, since you know that my activation function is just a linear line, right? In this particular case, the calculation will be super fast because it is max 0, x, right? Max 0, x. So the calculations is super fast. I'd also like to add one point is that the ReLU function has a linear relationship. Okay, whether it is forward or backward, at the end of the day, you are able to see a linear relationship. Both. See, here also you are able to see the straight line. Here also you are able to see the straight line in both forward and backward, right? So it is much faster than sigmoid. So here, third point I'll say it is much faster than sigmoid or tan H. Okay, but here obviously you have one problem, that is dead neuron, and the second thing is that ReLU functions. See, ReLU output is either, if I probably say with respect to ReLU functions, right? ReLU functions, right? Output, it is either 0, x, right? So this is not, it is not zero centric. That basically means it is not, the mean is not going to be 0 at all, right? So this is not a zero centric at all. Either you get a 0 or a positive number. 0 or positive number. So this was some of the advantages and disadvantages with respect to ReLU. But again, there will be scenarios where we can also handle that the Z will never be negative. But again, for that we'll be seeing other type of activation function. But I hope you got an idea about ReLU activation function, what exactly it is. This was about this particular video. In the next video, we'll see a better version of ReLU, which is called as leaky ReLU, right? So this was it from my side. I'll see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to activation functions. In this video, we are going to discuss about leaky ReLU and parametric ReLU. Now, already we have seen in ReLU what problem we are facing. There was a concept of something called as dead neuron, or we also say it as dead ReLU problem, right? Wherein the entire neuron was getting deactivated. Now, the dead neuron or dead ReLU problem is basically solved by this leaky ReLU and parametric ReLU. Let's see how this is getting solved. Now, if you remember with respect to the ReLU activation function, here you could see that my derivative was either 0 or 1, and in ReLU also my entire formula was max 0, x, right? So here what we do is that we add a small constant. So here you can see with respect to the formula, we multiply a small constant like 0.01 multiplied by x, x. Before in ReLU it was max 0, x with respect to forward propagation. But here we are just adding we are multiplying one small constant like 0.01. So that is the reason here you can see that my line is not exactly 0, but it is somewhere below 0, right? Because of this constant that we are trying to multiply, right? Now with respect to parametric ReLU, we have this, that is max alpha x, x, right? So here, this alpha parameter is a kind of hyperparameter which we try to find out, okay? What should be this hyperparameter value? And this can be found out with the help of hyperparameter tuning, right? So this alpha is nothing but this alpha itself, and this is a kind of hyperparameter which we specifically use it as parametric ReLU, right? Now, if this is considered as a hyperparameter, it can have any value. It can have 0.01, it can have 0.02, it can have 0.03, that depends on the problem statement. So if we are considering alpha, we basically say it as parametric ReLU, and if I try to define a constant like 0.01, then it is basically called as a leaky ReLU, okay? Now with respect to this particular changes, what will happen is that the derivative with respect to this particular leaky ReLU, you'll be seeing that we'll never be getting 0, right? It will be small positive value. So here you can see that it will be a very small positive value, okay? And for all the negative numbers also it will be a small positive values, and for all the remaining values that is greater than 0 it will be 1, right? So this is the changes. Now what is happening because of this? In the back propagation we will never get a value of 0, right? So this way the dead neuron problem is getting fixed, right? So with respect to the advantages here, right? Leaky ReLU has all the advantages of ReLU, right? So this is the first advantage, and the second will be that there is no dead ReLU problem. It removes the dead ReLU problem, right? And I've shown you why. Because we are multiplying with this small constant over here with respect to x. Only that much is the change, guys. And with respect to this, you are actually being able to solve both vanishing gradient problem and the dead ReLU problem, right? So that is the reason why leaky ReLU is much more better than ReLU. See, based on the concept, obviously you can see that it can work well, but at the end of the day, you really need to try each and everything whenever you're trying to solve a problem statement, right? So you got a basic idea with respect to leaky ReLU and parametric ReLU. In parametric ReLU, this alpha will be hyperparameter, and with the help of hyperparameter tuning, you should basically be selecting this, okay? And this side, whichever derivative you basically see, this is basically happening in the back propagation, okay? So yes, this was it about leaky ReLU and parametric ReLU. In the next video, we are going to see about one more linear unit, which is called as exponential linear unit. And whenever I say ReLU full form is nothing but rectified. Let me just write it down. Rectified linear unit. Okay. So in the next video, we are going to discuss about ELU, that is exponential linear unit. Right. So this was it from my side. I will see you all in the next video. Thank you. Take care. Hello guys, so we're going to continue discussion with respect to activation functions. Already we have seen about leaky ReLU and parametric ReLU, and this was basically used to solve the problem of the dead neurons or dead ReLU problem with respect to the ReLU, right? Again, one disadvantage which I missed in my previous video was about zero-centric, right? Yet this leaky ReLU and parametric ReLU, it is not zero-centric, right? If it is not zero-centric, then the weight updation will not be happening efficiently. So this is not zero-centric. Okay. Now what we'll do is that in ELU we'll try to understand, and again ELU is also used to solve the problem of ReLU, but it has more advantages than the leaky ReLU and pre-ReLU. Pre-ReLU basically means parametric ReLU. Okay. So here you can see with respect to ELU, that is exponential linear units. This is the formula that is used. Whenever the x value is greater than 0, then it is going to use x. Otherwise, it is going to use this specific equation. So this is what is basically in the forward propagation. So at the end of the day, you're not getting a straight line like how we used to get before. Instead, you're getting something like this. And in the backward propagation, you can see that your value is having something like this, right? So you'll be getting the max value like after this, right? After this range, whatever value you probably get, it'll keep on increasing. But anything that is greater than 0 will be 1. Anything that will be less than 0, it'll be having this kind of shape and it'll be having those values. Okay. So that is what is with respect to the ELU, right? Now what all things it is solving? Obviously, it is solving the dead ReLU problem. Why it is solving the dead ReLU problem? Because we're not never going to get zeros over here, right? It is not like we're not never going to get zeros, right? Whatever values it is coming greater than 0 in this particular case, right? So over here with the help of ELU, the advantages is that the number one, no dead ReLU issues. Okay. No dead ReLU issues. The second advantage is that it is also zero-centric. Zero-centric. Okay. Zero-centric basically means all the points are now in zero-centered, right? This is basically, or I can basically like zero-centered, right? So that basically means my mean is almost 0. Zero-centered. Now in the previous case, it was not zero-centered, but now it is zero-centered. You can see all the values. It is passing through 0, but it is also having different negative values, right? So these are the major advantages. Again, disadvantages wise, the equation that is used, the mathematical equation that is used, or I can basically say, okay, it is slightly more computational when compared to the previous technique, like leaky ReLU and all. Okay, computationally intensive. I can also write this one. Okay, so this was with respect to ELU. Again, it is used to solve ReLU problems only. It is used to solve ReLU problems. See, at the end of the day, what is basically happening? Just get this proper understanding, guys. We are trying to fix some problems, and this entire use of activation function will be based on what kind of activation function you're using and what kind of data set is there. You can play with different activation functions. Now, what is the best combination of activation functions that we should definitely use? That is what I will be talking in my next video. Should we use ReLU? Where should we use sigmoid? Or where should we use pre-ReLU? All these kind of things I'll be discussing in my next video. But I hope you got an idea about exponential linear unit, and this is also used to solve the ReLU problems. So yes, this was it from my side. I will see you all in the next video. Hello guys, so we're going to continue discussion with respect to activation function, and in this video we're going to discuss about another new activation function which is called as softmax activation function. Now why softmax activation function is used? It is specifically used in the output layer for a multi-class classification problem. Okay, super important. Please make sure that you watch this video clearly because this is super important, because in most of the problem statement you get multi-class classification problems, right? And for that in the output layer you specifically have to use softmax activation function. Now what does that mean? Let's say I have an input layer wherein I have 3 specific inputs. I have a hidden layer where I have 2 neurons, and then one more hidden layer where I have 2 more neurons, and finally I have my output layer which I have 1 neuron, right? Let's say this is the situation, and as you know that I have to connect each and every layers by using weights, right? So this will get connected to this will get connected to this. Similarly, everything will get connected over here, right? So, and finally it will get connected to the output layer. And then what we have basically a loss function, and then we do the backpropagation. So here we give our input x1, x2, x3. Okay. Now let's say this particular output, since I've used only 1 neuron, so this is specifically binary classification, right? Now, usually in the binary classification, the output layer over here, so this is my output layer, the output layer will specifically have a sigmoid activation function. Why? Because sigmoid activation function transforms the value between 0 to 1. Right? Now, since it is transforming between 0 to 1, let's say if I keep a threshold where I say if it is greater than 0.5, then it is going to give us 1. If it is less than 0.5, it is going to give us 0. So this way, we can basically solve a binary classification problem. But what if, instead of just a single, you have just a single output, right? What if I have multiple outputs? Okay, and let me give one more example for the same, right? Let's say that I have, again, the same thing over here. So let's say I have this 3 neurons in my input layer. Let's say I have this 2 neurons in my hidden layer 1, another 2 neurons in my hidden layer 2. And finally, in the output layer, let's say that I have 3 outputs. Or 4 outputs. Let's consider that I have 4 outputs. And my main task over here is to basically determine, let's say I'm just going to give you a problem statement. I am giving an image in my input layer. Let's say this is my image features. I can basically say, let's say this is my x1, x2, x3, and this is basically getting connected here to here, here to here, and this will basically get connected like this, because every nodes will be connected to the hidden neurons as we go from layer to layer, right? So finally, this will get connected over here, and this will get connected over here, and this will get connected over here. So this is how you'll get connected to each and every. But here you can clearly see that in my output layer, this is a multi-class classification problem, because I really need to find out 4 outputs, right? So let's say if x1, x2, x3 are my input features, and I need to predict whether the features that I'm actually giving is basically a car or a car. I'll give animals, right? Let's say whether it is a cat or a dog or a monkey or a horse. So let's say I want to predict this, right? Now in this scenario, I cannot use sigmoid activation function because sigmoid activation function will only be giving me binary outputs, that is 0 to 1, right? And for that, I just have one neuron, right? But here, since I have four neurons, the four output neurons, the four output in the output layer, I have four nodes, right? So this will give the probability of cat, this should be giving the probability of dog, this should be giving the output of the probability of monkey, and this should be giving the output of the probability of the horse, right? Now in this scenario, we cannot use sigmoid. So for this scenario, we use something called as softmax activation function. That basically means in the output layer, instead of using sigmoid as an activation function, we use softmax activation function. Okay, so I hope you got a clear idea about why do we use softmax activation function. Now let me show you how the softmax activation function work. Okay, so let's say that before applying the activation function, that is softmax, I got the output like -1, 0, 3, and 5. Let's say I got this output. And how do I get the output? Whatever output I'm getting from here, it will get multiplied to this weights, and then a bias will get added over here, right? I'm not drawing each and everything because I probably think you should know right now. And similarly, this line will have different weights. This output will get multiplied to this weights, and whatever bias is getting added over here, that will give me an output of 0. Let's say that after that calculation, I got this. Now after this, I need to apply softmax activation function. Now what is the formula for softmax? See this. Softmax formula is very simple. It is nothing but e to the power of y of r divided by summation of k is equal to 0 to n, and this e to the power of y of k. I'll talk about what is I. I basically means is with respect to every node. Let's say this is the first node, so this will be ei1. This is the second node, it will be ey2, right? Third node, ey3, right? And when I say k is equal to 0 to n basically indicates the number of output node. Okay, so 4 output nodes are there, so k will be iterating from 1 to 4. Now this is the formula. Okay, now understand I got the output. After this, I need to apply the activation function. Now let's go ahead and try to find out what will be the output after applying the activation function, that is softmax. Okay, so here what we are going to do is that quickly I'll apply the softmax function. Now to apply the softmax function, I will do it for horse. First of all, for cat. Now you know for cat, right? What will be the output? See, e to the power of y of I. Y of I in this particular case will be y of 1, right? So e to the power of, let me just write it down. E to the power of y of I is what? -1. So y of I is nothing but the output after doing all the calculation. That is the output multiplied by the weights and the bias. So here I'm just going to write it again. Y of I is nothing but the output, whatever output I'm getting, multiplied by the weights plus bias. Okay. So in this case, you will be seeing that softmax of cat, which is equal to e to the power of -1, right? So because whatever is here, after this only I have to apply the softmax activation function. So in this output layer only I'll be applying the softmax, right? Softmax. Now let me just remove this because I don't want to make this diagram quite messy. So e to the power of -1, and then here you can see that summation of k is equal to 0, e to the power of y of k. That basically means I need to do the summation of with respect to all the output. So here it will be e to the power of -1 plus here you can see e to the power of e to the power of 0 plus e to the power of 3 plus e to the power of 5, right? Now when I do this specific calculation, and probably you can also do this calculation, it is very much simple, not a big deal. E to the power of -1 will basically give you somewhere around means e to the power of -1 divided by this will give you somewhere around 0.00033. I've done the calculation, you can check it out. Okay. Now similarly, softmax with respect to the next category, right? At the end of the day, we'll be finding probabilities. Like what is the probability of this particular output to be cat, right? Something like that. So the second one is nothing but dog. So for dog again, e to the power of what is e to the power of 0, and again we will be dividing by this entire same thing, that is e to the power of -1 plus 0 plus 3 plus 5. And here if you do the calculation again, you're going to get something like 0.024. Sorry, 0.0024. Then coming to the third one, that is monkey. And this is with respect to applying the activation function. Okay. Now monkey over here you can basically write e to the power of 3 divided by e to the power of -1 plus 0 plus 3 plus 5. And this is nothing but if you do the calculation, it is somewhere around 0.0183. Okay. And finally, when you do the calculation with respect to horse, okay, then here you'll be able to see e to the power of 5 divided by e to the power of -1 plus 0 plus 3 plus 5. And here you're going to get 0.1353. So obviously from this, you can see the value of the horse is maximum. But still we need to calculate the probability. And you know that the sum of all these categories, right, with respect to probability, it should be 1. So if I really want to find out the probability of the output of being horse, here what I can do is that I can take 0.1353 and divide by all these values, that is 0.00. So here let me write it down again, divided by 0.00033, then it will be 0.0024 plus 0.0183 and plus 0.1353. And finally, you will be seeing that the output that you're probably going to get is something somewhere around 86% approximately. So here the output that you're going to get is nothing but 86% approximately, that is 0.86. So obviously, similarly, you can find out the probability of cat, dog, monkey, right? All you have to do, take this value, divide by all the other values. But from this, you can definitely see that based on this output, I'm actually getting the highest probabilities with respect to horse. So the output will be selected with respect to the horse itself, right? So I hope you understood with respect to the softmax in the output layer, we apply the softmax activation function to calculate the multi-class classification probability with respect to all the categories that are present, right? So this was it with respect to the softmax activation function. Now in the next video, I'm going to finally discuss which activation function to use when. At least you got with respect to sigmoid and softmax. Whenever you have a binary classification problem, use sigmoid. Whenever you have a multi-class classification problem, use softmax, right? So yes, this was it from my side. I will see you all in the next video. Keep on revising, keep on learning. Never give up. If you're finding it difficult, try to go again the video again and again. Just go through the video again and again. You'll be able to understand things. So yes, I will see you all in the next video. Thank you. Hello guys. So till now we have discussed about so many different kind of activation functions, and still one question that probably may be coming in your mind is that which activation function to use when, right? So let me just explain you in this. At least with respect to sigmoid and softmax, you've got some idea in the output layer. If it is a binary classification, you should use sigmoid. If it is a multi-class classification, you should use softmax, right? So let's say I have my input layer. I'm just giving as an example. Let's say I have two hidden layers, right, like this, and probably let's say I have one more hidden layer, and I will keep an option, right? So first of all, let's say that I just have one output node. Okay, so let's say I have one output node in the output layer. And you know that in this case, what will happen? It will just get connected, or everything will get connected. And remember, this needs to be connected. That basically means all the weights will be initialized in this. And going further, we'll also be talking about which all techniques are there with respect to weight initialization. Okay. So here are your x1, x2, x3. So let's go with respect to x1, x2, x3. And this is basically your HL1. This is your HL2. And finally, this is your output layer. Okay, output layer. Let me make it up like this. Output layer. Now, usually, See, what happens over here, we take the inputs, we multiply by the weights. So let's say over here, I'm just initializing some weights, W1, W2, W3, W4, W5, W6, right? So these are the weights. So first initially what happens, before we go to the hidden layer 1 neuron, this input get multiplied with the weights, and then a bias is getting added. So a bias will get added, B1, which is giving a constant value like 1. And then after this, in the second step, we apply an activation function, right? In the second step, we apply an activation function. Now, before I discussed about sigmoid activation function. So always remember what happens in the hidden layer if we use a sigmoid activation function. And let's say this entire neural network is very deep. That basically means, let's say I have 5 to 10 hidden layers. So when I say deep, right, that basically means many number of hidden layers and many number of neurons. So if I use sigmoid in the hidden layer, so if I use the sigmoid, so if in the hidden layers we use sigmoid as an activation function, then what will happen? This will lead to vanishing gradient problem. This is super important, right? Vanishing gradient problem. And we understood what exactly is vanishing gradient problem, right? So because of this, what happens is that usually whenever we are doing some kind of coding, we never use sigmoid or tanh, even tanh, right? If you try to use tanh also, this problem may come up, right? Like vanishing gradient problem. So always remember, in the hidden layer, in this and in this, we always try to use ReLU or its variant, right? Now, when I say variants, what does that basically mean? We can use pre-ReLU, we can use leaky ReLU, right? Which we have actually discussed, or we can also use pre-ReLU, leaky ReLU. We can also use ELU, right? Because these are solving some ReLU problems. Because in ReLU also you have a leaky, dead leaky ReLU, right? There is a dead neuron concept, right? Because the ReLU derivative is either 0 or 1. So you can actually use ReLU or its variant in this layer, that is your hidden layer 1 and 2. But with respect to the output layer, if this is a binary classification problem, use sigmoid. But if this is a multi-class classification problem like this, at that point of time, use softmax, right? Softmax. This is the thing that you should always keep in mind whenever you're building a ANN of any depth or any length with respect to any number of hidden layers or with respect to any number of hidden neurons. This is the simple concept of which activation function to use when. Because if you use softmax or tanh in the hidden layer, obviously there will be a chance of vanishing gradient problem, and you know what happens because of the vanishing gradient problem. So it is always good that try to use sigmoid or softmax always in the end layer to basically distinguish between binary and multi-class classification. So here I'm basically going to write it for binary classification, and this will be for multi-class classification. Very simple. Okay. So always keep this in mind, and please be patient with respect to all the theory. Once we complete all the theory, right, everything will make sense once we start implementing things, and all these things will probably be coming up when we try to implement with the help of TensorFlow. So yes, this was it from my side. I hope you have understood this particular video. Keep on revising. If you find any difficulty, keep on revising things. Never give up. You just have to learn these things. You need to understand those things, and with the help of some powerful libraries like TensorFlow, it will be very, very easy to implement. So yes, this was it from my side. I'll see you on the next video. Thank you. Hello guys, so we're going to continue the discussion with respect to artificial neural network. In this video, we're going to discuss about loss function and cost function. Now, already we have finished up with all the activation functions and all. So let's say that I have my neural network. So let's say that this is my neural network. This is with respect to my input layer, and this is my hidden layer, and finally I have my output layer. Okay. So here again, I'm using a 2-layer neural network. Okay. So and always remember, guys, while practicing also, you should continuously draw this kind of diagram so that you'll be able to understand more properly, and you'll be able to get the whole idea about this, right? So let's say I have 3 inputs, x1, x2, x3. Now till here, what we did is that in the forward propagation, we multiplied this inputs with the weights, and then we applied an activation function on the second step. Similarly over here also we have something like b1. Here we have something like b2, right? So we add a bias with one constant like 1, and this will basically get multiplied, and then again this output will get multiplied with this weights, and finally I get this particular output. Whatever output I get, I basically have, I call it as y hat, and then we calculate the loss function, wherein our main aim is to basically reduce the difference between y minus y hat. Y minus y hat basically means it is with respect to the actual point and the predicted one. That specific difference I have to keep on reducing, and this will get reduced with the help of optimizers. And gradient descent was one of the example of the optimizers which we have considered, right? So gradient descent, and what it does is that in the back propagation it updates all the specific weight. Now still we have to discuss about optimizers also, but before that I really want to talk about what are the different types of loss functions, right? Because loss functions are various different types, and there is also a concept when in many research papers you also find out where they'll be talking about cost function. So first of all, we'll try to understand the difference between loss function and cost function. Let's say that I have my inputs like x1, x2, x3, and this is basically my output. Let's say these are my data points, and this is basically my output 1, 0, 1, right? So here with respect to this, let's consider that this is my data set altogether. And with respect to this particular data set, the first thing that we are going to understand over here is that what is the difference between loss function and cost function. Okay. What is the difference between loss function and cost function? This is what I really want to talk about first of all. Whenever we talk about loss function, guys, what happens is that we take every single data point and we do the forward and backward propagation. See, what I'm saying is that we in the loss function, let's say one of the loss function that I'm using, which we basically say it as mean square error. I'll be discussing in depth about it. In mean square error, what we do is that we just take y minus y hat whole square. So suppose let's say this is my loss function over here. That basically means I'm trying to find out the difference between y and y hat. Okay. Now when I try to find out the difference over here, you can see that I will take one data point, I will pass this x1, x2, x3, then all the forward propagation will happen, all the calculation will happen. Finally, we get the y hat, and then we compute the loss, and then with the help of optimizer, we update all the weights, right? So for every data point, you will be seeing that forward and backward propagation will be happening. Okay. But with respect to cost function, the same MSE formula will become 1 by n summation of I is equal to 1 to n y of I minus y of I hat whole square. So here what we are doing is that instead of taking one point, we can basically pass all the points together, right? So and we can also pass batch of points, which I'll be talking about what is batch and what is other things. But here what we can do is that we can actually send in the forward propagation with respect to all these data points. We can send it at one time itself, right? Now when I'm sending all the data points at one side, so all the forward propagation will happen, right? So after the forward propagation will happen, what will happen? All these operations will take place. Then y hat will get computed. Now y minus y hat will happen for each and every data points, because for this I will be getting a different y hat. For this I will be getting a different y hat. For this I'll be getting a different hat. So with respect to cost function, you'll be seeing that my formula will be 1 by n summation of I is equal to 1 to n y minus y hat whole square. So here what I'm doing is that whatever output and the predicted output is with respect to each and every data point, that entire summation, this error summation will happen, and then we'll find out the mean. And our main aim is again with the help of optimizers, we really need to reduce the cost function also. So in the backward propagation, only once all the weights will get updated. So the basic difference between loss function and cost function is that in loss function, As we pass each and every data point, for every data point we calculate the y hat and then we calculate the loss. And with respect to every data point, we do the back propagation where we update the weights. Okay. But with respect to the cost function, we pass all the data points all at once. And for every data point, we calculate y minus y hat for every data points. And then we do the summation of all these errors. And finally, we find out the mean. And then we have to reduce the cost function. Okay. And the reducing of the cost function, what happens, will be using some optimizers. And all the weights will get updated only once. Okay. In this particular case. So this is a basic understanding about the difference between loss function and the cost function. Always remember, if you want to play with every data point and update the weights, you use loss function. Or if you want to basically use all the data points and only update the weight at once in the back propagation, you can use cost function. So that is the reason why I have written summation of I is equal to 1 to n y minus y hat whole square. Okay, so this is the basic example. Okay, so I hope you have got the understanding with respect to loss function and cost function. Now in the next video, we're going to discuss about how many different types of loss function or cost function we have. And with respect to this, again, it will be with respect to the regression and classification problem, because with the help of AN, we can solve both regression and classification. And that is what we're going to discuss about in the next video. Thank you. Hello guys, so we're going to continue discussion with respect to loss function and cost functions. Now we're going to see what are the different types of loss function and cost function, and we'll see with respect to two important problem statements. Now we have been discussing about ANN, and as you know that with the help of ANN, we can solve both classification and regression problem. Classification and regression problem. First, what we'll do is that we will discuss about all the loss functions that are used in regression problem, and then we'll be discussing about all the loss functions that are used in classification problem. Now usually in regression, we use something called as mean squared error. Okay, we use, which is also called as MSE. We use the second one that is called as mean absolute error. Mean absolute error, that is MAE. And the third one we specifically use is something called as Huber loss. Okay, Huber loss. And one more loss function which you can basically use is something called as root mean squared error. Okay, so first of all, we'll just try to complete the understanding of all these particular loss functions, that is mean squared error and all, and then we'll move towards classification. So in this video, let's complete the entire loss function of mean squared error. Now the first one that we are probably going to discuss about is something called as mean squared error. Now usually the mean squared error, which is also denoted as MSE, there are two things. If you are probably moving with respect to only one data point and updating the weights, I will say is as loss function. And the loss function is very simple, y minus y hat whole square. Okay, and this is with respect to every data point you try to calculate. Whereas if I really want to talk about with respect to the cost function, so the cost function formula will look like 1 by n, when I'm doing the summation of I is equal to 1 to n, y of I minus y hat whole square. Right? Now this specific loss function is super important. Why? Because at the end of the day, you'll be seeing that this is all loss function, right? See, at the end of the day, whenever I say y hat basically means what? Whatever input multiplied by the weight, and then whenever we apply an activation function, whatever output is basically coming, that is basically my y hat. Right? After performing all the forward propagation. Right? Forward propagation. That is basically my y hat. And then I have to probably calculate the loss function with the help of optimizers. We have to back propagate and update the weights. See, this particular loss function that we have written, it is basically in the form of quadratic equations. Okay. Now there is one very important thing about this quadratic equation, and there are some importance with respect to this quadratic equation, because whenever I take this quadratic equation, and let's say if I plot this quadratic equation with weights and the loss value or the cost value, loss or cost value, you'll be seeing that we will be getting a very amazing gradient descent, like this, right? So this is what we are going to get. We are going to get this kind of parabola curve, and you know the importance of this parabola curve, right? Why? Because this point that you see is basically called as the global minima, right? This point is basically called as the global minima, and our aim is to update the weight in such a way that we should be coming towards this global minima, so that my loss function will keep on decreasing, right? So that is what is basically possible with the help of this particular loss function. And we have already discussed this probably, if you know about machine learning, where we have discussed about gradient descent. So this entire parabola curve is nothing but it is called as gradient descent. Okay, the importance of gradient descent is that it has one global minima. It knows that how the loss needs to keep on getting reduced, and you know that weight updation formula also that is basically getting applied. So whenever we try to plot this weights with this respect to this particular loss function or cost function, I'm always going to get this kind of parabola curve. Let's say if I'm trying to probably apply with this cost function, then I will be getting a lot of weights. It can be W1, W2, W3. At that point of time, I may get a parabola curve which will be looking like this, right? So in a 3 dimension, you can see that these will be the points, and our main aim is to basically come over here, which is my global minimum, right? To come over here. So all these points will be coming at this side, right? So that is how it basically works. And if I probably consider in a 4D or 5D, obviously we'll not be able to visualize, but in a 3D I'm able to show it to you. Okay. Now there's some advantages and disadvantages of using this mean squared error. So first of all, let's go ahead and discuss about the advantages. So here are my advantages, and here are my disadvantages. Okay, the first major advantages is that whenever we have this kind of parabola curve, this is very much differentiable. So MSE is actually differentiable. Now whenever I say differentiable, that basically means at any point of time I will be able to find out the derivatives, and already we do that in the weight updation, right? Super important for the weight updation, because if you remember the weight updation formula, what it is, W new is equal to W old minus learning rate of derivative of loss with respect to derivative of W old. If you remember this formula, here we are basically trying to find out the derivative. This is nothing but this is the slope, right? So it is basically differentiable. This MSE equation is differentiable. Okay, now coming to the second point over here, and we have discussed about all these points, and probably it'll just give you a revision over here. So it has one local or global minima. Right, super important topic again. Over here you can see that I just have one global minima. Okay, what do I mean by local minima? Let's say that I'm having a curve which looks like this. Okay, so here all these points that you see, this is local minima, right? And when you don't have a quadratic equation, you basically get this kind of local minima. But always remember, in my parabola curve, I should only be getting one global minima, right? So here this is my local and this is my global. If I'm stuck in the local minima, here also the slope will be 0, so I cannot go towards the global minima itself. So here it is very much clear with the help of this quadratic equation, it has one local or global minima. Then the third step, the third very much advantage point is that it converges faster. It converges faster. Why? Again, because I'm getting a smooth gradient descent over here, and because of the weight updation formula, we'll be able to converge it quite faster. Okay, with respect to finding the global minima. Let's talk about the disadvantage. Disadvantage is very much simple over here. It is not robust to outliers. Now, why it is not robust to outliers? Let's consider that I have a problem statement over here. Let's say this is my regression problem, and I have some other data points like this, right? Our main aim of using ANN in this problem statement is that I really need to find out a best fit line, right? Now, when I find out a best fit line, this is fine, right? We basically go ahead and calculate our cost function. The cost function is nothing but 1 by n summation of I is equal to 1 to n y of I minus y of I hat whole square, right? Once we do this, you'll be able to see that. We'll be able to get the error. But what happens? And over here, you have to remember this term, yi minus yi hat whole square. That basically means we are increasing the error. We are squaring it up, okay? Now, just imagine if my outlier is here. Let's say this is my outlier. Now, because of this outlier, what will happen is that my cost function will keep on increasing. my cost function will increase because this is also my y high, and based on this particular data set, my y hat will come over here. So this error is also increasing. At the end of the day, I'm squaring it up, right? I'm squaring it up. Summation of I is equal to 1 to n y of I minus y of I hat whole square. I'm squaring it up. So when I square it up, that basically means because of the outlier, I'm penalizing the cost function. Okay, understand this word. We are penalizing the cost function. The cost function. We are squaring it up. So if there is an outlier, the error will keep on increasing. Now because of that, what will happen? This line will get moved by a lot. That basically means again I have to change all my weights and I'll get updated over here. Now here you can see there's a major movement. This was an outlier, but because of an outlier, there is a major movement like this, right? So this equation is not robust to outliers. Why? Because we are penalizing the cost function with respect to error. I can basically say we are penalizing the error, right, over here. Right? So this is the major disadvantage with respect to the mean squared error. Now let's focus about the second one. Okay, the second one is basically called as mean absolute error. Mean absolute error is nothing but it is called as MAE. Okay. Now what is the mean absolute error and how the loss function and the cost function formula is? So my loss function formula will look something like this: y minus y hat with respect to this. You can basically say this is a kind of mode sign. Okay, and then I will write my cost function as 1 by n summation of I is equal to 1 to n y of I minus y hat. I'm not squaring it up, but I'm just using a mod sign. Okay, that basically means even though a negative value will come, it will be basically coming as a positive value. Okay, now with respect to the major advantage over here, what are the advantage of using this? Okay, and one thing you really need to understand, guys, with the help of this, right? Okay, first of all, let me talk about the advantages. Now the advantages over here is that number one, okay, it is robust to outliers. Why it is robust to outliers now? Because understand over here, before we were squaring the error. That basically means we're penalizing the error. Here we are not penalizing the error. So what happens is that even though I have an outlier, which will be this kind of data points, let's say if this is my data points, okay, and let's say this is my best fit line that I've computed, even though an outlier comes, but we are not penalizing this error, we are not squaring it up, the cost function will increase by a little bit value, but what will happen is that this line, it will just move a little bit. It will not have so much major movement like how we had, right? So whenever in our data set we have an outlier, we should definitely use mean absolute error. Okay, now coming to the with respect to the disadvantage, what is the disadvantage of using this? Number one, see over here in the previous equation we got something called as a parabola curve. In this we don't get a parabola curve, we get this kind of curve. Okay, now what this is here, since our parabola curve looks like this, here we cannot directly use gradient descent concepts. Here what we do is that we basically use subgradient concept. So we take a part by part and then we calculate the slope, right? Usually whenever we have this kind of curve, we'll be able to calculate the slope very much easily. But with respect to this particular equation, we get this kind of curve, so we have to basically call this as subgradient. We take a subgradient and then we calculate the slope. So usually, just for terms of understanding things, you can basically say that convergence usually take time in this. Convergence usually takes time with respect to this, right? Usually takes time in ME, right? Because here we don't get a parabola curve, instead we get this kind of curve, right? And with this kind of curve also you cannot find gradient descent very much easily. You have to use a subgradient concept where you take part by part and then you calculate this. Okay, so this was our idea about mean absolute error. See, at the end of the day, I will talk about that. Even though you don't have any outliers, let's say, sorry, if in the data set you have outliers, I would suggest you to go with mean absolute error. If you don't have outliers, then you can probably go with mean squared error. Now see, even though you also have outliers, what you can do, you can remove the outliers and also use mean squared error. But in this, you will be losing some amount of data. Okay. Now the third one is basically called as Huber loss. Now this is also very much important. So here you have something called as Huber loss. Now Huber loss is nothing but it is a combination. You can basically say that it is nothing but it is a combination of MAC and then it is basically a combination of ME. Okay, and with respect to all the things, right, the loss function will look something like this. Sorry, this will be my cost function. The cost function will look like this. Okay, it is basically saying that you can use a combination of both of them. Let's say if you are having an outliers, then probably use this particular equation. Sorry, if you don't have an outliers, then you use MSE. And how do you determine this? Here you'll be writing if y minus y hat is below some threshold. Okay, is below some threshold. This threshold is basically a kind of hyperparameter. If this error is below this particular threshold, then we can use mean squared error. Otherwise, you go ahead and use the next one, that is y minus y hat. That is nothing but your MAE. And here I'll be subtracting this with the same hyperparameter square. Okay, so this is basically the equation that is used in this case. In short, what we are doing is that if there is an outlier, so this indicates that there is an outlier. Okay, sorry, if this indicates that there is no outlier because the error is less than this particular hyperparameter. So here I can say here this basically indicates that this is not an outlier. If this is less than this particular value, here you can basically say that I'm going to use MSE. Otherwise, basically in the else condition, what we can do, if there is an outlier, if it is greater than this particular value, we can directly use this ME concept. And here what we are doing, we are multiplying with this kind of hyperparameter minus half of this particular square. Okay, so this is nothing but this is a hyperparameter over here. Okay, so this was the basic understanding of the three common loss functions that we use, that is mean squared error, mean absolute error, and Huber loss. The fourth one is something called as root mean squared error, RMSE. Okay, we basically say it as root mean squared error. Now what exactly is root mean squared error? With respect to the root mean squared error, the cost function is nothing but it is basically summation of I is equal to 1 to capital N y of I minus y of I hat whole square divided by capital N. Okay, that N is nothing but the number of data points. So this is basically on top of mean square error, I'm just applying a root. Okay, on top of mean square error, I'm just applying a root. Now just think over it, guys, and just take this as an assignment. What do you think are the advantages and disadvantages with respect to root mean square error? Okay. So guys, yes, this was it from my side. I hope you were able to understand all the different kind of loss functions for regression problems. Now in the next video, we'll be discussing about all the loss functions that we usually use in the classification problem. So yes, this was it. I will see you all in the next video. Hello guys, so we are going to continue the discussion with respect to loss or cost functions. In our previous video, we already discussed about the loss and various loss and cost functions for regression problem statement. In this video, we are going to focus on loss or cost functions for various classification problems. So at the end of the day, why loss function is basically required, because our main aim is that with the help of optimizer, we'll try to reduce the loss functions. So to begin with, let's say I'm just going to write over here as classification. In this classification problem, if I probably consider there are two types of classification problems that we usually solve, right? One is binary classification and one is multi-class classification. Now with respect to this particular classification, the technique that we specifically use, we say it as cross entropy. Okay, and this is the loss function name. Okay, so we write it as cross entropy. And usually based on the different types of problem statements, like whether it is a binary classification or whether it is a multi-class classification, we have three different types of this kind of cross entropy loss functions. The first one is basically called as binary cross entropy. The second type is basically called as categorical cross entropy. And the third type is basically called as sparse categorical cross entropy. So sparse categorical cross entropy. So with respect to any classification problem, let's say binary cross entropy is specifically used for binary classification. This is used for multi-class classification, and this is also used for multi-class classification. So we will try to understand what is the mathematical formula that is basically used in binary cross entropy, and then we'll also try to understand what is used in categorical cross entropy and sparse categorical cross entropy. So we'll try to complete all these things and understand, guys, these are super important interview questions. Okay, so to first we'll go with we'll be discussing about binary cross entropy. Now, guys, if you have probably learned logistic regression, then this binary cross entropy will be very much simple to understand. In binary cross entropy loss function, we basically write this specific loss as nothing but minus y multiplied by log of y hat minus 1 minus y multiplied by log of 1 minus y hat. So the entire loss function is basically based on this particular log loss formula. Okay, and you know that this is the same log loss formula that we specifically use in logistic regression. Now, what does this loss function basically specify? And as you know, y is nothing but the actual value. Okay, and y hat is nothing but the predicted value, right? Predicted values. Now, with respect to the loss function, I can also write this by giving two important statements. Let's say if y is equal to, if I say if y is equal to 0, if y is equal to 0, in this particular case, this will entirely become 0. So here I can specifically write that if y is basically 0, see this y will be 0 and this 1 minus 0 it will be there. So this entire thing will become 0, right? Whereas over here I can basically write minus log 1 minus y hat. Okay. I'll also be talking about how do we solve this particular y hat also. How do we find out that specific y hat? And the other condition is that if y is equal to 1, okay, now in this particular scenario, here you can see this will become 1. So at the end of the day, I will be getting minus log y hat. This entire term will become 0 in this particular case. Now, these are the two scenarios that we specifically use, okay? Now, let me just show you with the help of a simple neural network, okay? Let's say in the input layer, I have two neurons. In the output layer, in the hidden layer, I have one neuron. And one more neuron I have, and this is finally my output, okay? So let's consider this is my simple neural network. And usually, this loss function where I'll apply over here after getting my y hat, right? So if I'm using this particular formula to predict the output, understand this y hat, how it will be computed. Understand this thing, okay? Here, whatever output I will be getting, this will get multiplied to this weights, right? So if I probably initialize this weights, it will be W1, W2, W3. Here, you know what is the output? It is O1. This O1 will get multiplied by W3, and then here we'll be adding a bias, let's say B2, and this will be 1. This will get multiplied by this, and then we'll be adding this particular bias, right? So over here, what is the O2 that I'm getting? O2 is nothing but, here I'm applying an activation function. And since this is the binary classification, what kind of activation function I will apply? And we have learned this, right? The activation function that we are going to apply is nothing but sigmoid, right? So in short, since this is my output layer, here, and it is a binary classification problem, what we are going to do is that we are going to apply the sigmoid activation function here, because I require only zeros or ones. The output can be either 0 or 1, right? So since this is a binary classification. So this O2 is nothing but, I'll be applying a sigmoid, wherein I will say O1 multiplied by W3 plus B, right? So this is what is the formula to get the O2, right? So this O2 is nothing but, this is nothing but y hat only, right? So over here, if you really want to compute the y hat, all I'm doing is that I'm applying an activation function e to the power of minus z. So that basically means, and why is the actual output? Okay, so this is super important to understand. First, whenever you're using a loss function, how we are calculating the y hat, you know that, right? Because y hat is nothing but the output value that I'm getting, and that is nothing but this O2 itself, right? After applying the activation function over here, whatever is I'm getting, I'm basically getting the y hat. And then what I do, I actually find out the difference between y and y hat, and based on that, we basically get a loss. And then while doing back propagation, we apply an optimizer and we try to reduce this loss. That is what we are basically doing. And this forward and backward propagation will keep on going unless and until we have a less loss value, right? So in short, whenever we talk about binary cross entropy, this is the loss function that we specifically use, and this is used after you get the predicted output, right, to calculate the difference between y and y hat. Okay, and I've also told you how do we get this y hat? It is nothing but we apply this simple sigmoid formula, okay, sigmoid activation function, and this is only applied at the output layer. Okay, so I hope you have got this. Now coming to the second one, right? So over here binary is done. Now we need to understand this categorical cross entropy. Now in order to understand categorical cross entropy, let me give you a very good example. That basically means this categorical cross entropy that we are using. Let me write it down. Categorical cross entropy, right? And this is the loss function, and this is specifically used for which problem statement? It is used for multi-class classification problem. Now in order to make you understand how this loss function is applied, I just want to give you a simple example. Let's say that I have a data set. I have features like F1, I have features like F2, I have features like F3, and let's say this is my output. Okay, so let's say I'm putting some random value like 2, 3, 4. Okay, I don't know what is this feature 1 and feature 2, but I'm just putting like the output. Whenever I get this particular input, the output is good. Whenever I get this particular input, the output is bad. And whenever I probably get this particular input, the output is neutral. Let's say, so in short, what this is a multi-class classification problem, right? Because the output I have more than 2s. That is, this is not a binary classification, but multi-class classification. Now during this scenario, we cannot use binary cross entropy, right? So we have to probably go with categorical cross entropy. Now how does categorical cross entropy act in this? The first thing categorical cross entropy, what it will do is that it will take this output variable and it will apply something called as one hot encoding. That is OHE. OHE is nothing but one hot encoding. That basically means whatever output that I'm getting over here, it is just going to convert this into one hot encoding. Now one hot encoding, what it will do? It will just go and see the output. So over here the first output is good, right? Over here the second output is bad, and the third output is something like neutral. Now wherever it is good, right, that value will be 1 and remaining all will be 0. So in short, what I'm doing, I'm converting this categories into one hot encoding, right? Whenever the output is bad, this will become 1 and remaining all will become 0. And whenever the output is neutral, that will become 1 and remaining all will be 0. So this is the first step that is probably done by this categorical cross entropy with respect to the output variable. That is y. Okay, this is with respect to the output variable. And let me just denote this as j is equal to 1, j is equal to 2, j is equal to 3. So this is basically denoting all the categories over here. Now understand this thing, okay? The loss function for this categorical cross entropy with respect to x of I, y of I is nothing but minus summation of j is equal to 1 to c. C basically means how many number of categories are there. Okay, c over here I'm writing number of categories after one hot encoding. Okay, number of categories, and here I'm just going to write this particular formula y of ij multiplied by log of n y hat of ij. Now this is the entire loss that is basically used for categorical cross entropy. Okay, now we'll try to understand this, what exactly this is. Okay, see, whenever I say y of ij, what does this basically mean? Y of ij. Okay, I will be iterating between all the data points. So this I is nothing but, I can also write one thing over here. This I is nothing but it is iterating from I is equal to 1 to n. N basically means all the data points. Okay, all the data points. So suppose if I take this y of ij, okay, and let's say I want to denote this first row first row output, right? Then this particular value will be treated as something like y11. Then the second output will be treated as y12, and the third output will be treated as y13. Okay, so this is what it is basically coming, because I have three categories. Let's say if I have n categories or c categories, it will look something like this. So y13 like this up to y1c. Why we say 1? Because this is for the first data point, and similarly for the second data point, my output will look like y21, y22, y23 like this up to y2c, and similarly I will be having for all the other data points. Okay, that is what I'm trying to show you, that how this output is basically generated with respect to y. Now, one very important thing is that what this y of ij basically denotes. Y of ij is nothing but it will be 1 if the element is in the class. If the element is in the class. Very super important. Now, what does this mean? Let's say if this first output has good, then good will be 1, remaining all will be 0. That is what I've written. 1 if the element is in the class, right? So if good is there, then this will be 1, remaining all will be 0. Okay? And here I will write 0 otherwise. This is what my y basically denotes, y of ij. And you know that this y of ij is nothing but my actual value. From the data set only I'll be able to get this. Right? From the data set only I'll be able to get this. Wherever it is 1, it is going to be 1, remaining all will be 0. Right? Wherever this good element is present on the data point, that will be 1, remaining all will be 0. Okay? So that is what the denotation is. But now the question arises, how do you calculate this y ij hat? So y ij hat, y ij hat. Now this is the problem. Like this is the thing that you need to do, and this is basically your predictions. Now, in order to calculate the prediction for a multi-class classification problem, which activation function you'll apply? You will basically apply a softmax activation function. And what is the formula for softmax activation function? Let's say I'm denoting this as soft of z. This is nothing but, you remember that in my previous video I've told you, E of j of I is equal to summation of j is equal to 1 to k, E of j of k, right? So this is what is my formula, right? To calculate the softmax activation function output, right? So if you remember this was the entire activation function that I've discussed. And in multi-class classification problem, we apply the softmax activation function, right? So what does this mean? Let's say this is my input layer, this is my hidden layer, and this is my hidden layer. And let's say that in my output layer, I have 3 categories. So where do we apply a softmax activation function? In the last layer itself, right? We apply an activation function in this particular layer after we get all the values. And then finally my output will be applying the softmax activation function. So here we'll be applying the softmax activation function, right? Now, you know, with respect to softmax activation function, what I'll get? The output y of ij hat will be in the form of probabilities. Okay, let's say if I have 3 categories, then I may get a probability like 0.2%, or so like 20%. It is saying that the output is the first category. Then it may say that 0.3%, that is 30%. It is basically saying the output is for second category, and remaining all 0.5% may be the output for the third category. So this is what is the output we get after applying categorical cross entropy, right? Categorical cross entropy. And this is what is the output that we specifically get based on the number of categories. If you have 5 categories, let's say if I have 5 categories at all, right? Let's say if I have 5 categories, and then I may have, I will get probabilities of some values like 1, 2, 3. Here you can see 3, 5, 6 it is, and let's say over here 0.2, and here also 0.2. So I may get for 5 categories, you'll be seeing that if I probably add up all this probability, it will be 1. And this is what is the output that I will get in categorical cross entropy. So categorical cross entropy actually also talks about that how much probability it belongs to the second category, or how much probability it may belong to the other category. That is the most important thing with respect to categorical cross entropy. So this also gives the value. This also gives the probability of other categories also. Super important point of other categories. So super important point, guys, and that is way how you can differentiate categorical cross entropy with sparse categorical cross entropy. Okay, so I hope you got an idea about categorical cross entropy, and this is specific used for multi-class classification. And I've also used all the formulas and all with respect to this, how you can calculate y of ij, y of ij hat. You know, at the end of the day, we apply softmax activation function. This is my input, and I have actually discussed all the things. Now let's come to the third one, which is super important: sparse categorical cross entropy. Now in sparse categorical cross entropy, there is not much difference. See, here we are probably getting things in probabilities, right? Let's say this is there, 0.2 belongs to 20%, it belongs to the 0th index or 0th category. Then this belongs to the first category, and 0.5 it belongs to the second category. I'm not worried about what category this is, okay? Right now, I'm just put some index with respect to category. So this is my 0th, first, and second categories. Now here I get the same output, but the final output I will just be getting the index. So this basically refers that the output for this particular thing will be second index. Why? Because the probability is very high. Now the difference between sparse and categorical is that, sparse categorical cross entropy and normal categorical cross entropy, the difference between this one and this one, over here, it does not focus more on finding out what will be the probability of other categories. At the end of the day, it will just say that which category has the highest probability, and this will be your final output. Okay? That basically means, let's say if I have 5 categories, like 0.2, 0.3, 0.1, so 0.2, so this you can see 5, 6, 7, 8, and again you can basically write 0.2. Let's say these are my 5 categories. This is for my 0th index, first category, second category, third category, and fourth category, right? My final output will not be coming in this form of probabilities, but it will directly say that which index, that is the first index, are having the maximum probability. So this first index, whatever category will be there, that will be my output. Okay? And this is the basic difference between sparse categorical cross entropy and categorical cross entropy. So I hope you are able to understand with respect to the loss function. These are the main 3 which will be seen even in practicals when we go through that. But in my next video, I'll show you that what is the combination of which loss function you should use for what kind of problem statement. But here I've also told you that if it's a binary classification problem, use binary cross entropy. If it is a multi-class classification problem, you can use either categorical cross entropy, or you can basically use sparse categorical cross entropy. But understand, if you want to know the probabilities with respect to other categories also, at that point of time, use categorical cross entropy. If you don't want to know the probabilities of other, right, you just want one single output, at that point of time, use sparse categorical cross entropy. Here you have some disadvantage, right? What is the disadvantage? You're losing information, right? Losing info about the probability of other categories, right? Probability of other categories. This is the only disadvantage over here. And apart from that, it is up to you. Wherever you want to use it, you can definitely use it. So I hope you like this particular video. This was it from my side. Yes, going forward, we're also going to discuss about optimizers. And till now, only theory part is there, guys. Understand, but these all are some very basic things. Even in interview, you'll get this kind of questions where you really need to answer a lot of things. So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so we are going to continue discussion with respect to the loss functions. Now this specific video is about right combination, because many people will be thinking that which loss function to use when, right? So over here, simple. Let's say that in the hidden layers, if I probably use a ReLU activation function, okay, in the output layer, let's say if it is a sigmoid activation function that we are basically using, then this becomes a binary classification problem, right? Now, if I'm using a binary classification problem, it is very much simple. What loss function I'll be using? It is nothing but binary cross entropy, right? So these are the combination, and I'll also be showing you in the practical part also. So this is the first combination. Let's go with the second combination. Let's say in the hidden in the hidden layer, we'll obviously be using ReLU, but if in the output layer we use something called as softmax. So what kind of problem we are solving? We are basically solving multi-class classification problem, and the kind of loss functions that we will be using for this is that either you can go with categorical or sparse cross entropy, right? So here you can see that I will be writing categorical or sparse cross entropy, right? So I'll write CE, right? Cross entropy. So this is with this specific combination. If in the output layer I'm using softmax, in short, I'm solving a multi-class classification problem. And in the case of multi-class classification problem, we really need to use the loss function that is categorical or sparse cross entropy. Now coming to the third combination, let's say in the hidden layers, we use ReLU or variants or its variants. I can also write its variants. Why? Because there are something like leaky ReLU and all. So or its variants, okay? I'll use this combination because we can have that all things, right? We can have leaky ReLU, we can have pre-ReLU, ELU. And let's say there is also one more combination with respect to activation function, which is called as linear. So here what we are doing is that we are basically using activation function in the output layer. And there is also an activation function which is called as linear to solve the regression problem. Okay, so this is basically solving a regression problem statement. And as you know that what all active loss functions we can use MSE, right? We can use MAE, we can use Huber loss, and we can use RMSE, right? So these all are the activations that functions that we can definitely use, not activation functions, sorry, loss functions that we can use with respect to the hidden layer and this output layer combination where I'm specifically using this activation functions. So this is what I really want to talk about in this specific video, all the possible options or combinations of options that you have, right? And always remember that when I say output layer, I'm basically talking about the activation function applied in the output layer, okay? And by this, you will be able to select it when you are doing it in the practical way, right? So this was about the right combination, and in this way, when you're combining things, you will be able to train your neural network efficiently, and you will also be seeing that your loss value will keep on decreasing. So yes, this was it from my side. In the next video, we are going to discuss about optimizers. We have completed loss function, we have completed activation functions and all. Now optimizers is the last thing. Once we complete that, then we need to also discuss about weight initialization techniques, and then finally we'll start the practical. So yes, be patient, go ahead and try to understand this everything. Trust me, the practical will be very much simpler to understand and to implement, right? So yes, I will see you all in the next video. So guys, we're going to continue the session with respect to deep learning. Till now, we have completed all the activation functions. We have also seen all the loss functions with respect to regression and classification problem. Now, the main thing is that you also need to know about optimizers, right? Now, because at the end of the day, optimizers is basically responsible for reducing the loss function. So what are optimizers we are basically going to see, right? We're going to talk about gradient descent, then we're going to talk about stochastic gradient descent, and then we are going to talk about mini batch SGD, then SGD with momentum, ADA-grad and RMS prop, and finally, we'll also be discussing about ADAM optimizers. So without wasting any time, let's go ahead and understand about gradient descent. So that should give you an idea what exactly is an optimizer, because this is nothing but gradient descent optimizer, right? Let's say that I have this neural network. It is a two-layer neural network. I have this one as my HL1, that is hidden layer one, and this is basically my output layer. You know that weights are initialized like this, and how the weight initialization technique takes place, I will be talking about it, okay? So let's say these are my x1, x2, x3 inputs. Now, usually you know that these inputs will get multiplied by the weights, and then a bias will get added. After that, an activation function will get applied. Then we have another weights that are getting initialized over here. And finally, we get the output. The output is nothing but y hat. In the next step, we calculate the loss, and we have discussed about various loss functions. Now, main aim is to reduce the loss, because if we reduce this loss, and if it is near to zero, then whatever prediction is there, it will match the output. Now, who is responsible for reducing the loss? That is where optimizers come into picture. We know with respect to the forward propagation what happens. All this particular operation that we have discussed happens in forward propagation, and we basically get y hat. Now optimizers is responsible for reducing the loss function in the back propagation, right? Backward propagation. Now in this backward propagation, the main aim of the optimizer is to basically update all the weights. So it's just going to update all the weights, right? In this video, we're going to discuss about the gradient descent optimizer. Now, when we say weight updation, so what is the weight updation formula? It is very much simple. We have already discussed so many times with respect to the weight updation formula. It is nothing but W new is equal to W old minus learning rate of derivative of loss with respect to derivative of W old. So this is exactly the weight updation formula. And how many, all the optimizers that we'll be seeing, we will be understanding how it updates the weight. And this formula is going to change for every optimizer as we go ahead. And as you know, this is nothing but it is basically learning rate. And you know why learning rate is used? Because it basically talks about the speed of convergence to the global minimum. And I've already discussed about gradient descent also, just to give you an idea again. If we probably plot after the forward propagation, if we plot the weights with the loss function or cost function, we are going to get this kind of parabola curve. And this is nothing but, this is called as a gradient descent curve, okay? Gradient descent curve. Okay. Now, always remember our main aim is to come to this particular point, and this point is nothing but it is called as global minima. Okay. So what happens with respect to this weight updation? Let's say initially the weights are over here. Okay. We are just going to make sure that we update this weights so that it reaches the global minima with respect to various number of epochs. Okay. I will talk about what exactly is epochs. So our main aim is that wherever weight comes, the weight updation formula will work in such a way that it will always make sure with the help of this learning rate, it will try to move towards this global minima. Okay. With respect to this point or this point. Our main aim is to come towards this global minima. And once it comes towards this global minima, you know that when we calculate the slope over here, it will be zero. So what is going to happen? The weight updation will not happen. Then the W new will be approximately equal to W old. At that point of time, we will definitely know that the loss function has reduced, or loss of the cost function has reduced. Now let me talk about some very important thing with respect to this. Obviously, I've discussed about what is the difference between loss and cost function. Now, what does gradient descent basically do? Okay, let's take one example with respect to the loss function. I will show you an example with respect to MSE. With MSE, the loss function formula is nothing but y minus y hat whole square. So in short, we are trying to find out the difference. Whereas the cost function formula is nothing but 1 by n summation of I is equal to 1 to n, and then we have y of I minus y of I hat whole square. Right? This is basically the formula that we use with respect to loss function and cost function. Now, whenever we use gradient descent, there are two important topics that you really need to understand. That is nothing but epochs and iteration. Okay, epochs and iteration. Now, what does epochs and iteration basically mean? And this is specifically to this cost function only. Let's say my I have a neural network. Now I do the forward propagation, then I compute the y hat, and then after that I compute the cost function. Let's say. Now in cost function, what happens over here? Whenever I say cost function, it is going to take all the data points. See, I is equal to 1 to n. It is going to take all the data points. It is going to compute the y hat, and then it is going to find out the error, and it is going to do the summation of all the errors. Right? So that is the thing. So let's say if in my data set I have 1000 data points. I have 1000 data points. Please listen to this. Very important, guys. If I have 1000 data points, what is happening in the forward propagation? I take up all the 1000 data points. I compute y hat for every data point. Like if I compute y1 hat, y2 hat, y3 hat, like that. For all the data points with respect to some weights, so that is basically get assigned with all the operations in the forward propagation. We compute y hat. Then we assign it to the cost function. We get some cost function by applying this formula. But here we are not taking one data point. See, gradient descent works in this way. It does not take one data point. Let's say that it considers all the 1000 data points and it will do the forward propagation. Now after this, let's say what will happen? We need to reduce this cost function, right? Now what we are going to use? We are going to use a gradient descent optimizer. Now what this gradient descent optimizer is going to do? It is basically going to do the backward propagation, and weights will get updated. So what is basically happening over here? One forward propagation with all the data points and one backward propagation. This combines into one epoch, right? And this process we will continue on doing till we reduce the loss value or cost value, the cost function, right? So this will be my second epoch. Like this, I can have any number of epochs. Let's say 100 epoch. I can basically perform any number of epochs with respect to this forward and backward propagation. Okay. Now what I'm actually doing over here, I'm taking 1000 data points, all the data points in every epoch. I'm finding out the cost function. I'm reducing this cost function by updating the weights in the backward propagation. Then in the second epoch, again all these 1000 data points will be taken. Again, y hat will get computed. Again, the cost function will get computed. Again, it will keep on reducing. Why? Because this gradient descent, it is going to change the weights, right? And how it is going to change the weights? By applying the same weight updation formula. So here, specifically if I talk about here, the weight updation formula will get applied. Weight updation formula will get applied. Here also, weight updation formula will get applied. So this way, as we go and do many number of epochs, the loss function will keep on decreasing. And this is how this entire gradient descent works. The gradient descent optimizers work. Now here you need to understand, I spoke about epochs. Then what is iteration over here? Now see guys, all the data points I'm taking over here and I'm doing the back propagation, right? In every epoch. So one epoch in this gradient descent, one epoch is equal to one iteration. Why I'm saying one iteration? Let's say if this 1000 data points are divided into 10 iterations. Then what will happen? In epoch 1, in the first iteration, I'm providing 100 records. Why? Because 1000 divided by 10 is nothing but 100, right? So in the first iteration, 100 epochs, in the second iteration, 100 epoch. Like this will continue and will complete all the 1000 records. So this will become one epoch. But in gradient descent, that does not happen. We take all the 1000 data points, okay? So in one epoch, you can have any number of iterations based on the number of iterations that we are selecting. But in this case, one epoch is equal to one iteration, okay? But now we'll be seeing other variations, right? At that point of time, you'll be able to understand. Now let's understand what are the advantages and disadvantages of gradient descent. See, the advantage is that, yes, the advantage is that obviously convergence will happen easily, okay? I'll not say easily, but convergence will happen, okay? Because of the weight updation formula. But if I talk about the disadvantage, and this is super important. The disadvantage of this is that you require huge resource like RAM. Huge resource you require like RAM and GPU. Why? Because let's say right now I've just taken 1000 data points. Let's say in my data points I have 1 million data points. If I have 1 million data points, then in the forward propagation I have to take 1 million data points, and then we also have to update that many number of weights. Okay, based on the neural network. But this 1 million data points will require huge RAM, right? To basically take up all the data points, store it at one location, and then probably also and this weight updation also, right? For that you require GPU. So if you're increasing the number of data points at once, that many number of weights will get created. So huge resource, RAM, GPU will definitely get required, right? So usually, like let's say if you are having less resources or you don't have a powerful system, you won't be able to train this million records. Your system will completely hang, right? And obviously this you can do it in cloud, in AWS cloud. But again, there will be some cost involved in that. Okay, so I can definitely say that this is resource intensive. Okay. So this was about the gradient descent optimizers. In my next video, I'm going to talk about stochastic gradient descent and what problem it is solving, whether it will be solving this huge resource problem or not, or resource intensive problem or not. Okay. So yes, I hope you got an idea about gradient descent, you got an idea about backward propagation, you got an idea that how the weights are getting updated, and you have probably understood what are the advantages and disadvantages of gradient descent optimizer. So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so in this video we are going to discuss about stochastic gradient descent optimizer. Already we have discussed about the gradient descent optimizers and we understood what are the advantages and disadvantages. And obviously over here you can see that if we have 1 million data points, right? At that point of time, we really need to have a huge resource. So this is resource intensive. Now let's talk about this stochastic gradient descent optimizer and how it is basically solving this resource intensive problem, right? Already I have discussed about something called as epochs and iteration, right? Now you know that, let's say if I have 1000 data points, right? With the help of gradient descent, during the forward propagation, I was giving 1000 data points and then I was back propagating. But with respect to stochastic gradient descent, I will give every data point, right? Let's say in this epoch 1, right? So let's say this is my epoch 1. So in this epoch 1, when it starts, right? And then we start the iteration 1. Okay. So here what I'm doing is that instead of giving all the 1000 data points, I will be giving just single record in every iteration. So in every iteration, I go ahead and compute my y hat, and then we go and calculate the loss function. And then what we do, we minimize this loss function by what? By using a stochastic gradient optimizer, right? And what it is going to do, it is basically going to update the weights, right? Weights updation. Then again, in the iteration 2, I will go ahead and give my second data point. So now what will happen? My second data point will go, and like this it will continue. Now within one epoch, since there are 1000 data points, you'll be able to see that there'll be 1000 iterations that will be going on to complete one epoch. Okay. To complete one epoch, it will be basically taking 1000 iterations. Okay, and this is what we are basically doing. Now see why we are doing this, and again we can have how many number of epochs we can have. Unless and until the loss value does not decrease, we can keep on continuing doing different number of iterations. Let's say 100 iteration, 200 iteration, based on the loss value. Okay, so like this we can continue many more epochs as we go ahead. But now understand why we are basically doing this. There are some certain advantages and disadvantages with respect to this. Again, main thing is that with respect to this advantage, if I talk, right? First major thing is that now, even though you have just a 4 GB RAM or 8 GB RAM in your system, right, you basically can also train the specific model, right? So it basically solves the resource issue, right? Now you don't have to have huge resources over there because now you're just taking one record and you're updating the weights, right? One record at a time, updating the weights, then going to iteration 2, again taking the next data point. So this will be my second data point, third data point, and this will basically be your 1000 data point, right? And you're basically updating the weights. So it definitely solves the resource issue, right? But what is the major disadvantage by using this technique? Understand, guys, this all things that I'm teaching you, right? We will go in a story pattern, right? You've seen Bollywood movies, Hollywood movies. Why you do remember those movies for a longer period of time? Because you know the story, you have understood the story. Similarly, I'm also teaching you with respect to all the stories. Here, initially with the help of gradient descent, I was passing all the data points, and stochastic gradient descent, I'm just passing one data point and basically reiterating it, right? So with respect to the disadvantage over here, obviously one thing is time complexity, right? It is going to take a huge amount of time, right? This time complexity is huge. Why? Because I'm just taking one single data point and I'm updating the weight, and I'm doing it for 1000 points. Just imagine if there are 1 million data points. Okay, 1 million data points. At that point of time, what will happen? One epoch. Let's say if I want to do 100 epochs, then 100 epochs, in every epoch I have to run 1 million iterations, right? So huge time, right? So time complexity will definitely be more, and your system is always really going to take more time to train the entire model with 1 million data points. Yes, if you have less number of data points, you'll be able to see the progress, right? And the next important thing is that the convergence will take time. So time complexity is more, the convergence will also take more time. More time. So the third disadvantage that I really want to mention is that noise gets introduced. Now, what is this noise gets introduced? Let me just talk about it. Okay, let me just explain you about these 2 points, right? You obviously know that we basically get a gradient descent curve, right? Like this. Now just imagine our main aim is to basically come to the global minima, and let's say my data point is somewhere here. Initially with the gradient descent on the top, we already saw that there is a smoother convergence, right? And the reason was that we were probably taking entire records in the forward propagation, and then we were computing a y hat and probably calculating a loss. I'll not say loss in this case, but I'll say cost function, and then we were doing back propagation. So because of that, we were basically having smoother convergence. But now in the stochastic gradient descent, here we are taking only single record, single data point at a time, and we are updating the weights. So because of this, what will happen is that now the smoother convergence will not be there, but instead you'll have a lot of noise like this. Okay. And probably it will take more time to converge to the global minimum. So this kind of noise will be there, where this entire data points will be where this loss will be continuously roaming here and there, and then finally merging into the global minimum. So that is the reason why time complexity increases. And here, since we're taking single data point and we're doing the back propagation, this kind of noise gets introduced. Now, because of this noise, you will be seeing that our model training usually takes time. And the convergence will also take time, right? So this is what I really want to talk about with respect to the noise, right? Now, as we go ahead, we really need to understand how we can reduce this noise, and that is where we bring up something called as batch concept. Batch concept basically means we will try to bring up we'll not just take single data point and do the forward and the backward propagation, but instead we'll be taking a batch of data points and doing the forward and the backward propagation. And that is what we're going to learn in our third optimizer, that is called as mini batch SGD, right? So I hope you got an idea with respect to what exactly is SGD and how does it work. Always remember over here, with respect to every iteration, we'll be taking one data point and updating the weights, and because of this, it usually takes time. The convergence will also take time. It will be very slow, and because of this, noise gets introduced because now we are not going to get converging. We are not going to converge very smoothly over here, so it will be jumping here and there before it merges into the global minimum, right? So yes, this was it. In the next video, we are basically going to discuss about mini batch SGD, which is basically solving this particular noise itself, and we'll try to see that how noise will get introduced or how that noise will get reduced with respect to this, and we'll be discussing about that as we go ahead. So yes, this was it. I'll see you on the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to the optimizers. In this video, we're going to discuss about mini batch SGD, and obviously we have completed our stochastic gradient descent, and before that we had also completed gradient descent, and we understood what was the problem over here. In stochastic gradient descent, obviously you saw that in every iteration I'm passing just one data point for the forward propagation, and for the backward propagation I'm basically updating the weights, and this usually gets divided into many number of iterations, so every epoch will have many number of iterations. Now because of this, what will happen, the weight updation will not happen efficiently, so there will be a lot of noise. So this specific thing, I called it as noise. Noise basically means the path of the convergence is not very smooth. Instead it is having a lot of zigzags that is going here and there and probably coming to the global minimum. Now in order to reduce this, I'll be introducing to a new concept which is called as mini batch SGD, and in this mini batch SGD, along with epochs and iteration, we are going to bring one more concept which is called as batch. Okay, and let's say I'm just going to introduce to something called as batch size, right? Now let's say if I have 1 lakh data points, let's say if I have 100k data points, right? So the total number of data points in my data set are 100k, right? 100k, right? So if there are this many number of data points, now let's say I want to perform some epochs, so this will be an epoch 1, okay? And here what I'll do is that since I'm introducing batch size, let's say my batch size over here is somewhere around 1000 records, okay? Now when I say that in every epoch I'm going to take 1000 data points and I'm going to perform that many number of iterations, okay? Now when I say this, as soon as I take a batch size of 1000, then the number of iterations will be equal to, like in every epoch, the number of iterations will be equal to 100k data points divided by 1000. This will get cancelled, and here you'll be able to see 100 iterations. So the main purpose of bringing this batch size was that in every iteration now, I'm not just going to pass one data point, because if you just pass one data point with respect to forward and backward propagation where we update the weights, there'll be a lot of noise. So what we do is that we introduce this batch size. Because of this, what happens is that in every iteration, based on the batch size, let's say if I'm considering the batch size is 1000, that basically means in the forward propagation, I'm going to give 1000 data points, and in the backward propagation, with respect to this 1000 data points, what we'll do, we will calculate the cost function. The cost function formula I hope everybody knows. I is equal to 1 to 1000, because 1000 is my batch size, and then I will take y minus y hat whole square. So I'm just showing an example with respect to mean square error. So this will be my cost function. Now in order to reduce this cost function, what I'll do, I'll be using an optimizer. And which optimizer I'm using here right now, this is nothing but mini batch SGD. And what will be the mini batch SGD main work? It will basically optimize the weights, or it will just change the weights, right? So here what we have done, we have introduced this batch size, right? So that basically means for completing one epoch, I have to perform 100 iterations, right? So this will be my second iteration where I'll take the next 1000 data points and I'll perform all these steps again and reduce the cost function, keep on reducing the cost function, right? Because in the backward propagation, we update the weights. Then similarly, we'll go to iteration 3, right? With respect to this, we'll do the forward and backward propagation. We'll continue this till iteration 100, because my batch size over here, I've taken basically to 1000, right? So batch size, if you're taking 1000, what is the advantage with respect to this? Let's say if you have 8 GB RAM, if you're passing only one data point in every iteration, then also the weight updation will happen. If you pass 1000 data points also, then also the updation will happen, because it will not be a very big constraint with respect to resources. Let's say if you pass, instead of 1000, if you pass 5000 data points, then what you can do, instead of 8 GB RAM, you can basically have 16 GB RAM. Right? You can basically have 16 GB RAM, right? With respect to 5000 data points, right? So at the end of the day, what we are doing is that by bringing up batch size, we are reducing the number of iteration, and this in turn will also lead to the it will also lead to the reduction of the noise, because now if I'm considering the batch size, and if I probably see my gradient descent function or gradient descent curve with respect to weight and my cost function, you'll be seeing that initially what happened. See, let's say if this is my point, okay, if this is my data point and this is my global minima, right? Global minima. We saw that with the help of gradient descent, we were able to converge very much easily, right? But when we brought SGD, then what happened? A lot of noise came, right? So this was the noise, right? This was a noise, a lot of noise, and like this it'll be noise and it'll take time to come over here. But now because of this batch, that is mini batch SGD, because I'm bringing a batch size over here with respect to all the data points that I'm going to pass through every iteration, this noise will get reduced, and this time it will be reduced something like this. Since my batch size has, there's a batch size with respect to every iteration, the number of iteration has been reduced. So now this noise has got reduced. This noise has got reduced. Why? Because I'm not giving now single data points every time. Instead, I'm giving a batch of records. Instead of one, I'm giving 1,000 records, and I'm updating the weight at once for 1,000 records, right? In the back propagation, right? In this way, what happens? The noise is getting reduced because now I will not have this much noise, and it will have a definitive path to go to the global minima, right? So let's talk about the advantages and disadvantages again. I really want to write on all the advantages. So the first advantage over here is that when compared to SGD, the convergence speed will increase, right? So my convergence speed will increase. Why? Because now I have introduced a batch size, right? The second point when we're discussing over here, noise will be less when compared to SGD, where we are just providing one data point, right? So this is the second one. And third point, it is also solving what? Since we're giving the batch size, it is also solving efficient race. It is actually helping us to use the efficient resources, right? Efficient resource usage. So I'm just going to write like this: efficient resource usage. Example, RAM, right? So this is the major advantages, right? But what about the disadvantage? If I talk about the disadvantage, see, it has reduced the noise, right? It has reduced the noise, but still this noise is there. Still this noise is there, right? Still this noise is there. So we can just say that the noise still exists. And again, if the noise still exists, it may be efficient than SGD, but it may still take some amount of time to converge, right? So in the next step, what we will do is that instead of having this noise, what we will do is that we will try to smoothen this noise. Okay, smoothening this noise so that this much noise should not be there. We'll try to smoothen this, and based on the smoothing, what it will do is that even though some amount of noise exists, if we smoothen this entire curve, it will actually help us to reach the global minima quite faster. Okay, here obviously we know that the convergence speed is increasing, but still there is some noise, right? We are basically happening. Like if I probably try to draw this diagram again, let's say this is my gradient descent. Okay, when we initially started with this SGD, let's say if this is the point, we had a lot of noise like this, right? Now we know that. But with the help of mini batch SGD, the noise will reduce, but it will still be there. So this will be, let's say, the new noise that I'm going to get. It is getting reduced because of the batch size, but it is not reducing completely. Now my aim should be that what I should be able to do is that I should be able to smoothen this curve, let's say, because there's so much noise over here. Our next aim should be that we should try to smoothen this curve so that the convergence will be faster. And for this, we specifically use something called as SGD with momentum. This momentum is nothing but it is called as smoothening. And this is what we are going to discuss in the next video. Okay? Understand at the end of the day, all these optimizers shows you how efficiently we can update the weight by changing the batch size till now. Right? Now, going forward, when we discuss about SGD and momentum, we will see that how we can smoothen this noise also. So I hope you are able to understand till here. We have discussed till now 3 optimizers. There are around 3 to 4 more optimizers which we are going to discuss over here. Understand each and every optimizer is super important for understanding, because in an interview they may ask you any question. If you are also a researcher, you will have this knowledge like what is the difference between each and every optimizers. But at the end of the day, the best optimizers we'll try to use for our practical implementation. That I'll be talking about like which is the best one as we go ahead. Right? So this was it from my side. I'll see you all in the next video where we'll discuss about SGD with momentum. Thank you. Bye. So guys, we're going to continue the discussion with respect to the optimizers. In our previous video, we have seen mini batch SGD, and we also understood now what we're going to do with the help of SGD with momentum. Now, let's go ahead and let's see it once again. What we are planning to do is that right now, you have already seen that with respect to our weights, right? And if I probably consider this is my weight or my cost function, if you see this gradient descent, right? At the end of the day, you could see what is the disadvantage with respect to the, the mini batch SGD. Before that, or the SGD also, it had a lot of noise, right? And the use of mini batch SGD, what we did is that we tried to reduce the noise. So let's say this is how we reduce the noise, okay? I'm not going to use this color. Let's say I'm going to use this color. So we try to reduce the noise, okay? But still, the noise is there, right? And obviously, if noise is there, obviously what we need to do is that the convergence will usually take time with respect to the noise. Now, our plan is that we should try to smoothen this noise with the help of SGD with momentum, okay? So in short, what we are going to do is that we're going to understand that how this smoothing is going to happen, okay? How this smoothing is going to happen. Now, before I go ahead, let's say that this is my weight updation formula. So W old minus learning rate derivative of loss with respect to derivative of W old, right? Now, this formula, I'm just going to change a bit, so that I can incorporate this momentum topic over here, right? Why momentum is required? Momentum, how it is making sure that the smoothing is happening, right? So instead of writing W new, and as you know, that's in the back propagation, we also need to update the bias, right? So I can write bias new is equal to bias old, learning rate with respect to derivative of loss with respect to derivative of bias old, right? So these are the two updation formula that we specifically use, right? We also have to update the weights, we also have to update the bias, right? So don't forget about this, because bias is also an important term, right? Which is added as a parameter. Now, instead of writing like this, let me just change this equation a bit and write with respect to something like time series. Why? I'll just let you know. So here I can write W of t is equal to W of t minus 1 multiplied by the learning rate derivative of loss with respect to derivative of WT minus 1. Now see, why I've written this? W of t, that basically means the new weight, is basically dependent on the previous weight minus learning rate of derivative of loss with respect to derivative of WT minus 1. So this is the representation that I'm going to use going forward, and how by using this representation, we are going to basically understand how this entire thing is going to smoothen up, okay? So this process is basically like, obviously this is my weight updation formula that I have updated, right? So this is my weight updation formula. Okay, so I hope you got an idea about this. I am trying to write new and old with respect to time, right? So this is the current time. The previous time is t minus 1 multiplied by minus learning rate multiplied by derivative of loss with respect to derivative of WT minus 1. Okay. Now, how the smoothing is going to happen? For that, you really need to understand something called as exponential weighted average. Okay. Now, this is super important. Because of this exponential weighted average, we are going to perform this smoothing, and the smoothing is going to happen because of this. Now, what is this exponential weighted average? Now, this is super important, right? And with respect to this, let's say that I have at time t1, at time t2, at time t3, at time t4, like this at time tn. Let's say that I have values like a1, a2, a3, a4, and like this I have an. Okay. So these are my values, some values that I have, and this is basically my time. Now, in order to smoothen this, right? Let's say that in order to smoothen this time series problem, and this is basically a time series problem altogether, right? So this is a time series problem. Let's say with respect to this particular time series, and the same thing I'm going to apply with respect to weights also when we keep on updating the weights, right? So over here you'll be able to see at t1 is equal to, at time t1 I have value as a1, then t2 I have value as a2. Now how I will be able to apply this exponential weighted average? So can I write my value of t1 is equal to a1? That basically means the value at time t1 is equal to a1, and this is the time series data. Then in order to apply the exponential moving average, just understand this, guys. What is exponential moving average? Let's say I have this data point at time t1, at time t2. Let's say, or at time t2, let's say I have another data point over here. So this is my a2 data point, this is my a1 data point. Now, understand that if I probably join this a1 and a2, I will be getting something like this, right? And then let's say at time t3, my a3 is here, okay? Or my a3 is somewhere here, okay? Or just let me show you, okay? So let's consider that at time t2, my a2 is over here, and then time t3, my a3 is over here, the value is over here. So this is with respect to t2, this is with respect to t3. Like this, I have all these values, okay? With respect to all this time. Now, as you know that, if I probably connect all these dots like this, you'll be seeing that these all are connected, right? Now, if I really want to apply the smoothing on top of it, how will the smoothing will get applied? Now see this, at value of t1 is equal to a1, I have this particular point. Now, at value is equal to t2, what I will do is that I will use a parameter which is called as beta, and here I will say that I will multiply with v of t1, that is value of t1, plus 1 minus beta multiplied by a2, okay? Now, what I'm actually doing, see this. If I have 2 points like a1 and a2, if I need to apply an exponential weighted average between these 2 points, I will introduce a term which is called as beta, and this beta is going to control the smoothing function. Okay, let's say over here by default I select a beta value as 0.95. So what does this basically mean? This I will try to write 0.95 multiplied by vt1 plus, and vt1, you know what is vt1? Vt1 is a1, right? Plus 1 minus 0.95 is nothing but 0.05 multiplied by a2. Now let's say I'm trying to apply an exponential weighted average on two values a1 and a2, and I want a1 to control more. Obviously remember this beta value ranges between 0 to 1. Always understand this. If I'm putting this beta value as a higher value, that basically means I want the previous value to control the smoothing. Okay, to control the smoothing. So that is the reason I've given maximum weightage to the previous value, right? So the current weightage, the weightage to the current value, that is at value at time t2, it will become less, right? So this is how I apply smoothing, right? I am basically saying that how much control I have to the forward time series value, and based on it I'll try to smoothen it. Now once I apply this formula, right, then you'll be able to see that my smoothing function will look something like this. It will look something like this. It will go like this, where I will not be getting like this kind of zigzag line, but instead I will be getting a smoothened line which looks like this, right? So this yellow line is basically my smoothening line. So this is how we try to reduce the function. We reduce the noise, sorry, not function, noise. Understand, again I'm trying to repeat it over here. How do we apply exponential weighted average, and why this exponential weighted average is applied? It is specifically for this smoothing purpose. And why we really want to smoothen it? Because we want to reduce the noise. We want to reduce the noise with respect to this. And in order to apply the smoothing, we use something called as exponential weighted average. Now what we are going to do is, let's say that value at time t1 is equal to a1, right? Now if I have some value at time t2, if I want to apply an exponential weighted average, how do I apply? I'll introduce this beta term, which values ranges between 0 to 1. Let's say this beta multiplied by value of time t1. If I'm assigning this beta value very high, that basically means the previous point controls the smoothing, right? And the current point has less control with respect to the smoothing. So what is happening? That this particular point will take the control and it will try to smoothen it in a proper way, right? And similarly, like this, we will apply the smoothing with respect to all the other points. Okay, vt3. Now in vt3, what I will say? I will write beta into vt2, okay, plus 1 minus beta into multiplied by a3, right? Now what is vt2? Now I want, let's say my beta value is 0.95. This vt2 will be nothing but this entire thing, right? This entire thing what we have written, where the control is maximum with respect to vt1. So again, I'll write 0.95 multiplied by a1, okay, plus 0.05 multiplied by a2, and then I have 0.05 multiplied by a3. So here what I'm doing again, the second point will try to control the smoothing of the third point. Then we will be getting a better smoothing curve. And that is what is going to basically happen for this entire term, for this derivative term with respect to all the time, right? So here we are basically going to apply an exponential weighted average, wherein our task will basically be to smoothen this entire curve. So at the end of the day, the optimizer, which was having the weights and which was having the cost function, you'll be able to see that because of this curve, which had a lot of noise, right? In mini batch HJD, we had this noise, right? We had this noise, still we had this noise, right? And it was coming to this global minima. Now, because of the exponential weighted curve, exponential weighted smoothing, so basically the exponential weighted average, we are basically going to smoothen this like this. Okay, we are going to smoothen it like this. So this will lead to faster convergence. Faster convergence. Understand this. What we have done, nothing new. We have just introduced a concept of exponential weighted average with respect to finding out in the weights. And the same thing we're going to apply over here with respect to every time. What we are going to do, we are just going to, for every chain rule, we are going to just apply the exponential weighted average, because of which smoothing will basically happen, right? Now, if I probably talk about the advantages, so let's go ahead and talk about the advantages in this case, right? So first advantage is that it obviously reduces the noise. Why? Because we are bringing the smoothing concept. The second thing is that it also leads to quick convergence. Okay. So I hope you're able to understand the importance of HJD with momentum. We are just bringing this exponential weighted average, and this usually happens in time series data where you use techniques like ARIMA, SALIMAX, if you heard about this all terms, right, in the time series, right? So yes, this was it from my side. I hope you like this particular video. Now in the next video, what we are going to do is that we are going to discuss about our next optimizer, which is called as ADAGRAD, and I'll talk about it why ADAGRAD is super important. Because till now we were just playing with this equation, right? Now we need to play with this learning rate also. Okay, so that is what we're going to see, how we're going to play with this learning rate, because we also want a dynamic learning rate. Okay, so yes, this was it. I will see you all in the next. Hello guys, so we're going to continue the discussion with respect to optimizers, and in this video we're going to discuss about ADAGRAD optimizer. Now if you don't know about ADAGRAD optimizer, it is basically adaptive gradient descent, okay? Now guys, the researchers, they have come up with these amazing optimizers, and each and every optimizer is important for some specific task. Now why, like what is so special about this optimizer? Till now guys, we have discussed, right, the weight updation formula. I've written W of nu, but I'll just now change it with respect to W of t. So W of t is nothing but W of t minus 1 minus learning rate multiplied by derivative of loss with respect to derivative of WT minus 1. And till now, I've actually discussed about, and I've actually told about the learning rate, right? Till now, this specific symbol is nothing but is basically called as learning rate. Until now, we have discussed that learning rate usually is a value, and it is a small value between 0 to 1, and everybody knows the importance of the learning rate. It basically shows the speed of the convergence. So let's say over here, the learning rate value was somewhere around 0.001, okay? And this is usually initialized in the initial stage. Till now, whatever optimizers we have spoken about, this learning rate is usually fixed, okay? It does not change as the convergence usually happens. So what if now we try to make this learning rate dynamic? Okay. Now, when I say dynamic, what does this basically mean? Let's say that I'm going to probably plot this plot with respect to W and loss. Okay, loss or cost. And let's say this is my global minima. And let's say initially my point was over here. Now the convergence speed should happen. First of all, it should take bigger step. And then when it is coming near to the global minima, it should minimize the steps. That basically means as the convergence happen, the learning rate should change. The learning rate should change, and that is what we really want, and that is what adagrad is also doing. Okay, initially instead of taking the small value 0.001, because 0.001 is also small value, or 0.01 is also small value, so initially what we'll do is that we'll try to make the convergence faster by taking a bigger step, and then when it reaches near the global minima, we try to reduce the size of the learning rate. That is what we really want to do, and that is how we can make this learning rate from fixed to dynamic, and that is what adagrad is actually doing. Now how this specific thing with respect to this optimizer is doing. So let's say I'm again going to write the formula w of t minus 1 minus, before I used to write learning rate, now I'm just going to write learning rate dash. Okay, this is a new symbol which I'm basically giving it, and I'm going to say derivative of loss with respect to derivative of wt minus 1. Now we need to understand what exactly this learning rate dash is. Okay, this is just a symbol to talk about that this particular learning rate is dynamic and it is not at all fixed. So here I'm going to consider what is this specific value, learning rate of dash. Okay, I'm just saying this. I'm given this particular notation. This is nothing but it is learning rate divided by a parameter which is called as alpha t plus epsilon. Now we will discuss about this and how this learning rate is going to become dynamic. We're going to discuss about this. This is nothing but it is called as epsilon. And epsilon will usually be a small value. Why we are using this epsilon? Because let's say if this alpha t becomes 0, at that point of time you get a divide by 0 condition, right? So I don't want that particular thing to happen, right? Never this denominator, I don't want it to become 0, so I'm adding a small epsilon value. Okay, so this is my learning rate and this is divided by root of alpha t plus epsilon. Okay, so here what exactly is alpha t? Alpha t is nothing but alpha t formula can be given as summation of I is equal to 1 to t, and this will be derivative of loss with respect to derivative of w of t whole square. Now see, as you know, as our backpropagation will happen, right, in a deep neural network, and as we go with respect to t, right, when I say I is equal to 1 to t basically means what? First of all, I will go with respect to the first layer, then the second layer, then the third layer, right? When I keep on increasing the alpha t value will keep on increasing. So as the convergence, initially it was taking a bigger jump, later on you'll be seeing that as this alpha t value is increasing, since we are dividing this learning rate by alpha of t, this entire value will keep on decreasing. So this will keep on decreasing. It is very simple, right? As alpha t keeps on increasing, this value keeps on decreasing, right? And over here you can see that I is equal to 1 to t basically means, okay, the first hidden layer, second hidden layer, third hidden layer, and that is what we are going to find out with respect to derivative of loss with respect to derivative of w t whole square. So as we go with respect to each and every hidden layer with respect to the backpropagation, the alpha of t value will increase. And that is how your entire learning rate, that is the new dynamic learning rate, will keep on decreasing. Okay, so let's say at t is equal to 1, my learning rate was, I'm just giving as an instance as 0.01, okay, which we initialized initially. At t is equal to 0 or 2, my learning rate will change it to 0.005, let's say. At t is equal to 3, still my learning rate will keep on decreasing and it will become 0.003. So that is how this changes will happen. Okay, this changes will happen. Now, what is the disadvantage of using this? These are probably the best advantages things is that you're getting a dynamic learning rate. Okay, that is what you are able to get it from this, right? So you're basically getting a dynamic learning rate, right? But there is one disadvantage. What is this disadvantage? The disadvantage is that, let's say, in a very deep neural network, sometimes your alpha t will be so high that when you divide this value by alpha t, this value will become very, very small. So here I'm going to write a disadvantage that n dash, there is a possibility to become a very small value, approximately equal to 0, right? Now, if it is a small value, we are going to multiply the small value with derivative of loss, right? So when we multiply this will also be approximately equal to 0. So in this instance, you will be seeing that there is a possibility that wt may be approximately equal to wt minus 1, right? Now, if this is a scenario, that basically means again the weight updation is not happening, right? So this is one disadvantage with respect to this particular adagrad, and we will try to cover up this particular disadvantage in the next optimizer itself, and that is how researchers came up with a single, let's say one researcher came up with this adagrad. There's a problem over here, what we can basically see with respect to dynamic learning rate. Now the next researcher will come with a new optimizer and probably solve this particular problem, and that is what we are going to learn in the next optimizer, which is called as ada delta and RMS prop. At the end of the day, if it is asked in the interview, it is very simple to understand that adagrad actually helps you to bring up a dynamic learning rate. Okay, that basically means initially your learning rate will be high and it will keep on decreasing as you move towards the global minimum point. So yes, this was it from my side. I will see you all in the next video. In the next video, we're going to discuss about RMS prop and ada delta. So thank you. Hello guys, so we're going to continue discussion with respect to optimizers, and in this video we're going to discuss about ada delta and RMS prop, right? Now in our previous video we have already completed which is called as adagrad. Adagrad is nothing but adaptive gradient descent, and here the main aim was that I need to make the learning rate dynamic, right? So initially when I'm not reaching my global minimum, my learning rate should be high, but when I approach near the global minimum, my learning rate should be reduced. So for this we used a new formula. Over here I've written learning rate of dash is nothing but we will try to make it dynamic by making sure that we divide learning rate divided by square root of alpha t plus epsilon. I've already told you why epsilon is required, because this value can be 0. So epsilon will be a small value that will be always initialized so that we don't get a divide by 0 condition error. This alpha of t is nothing but summation of I is equal to 1 to t derivative of loss with respect to derivative of wt whole square. So in short, you'll be seeing that as the chain rule becomes bigger, right? So this alpha of t will keep on increasing, right? So when this alpha of t is keep on increasing, here you can see that since we are dividing the learning rate by alpha of t plus epsilon, this particular value, the new learning rate, the dynamic learning rate will keep on decreasing, right? And this is how we are going to make this learning rate as dynamic. But there is one disadvantage. If let's say this alpha t is becoming very, very high value, because in a deep layered neural network, right, the chain rule will be quite big, and there's a possibility that this alpha of t will become a very big value. Why? Because we are always trying to square this particular value, and we are doing a summation with respect to all the chain rule that we have, right, to the entire depth of the chain rule. So if this is a very big value, then this n dash, that is the learning rate dash, will be a very, very small value. Now when this is a small value, this is a small value, what happens? This value will be approximately equal to 0. It's just like having, you can just say that it is just having like 0.00001, right? So this is approximately equal to 0. Now because of this, what will happen? The weight updation will not happen. Now if the weight updation is not happening, that basically means the convergence is not happening. So this is the major disadvantage with respect to adagrad. But now let's talk with respect to ada delta and RMS prop. And to be frank, right, we really need to fix this problem where my alpha t is not becoming very high. So now we will be using a new formula, and the new formula will be the dynamic learning rate is equal to learning rate divided by square root of SDW plus epsilon. Okay. Now instead of alpha t, we are using SDW. Now what is this SDW? Again, we are going to use exponential weighted average. I'll write it over here. So I will write it as exponential weighted average. and that is what we're going to do. We are basically going to smoothen this update of alpha t. Okay, and how we are going to do this? This SDWT is nothing but we can basically write with the help of same formula that we use in exponential weighted average. That is beta multiplied by SDWT minus 1 plus 1 minus beta multiplied by derivative of loss with respect to derivative of WT minus 1. Now here you can see that previously also we were using this, right? We are basically derivative of loss with respect to derivative of WT we are using. But here we are restricting it with beta. Okay, we are restricting with this particular value. Let's say my beta is 0.95, right? So here the previous value will have 0.95, but this derivative of loss, which is basically getting increased because you're squaring it over here, and there is a possibility that, this value can also become a very big value. But you're restricting it with beta over here because 1 minus 0.95 is just 0.05, right? So based on this, what is happening is that now we are able to restrict this alpha t. Before it was alpha t, now it is basically SDWT. Okay, and initially to begin with, right, we initialize SDWT for the first timestamp is equal to 0. Okay, and then whenever it goes to the next timestamp, this will basically be used over here, and we can basically find out the derivative. Okay, so this is what we are doing. So in short, what is Adder delta and RMS prop doing? They are also bringing dynamic learning rate. They are restricting this alpha t value to become very, very less because we are just writing SDWT, right? So it is nowhere now alpha of t, right? So it is SDWT. The second thing is what it is doing is that it is bringing smoothing concept with the help of exponential weighted average. So these are the two amazing things that is being done by this Adder delta and RMS prop. Why we have two names? There is a slight different. Understand that these two are from two different researchers, and there is a slight difference with respect to this, but almost the working of this is exactly same. So I've written this as one optimizer. And finally, the weight updation is very simple. W of t is equal to W of t minus 1 minus learning rate, which is dynamic derivative of loss with respect to derivative of WT minus 1. So this is obviously the learning rate. When I say t and t minus 1, this is just like new weights and the older weights. That's it. Okay. So this was about Adder delta and RMS prop. And the next one that we are probably going to discuss about is something called as Adam optimizer. Now, Adam optimizer is the best optimizer, and whatever problems we see in all the other things, right? Over here, obviously, we are fixing the dynamic learning rate plus smoothing. But understand, we really need to bring many more things because this smoothing is basically happening with the update of the dynamic learning rate, right? But still, over here in Adder delta and all, we don't have something called as momentum with respect to weight, right? We don't have SGD, we don't have mini batch SGD. So that is what we are going to combine over here in the Adam optimizer. And most of the users, whenever you're trying to solve this problem, try to use Adam optimizer. This is what we're going to see in the next video. So I hope you like this particular video. You have understood about Adder delta and RMS prop. This was it. I will see you all in the next video. Thank you. Hello guys, so we're going to continue discussion with respect to optimizers. Finally, we are into the Adam optimizer, which is currently the best one. Why? Because it has all the advantages, things that we have learned in all these previous optimizers, right? So first of all, let's start with the beginning. First advantage thing when we saw is that we saw with SGD with momentum, because here we were getting less noise. So Adam is going to have SGD with momentum. Plus, we're going to use RMS prop. Now RMS prop, what all important features we had? We had something called as dynamic learning rate. Plus, we also had a technique of smoothing those so that the value does not become very high and my learning rate entirely does not become 0. Okay, so these two features we are basically going to combine together and we are going to use it for our purpose in the Adam optimizer. Okay, so my new weight updation formula. Now remember, guys, with respect to optimizers, the most important thing is your weight updation formula. So let's say with respect to weight updation, I will write W of t minus one minus the dynamic learning rate. Now instead of writing derivative of loss with respect to derivative of W, remember in SGD with momentum what we did? We used to write this, right? Vt, that is value of this particular one, with the help of beta and 1 minus beta. So this entire derivative of loss will basically become Vd of W. Okay, so this is one major update. And then similarly, you know that we also update bias. So Bt is nothing but Vt minus 1. Again, here we'll be having a learning rate, and instead of writing derivative of loss with respect to derivative of bias, we'll write learning rate multiplied by VDB. Okay, so these are the two major updates that will be happening. Understand this one, right? When I basically say what is this n dash? N dash is very much simple. This n dash is nothing but learning rate divided by, here we have already seen what is SDW plus epsilon. Okay, and you know with respect to SDW what is the equation? So equation is nothing but this, right? Initially with respect to, and this can be SDW of t, right? Initially the first SDWT will be initialized to 0. Then we go to SDWT plus 1, right? So then we will basically have beta multiplied by SDWT t plus, here you can see the equation, okay, plus 1 minus beta. So here I'm going to basically write 1 minus beta, and this will get multiplied by derivative of loss with respect to derivative of W of t whole square. Now why I've written t not t minus 1? Because I've taken t plus 1 over here. Let's say if I write SDW of t, that basically means this is for the next timestamp, and this was the previous timestamp. So this will become t minus 1, and this will also become t minus 1. Okay, understand the difference. This is super important, and this is the same thing that we have been discussing from that much time, right? So this is with respect to this one. Okay, so let me just again give this as my dynamic learning rate. So here you can see this n dash is nothing but my dynamic learning rate. The smoothing is basically happening with the help of this and this specific equation. Okay, so these are the two things, right? And similarly, finally, what will be this VDW in order to calculate it? So here we can write VDW is nothing but beta multiplied by, this is again the smoothing concept that we basically use with SGD with momentum. So this will be VDWT minus 1 plus 1 minus beta derivative of loss with respect to derivative of WT minus 1, right? And similarly with respect to VD bias, right? So B of t is nothing but, so here also t, beta multiplied by VDB t minus 1 plus 1 minus beta derivative of loss with respect to derivative of b t minus 1, right? So all these things we are basically combining in this entire weight updation formula, and this is specifically for momentum, right? Momentum, in short, we are smoothing the weight updates, right? Smoothing, that is what we are basically doing. So in short, if I really want to revise, in Adam optimizer you have SGD with momentum, and that is what is basically reflected by this and this. Okay, you have RMS prop, which is reflected by this. Along with that, you are also trying to smoothen the updates of this particular dynamic learning rate. So that is the reason why you are using this particular SDWT, which is having this exponential weighted average, right? So this is nothing but EWA. This is also nothing but EWA, and this usually happens for both bias and the weights, right? So all these updates is basically happening in the weight updation formula and the bias updation formula. So this is nothing but the weight updation, and this is nothing but the bias updation, right? Very simple. So this is nothing but weight updation. This is nothing but the bias updation. And this is the change that is basically happening in Adam optimizers. Now, many people ask the question, which is the best optimizer to use? What I would suggest always is that try to use this particular optimizer, that is Adam optimizer at the end of the day, because this will actually help you to do the convergence quickly, because it has all properties like SGD momentum, RMS prop, even batch size, where you have dynamic learning rate plus smoothing of those dynamic learning rate. And this will be a perfect optimizer to work for most of the use cases in ENM, right? Not only over here in CNN, also will be using Adam in RNN, in all the other optimizers will try to use this, right? You can definitely try other optimizers. It is nowhere restricted, but at the end of the day, Adam focuses and try to solve all the problems, right? So if you have any other idea with respect to weight updation formula, you think that you can build a better optimizer, go ahead with research and try to bring up this particular concept. If you see, right, after explaining this entire story, we have just played with this weight updation formula till now, right? And if you find out a better way to do the weight updation, trust me, you can also become a researcher, right? So yes, this was it from my side. I will see you all in the next video. Hello guys, so in this video we are going to discuss about something called as exploding gradient problem. Already in our previous video we have discussed about vanishing gradient problem. So let's go ahead and understand this because there are chances why exploding gradient problem can happen, and this is something related to the weights, right? Again, I'll try to showcase this entire thing like a story itself so that you'll be able to understand and connect all the dots. So over here, let's consider this neural network again. I have hidden layer 1, hidden layer 2, and finally an output layer. And let's say in the hidden layer 1 I have just one neuron and this is my another neuron. Over here you have seen that from my input layer to the hidden layer 1 I have initialized W1, then W2, then W3. After that, whatever output that basically comes up, right, with respect to multiplying the input with the weights plus bias, and then I will perform an activation function in the next step. The activation function can be ReLU. I will get an O1 as my output, right? So O1 as my output. And similarly, O1 will get multiplied by W2, and then plus B2 will get added up, and then we'll again apply an activation function. And finally, since we are solving a binary classification, in the second step, we'll apply a sigmoid activation function. Now, let's go ahead and calculate. And obviously, what happens after this, you get y hat, then you calculate the loss function, and you do the backward propagation, right? Now, very much important thing that you really need to understand over here. Let's say that I want to update derivative, I want to update the W1 weight. Let's consider this, okay? So how do I write my formula? W1 new is equal to W1 old minus learning rate of derivative of loss with respect to derivative of W1 old. So this is the formula I hope everybody knows with respect to the optimizers like gradient descent and all that we specifically use. Okay. Now what I will do is that I will focus on solving this because here only the gradient, the exploding gradient problem will occur. Here also the vanishing gradient problem used to occur. So if I really want to write derivative of loss with respect to derivative of W1 old, how can I write with respect to chain rule? Here you can see loss is dependent on O3, O3 is dependent on O2, O2 is dependent on O1, and O1 is basically dependent on W1, right? So we'll basically be writing derivative of loss with respect to derivative of O3 multiplied by derivative of O3 divided by derivative of O2, and then derivative of O2 divided by derivative of O1, and finally derivative of O1 divided by derivative of W1 old, right? So this is what we are basically going to compute, and obviously I've shown you based on the chain rule. So this is nothing but this is basically my chain rule, right? Chain rule of derivatives. And I've repeated multiple times now. I think you should be able to understand this. Okay. Now, what is the next step after this? Now, this is super important with respect to the next step. Now, over here, let's consider that. Let's go ahead and probably see with respect to O3 to O2. Okay. So let's go ahead and compute this part. Okay. And I will again be using another chain rule over here. So derivative of O3 with respect to derivative of O2. Okay. This according to the chain rule, how we can divide. Now you know that. Let's consider this is my input Z. And what is Z? Z is nothing but if I probably show you over here, O2 multiplied by W3 plus B, right? Basically plus B3. So this is what basically happens in the first step. So let's consider this is my entire Z, right? And after this, what I do, I apply an activation function, right? After this only I apply an activation function. The activation function in this particular case will be sigmoid, okay? Now what I'm actually going to do over here, I will split this, right? And I will split in such a way that now what I will write, I will say derivative of sigmoid of, okay, because this is the activation function that is basically getting applied, okay? So I'll take up this Z, okay? And I'll basically write derivative of sigmoid of Z, okay? One minor change that I'm going to do, I'm not going to write basically sigmoid over here. Let's consider this is my Z, okay? In the second step, we apply a sigmoid, right? So this is my step 1, and step 2, I apply after this sigmoid of Z, right? So this is what. So what I'm actually going to do, I'm just going to make this chain rule since O3 is dependent on O2 by writing derivative of sigmoid of Z with respect to derivative of Z, and then with respect to derivative of Z with respect to O2. Okay, so this is what I'm actually going to write. I'm just trying to split this O3 to O2, right? I'm just trying to apply a chain rule, and this also I showed you previously. Okay, now this first term that you probably see is the derivative of a sigmoid function, right? Sigmoid activation function. So your value will be ranging between 0 to 0.25, right? Now this is fine. Now what about derivative of Z with respect to derivative of O2? Now here Z is nothing but how can I write Z? I can basically go over here and see it is nothing but O2 multiplied by W3 plus B3 with respect to derivative of O2. Now see, whenever we try to find out the derivative with the same thing, now this W3 will only be remaining, O2 will become 1, and this is a constant, this will become 0 once I find out the derivative. So for the first value I have, this value will be ranging between 0 to 0.5 multiplied by, now you can see over here I will be having W3. Okay, remaining all will become 1, this will become 0. Okay, this will O2 will become 1, and over here it will be 0. This simple derivative. Okay. Now, in this particular scenario, I told you that vanishing gradient problem was coming up because of this, but now we have ReLU functions in all the other hidden layer. Okay. But what if, now just imagine, what if my weight, that is this weights that are initialized initially, the W3 old that is initialized initially is a very high weight. Let's say it is 500 or it is 1000, right? Or it is 1000. Then what will happen? This multiplication will again give us a very big number. Now what will happen with respect to every chain rule over here, right? Because of the weight initialization, let's say the weight initialization that actually took place, right? And in this weight initialization, what we did is that we took a very high value. We initialized with a very high value. Then you know what will happen? All these values will be very high. This will also be very high, multiplied by high, because this is all bigger numbers, right? I'll not say high, but I'll say all these are basically bigger numbers, right? So if I probably remove this, this will probably be a big number. And then as we go with respect to all the other things, so if all the weights are basically initialized a very big value, then we are going to have a very big value. Now when we multiply all this big value, then finally we are also going to get a very big value. Now if we get a very big value with respect to this derivative of loss, what will happen? This learning rate will get multiplied with this big value. It can be a negative value, it can be a positive value. Now when there is a big value, this entire thing will also be a big value again when we multiply with the learning rate and this all things, right? Because even though the learning rate is initialized with a smaller value, but since here you are getting a very big value, even though you multiply this, it will also be a big value. Now because of this, what will happen? W1 new can be very much greater than W1 old. Okay, W1 old. Or you can also have in a scenario that W1 new will be very less than W1 old, right? This both the scenarios will be coming, right? Now what is the problem with this? Now the weight updation that is happening, it is happening by a bigger number. So if I probably consider the same gradient descent with respect to weight and cost function, okay, if this is my loss or cost function, initially let's say the point was here. My main aim is to basically come to the global minima over here, right? Global minima. Now what will happen is that because of this, since the weight updation is happening by a very big value, you'll be seeing that this value will keep on rotating here and there. And there will be scenario that if you're lucky enough, then only it will come to global minima. If you're not lucky enough, it will go outside this entire gradient descent, and it will be outside only. Hardly, since the weight updation is happening with a huge difference itself over here, because this is obviously a very big value. So what will happen is that there will be a scenario you'll never reach the global minima. Now this problem is basically called as exploding gradient descent, and this happens because of the weight initialization techniques, right? Which weight initialization techniques? If these weights are very big. right? Weights are very big. So what I'm going to do is that I'm going to show you all the different types of weight initialization techniques that we basically use in deep learning so that we never face this kind of exploding gradient problem, right? So I hope you understood the importance of this specific video, what exactly is exploding gradient problem. Again, I'm trying to connect this as a dots and story so that you'll be able to understand everything. There is an exploding gradient problem. This is specifically happening because of weight initialization techniques. Because in the weight initialization techniques, we get a very big weight value, right? So what we do is that we try to use some techniques of weight initialization, which is proven, where researchers have actually used. And again, very, very thankful to the researchers. They came up with this amazing thing. Just understand the amount of efforts they have actually put, right? Again, hats off to the researchers who have come up with these amazing things where people are able to solve big, complex industrial problems. Now, in the next video, we're going to discuss about all the weight initialization techniques. Thank you. This was it from my side. I'll see you in the next video. Hello guys, so we're going to continue our discussion with respect to the weight initialization techniques, and we're going to discuss about three important weight initialization techniques. One is uniform distribution, Xavier or Glorot initialization, and then we're also going to discuss about timing he initialization. I hope I'm pronouncing it right. When I say Xavier or Glorot initialization, that basically means this person Xavier Glorot has actually come up with this, whereas timing has actually come up with this he initialization. So his name is timing he. I hope I'm pronouncing it right. If I'm not pronouncing it right, I'm extremely sorry. Okay. Now, some of the very key important points that you should really know about weight initialization, and those are these three key points. The weights that are initialized should be small, right? If it is big, then what will happen? You basically face a exploding gradient problem, right? Weights should not be same, right? When you're initializing the weights, it should not be same. Okay. That basically means, let's say if this is your input layer, and let's say if this is my hidden layer, okay, and finally this is my output layer. Let's consider one more hidden layer, and finally I have my output layer. Okay, so here you can see that if these nodes are getting connected, right? So here the weight initialization takes place. We're going to initialize some weights like W1, W2, W3, W4, like this, right? So these weights that are initialized should be small. It should not be same. So if it is same, right, that basically means all the neuron are basically doing the same kind of processing, right? Every neuron should have the capacity of thinking or processing in a different way, and that is only possible because of weights, right? So weight should not be same when you're initializing it, right? Then weight should also have good variance, right? Good variance basically means this W1, W2, it should be having at least some kind of variance, some kind of changes in that weight. That this both point you can basically say that it is supporting one another. Okay. Now let's go ahead and understand with respect to uniform distribution. Now one very important thing before I go ahead, let's say if this is my input layer, right, and this is my hidden layer, right? Whenever I say this, that basically means I can basically say I have one input, okay, that is x1, and I have three outputs, okay. Three outputs basically means, let's say if this is my hidden layer, and after this, let's say it is going with respect to one output layer like this, okay, then this basically indicates that I have one input layer and one output layer, okay, one input and one output. That basically means the number of neurons, right, and the output is one. How many inputs I'm giving? Actually one, right? So if I say here my input is equal to one, and here my output is equal to one, right? Now similarly, I can have different scenarios. I can basically have, let's say if I'm having three inputs, let's consider like this. If I have three input features, let's say this is my hidden layer 1, this is my hidden layer 2, and finally I have a multi-class classification problem where I have three nodes. Okay, let's say in hidden layer 2 I add up all nodes, right? Now in this particular case, this will be interconnected, right? This all will be interconnected, and you know that this is my input 1, input 2, input 3. That is my x1, x2, x3, right? And this will get connected to this, and this will get connected to this. This is how a multi-layer neural network works. And finally everything will be connected to over here. And this is basically my output layer. Let's consider, because here I'm specifically using multi-class classification problem, right? So in short, if you know what kind of activation function we'll use over here, softmax activation function. Now in this particular case, my input is basically 3, and my output is also 3. Right? Because I have three nodes over here, right? So this is the basic difference. Now let's go ahead and understand about the first one, that is called as uniform distribution. So uniform distribution, what we do is that whenever we initialize the weight, right? That basically means all this weight W1, W2, W3. Whenever we initialize, right, what will happen is that we initialize this, all the weights, based on some uniform distribution. Now, what is this specific uniform distribution? That basically means all these weights, which we specifically write W of ij. I basically indicates the input layer, j basically indicates the hidden layer. Okay, so if I say W11, W12, W13, like that, right? So from here you can see W11, W12. This will be like this. This will be W12. And similarly over here, if I go, it will be W21, W22, W23, like that. All the inputs will be going. So this weights that are basically getting initialized, it will be initialized from a uniform distribution. And in the uniform distribution, you should always remember we give two values, two range, a comma b. Okay, so this entire weights will be initialized based on this uniform distribution, wherein your a comma b, that is your limit of a comma b, which is your minimum and maximum value, will be -1 by root of input, comma 1 by root of input. Okay, so this is basically going to be your a comma b, that is your minimum and maximum value with respect to the uniform distribution. Okay, so if you know Python, you can also initialize the uniform distribution by giving this particular value. Now in this particular case, my input is 3, my output is 3. So if I take this example, it will be 1 by 3, sorry, 1 by root 3, minus 1 by root 3, 1 by root 3. Okay, so if I really want to write it again, what I can do is that I can basically write, or let me write this also in a better way. So the simple technique is that all these weights that is basically getting initialized, it will be initialized from a uniform distribution, wherein we specifically give a lower range and a higher range. The lower range is basically given by -1 by root of input, comma 1 by root of input. Okay, and here you'll be able to see that if I probably try to put up this value based on this particular multi-layer neural network, it will be -1 by root 3, 1 by root 3. Okay, so based on this uniform distribution, if you probably use a simple Python inbuilt function of uniform distribution with this specific values, it will automatically initialize all these weights with respect to all the hidden neurons. Okay, so this is with respect to the uniform distribution. Now we're going to discuss about the next one, that is Xavier or Glorot initialization. So the second one is nothing but Xavier or Glorot initialization. Why this initialization technique is coming up, guys? Because we do not want to face any problems that are related to exploding gradient problem, and researchers, they have invested a lot of time, and you don't have to even prove this because this is already proved, because this is going to work absolutely fine. Okay, now in Xavier or Glorot initialization, this was invented by a researcher whose name was Xavier Glorot. Okay, so you can basically say Xavier initialization or Glorot initialization. So over here you have two types. One is Xavier normal initialization, so I'll write it as init. The second type is something called as Xavier uniform. So this researcher, basically Xavier, came up with these two techniques. One is Xavier normal initialization and Xavier uniform initialization. Now with respect to Xavier normal initialization, all the weights of ij will be initialized from a normal distribution where your mean is 0 and your standard deviation is sigma. And over here, your sigma will be nothing but root of 2 divided by input plus output. right? Input nodes plus output nodes. So this will be your entire sigma value, right? So again, I'm repeating it guys clearly. So your weights will be initialized from a normal distribution, and this is nothing but your normal distribution will be with respect to mean is equal to 0 and standard deviation is equal to sigma, wherein your sigma is nothing but root of 2 divided by input plus output. So in this case, it will be root of 2 divided by 3 plus 3, that is 2 by 6, that is root of 1 by 3. Okay, so this is the technique that we are going to basically use in this. Very much simple. Now coming to the next one, that is Xavier uniform. Now in Xavier uniform, all the weights are basically going to get initialized from a uniform distribution. Understand this is very simple. And again over here, you'll be giving your a comma b value. So your a comma b, that is your min and max, will be nothing but minus root 6 divided by root of input plus output. Okay, and this will be comma root 6 of input plus output. Okay, so this is how you are basically going to use Xavier uniform, and this is with respect to Xavier normal unit. Okay, we'll also discuss like which initialization you can take all the time, and for which it will work well, Now coming to the third one, which is again, these are all weight initialization techniques, guys, which you specifically use for weight initialization. The third one that we are going to discuss about is timing key initialization. So let's go ahead and discuss about the third initialization technique, that is timing. I hope I'm pronouncing it right, guys. I'm extremely sorry if I'm not able to pronounce it right, but this is the initialization techniques. And with respect to timing key initialization, there are again two types. One is he normal, we basically say it as he normal, and the second one is something called as he initialization, or I can basically say he uniform. Okay, and again, you don't remember this particular formula, just understand it, because in all the libraries this kind of initialization technique is already taken. Okay, now with respect to he normal, it is very simple. All the weights of ij will be taken from a normal distribution of 0 mean and standard deviation sigma, when standard deviation is nothing but root of 2 by inputs, right? Now in this case 2 by 3, root of 2 by 3. So with respect to this particular distribution, all the weights will be initialized. Okay, now with respect to he uniform, all the weights will be initialized from a uniform distribution, and again the uniform distribution range needs to be given by a comma b, and this a is nothing but minus 6 by input, comma plus 6 by input, plus 6 by input. So this is how you basically initialize this weights with respect to this. Okay, all these examples I will be showing you in the practical. Remember, guys, you don't need to remember the formula, but I really wanted to connect all the dots and stories why these weight initialization techniques have actually come. Mostly these are the three most famous: Xavier, timing key, and the uniform distribution. And this is what we're also going to discuss while we're implementing things. So yes, this was it from my side. I hope you like this video. Please make sure that you keep on revising. And yes, as we go ahead, we'll be doing a lot of practical examples now. Thank you. I'll see you on the next video. Hello guys, so we're going to continue discussion with respect to ANN. Already we have discussed so many topics like optimizers, loss function, activation function, and many more. And today in this video, we are basically going to discuss about this dropout layer, very important topic altogether. And over here you can basically see that I've created a multi-layer neural network where I have specifically an input layer. So this is my input layer over here. This is my hidden layer, right? Hidden layer 1. This is my hidden layer 2, and finally I have my output layer, right? So all these layers are there, and here you can see that some of the inputs are not connected to the hidden layer, and similarly some of the neurons in the hidden layer are not connected to the next layer, right? And there's a reason why I'm doing this. So please wait for some time. I'll explain you exactly what exactly dropout layer is and why I have not connected all these things, right? So first of all, before I go ahead, one thing that you really need to understand is about overfitting. When does overfitting basically happen? Let's say if you're creating a deep learning model, and with the help of this particular model, you get a very good training accuracy. Let's say the training accuracy that you probably got is somewhere around 90%. Okay, and let's say with the test accuracy, when you probably get training accuracy is basically with respect to the training data, right? And test accuracy is with respect to the test data. So overfitting is a condition wherein, let's say if you've trained a deep learning model or any machine learning model, and let's say if you get a very good training accuracy like 90%, but let's say if you're getting a test accuracy of somewhere around 60%. Now in this particular scenario, you basically say that your model has been trained well with the training data. So your model is basically overfitting. At the end of the day, our main aim is to basically create a generalized model so that my model should be able to perform well with both the training data and test data. But here you can basically find that there's a huge difference, right? So because of this, what we do is that we basically say that the model is overfitting. So we should try to reduce this overfitting and try to focus on creating a generalized model. Obviously, if you know about machine learning algorithms, like if I probably take an example with respect to machine learning algorithm, if you know about decision trees, right? Now in decision trees, what happens is that we try to create a decision tree completely to its depth, if you know it, right? Decision tree we try to create completely to its depth. Now with respect to any data set, when we're creating completely to its depth, what happens? It obviously leads to overfitting, right? Now in order to reduce this overfitting, what all we can do post pruning, we can do pre pruning. There's a concept. If you don't know decision tree, it's okay, but just hear out this particular example. And there is also one more technique that we specifically use, which is called as random forest, right? Now in random forest, what we do is that we take many decision trees, we construct many decision trees. Let's say this is decision tree 1, 2, like this I may have 100 decision trees, okay? And in each and every decision tree, we try to construct it completely to its depth. But for every decision tree, we do something called as feature sampling. Feature sampling, that basically means that from all our data set, I don't give all the features. I give only a subset of features. And similarly, what we do row sampling. Row sampling basically means from the data set, we don't give the entire data points. We only give some of the data points, right? So that subset of rows and subset of features is basically given for each and every decision tree, right? And this all decision tree is basically constructed to its depth, right? And finally, you'll be able to see, oh yeah, what we're doing. We're giving only subset. Yes, some of the features, some of the data points may get repeated with respect to different decision trees, but you can understand that here we are basically focusing on giving the subset of the data set, right? With respect to features and data points. So when this decision tree is basically constructed and when we finally get the output, right? When we finally get the final output will be selected based on maximum number of decision trees giving the output. Let's say if there are 100 decision trees, 55 said 1 as the output and 45 said 0 as the output. Then maximum number of decision trees are basically saying 1, so that will be the output itself. So this way, how we are basically reducing this overfitting problem, and we're creating a generalized model with the help of random forest, right? So similarly, what we can do is that, let's say over here with respect to a neural network, a ANN, multi-layered neural network, since it has a lot of weights, so over here like each and every line is connected, right? So if each and every line is connected over here, it is basically initializing the weights over there. So we have so many weights and bias, right? And if I probably consider in a multi-layered neural network, there will obviously be so many weights and bias based on the number of hidden neurons and number of hidden layers that is there, right? So when we have so many weights and bias, what will happen is that this entire multi-layered neural network, or ANN, that is artificial neural network, also sometimes will go to overfit the model because it will be trained with the training data set in such a way that it will be able to understand each and everything. So it will be able to perform well with the training data, and it will try to not give a very good accuracy with the test data. So this kind of problem also occurs in this entire ANN. How do we reduce it? We basically use a concept of dropout layer. Now in dropout, over here also, we have seen, right, we use feature sampling and row sampling. Let's consider this feature sampling. So over here, what we do in that, from the input layer, right, we apply dropout. Now, as soon as I apply dropout, let's say if I say dropout of p value is 0.5. Usually the dropout value ranges between 0 less than or equal to 5, p is less than or equal to 1. So this is what the value will basically range, right? Now, as let's say in the input layer, I said the probability is 0.5. I'll not say probability, or let's say the probability of the inputs, or I can also consider that, okay, let's consider this feature sampling, right? Feature sampling, we give subset of features. So here I'm saying that if p is 0.5, so this is basically the probability from all these input nodes, 50% of the nodes will be deactivated, right? So that basically means over here, if there are 4 inputs that are going, I'm making 2 nodes as deactivated. That basically means I'm not passing 2 features in the first iteration or in the first epoch, right? So this entire, you can see that the connection is not there at all. So if the connection is not there, that basically means this input are not getting passed. No processing will happen with respect to the specific inputs. Then when it goes to the hidden layer 1, what happens over here? Here also, let's say I'm going to apply some dropout layer with some probability, and here you can see I have 5 nodes in this hidden layer, and over here you can see 2 nodes are deactivated. So the probability in this particular case will be nothing but 2 by 5. So 2 by 5 basically means that these 2 neurons are deactivated from out of all these 5 neurons. So again, this will not get connected. None of the processing will basically happen over here. Even though this has got the other inputs, none of the processing is going to happen because based on this p value, we have basically decided it. How to select the p value, I'll talk about it. Okay, and this I'll also show you in the practical implementation. Okay, then in the next step, what happens again? I will go ahead and initialize my p value. Let's say over here the p value is like, since there are 2 neurons which is not connected further, so I'm going to make this as 0.5. Right. So out of these 4 neurons, 2 neurons are deactivated, and finally I get my output layer. Right. Now this will happen in the forward propagation. In the forward propagation, based on the p value, some neurons will be activated, some neurons will be deactivated. In the back propagation, all the steps will happen again. These neurons that are deactivated, none of the processing will happen. Then again in the second iteration or second epoch, whenever the new forward propagation will happen, again this p 0.5 will get randomly initialized. Now the same neurons will not get deactivated. The neurons may change, or the input may change. Right. Instead of x2 and x4, now x1 and x2 can be deactivated, or x1 and x3 can be deactivated. Right. Because it will be randomly selected. Right. In the second epoch or in the second iteration. Right. If there is a backside, then it will be in the second iteration. Again, when we do the forward propagation. Then similarly over here in the hidden layer, some of the neurons will get deactivated based on this probability that we have selected, and it will be randomly selected. It will not be the same. And again, this step will keep on going on unless and until we get a very less loss. Right. And how that is basically happening with the help of optimizers. That all things are same. But here you understand the purpose. The purpose is very much simple. Is that we are trying to deactivate some of the neurons, along with we are trying to just provide some feature samples so that this entire model does not overfit. Okay. So I hope you're able to understand this. Now what we do in the next step is that this is with respect to training, right? Obviously, unless and until the loss value does not decrease, this training will be going with respect to the forward propagation and backward propagation. But what if with respect to the test data? How does the prediction happen with respect to the test data? Now, with respect to the test data, all things will get interconnected. Now, see, let's say our model is entirely trained, our weights are fixed, right? And it has basically used this entire dropout layer with respect to this particular probability. Okay. And how to select this particular probability? It will be based on some kind of hyperparameter. Okay. We can select multiple probability values, and we can see that in which, by selecting which probability of dropout, the model is able to perform well. So in the next one, for the test data, what will happen is that whenever we want to do the prediction for the test data, let's say these are all the neurons, right? And I'm just going to show you with respect to first layer. Let's say all the neurons will be interconnected. Let's say this is my input layer. This will get interconnected for the test data, because test data is, for the test data we need to do the prediction, right? So all this will be interconnected. All this will be interconnected. Now you may be thinking, Krish, what about the dropout that we have initialized? Yes, I hope everybody's thinking that. What about the dropout? So let's say if this is interconnected, and similarly this is interconnected, right? All this neurons are basically interconnected. Now what we do is that in this particular scenario, you know that we have initialized probability as, over here we have initialized the probability as 3 by 5, right? Oh sorry, 2 by 5, because 2 neurons are deactivated. Now with respect to all these weights, right? And here we know that we have decided probability as 0.5. That is what we have shown over here, right? Now in test data, whenever we need to do the prediction, we are not going to apply any dropout in the test data. Why? Because we need to do the prediction. So what we do is that we try to multiply all these weights with this probability. So here we multiply all these weights with probability as 0.5. In the next layer to next layer, what we do is that we multiply this entirely. Here also the probability is 0.5. Here we multiply all the weights with 2 by 5, and here we multiply all the weights with 0.5. And finally we get our output layer, which will basically be my output for this particular test data, whatever test data we gain. So what we do is that we don't deactivate the neuron in the test data itself, right? While doing the inferencing, what we do in order to make this neural network connected, we multiply all these weights with this probability that is initialized. So I hope you have understood with respect to the dropout layer, with respect to the training and the test data. This was it. I will also show you the practical application with respect to how you can implement a dropout layer. But at the end of the day, why dropout layer is basically used to basically create a generalized model. So I hope you like this. I will see you all in the next video. Bye bye. Hello guys, so we're going to continue the deep learning series. From this session, we're going to basically start convolution neural network. Already we have covered ANN, we have discussed about optimizers, loss functions, we have discussed about different activation functions. And remember, one thing is that all these things will again be reused in convolution neural network also. But just this is an introduction video about convolution neural network, which we basically say CNN, and we have a lot of things that we really need to cover. Okay. Now to begin with, till now, if you probably remember, right, we have already completed ANN, right? So the first thing that we probably completed is ANN, and with the help of ANN, we specifically say that we will be able to solve problem statements that are related to supervised learning, to supervised machine learning. That is both classification and regression problem, right? Classification and regression problem. And usually the inputs that are usually in a data set, right, in ANN, you specifically have input features, right? You have input features, any number of features it can have, F1, F2, F3. And obviously we have seen that fashion MNIST data set that we had 784 features, right? And similarly with respect to that, we also have an output feature, which will basically help us to probably solve a classification or regression problem. And usually these input features are in the form of numerical values or categorical values, and probably we can also convert categorical values into numerical values. Now we are going to basically start with CNN. And the most amazing thing about CNN, that is convolution neural network, here, your inputs will be in the form of images. Right? Now, when it is in the form of images, with respect to the specific images, we can solve various different kind of problem statements, right? Some of the examples are like image classification, we can definitely solve. So we can solve image classification. We can solve, and again, advanced CNN techniques, which we'll be learning, which is related to object detection. There, we are going to solve object detection problem statements. We are able to solve segmentation problem statements and many more, right? All these things we will be able to solve it. And this is what we are basically going to see in CNN. But first of all, we really need to understand like how does the convolution neural network works, how is it probably going to take these images and probably able to solve this kind of complex problem statements. Now, since this is just an introduction video about CNN, one very important thing about CNN that you need to work is that obviously you know the input is basically images. Now, again, this entire CNN working is completely based on how our human brain works with respect to images, right? Let's say I am seeing a cat, I'm seeing a camera, my brain is able to process and say that yes, this is a cat or a camera, right? So there's some important things, and again, since this is an introduction introduction video. You really need to know about this. Again, just understanding of this is sufficient. It is not like you have to become a researcher with respect to understanding all the parts of the brain and all. So here is an amazing diagram. I've taken it from www.dana.org. Amazing diagram that is related to this particular brain. Now here you can see our brain has some very important parts, and these are the 12 to 13 important parts, and all these parts are nowadays being converted into some functionalities that we can basically do with the help of neural networks. Okay, but here we're going to focus on this two important part. One is cerebral cortex, and the other one is something called as occipital lobe. Okay, so this is the 12th number and this is the first number. Again, you can basically check out all the parts over here. The first part is over here. This occipital lobe is related to visual area, that is sight, image recognition, image perception, right? And if I probably consider the second one is something related to association area, then the third part is related to motor function area. That is basically our movement of the muscles is basically controlled by this part of the brain. Similarly, we have Broca's area, muscles of speech, auditory area for hearing. This part of the brain is responsible, right? Then emotional area is basically the sixth part where I can see. I think sixth part is not visible directly over here, but I think it should be a very small part. Somewhere it should be available over here. Again, as I said, we are not going to become a researcher over here. So this sixth part is responsible for, okay, here it is, right? So the inter part of the brain. So here you have the sixth part, which is responsible for emotional area, pain, hunger, fight or fight response. Like suppose let's say if I'm feeling hungry, this part of the area is basically a response to that particular stimuli that I'm feeling hungry, right? Then the seventh part is basically over here. You can see this is nothing but the sensory association area. Olfactory area is the eighth part of the brain, right? So there are different things which will be able to perform different tasks and all. But with respect to input images, these are the two main things. One is the 12th area and one is the first area. And the first area is nothing about visual area. So for here, anything related to sight, image recognition, and image perception is basically possible. If I probably see the 12th area over here, so 12th area is responsible for eye movement and orientation. So let's say if I'm seeing a camera, all the signals will get processed in different layers. First of all, it will go to this cerebral cortex layer, and then it will send the signal to this particular occipital lobe, and then it will be able to understand what image it is probably seeing or what kind of image recognition we are basically doing. So if I probably talk about this entire thing, is that CNN, two main important components of the brain, two main important parts of the brain is basically getting replicated. That is with respect to cerebral cortex and occipital lobe, which we the cerebral cortex like passes the signals to something called as visual cortex, and this is what we're going to discuss in the next video, how those layers are basically going to get divided. And at the end of the day, after all the processing in this occipital lobe, where you'll be able to see or understand the image or visualize the image, that part will be there. It is somewhere over here, the back part of the brain itself, right? So this is something that you should have some idea about. Understand that nowadays researchers, right, bigger companies, if I probably consider this one, right, in initiation of voluntary muscles, nowadays robots or mechanisms, right, how the robot is able to stand, perform various tasks, whatever functionality basically happens in this particular part of the brain, that same thing is replicated with respect to the machines. So that is what researchers are basically seeing. They really want to use all these functionalities in the brain and probably convert that or apply it on a specific machine, which will be able to perform all these tasks, and that is what is basically happening. And with respect to CNN, object detection and all, there are much more advanced things that have basically happened. So yes, in the next video, we are going to discuss about cerebral cortex, visual cortex, and occipital lobe again, but just understand that initially the cerebral cortex will, with respect to human, like if I have an eye, right, I'm seeing some object, the signals are basically getting passed through my cerebral cortex, and then it passes through multiple layers, which we basically say V1 to V5, which is the part of visual cortex. It processes each and every signals, and then finally in the occipital lobe, it will be able to visualize or it will be able to recognize that specific image, right? So that is how it actually happens. This was just an introduction video. In the next video, we will go towards advanced understanding with respect to various layers, like V1, V2, V3, V4, V5. So I hope you like this. I'll see you all in the next video. Thank you. Hello guys, so we are going to continue a discussion with respect to cerebral cortex and visual cortex, which we have already seen as a part of the brain. And this is super important because this will actually help us to understand like how does a convolutional neural network actually work. So in short, over here in this video, we're going to understand the basic differences between a CNN versus a human brain. And for this, we really need to understand that how a human brain processes the images. Again, we're not going to learn it like a medical student, but instead try to understand that how things basically happen and how the object is basically recognized in the back part of the brain itself, right? So over here, I gave you a brief idea about cerebral cortex, which is this 12th region. And here you can see it is nothing but motor function area, eye movement and orientation, right? Now from this cerebral cortex, and here you know that this is the occipital lobe. Here the sight, image recognition. Sight basically means the image will get visualized over here. You'll be able to see the image. Suppose let's say the camera is over here. This entire image is basically processed and probably visualized in this region only, right, in the occipital lobe. And then you also have image recognition, object detection, all those things you can basically do it over here. Now as soon as the signal comes to the cerebral cortex, then what happens is that it goes to the visual cortex, okay? And this visual cortex is basically present in the occipital lobe, okay? Occipital lobe, just understand this, okay? So this visual cortex is responsible. See, it is the region of the brain that receives, this is super important, that receives, integrates and process visual information, right, relayed from the retina. Retinas are basically in the eyes itself. So this signal first of all goes to the cerebral cortex, because cerebral cortex is responsible for that with respect to the eye movement and orientation, and then those signal passes through this visual cortex, which is present in the backside of the brain, that is occipital lobes, right? So visual cortex is basically present in the occipital lobe of the specific brain, that is the region 1. Now this visual cortex is responsible, see, the region of the brain that receives, integrates and processes the visual information relayed from the retina, that is that specific part. And usually a visual cortex is divided into 5 different layers, which we mention it as V1 to V5. Now understand, this is super important. First, when the signal goes to the V1 layer, right, and this V1 layer is basically called as primary visual cortex, okay? And what is the main aim of this V1? It is nothing but orientation of edges and lines. So that basically means, let's say if I am seeing an image, if I'm seeing a cat or a dog, as soon as the signal passes through V1, it will be able to determine the edges, it will be able to determine the lines and all those things. So orientation of all those edges will be able to be processed by the layer V1, right? And remember, similarly over here V1 to V5 will be performing different functionalities. Right now we have understood that as soon as the signal passes from the retina to the visual cortex, it passes through the first layer V1, which is called as primary visual cortex, and it actually helps us to understand the edges and lines of that specific images or object that we are probably seeing. Then those information passes to the next layer, that is called as V2. Now in V2, the researchers have found out that as those signal passes through V2, they'll be able to understand the differences in color, complex patterns, object orientation. Complex patterns basically means whether the object is round, whether the object is square, or whether it is very much complicated. It will also be able to process the differences in signals, in colors, right? Whether the color is red, pink, green, right? Based on the capability that how how a brain can, right? So this is the second layer that usually passes, right? First it passes to V1, second it passes to V2, and over here this processing is happening. Processing basically means you are able to understand something from those images inputs that is probably going through our brain, right? You're able to understand, like in the V1 layer, you're able to understand the edges itself, you're able to understand the lines itself. In the V2 layer, still more, because the same signals is getting passed to the V2 from this, right? Then you'll be able to understand the differences in the colors, you'll be able to understand more complex pattern, like whether the object is round, whether the object is square, whether it is a very complicated pattern itself. You're able to find out in V2. Then what does V2 do is that V2 also sends the signal back to V1, and it can also send the signal to V3, V4, V5. And complex operations like object detection, object recognition usually happens in this V3, V4, V5 layer. And finally, the layer that you see over here, occipital lobe, right? This all are present over there itself. And finally, you'll be able to visualize the image in this region. Right? And that is how things happen. But understand the main things in human brain, as the signals are passed from retina to these various layers, signals are processed, right? And more understanding of those particular object will finally get formed over here after V3, V4, V5 is basically crossed. So after this specific layer is crossed, we are finally able to visualize this image. Whether it is an object, whether it is an image, it is finally making sense to the human being in short, right? And this is how the processing happens. Now, why these things are important? Because with respect to CNN also, now the researchers, what they did is that they try to replicate the same functionality with respect to CNN. So once you know this, you know that each and every layer is able to get some information, pre-process some information over there. Similarly, we'll try to understand with respect to convolutional neural network, how it is going to perform all this particular task. In convolutional neural layer, we basically find out these edges and lines using filters, right? So with the help of some filters, we'll be able to get the straight line. With some of the filters, we'll be able to get a circle, right? Or with some of the lines, with some of the filters, we'll be able to get the horizontal lines. All these things, right? So similarly, with respect to CNN, also we can perform all this task. That is the reason I showed you over here, like how in our brains usually the processing usually happens. And again, this is just a 100 feet overview. I'm not deep dived inside every layer and probably broken down into many more pieces because definitely we don't want to get into medical, but instead we really want to understand how CNN actually works, right? So yes, this was it with respect to this particular video. In the next video, we're going to understand how CNN basically works, and we're going to divide, and we're going to see that with respect to this layers, what is the alternate layers that is present in the CNN itself, and what each and every layer does, and how the mathematical operation is there over there, right? So yes, this was it from my side. I will see you all in the next video. Hello guys, so we are going to continue discussion with respect to CNN. In this video, I just want to give you a brief idea about RGB images and grayscale images. Now over here you can see on the left hand side, and probably this is the basic things that you should know before starting or understanding how does the entire CNN neural network basically works, right? So over here you can see one image, okay, this image is over here, and usually all these images that you see, specifically colored images, even the face that you're probably seeing of mine, right? This is basically divided into three channels, right? So one is the red channel, green channel, and blue channel. Whenever these three colors are basically combined, you actually get any colored images, right? And again, it depends on the values that are there in this red channel, green channel, blue channel. Similarly, on the right hand side here, you can see here is a mountain, mountain along with a hut that is in front of it. And if you try to see the RGB channel of this particular image, it looks something like this. This is the red channel image, green channel, blue channel. So this particular image has been taken from research.net, okay? And here you can also see one more image of a parrot. And if you see the RGB channel, here you can see the red channel, green channel, and blue channel. And if I probably go over here, one step to the right, here you'll be able to see the gray channel, right? Usually we say gray channel has a black and white images, and these are basically color images, which combines RGB itself. So with respect to any images, there's some important information that you should know. Image are usually, whenever you say that, how much pixels of this images are. What does that basically mean? Let's say if this is an image, right? This images will be divided into pixels. So let's say if this many number of pixels are there. Okay, so how many pixels were there? 1, 2, 3, 4, 5, 6. 6. And let's say if I divide it more like this, 3, 4, 5, 6. So for this specific image, whatever the image may be over here you can see this image has somewhere around 6 pixels in the horizontal and the vertical. So I can basically call this image as 6 cross 6. Now, usually this image, that the pixel values will be ranging between 0 to 255. So all the pixels will be ranging between 0 to 255. And let's say if only one single image is there, over here we basically say 6 cross 1. That basically means this is a grayscale image. In grayscale image, you don't have 3 channels like RGB, you just have one channel, okay? So over here you can see 6 cross 1, which is nothing but 0 to 255. Every pixels will be having, right? So we can basically say this as a black and white image. So this image is nothing but it is a grayscale image, okay? So most of the images that you see over here like this and below like this, it is a grayscale image. And before also, many movies used to come up in this white and black and white background, right? So this usually happens, right? Now, if I probably want to see with respect to a colored image, now colored image will look something different. There will be 3 channels, which is called as R channel. So R channel will have one channel like this. Let's say I have a 4 cross 4 image itself, right? So here you can see, let's consider, I'm just taking as an example that this particular image is 4 cross 4. Okay, 1, 2, 3, 4. Similarly, 1, 2, 3, 4. So this channel is basically called as the R channel, the red channel. Okay, red channel. Similarly, if I probably say like how we can have this RGB, then when we combine this RGB, this kind of colored image is formed, right? And again, all these values with respect to R also will be ranging between 0 to 255. Okay, every pixels will be ranging between 0 to 255. And similarly, what we'll do is that we'll also have a green channel, like, which looks like this. Okay, so this is my green channel, which will get combined something like this. Okay. So this will be my R channel again. And with respect to this R channel also, I will be having this kind of lines. Okay, this kind of lines. Just let me draw it like this. I'm sorry, I'm very bad at drawing, so just cooperate with respect to my drawings itself, right? So here you can see this is my R channel. Okay, and this is my green channel. So this also, every pixels will be basically ranging between 0 to 255. Okay, so this is basically my green channel. Again, all the values inside this channel will also be between 0 to 255. Similarly, after that, we can also have a blue channel. So let me take a color of blue over here. So this is my blue color. I hope this is blue itself. Yeah, so let me again take this example. So let's say that this is my blue channel over here, and I have this specific channel. Again, this will be divided into pixels with respect to this. Now, when all the channel values with respect to this, like let's say if this is my first record over here, first pixel over here, second pixel, third pixel, fourth pixel, when this all are combined, it usually forms this kind of images. And again, this is basically my blue channel, right? And again, all the pixels will be ranging between 0 to 255. So this is how a colored image looks like. So this specifically is my colored image, right? That is my grayscale image, colored image, right? So this is the basic difference that you really need to understand with respect to RGB image and grayscale image. This is an example of grayscale image. Usually for this, we just have one channel, so we write 6 cross 1. Now here you could see that we had 3 channels. So for this, I can probably write 4 cross 4 cross 3, right? So this this is how we probably share the dimensions of the images, right? With respect to pixels, the first two represent pixels, and the last term basically represents the number of channels. In this, since it is a grayscale image, it is having only one channel, and for this, it is basically a 3-channel. So this is the basic thing that I really want to talk about RGB images and grayscale. Now, in the next video, we're going to understand each and every processing, like how things happens with respect to. First of all, we start with grayscale image and we try to understand how does the convolution neural network work, and then we'll move towards the RGB images, that is the colored images, and probably make you understand how does the convolution operation actually work. So yes, this was it from my side. I'll see you in the next video. Thank you. Hello guys, so we are going to start the first operation of a convolution neural network, and here we're going to understand the intuition, like how does the convolution neural network work. The first operation is basically called as convolution operation. So let's take a very good example over here. So I have a specific image, and this particular image is nothing but it is 6 cross 6 pixel. You can see that it is basically having 6 columns, 6 rows. So we basically say this as 6 cross 6 pixels. And since this is a grayscale image, because we'll understand the convolution operation with respect to a grayscale, and then we'll go to understand with respect to the RGB image, but the operation will be almost similar. So since it is a 6 cross 6 image and it is a grayscale image, we can basically write it as 6 cross 6 plus 1. Now as I've said that all the pixel usually ranges between 0 to 255. So let's consider this specific image. Let's say all are zeros over here, and then we have 255s. Usually zeros are indicated as black color, okay? And 255 is indicated basically by white color. So if you probably see this image will look something like this, where it is basically having this black color and this is entirely white, right? Now, the first thing that you really need to understand is that what is convolution, right? What does convolution basically say? Now, I've already discussed about visual cortex having various layers like V1, V2, V3, V4, V5. And you know that every layer is processing some information, you know. Let's say V1 layer is responsible for understanding the edges, orientation and all, right? Now here also you can basically see that there is an edge between this white and black color, right? So similarly, convolution operation also does this kind of work, that is with respect to this V1, V2, V3, V4, V5, V6 layers, okay? It is going to process this image and it is going to find out some information from the image itself, okay? Now, whenever initially you start this convolution operation, the first thing that you really need to do is that whenever you get this particular pixels, you need to normalize this pixels, okay? You need to normalize it. And this is probably the first step. I'm just going to write it down over here. Whenever you get a data set, you really need to normalize in the step 1. Okay. Now, when I say normalize, what do I mean? I'm basically saying that converting all these pixels between 0 to 1. Okay. And this will probably help us. And this is a must method in any convolution neural network. Whenever you get an image, first of all, is the specific task you need to convert all these pixels between 0 to 1. Okay. So that it will help you in doing the further pre-processing very quickly, very easily, very efficiently. Now, since over here you have 0, which is the minimum value, and maximum is 255. Obviously, every pixel ranges between 0 to 255. So what if we just divide all these pixels by 255, right? So what will happen? This will already become 0 because we want all the values between 0 to 1. And this all 255 will become 1, right? Because 255 divided by 255 is nothing but 1. So what we do? We divide all these pixels by 255. Okay. So I've just written it like this. So I hope you'll be able to understand. So how do we normalize it? We divide by 255, which is the maximum pixel that any block can basically have. Now once we do this, what will happen? My new image will look something like this, where I will have all the ones like this, right? So this will become all the ones. And this is just for this purpose so that we are normalizing it. Okay. Perfect. Now here we have all the things, right? And we have done this. Okay. Now let's talk about the convolution operation. Now, as I said, in our visual cortex, we have various layers like V1, V2, V3, V4, V5, V6, right? Each and every layer is processing some information. Now, the same thing with respect to CNN, the layer work is basically done by something called as filters. Okay, so this term, that this entire 3 cross 3 matrix that I've taken is basically of filters. Okay, so here I will just write down the size. It is nothing but 3 cross 3 filter, and your filter can be of different sizes. Okay, but understand what is the main work of this filter. The main work of this filter is to take out information from this particular images. The information can be in the form of vertical plane, vertical edges, horizontal edges, round shape edges. It can be different things, right? So this is nothing but it is a 6 cross 6 filter, cross 1. Okay, and this is 3 cross 3. And finally, after we apply this convolution operation, I'm going to get 4 cross 4. How we are going to get? I'll just explain about it. Okay, now let's understand this. What this is the operation that we are talking about. What is this convolution operation in short? Okay. Now the convolution operation basically says that we will take this 3 cross 3 and we'll just place it on top of it. Let's say we are going to place it in the first 3 cross 3 pixels over here. Now after we place it, what we do? We have to multiply this entire value with this specific value where it is placed. Okay. So over here, the first operation that you'll be seeing is nothing but 1 multiplied by 0. Since this 1 is getting multiplied by 0, then this 0 will get multiplied by 0. So we have to do the summation afterwards. 0 cross 0, 0 multiplied by 0. Then I have minus 1 multiplied by 0. Okay. So I'm going to basically do minus 1 multiplied by 0. Then we'll go to the next row. So here also you can see 2 multiplied by 0. Then again you have 0 multiplied by 0. And then again you have minus 2 multiplied by 0. And then finally you'll be seeing 1 multiplied by 0 plus 0 multiplied by 0 plus minus 1 multiplied by 0. And at the end of the day, we are just multiplying everything, and finally we get entirely as 0. Okay. As soon as I place this entire filter on top of this particular image, and I form a convolution operation. And this convolution operation is nothing but I'm just multiplying this number with the placed number on top of it, right? And then I'm adding up all the numbers, right? So that is what I've done. I've multiplied each and every number to that specific number, and I've just done the summation. At the end of the day, I'm getting 0. So the final output that you see over here is basically 0. Okay. So this is the first step, right? Now the first operation that we did was exactly we got it as 0. Now then the next step, what we do a jump of 1 to the right, and this is basically called as stride. Okay, stride is nothing but it is a jump to the right or to the left or to the bottom. Okay, so here I will be considering, let's say if I'm considering stride is equal to 1. Okay, let me just write it down properly so that you'll be able to see it. Stride equal to 1. When I write stride equal to 1, that basically means you're jumping one position to the right. Now your next position will be this one, entirely this one, and it will go till here and it will be here. Now you'll be performing the same operation. Now you place this entire filter on top of it, right? Again, the first operation will be what? Plus 1 multiplied by 0, so it is going to be 0, plus 0 multiplied by 0, it will be 0, then minus 1 multiplied by 1, now it is going to become minus 1, right? And then what we do after this plus, we go down, 2 multiplied by 0 is 0, then 0 multiplied by 0 is 0, and then minus 2 multiplied by 0 is minus 2, right? Sorry, minus 2 multiplied by 1 is minus 2. Then similarly, we go to the next term, this plus 1 multiplied by 0 is 0, then again you have the next term 0, and then finally you have minus 1 multiplied by 1, which is nothing but minus 1. So the final output that you'll be seeing is minus 4. That is the reason you can see minus 4 over here as the output. Then again what will happen? We will make one more stride jump as 1 and we'll come over here. Right? And similarly, we'll do all the operation and finally we'll be getting the output. Let's say we come over here, we come to this particular end, right? At last end. Then what will happen? We cannot move again to the right. What we do? We have to come towards the downside and we have to take the next rows from the bottom, right? So here, and this will be my first stride, and again it will jump like this, then it will jump like this, then it will jump like this. And finally, we'll do all the calculation, we get all the values like this. Okay, you can just do the calculation very simple, but at the end of the day, you're basically going to get 0 minus 4 minus 4, 0, 0 minus 4 minus 4, 0, 0 minus 4 minus 4, 0, and 0 minus 4 minus 4, 0. Okay, perfect. This is super, right? But now we'll try to understand this kind of output that we have got. What is the importance of it? Okay, now you know that let me do one thing, okay? You know that we had actually done some normalization with respect to this particular data. Let's go ahead and do the same normalization for this data also. So if I probably do the normalization, or if I do the denormalization basically means converting back to the same numbers. Now, how will my output look like? It will be a 4 cross 4, right? Whichever is the minimum value, that will get converted to. So here you can see, right? Whichever is the minimum value. Let me just draw this again. Let's say if I'm converting this back to the original format, then all the zeros are the maximum number over here. So 0 will become 255, 255, 255, 255, right? And minus 4, since it is the lowest number, this will become 0, 0, 0, 0, 0, 0, 0, 0, right? And this all zeros will become 255, 255, 255. Now this is super important. Why I'm again converting back to the same original format? To just make you understand. This usually does not happen, it will just continue, okay? But just to make you understand. So finally, this is nothing but what is the understanding from this particular output that you get? I am actually going to get an output which looks like this, right? Over here 0, 0, 0, 0 is nothing but your black, you can basically 0 pixel is nothing but black, right? So let's consider this. So here I'm just going to get the 0, 0, 0. So this will be entire black. And here you'll be able to see that I'm going to get entire white over here, right? Because 255 is nothing but it is white. Now see, when this image got passed to this particular filter, we got this particular output. When I denormalize it again back, I'm going to get this kind of output. Now what exactly this filter is doing? This filter is able to find out the edges, the vertical edges. Now where was the vertical edges from this particular image? The vertical edge was over here, right? And just by passing this particular image through this particular filter, I'm able to get this particular edge detection. So this filter is nothing but it is basically called as vertical edge filters. Now I already told you in visual cortex, right? The V1 layer, which was primarily visual cortex, that was responsible for finding any edges or orientation. Now over here in the convolution operation, this entire edges is basically found out by filters. Okay, here I have directly put up this particular value because this filter with this value is basically called as a vertical edge filter, right? And whenever I pass any images through this particular vertical edge filter, it is always going to find out the vertical lines, the vertical edges, which shows this kind of difference of black and white. Whenever you'll be able to find out the vertical edges in an image, it will be able to determine from this particular filter. Now this filter is playing the same role as the V1 layer, right? Similarly, I can have any number of filters, right? Some of the filter will be responsible for finding out the round edges. Some of the filter may be responsible for finding out the horizontal edges. Now with respect to the horizontal edges, this filter will just be changed this much, right? Whenever I have this particular filter, now my horizontal edge filter will look something like this, right? Now with respect to horizontal edge filter, it looks something like this, right? All I have to do is write +1, +2, +1, 0, 0, 0, -1, -2, -1, right? So when I pass this particular filter through this particular images, I'm also going to get a horizontal edges. Now these filters are already predefined. Usually in a convolutional neural network, we don't define the values over here. We randomly initialize the values. Later on, through the forward and the back propagation, and back propagation, these values are getting updated. I hope you're able to understand this. But here, just to give you an example, how does a filter basically work? I had to show you this with a fixed value. But in the real world scenario, these values are not fixed. And this kind of filters will be many present over here. And again, the size of the filter need not be 3 cross 3. It can be 5 cross 5, it can be 7 cross 7. We'll be seeing with respect to different techniques that we're going to see over there. Going forward in transfer learning techniques, there's a concept of transfer learning techniques. You'll be able to find different filters. Right? I hope you're able to understand this. Understand this is basically a convolution operation. You're basically passing an image through a filter. A filter is basically passed through it, and you get some output. And through that output, you're able to find out some information from that image, like vertical edges, horizontal edges, round edges. It can be different things. Right? Here I've just given you one example of filters like this. We can have any number of filters as such. And based on that, we'll be getting that many number of outputs. This is the first operation in the CNN, which is called as convolution operations. Right? Super important topic and all. One important thing that I really want to talk about is that over here you know that it is a 6 cross 6 image. So let's consider the n value is basically the size of the image, that is nothing but 6 cross 6. The filter size is nothing but 3 cross 3, so I'm writing is 3. And the output that I've actually got is 4 cross 4. Right? So usually what we do is that we apply a formula whenever I give an input n, and if I try to subtract it with the filter and do +1, I'm going to get the output size of the image. So here, whenever I do 6 minus 3 plus 1, I'm going to get 4. And that is the reason why I'm getting the 4 cross 4 output. But here you need to understand one very important thing. Since I've given a 6 cross 6 image and I'm getting a 4 cross 4 image, that basically means I'm losing information. Right? So how do we prevent this loss of information? And what is the technique that we can apply? It is basically called as padding. And that is what we're going to discuss in the next video. But I hope you got a clear idea about convolution operation and how things happen. At the end of the day, convolution is basically used for processing this particular image and finding out some information like vertical edges, horizontal edges, some patterns, so that it'll help the model to do the classification and all. Right? So I hope you like this particular video. In the next video, we're going to discuss about padding, which is super important again. And yes, please make sure that you revise it again before you go to the next video. Thank you. I'll see you in the next video. Hello guys, so we're going to continue a discussion with respect to CNN. In this video, we're going to discuss about padding. We've already seen in our previous video, let's say that if I'm giving a 6 cross 6 image, I'm passing through a 3 cross 3 filter, I'm going to get an output of 4 cross 4. And we've also seen that based on this formula, that is n minus f plus 1, I'm going to get the output as 4. But what is the problem over here? Initially, we had this 6 cross 6 pixels, but the output that I'm getting is basically 4 cross 4. So here, some amount of information is getting lost, right? So how do we make sure that, how to prevent this loss of information? So if I'm giving a 6 cross 6 image, I should actually get an output of 6 cross 6 image, so that none of my information is basically lost. So what do I do that? So in that particular case, we specifically apply something called as padding. Now, if I try to just update my formula based on padding, padding is nothing but we are just going to add one more layer of cushion, right? Let's say if I'm just adding one more layer of cushion, okay? And you can add 2 layers of cushion, 3 layers of cushion, right? But it depends on the type of output that you want, right? And I will also show you that how you'll be able to place it, okay? So let's say that you're just adding one layer of cushion. Now, once you add one layer of cushion, what will happen? Right? Suppose let's say you're adding one layer of cushion, and here in this particular cushion, you're just making it like this, right? Initially, your image was 6 cross 6, right? Initially, your image was 6 cross 6. Now, as soon as I add this cushion, it becomes 8 cross 8. But the original size of the image is 6 cross 6. Okay, just listen to this very much properly because it is important. Because we should also be performing padding so that it will, so that you'll not lose any kind of data when you do the training with the help of CNN. Right? So let's say I'm going like this over here. So here, what I've done is that I've added one layer of padding. Now the 6 cross 6 is basically getting converted to 8 cross 8. Okay, 8 cross 8. Initially, it was 6 cross 6, but now it has got converted to 8 cross 8. Now, when it passes through this 3 cross 3 filter, I'm going to get the output as 6 cross 6. Now, if I talk about the updated formula, like how much padding I need to apply so that whatever image I'm giving over here after the convolution operation, it should have the same size. So for that, we use something like n minus f plus 2p plus 1. So let's say if my original size of the image was 6, minus filter size was 3, plus 2 padding, I don't know what the padding may be right now, and let's say if I want the output as 6. right? I want the output as 6 plus 6. So in this case, I can apply this formula. This will be 3 plus 2p plus 1 is equal to 6. It will be nothing but 6 minus 4 equal to 2, right? Which is going to be equal to 2, 6 minus 4. And here I can write p is equal to 2 by 2, which is nothing but 1. So when we do a padding of just one layer, so that is the reason why I have created just one layer of padding on all the side, right? Then you'll be able to see that if I pass a 6 plus 6 image, and after that if I apply one layer of padding, and if I pass through a filter of 3 cross 3, I'm going to get an output of 6 cross 6. Now when I say I'm going to get an output of 6 cross 6, I'm also going to add one more layer on top of it. Now understand the importance of this. From this, you're not losing any information, right? So here you'll be able to see all these images like this. Right? So I hope everybody is able to understand like how do we prevent this loss of information with respect to with the help of padding itself. But one question that usually arises, Krish, what will be these values that we are going to put? Now there are two ways that we usually do. One is that we can use zero padding. Zero padding basically means that where we can apply just zero in all this, right? Zero in all this. That is basically called as zero padding. Wherever there is empty, we're just going to apply zero. And there is also another technique which is called as neighbor padding. Okay, neighbor padding. Now, what does this neighbor padding basically say? Whatever is your neighbor, you just try to assign that particular value. Let's say over here you have 1, 1, 1. I'm just going to assign 1, 1. Whatever is the neighbors, we'll go ahead and we'll assign that particular value. So these are the two padding techniques, and understand what is the importance of padding is that we don't want to lose much information from the entire image. So what we do is that we do some level of padding which can basically be calculated by this formula. And again, the main aim is that whatever input size image that I'm giving, this was 6 cross 6 initially. Now you can see that I'm getting 6 cross 6, and again you can perform the convolution operation with respect to that, and you can get the output over here, right? So this is basically called as padding, and you can apply this formula to find out how much padding you really need to do. Okay. So one assignment that I really want to give is that let's say if your image is 7 cross 7, okay, if your image is 7 cross 7, and if your filter is 3 cross 3, just tell me to get the output of 7 cross 7, how much padding you need to apply. Okay, how much padding you need to apply? You need to apply. So this is a question you can basically solve again by this formula. Just let me know the answer. I will see you all in the next video where we are going to discuss about the next thing that is called as max pooling. Okay, so yes, I will see you all in the next video. Hello guys, so we're going to continue the discussion with respect to CNN, and in this video we're going to understand the differences between operation of CNN versus ANN. Now here, let's go back to ANN again. We have learned already ANN part, right? Let's say that this is a multi-layer neural network. This is a two-layer neural network where you have one input layer, one hidden layer, and one output layer. Now you know that the first operation that usually happens is summation of I is equal to 1 to n w transpose x of I, right? So this is what actually happens, right, with respect to all the weights over here, right? We're going to multiply all the inputs with the weights, and then we need to add a bias. So let me just write this in a better way. So here you basically know that how do we do it? We just do w transpose x of I plus bias, right? And after this we apply an activation function in the step 2 on this particular one, and one of the activation function can be basically ReLU, right? And then we go ahead and do our forward propagation. We calculate our loss. We try to reduce our loss with the help of optimizers, wherein we update all these weights, right? So this is the process of the ANN. Now similarly, if we really consider the CNN part, already you have seen that. Let's say this is my image in the CNN, right? I pass it through the filter. Understand this filter plays a very important role because it's just like how we discussed. Let's say that there are various layers like V2, V3, V4, V5, right? And you know that in this visual cortex, right? These all layers play an important role in processing the information that is coming from retina, right? Probably V1 layer is responsible for finding all the edges. V2 is basically to find out the color differences and different patterns, and V3, V4, V5 is used for doing some advanced things like image classification, object detection, or pattern recognition. It can be anything as such, right? So similarly, this filters play similar kind of role, and as I've already said that you can have any number of filters over here, and each and every filter will be performing different tasks, right? It can be a 3 cross 3 filter, it can be a 5 cross 5 filter, right? So like this I can have any number of filters, and understand over here I've used a vertical edge filter, but usually when we are training a CNN from scratch, these filters are randomly initialized, right? Randomly initialized. So what happens, these filters, when we are placing on top of it, all the multiplication plus addition will happen, and finally we'll get the output with respect to 1. This is basically called as a convolution operation. Similarly, I may have another filter like F2, I may have more filters like F3, right? We may have any number of filters like F3 like this to Fn. So many number of filters will be there. Each and every filter can play some important role, like how these layers are actually performing, right? Or how they're working, right? With respect to finding some patterns, some shapes, some edges, all these things. And initially, during the training time from scratch, we initialize all these values randomly. And then with the help of forward and backward propagation, what we do, we try to update this particular filter, right? We update this filter's values. We try to update all of this particular value. And over here, we have already learned in ANN, right? We do forward and backward propagation. Here also we update the weights. Now, whatever output we get, right? This is super important, guys, because this is the operation that basically happens next. In all these values, right? In all these values that we have, right? We are basically going to perform a ReLU operation, right? We perform a ReLU operation. Now, you know that what is the task of a ReLU? It basically finds out max of 0, x, right? This is what ReLU basically performs. It basically performs max of 0, x. So whatever value is there, right? It is just going to apply this particular rule on each and every value, and it is going to transform the value. Now, you may be thinking, Krish, why ReLU is applied in all these values? That is super important to understand, right? Because as I said in the back propagation, we need to update all these filter values, right? Now, when we are updating all these particular filter values, so we really need to do kind of back propagation. Now, in back propagation, if I'm applying ReLU operation over here, you know that we will be able to find out the ReLU derivative also, right? And the derivative of ReLU is either 0 or 1. Right? So in the back propagation, since we have applied ReLU operation in the forward propagation, the back propagation we will easily be able to find out the derivative, and we are also not going to face up the vanishing gradient problem because the value or derivative of ReLU is either 0 or 1. Right? So based on that, all these weights can be easily updated when we are trying to find out the derivative, and it uses the same backward propagation technique, whatever things we basically have learned in ANN. Right? So in the forward propagation, first of all, filter will get applied over here. How many number of filters are there? Right? That many number of outputs we will be getting like this, 4 cross 4 outputs. Right? We will probably getting so many 4 cross 4 outputs like this. Right? Based on the number of filters, and on all these values, what we do is that we apply ReLU. In all these things, we basically apply ReLU. Right? Very much clearly, we basically apply ReLU, and the reason is very much simple because in the backward propagation, we should be able to find out the derivative, and understand at the end of the day, we should be able to learn this parameter. Because the images can be completely different. Right now, I've just taken a grayscale image. It may be an RGB image. RGB image will be with 3 different channels. So at that point of time, when it is doing the back propagation, still this particular values needs to be learned, and that is only possible by this particular technique. Understand? After the convolution operation that takes place, the next step that basically takes place is the ReLU operation. And if someone asks in the interview why ReLU operation is required, you can also apply other variants of ReLU also, because you'll be able to find out the derivative of that. Right? Yes. After this, there's still some more operations like max pooling, and all. We'll try to understand what max pooling is, but understand at the end of the day why we are using ReLU operation so that we can find out the derivative and we can update these values, because these are the filters that is going to learn how we will be able to process this particular image in an efficient way so that we get the right kind of output. Let it be with respect to image classification or object detection. Usually for object detection, we have different architecture, but if I just consider with respect to image classification, it will be able to learn from the specific images, right? So this was the basic difference between CNN versus ANN operation. Similarly, like in ANN also we are taking the inputs, multiplying by the weights, and then we apply a relu activation function in the hidden neuron itself. So here also we do the same thing. We take the image, we apply all these particular filters on top of that, and after this, whatever output we are getting, we just apply a relu operation. And remember, we can apply any number of filters that we can basically find out with respect to different images what all information we'll be able to track. Okay, so all these things I will also be showing you practically as we go ahead. So I hope you understood the basic differences between the operation of CNN versus ANN. Now in the next step, after this convolution operation and then a relu operation getting applied, what is the next step that we are probably going to do? That is basically called as max pooling, right? So that's what we're going to learn in the next video. So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so we are going to continue our discussion with respect to CNN. In this video, we are going to cover something called as max pooling, min pooling, and mean pooling or average pooling. So all these three terms we'll be discussing. Now, I missed just one point in my previous lecture is that when we were discussing about the operation of CNN, right? This entire operation where we take a filter, apply on an image, and then we get the output, and then we apply a relu operation. This entirely is basically called as a convolution layer, a single convolution layer. Okay, so this is entirely called as a convolution layer, and we can basically add any number of convolution layer as in a horizontal wise, right? So after completing this one convolution layer, we can still add one more convolution layer with different filters, any number of filters with different filter size, and again we can get the output, right? So any number of horizontal addition we can basically do with respect to this. Now in this video, we're going to focus on max pooling, mean pooling, and mean pooling over here. Now you can understand over here, guys, this entire operation here you can see I've taken a 4x4 image. If padding is equal to 1 and stride is equal to 1, if I pass through a 2x2 filter, I'm basically going to get a 3x3 output. And then what we do, we apply in every cells, right? We apply a relu operation, right? A kind of activation function. Why it is required? Because in the backward propagation, I can actually find out the derivative of this, and I can update all the weights that are present in the filter, right? I can update this filter values, right? So this entire operation is basically called as I again said, it is basically called as convolution layer, right? It includes convolution operation along with relu. So this is basically called as a convolution layer. Now let me talk about max pooling. Now before talking about max pooling, one thing that you should basically note is that now let's say that after this particular operation, the values that I have over here are like 1, 2, 3, okay, and it is nothing but 4, 3, 6, and along with that you have something like 2, 8, 4. Let's consider that after this particular operation I'm getting this, okay. And what I'm actually going to do is that now I'm going to show you what exactly max pooling is. Now let's consider that I'm going to use a 2x2 filter, and on top of it I'm just going to apply this as my max pooling. And this max pooling is applied on this output that we have probably got. Okay, so let's say that after applying the relu operation, I've got this particular thing as an output. Okay, and now what I'm going to do is that I've initialized a 2x2 max pooling, and I'm just going to apply this particular filter on top of this output. Okay, this is not the part of convolution layer. This is a separate thing which is called as max pooling. Why max pooling is basically done? There is a very important concept which is called as location invariant. Okay, location invariant. Okay, and let me tell you one of the examples. As you know, we use multiple filters to determine different edges. It may be different things. Let's consider in this. I have 3 cat images. Okay, I have 3 cat faces. Okay, and I'll tell you that why this max pooling can play a very important role. Okay, now location invariant basically says that any number of cat images if it is there, and suppose if you're using a filter, and let's say that this filter is responsible in finding out the face images over here, right, through this particular output, right? Now with the help of max pooling, what will happen is that if I try to apply max pooling on this output layer, I will be able to extract this face images very much clearly. Okay, very much clearly. It is like whatever output I'm getting from here, it will be able to detect. Or let's say it is able to detect all these round edges, right? What max pooling is doing is that it's concentrating completely on this particular face image, and it should be able to get the output. Okay, so over here with the help of filter, obviously we are getting some kind of edges, some kind of round shapes, but with the help of max pooling, we are focusing more on getting all the important information irrespective of this particular filter, right? So how max pooling is basically applied. Okay, so let's say that over here, if there, I can take another example with respect to cars. Let's say there are multiple cars over here, many cars that are placed in this image. Let's say there's one filter that is being able to determine the wheels of the cars, the round wheels of the car. Let's say, okay, if I get the output over here, the max pooling is going to just focus on those car wheels to take out that specific information after I apply max pooling. Okay, and there's a concept which is called as location invariant. So it basically says that wherever those specific images or those specific shapes should be present, right, max pooling should be able to extract that specific part. Okay, so here, how does the max pooling actually work? So the output of this is that when I apply a max pooling on top of this, right, max pooling over here I've taken it as 2x2. Again, it can depend. You can basically use different max pooling also. Now what max pooling is going to do is that it is just going to apply a same concept like how we did in the convolution. It's just going to apply this particular filter on top. Since it says max pooling, so the output will come something like this now. Okay, now let's see the output how it will come. So the first thing with respect to the output over here. Okay, so the first output here you'll be able to see that it will try to find out, okay, from this particular filter, from as soon as I apply, which is the maximum value. And here you can clearly see that out of 1, 2, 3, 4, right, I'm going to basically get the maximum as 4, right? Now what max pooling does is that then it will make a stride of 2, not 1. Stride of 2, because it is just trying to pick out the maximum intensity pixels out of this, right? So it is not going to focus on every stride. So what it does is that it makes a jump of 2. 2 basically means will go over here. Now the next stride will be something like this. It is not going to repeat. Okay, so once it goes over here, you can see the maximum value with respect to 3 and 6. It is basically 6. So I'm going to get the output as 6. Okay, then it is again going to jump stride with 2. So it is going to go down. So it is going to catch this one. Okay, and from here again you can see that which is the maximum element. Again 8 is there, so it is going to pick up 8. Then again it's going to make a stride jump of 2, which is going to come over here, and over here you can see it is 4, so it is basically going to pick up 4. So here initially my pixels were something like this. After the convolution output I got like this. Now here you can see that highest intensity, highest most important feature, right? It is being able to pick, and that is the reason we're getting as 4684. So just imagine that I'm just taking some assumption with respect to this particular value to just show how the max pooling convolution basically happens, right? So over here you can just consider that output will be more focused on this particular image with respect to the pixels. That is what we're going to get with respect to the max pooling layer. And usually in most of the scenarios when we'll be seeing different architectures, you'll be seeing that convolution layer plus max pooling layer, they will be horizontally stacked any number of times, right? First of all, as soon as you pass to the input, then we go to the convolution layer. Then in the convolution layer, obviously what are things you're basically applying? You're applying multiple filters, then you're applying a relu operation, and then you're probably applying max pooling, right? So convolution layer plus max pooling, and then probably getting the output. Then again you're applying convolution layer and max pooling. That is horizontally stacked. Okay, to find out more and more information over here, right? So this is what you basically get with respect to the output, right? And again, since max pooling is just not getting applied on this, because I will also having different filters like F2, F3, F4, which will have different outputs. So in all those outputs also this max pooling will get applied. Okay, so I hope you're able to understand this max pooling will get applied, and with respect to this I will be getting different outputs, right? So this is what is all about max pooling. And again there are two different types of pooling techniques also, which is called as mean pooling and mean pooling. This mean pooling basically means that instead of taking the maximum element, we take the minimum element. So with respect to mean pooling, I will get a different output where I take a minimum elements like 1 from here, then from here we take 3, then from here we take 2, and from here we take 4. Now why mean is required? Because we don't want to focus on the main thing. We want to focus on the minimum intensity pixels that are available over there in the image. That's for that specific image. Again, it depends on use cases to use cases, which pooling you basically need to apply. The third one is basically the average pooling. In average pooling, you just try to find out the average of all this particular value and you get the output. Okay, this is the basic difference between max pooling, mean pooling, and mean pooling. Please, if you're not able to understand, don't worry. Further, I will be showing you the entire how the architecture will look like with respect to convolution layer. The entire CNN that is convolution neural network. But just understand that it is just a combination of convolution plus max pooling, and then you can have any number of convolution and max pooling just to find out more information from the specific image. And at the end, you just apply a fully connected layer. That is what I'm going to teach in the next video. But I hope you have understood about max pooling. I hope you have understood about location invariance, and this is what I really wanted to explain in this specific video. So yes, so this was it. I will see you all in the next video. Thank you. Hello guys, so we're going to continue discussion with respect to the convolution neural network. Now, if you're confused from the previous discussion, now here you'll be getting a clear, precise idea about what I was discussing from so long with respect to different kind of things like convolution layer and all, right? So over here, let's see this. Okay, you'll be able to understand it very much clearly now. So this kind of data set that we have is basically called as a handwritten data set, and we really need to classify. I hope everybody's heard about this MNIST data set, right? So in this MNIST handwritten data set, you have 0 to 9 digits with respect to different images, and with the help of CNN, we try to predict like which digit this basically belongs to, right? Whether it is 2, 1, 4, 5, 0, or 9, right? So here you can take this. This is basically a grayscale image. So here you can see that it is 2, and the input size is somewhere around 28 cross 1. The reason why 1 is written over here because this is a grayscale image. Okay. Now the first operation that you see is the convolution operation. Now in this convolution operation, when I say 5 cross 5 kernel, that basically means my filter that is basically getting applied is nothing but 5 cross 5. Now here you can see that my output after passing through this filter is 24 cross 24, and the N1 challenge basically indicate that how many number of filters we are going to use. So over here, let's say if there are 10 filters or 15 filters, so this N1 will get replaced by 10 filters. Okay, something like that. Now with respect to that, you remember that the first formula that we discussed, right? Here valid padding basically means we are not applying padding in short. Okay, so this valid padding will be seen in the practical also. Let's say if you're not applying padding, then what is going to happen? See this 28 minus 5 plus 1, it will be nothing but 24, right? This is how the formula is basically used. So we are able to get this 24 cross 24 output after passing through this particular filter, right? And obviously after this, you know that we apply a ReLU operation also, right? Then let's say we pass through a max pooling layer of 2 cross 2 filter. Then here you can see after soon as I pass through a max pooling layer of 2 cross 2, my image size will decrease by 12, and we will be getting another output because here we are now more focusing on the location invariant, the more intensity passed, right? So through the max pooling, the more intensity part information will be able to gather it, right? So this square box you can see now we are able to see this in the form of dot, right? So here again, and this N1 channel, how much it will be over here? The same N1 channel will be here because this max pooling gets applied to every output over here from this particular filter. Then after this is one combination of convolution and max pooling. Similarly, we can use another convolution and another max pooling, right? Understand whenever we say convolution, that basically means we are applying a filter and then we are applying a ReLU operation. Max pooling, I hope it is very much clear what you have understood from the previous video which we discussed over here, right? Then again we can apply another horizontal stack convolution layer and max pooling layer. Now here you can basically see that it is 12 cross 12. Now we're getting as 8, 8, right? 8 cross 8. So again, if I probably say 12 minus 5 plus 1, it is nothing but 12 minus 5 is 7, 7 plus 1 is 8. And if you remember, this formula is coming for n minus f plus 1, right? Because we are not applying padding over here, right? Because we need to get, if we need to get the same output, we could have applied padding, right? And finally here you can basically see that after this we are again applying the max pooling layer, and it was 8 cross 8. Always remember whenever we apply max pooling layer of 2 cross 2 filter, it is just going to divide all these particular pixels by 2. So it is now you're basically getting as a final as 4 cross 4, right? So this is what happens after a combination of convolution and max pooling. You're basically passing all the images, and this is what you get. Now it is a very important thing which is called as flattening layer, okay? And then we'll discuss about the fully connected over here. So here I'll also be talking about the flattened layer, all right? Now here you know that you have a lot of outputs. You have this one output, 2 output like this. You have any number of outputs. Now what is this flatten? Let's say this particular output is something like this. Okay, I'm just considering the first one. Okay, this first one. And let's say I have these values 1, 2, 3, 4. When we say flatten, right, what we're going to do is that we're just going to make this elongated like this 1, 2, 3, 4. We're just flattening it. Okay, we're just making it in a straight order. That's it. Okay, like this. Then similarly, after this, you'll be seeing that the second one, let's say the second one has a different values. Okay, second one has a different values like this. It can be 3, 4, 5, 6. Okay, I'm just putting in random values, right? If we flatten this, what will happen is that it will get attached to this one, and this will further get attached like this. So here we'll be having 3, 4, 5, 6. Like this, we are going to flatten this entire output that we have got from this particular max pooling, like this straight wise. Okay, and once we do this, this basically is again this will be extended till we complete all the flattening of all this, right? And after this, what we do is the next layer that you'll be seeing is something called as fully connected layer. So here now you'll be having a fully connected layer, and this fully connected layer is the same layer which we specifically used in ANN. So we will be having any number of neurons in the hidden layer, and this all will be connected to this. This all will be connected to this. Right, so this will basically get connected. Let me make this. Okay, this will be connected to this. Right, so this will also get connected to this. So it will be like same ANN what we have basically discussed. Right, similarly, right, all the layers will basically get connected. And finally, you know that in MNIST you have 0 to 9. That is 9 outputs. The final layer will be your dense output layer, which will be your output layer. And over here you'll be having 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be a 9 output, and this will all get interconnected, and it will be able to do the prediction. Sorry for the bad handwriting, but here the entire assumption is basically shown. And finally here you can see that I've used one fully connected layer, and this is your output layer, and here you'll be able to do the prediction. So at the end of the day, what will happen is that you're just going to do the forward propagation and the backward propagation, and you are just going to update all this filters values, all these filter values you're just going to update with the help of back propagation. And you know that in the convolution you basically apply ReLU, and here also you apply ReLU, so you'll be able to perform the back propagation in short. Right? So this was an entire idea about like how the entire CNN basically works. Now you may be also thinking, Krish, what about RGB image? That I will be showing you in my next video, where you'll also be getting the idea about it. Right? So I hope you got a clear idea about how things happens, because after this, what happens is that you calculate the loss function, and your main aim is to reduce the loss function, and we'll be using the same optimizers like Adam and all, and it will be basically doing the back propagation and updating all this convolution weights that is present inside the filter. Right? So yes, this was it from my side. I will see you all in the next video, where we'll be discussing about the RGB images also. Thank you. Bye bye. So guys, here we're also going to see one amazing CNN complete example, and over here you'll be able to see that it is basically an RGB image, okay, like a zebra. And here you can see that now here's a combination of different layers like this, right? Convolution plus ReLU, then pooling, then convolution plus ReLU, then pooling, then convolution plus ReLU, then pooling, and then finally when you get the output, you're basically getting the flattening layer. So this is an amazing way to basically determine this. So here you can see that always a convolution plus ReLU is one convolution layer. So here in short, we are basically using the combination of 3 convolution layer with pooling, right? So here you can see one convolution layer with pooling, then again a convolution layer with pooling, and then again a convolution layer with pooling, right? And once you get the specific output, this is basically your flattening layer where you're flattening all the entire output, and then we basically created a fully connected neural network. And let's say if my number of outputs were 3, like I need to determine whether this particular image is a horse, zebra, or dog, we can basically use these 3 outputs, and here we can apply a softmax activation function. Now, all these outputs that we are probably getting, this is basically called as feature maps. Okay, we also use this particular terminology, which is called as feature maps. And this entire process from wherein we take the input, apply this convolution layer along with pooling continuously, and we get till this particular value, we basically call this as feature extraction. So in short, we're trying to extract more and more and more features, right? And then from the time we start the flattening layer with the fully connected layer, this we are specifically using for classification purpose. And then when we apply the softmax activation function, we are basically trying to find out the probability with respect to the specific output. Understand, in the forward propagation, what we do is that we pass through all these things, right? We apply the ReLU activation function on all these values, right? Wherever we are applying the convolution layer, we apply ReLU activation function. Only the main purpose is that whenever we do the backward propagation, we need to be able to find out the derivative of those values, right? Now, as we go ahead, here you'll be able to see the flattened layer, then probably you'll be able to see the fully connected layer, and finally output layer. Now, as you know, after this, we basically calculate the loss with respect to y hat and y, and we try to reduce this with the help of back propagation. Now, in back propagation, every time we try to find out the derivative, and we try to find out the output with respect to this. Okay, an amazing example from this over here. And again, I would like to definitely call out from where I've actually taken this amazing figure. It is basically this amazing website, which you can also refer it wherever you want. But this was an amazing diagram over here, right? So let me just open this website so that you'll be able to see this. It is an amazing website. I definitely want to give the credit to this because it was so clearly available with respect to this. Because I was trying to find out many things with respect to that, but I could not get one good one. So I thought of just referring this over here, and it is a very good example. So this is the website that is developerbreach.com with respect to the convolution neural network. Again, the entire credit goes to them. An amazing diagram with respect to all these things is basically there. So in short, you're basically doing the forward and the backward propagation. In the backward propagation, you're updating all the filter weights, right? So here internally you'll be applying the filters, right? In this convolution layer, so wherever is there, you'll be just applying the filter, and you'll be able to see the output over here, right? So this was the entire operation. I hope you understood with respect to feature extraction, you understood with respect to classification, and I hope you understood with respect to this probability distribution, right? So yes, this was it. I hope you are able to understand these things. The main purpose of this was to make you understand in depth regarding the convolution neural networks, right? So this was it from my side, guys. Yes, I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to artificial neural network. Now in this video and in the upcoming series of video, we are going to develop an end-to-end project using deep learning where we are specifically going to train artificial neural network. Here, one of the 2 most important libraries that we are going to use is Keras and TensorFlow. Okay, so TensorFlow is over here and Keras is over here. Now, if you don't know about TensorFlow, this is an open source library specifically used to create end-to-end deep learning projects, and it has some amazing features. And you will be able to implement various kind of neural networks from ANN to RNN to LSTM RNN to GRU to transformer. Each and everything you'll be able to implement from this. Now, many people may be thinking, Krish, is it a good idea to probably create all these specific models and train all these neural networks completely from scratch? I would suggest, guys, right now, since all these libraries are open source, right? Like you have TensorFlow, you have PyTorch, and I would always suggest you be an expertise of one of this. You need not learn both the libraries, because at the end of the day, when we start learning generative AI, or when you will be learning generative AI, there all the LLM models, all the generative AI models that we will be specifically using in the backend, we will be able to convert or change the libraries from PyTorch to TensorFlow at any point of time. So again, my suggestion would be learn any one of the specific libraries and learn how to build end-to-end projects. That is very much important. So in this course, we will be focusing more on TensorFlow, and we will try to create end-to-end projects with the help of machine learning, deep learning, like ANN. We will try to see how we can train. And again, along with TensorFlow, we'll also be using this Keras API. Now, Keras is just like a wrapper on top of TensorFlow. So in TensorFlow, we will be able to create sequential neural network. We'll be able to create RNN. We'll be able to create ANN. We'll be able to create LSTM RNN. So when we are creating all these things, we really need to write a lot of code if we are only using TensorFlow. But if you go ahead and use Keras, which is again integrated into TensorFlow, this actually provides APIs. And this API is so good that you will be able to call each and everything. You'll be able to create your entire neural network just with less lines of code. Okay, but don't worry, I will be talking about it. So here you can see Keras also works with JAX, TensorFlow, and PyTorch. Right now in this course, we'll focus more on TensorFlow itself. Okay, so what is the problem statement that we are going to discuss? Okay, so here I have a data set. Okay, so this data set is basically called as churn modeling.csv. And as you all know, we use ANN to solve, if you have a tabular data, we have some classification or regression problem statement, we will be able to solve with the help of ANN. So here you'll be able to see I have this churn modeling.csv file. And here my output is something called as exited. Exited basically means this data is from a bank. Based on some information, the data is basically given that whether the person is going to leave the bank or not. Okay. And over here, these are the past data from this particular bank, which shows that this information was there and the person left the bank. When these informations are there, the person did not leave the bank. Okay. There are some features like credit score, geography, gender, age, tenure, balance, number of products, has credit card, is active member, estimated salary. And then here you specifically have whether the person has exited or not. Okay. So what we'll do is that we'll try to solve this simple binary classification problem again with the help of ANN. Here you'll be seeing that whatever things we have learned in ANN, right? Like how a neural network is basically created, how forward propagation actually happens, backward propagation actually happens, how to calculate loss function, how to use optimizers. That everything will be explained when we are creating this particular project. And this project will be completely end-to-end. We'll also focus on the deployment. We'll try to create pickle files. I'll tell you why pickle files will be required over here, each and everything. Okay. So this is the entire problem statement. Again, our main aim is that based on some features, we need to predict whether the person is going to leave the bank or not. Okay. So just to give you an idea what exactly we are going to do in this particular project. First of all, we'll go and focus on classification. So here we have this particular data set. Now we will take this entire data set. Okay. We'll take this entire data set. We'll perform some of the basic feature engineering. Okay. Basic feature engineering. Now what all basic feature engineering we will do? We will convert, let's say, categorical variables into numerical. Okay, we'll convert this categorical variables into numerical. We'll be doing some processing. We'll use some standardization process, right? All these things we will specifically. So this is the first step, some type of basic engineering where we will be transforming the entire data. After we do this, we will be getting our good data itself that will be available with us. Then we will try to create an ANN. So if I just consider as an example with respect to ANN, let's say in this particular feature you have 11 features, okay, 11 independent features. So this will basically be my input layer, okay, with 11 nodes like this. I've just written dot dot. Then we will go ahead and create our hidden layer. Okay, let's say this is my hidden layer that I'm actually going to create. One more hidden layer I can create over here. Okay, it's up to us how many hidden layers you will be creating and all. And then finally, you know that this is basically giving you output as one, right? So here I will be having output as one, and finally we will go ahead and basically we create this entire ANN. And as you all know, this will be interconnected, right? This will be interconnected. So I think you can go ahead and do the connection. I'm just doing one part of the connection. And this is finally going to go ahead with the output layer. Okay. Here I will also show you how you can apply dropout. Okay, dropout basically means some of the nodes I will disable it while doing the forward propagation and backward propagation. Like some of the weights we will not be updating. Okay, why do we do that? So that our model does not overfit. Okay, so it does not overfit. Then after training this particular model, we will see the concept of, so this is forward propagation. We'll go ahead and calculate the loss. We'll use some kind of optimizers, right? Everything we'll try to write this particular code with the help of Keras TensorFlow. Keras TensorFlow. Okay. Now once the model is trained, then the next step will be that how do I take this model and convert into some file format. Let's say I will be using some pickle file format or .h5 file format. Okay, we'll talk about this file format, what exactly it is. Because if we really want to do the deployment, we really need to convert this particular neural network. We need to save their weights. We need to convert them into pickle format file or h5 format file so that we can reuse this and deploy it in any environment that we want. After doing all these things, we will go ahead and further we will use Streamlit to create our web app. Okay, and from this web app, we will integrate all our models. Okay, we'll integrate all our models and we'll deploy this in the Streamlit cloud. So all these things are basically going to happen. Okay. So this is the overall things that we are specifically going to do in this particular project. It will be step by step, and how this neural network is basically created, how optimize the loss function, how dropout will be done. Everything I will be discussing about it as we go ahead. Okay. So first thing first, what I will do, I will go to my folder over here, and I will just go ahead and open my VS Code. Now, as soon as I open my VS Code, this is my VS Code over here. Okay, so here you can see my file is there. Now, quickly, as you all know, the first step, because I'm going to do this in my local, and if you have a little bit powerful machine, like let's say i5, i7 processor, you will be able to run this entire code in a faster way. Again, obviously, when we see more complex projects in the future, we will not be using local machine. Instead, we will go ahead with Google Colab. Okay, but right now, I think the data set that we have, I've also tried it to run in my local machine. Everything will be running. So I'll just give you a brief idea like how you can do that deep learning project setup in your local machine also. Okay, so first of all, I will go ahead and open my terminal. Quickly, let's go ahead and open my command prompt. Okay, here I'm just going to use this conda. And I'll say, hey, conda create -p v environment. And let's say I take python double equal to 3.11. Okay. And I'll say yes. So this entire environment I'm actually creating. And here, once this environment gets created, I'm going to just create my requirement.txt file. Requirements.txt file. Understand now there are different versions of TensorFlow that have earlier come, but I'm just going to do with the recent one. The reason is very simple because now you have Keras integrated within TensorFlow. Before Keras was a separate library and TensorFlow was a separate library. Now Keras as an API has been integrated inside TensorFlow. So let us go ahead and write the first library that we are specifically going to use. Okay, and again, as I said, we are going to use the recent TensorFlow version. So I will just go ahead and write TensorFlow. TensorFlow. Let's say that I will go ahead and use 2.1.50. Okay, and I think this is the recent one that we are specifically going to use. And if any update comes, let's say you don't want to use this, just remove this particular version and just remove it in this way. Whichever will be the recent one, that will get updated. But right now, since I have implemented this project with 2.1.50, you'll be able to see that it will work absolutely fine. Along with this, what I'm actually going to do, I'm going to use pandas. I'm going to use NumPy. Along with this, I will also use scikit-learn because I'm going to use some of the feature engineering libraries or data transformation libraries that are available from scikit-learn, like standard scalar. You also have we'll convert that into a pickle file also. Then we'll also go ahead and use this tensor board. I'll talk about this tensor board, what exactly it is and all as we go ahead. Then we have this matplotlib for some plotting, and finally we also go ahead and use this Streamlit library. So all these libraries we are going to specifically use it. Now let me quickly go ahead and activate my VNV environment. So I'll go ahead and write conda activate VNV. Okay, and now from here I'll go ahead and write pip install -r requirement.txt. So now you can see that my installation of this entire libraries will happen. It will take some time because TensorFlow is also a big file. And it will download based on internet speed. By default, I'm just going to use TensorFlow not with GPU, instead with CPU. As I said that if we are solving a larger problem statement, CPU sometimes will not be sufficient. Okay, and based on that, we'll try to further do this discussion. Okay, so let this installation take place. Now in the next video, we will start implementing our problem statement, and we'll take this particular dataset, we'll read this dataset, and we'll see step by step what all transformation techniques we're going to use, and how we're going to create the ANN with the help of TensorFlow. So yes, I will see you all in the next video. Thank you. So guys, we're going to continue the discussion with respect to this particular project. You can see over here all the libraries has been installed, okay, and I even did not get any kind of error, okay. Now I've also activated this specific environment in my terminal. So let me just hide my terminal right now because I will not be requiring. What I will do along with this one last thing I also need to do the installation, that is nothing but IPy So since the first experiment that I'm actually going to do, I'm going to do in my Jupyter notebook, and for that I require this IPy library so that I'll be able to attach a kernel and execute my Jupyter notebook file. So here I'm actually going to write pip install IPy okay. So once I execute this, you'll be able to see that the installation will take place. Okay. So once this IPy has been executed, then I'm going to probably start my coding. And first thing that I will do is that I will read this entire CSV file. And let me do also one more thing. Let me just go ahead and create my experiments.ipynb file. Okay. So I'm going to use this ipynb file, and in this my entire experiment will happen. Okay. So right now here you can see my IPy kernel library is basically getting installed. That is going to take some amount of time. Now it is done. Now I will quickly hide this terminal. Okay. Let me just go ahead and select my kernel first of all. Like here I've selected my kernel with Python 3.11. Okay. Now I will just go ahead and make some more code cells. Now let's start this entire coding. Okay. So first of all, what I'm actually going to do is that I'm going to import pandas. So let me just go ahead and import pandas as PD. Along with this, I will go ahead and import from sklearn.model selection because I also have to do the train test split, right? So for that, I'll be using this model selection import train test split. I hope you know this from the machine learning, which we have actually used. Then along with this, I'll also go ahead and import from sklearn.pre-processing. So here I will just go ahead and write pre-processing, and then I'm going to import two important libraries. One is standard scalar, and the other one that I'm actually going to use is something called as label encoder. Okay. So these two libraries I'm actually going to use. Along with this, I'm going to go ahead and import pickle file. Okay. Pickle is specifically for pickling because when we are using this standard scalar and label encoder, it is important that we go ahead and pickle this file so that we can reuse it when we are doing the deployment. So here are some of the libraries that we have already done the installation on, and we are just going to import it. Okay. So these are some of the basic libraries. Now let us go ahead and load the data set. Okay. So for this, I will say data is equal to pd.read_csv, and here I'm going to basically call churn_modeling.csv file. Now over here you'll be able to see I'll just go ahead and display data.head. Okay. So these are all my values or all my features that are available over here. I've already told you in my previous problem statement what we are going to do. We're going to take this credit score, geography, gender, age, tenure, balance, number of product, has credit card, is active member, and estimated salary as my independent feature. And I'm going to predict whether the person is going to exit the bank or not. Okay, and this is the past data from the bank which shows which person has exited or not. So this is just the top 5 records. Now the first important thing is that this first 3 features are not that important, right? You have row numbers, you have customer ID, you have surname. This definitely will not play a very important role. So first of all, what we'll do, we will go ahead and pre-process the data. Okay, what we're going to do here, we are just going to drop irrelevant features. Okay, which we can directly see it. Okay, so here I'll use this data variable, and from this I'll say, hey, go ahead and drop which all features we need to drop. Okay, so drop is a function over here. We really need to drop this row number, so I'll copy and paste it over here. Then we have something called as customer ID. Okay, then we have something called as surname. Okay, and we're going to drop all these things with access equal to 1. Access equal to 1 basically means column wise. Okay, so once we do this particular drop, we will be able to get the data value. So here is my data value. Now here you can see my features are starting from credit score, geography, gender, age, balance, and all these values are there. Okay, perfect. So this is good enough. We have done this. Now here you can actually see we have a column called as geography over here, right? So geography is there. Okay, and then we also have this gender. We have this these two features we specifically have, geography and gender. Now geography and gender is specifically in this particular case you can say it is a categorical variable. Okay, now in the case of categorical variable, what I can actually do is that I can apply some kind of encoding for this categorical variable. Okay, and that is what I'm actually going to do. Now let's go ahead and encode one categorical variable. Now in this I will say, hey, let's take first of all gender. I'll say label underscore encoder underscore gender is equal to label encoder. Okay, I'm going to just use this, and I'm going to say, hey, df of gender, or I'll say data of gender because we have used this particular feature, data of gender, and I'll just use this label encoder underscore gender dot fit. And along with fit, we will also be using transform. And we have already discussed this, why we use fit underscore transform. And here I'm going to take this particular data. I'm going to basically apply this on my gender itself, right? So now let's go ahead and see the data, and let's see with respect to this particular gender. So here you can see, okay, I'm getting an error, the spelling mistake. I'll go ahead and write this one. Okay. So once I do this, so my gender will have 2 main features, right? One is male and female. So that male and female with the help of label encoder has got converted to zeros and ones. Okay. We have also seen this in machine learning. Okay. So this is one of the encoding techniques with respect to the categorical variables. Okay. I hope you are able to understand this. So guys, over here in the gender, we saw that our values are male and female, and so that is the reason we use label encoder and we changed it to zeros and ones. But what about this geography column? In the geography column, you basically have 2 to 3 features, right? 2 to 3 categories, like France, Spain, and Japan, Germany, right? So all these country names are specifically there. So here, if we apply, just imagine that if we go ahead and apply, the label encoder. So let me just go ahead and open my Epic Pen so that I will explain you over here why I'm specifically focused on this particular geography column, right? So let's say if I just go ahead and convert this into a categorical column. So here you'll be able to see I will be able to get France as 0, Spain as 1, and Germany as 2. And when these types of numbers are specifically coming up, then there is a problem because when we assign a value of Germany to 2, at the end of the day, ANN is all about numerical calculations. Since the number or since the label of Germany is 2, it will just consider that Germany is greater than Spain or Spain is greater than France, right? So this should not happen. So for this particular case, what we will do is that we will not directly convert this with the help of label encoder, but instead what we'll do, we'll go ahead and write some code and we'll use one hot encoding. Okay. Now one hot encoding will just actually give us some values with respect to zeros and ones. Okay. So now I will just go ahead and write one hot encode geography column. Okay. So here I'm just going to write geography column over here. Now quickly, let's first of all go ahead and import the one hot encoder. So I will say from sklearn.pre-processing, I'm going to just import one hot encoder. Let me just see this particular. I'm seeing the documentation sidewise, so it'll be helpful for me to also check it out directly instead of wasting time. Okay, and writing each and everything. Okay, so here what I'm actually going to do, I'm going to specifically use one hot encoder. Now quickly, I will just go ahead and use this one hot encoder. I will initialize this. And this time there's a parameter which is called as sparse, right? So I will just make this feature sparse is equal to false. I will let you know why we are basically using this. And once you see the encoded values, then you'll be able to understand. I'll create a variable called as one hot underscore encoder underscore geo. Okay, so this will basically be my values over here. Okay, now quickly the next step that we are going to specifically use is nothing but geo underscore encoded value, and I'll say, hey, let's apply this one hot encoder underscore geo dot fit underscore, okay, one hot underscore geo dot fit underscore transform on which column? Basically on my geographic column, right? So here I'm going to give my geography column, right? Now once this is done, you'll be able to see that. Let's go ahead and see how I'm actually going to get this geo underscore encoder. And let's execute this. So here it says got an unexpected argument sparse is equal to false. Okay, let me just remove it for now onwards. Okay, let's execute this. So here I'm actually able to get a sparse row matrix. Okay, I think in one hot encoder I have something called a sparse. Sparse is equal to false. Let's see. Got an unexpected argument called a sparse. I think in the recent version the sparse is not present. Let me just go ahead and use directly this one. Okay, now once I get this geo encoder over here, right? What I will do is that if I use this geo encoder, okay, or if I also go ahead and see what all features specifically we have, if I try to convert this into a numpy array, I will be able to see all the values. So first of all, what I will do, I'll just go ahead and write one hot underscore encoder underscore geo dot get underscore features underscore names underscore out, right? So if I go ahead and see this parameter, okay, sorry, out, and here I'm just going to give my function, and inside this I'm just going to give my column geography. So if I go ahead and execute it, it says get underscore features. Okay, it should be feature. Sorry, get underscore feature underscore names underscore out. Okay, so here you'll be able to see with respect to the geography, I have this three features that is getting converted into a one hot encoder, right? So with respect to this, if I try to convert, I'll use this particular features, and I will be using this sparse matrix that I've actually got in the form of data frame. Now in order to get that in the form of data frame, what I will do, I'll just go ahead and write geo underscore encoder or geo underscore encoder. Here I will use this particular value, and I will convert this entire into pd dot data frame. So I'll just go ahead and write pd dot data frame, and here what I'll say, this is my data geo underscore encoder. Along with that, if I really want to assign the columns to this, it will be nothing but this entire values, because from this I'm actually able to get the columns. Okay, so this is my data frame, and this is what I'm actually getting as my encoded underscore df. Okay, so let me just go ahead and execute this. So once I execute this, and if I go ahead and see my geo underscore encoded underscore df, I'm getting an error. The reason is shape of value is 1000,1. So guys, here you can see that I'm actually getting this particular error. It shape of value that is passed is 10,000,1, and it is specifically implying that it needs 10,000,3, because here we're giving 3 columns, right? Now, why this specific problem is happening? See, if I go ahead and print this geo encoder, it shows compressed sparse row matrix of d type, right? Now, if I probably convert this geo encoder to 2 underscore array, okay, and if I execute it, 2 underscore array, sorry, it should be 2 array. So here you'll be able to see that I'm able to convert this into a sparse value, right? And that is the reason, before I was just giving this. Instead of giving this, I will just go ahead and give this. Okay, so here you'll be able to see that if I go ahead and give it now, and if I go ahead and see this encoded underscore df, so here you can see that I'm actually able to get this geography France, geography Germany, and Spain. Wherever France is, that value will be 1, and remaining all will be 0. Wherever Germany is, that will be 1, like over here, and wherever Spain is, that will be 1. Okay, so this is how you fix this particular problem. Again, I'm not going to probably delete any of this or remove any part of this particular video, because I want everyone to see the errors that we specifically face. Because once you see the error, you probably become much more confident in solving that particular error, right? So let's go ahead and combine all the columns now. So here I will just go ahead and combine all the columns with the one hot encoded columns with the original data. Okay, with the original data. So here what I'm actually now going to do is that quickly, and this is really important because without this, trust me, because the new part of the code, right, what we did with respect to transformation, we really need to update that. So I will just go ahead and update it, and I will write data is equal to pd dot concatenation, and here first of all I have to concatenate the new geo encoded d underscore df without this particular data, right? So first of all, I will just go ahead and do the data dot drop. So I will go ahead and write data dot drop, and here I'm going to use my column, which is called as geography, because I don't require it anytime now, and here I'm going to just use it as x is equal to 1. Okay, so once this is dropped, the next thing is that I will just go ahead and concatenate with my geo underscore encoded underscore df, and this time I'm just going to give my x is equal to 1, right? So now if I go ahead and see my data dot head, you'll be seeing that okay, gender has become 0, 1, and along with this there'll be 3 more features like geography, France, Germany, and Spain that has got concatenated. Okay, so this is how we have actually converted our categorical features into numerical features, and we have basically used 2 important type of encoding techniques. One is label encoder, and the other one is one hot encoder. So I hope you were able to understand this entire thing, and see, everything I'm trying to do step by step, we'll do it very much in a slower way so that you get all the points, you understand things, and you go in. All these are like all machine learning kind of feature engineering only we did. Something new will not apply over here. Everything is same like how we have actually performed, right? Now let's quickly go ahead and see. One is what I have used label encoding. One I have used one hot encoder, right? So I have to probably go ahead and save all these particular files, right, in the form of pickle file, because this same one hot encoding and same label encoding I'm actually going to use in the later stages, right? So label encoder gender, I will try to go ahead and save it, and then one hot encoder with respect to the geo, I'm going to save it. Okay, so let's go ahead and save this particular file in the pickle, so that in our end-to-end project we have to probably use this. So I'll just go ahead and write save the encoders and scalar. Okay, so I'll say hey with open. I'll open a pickle file. I'll say label underscore encoder. Okay, label underscore encoder underscore geo. Okay, label underscore encoder underscore gender. First of all, we'll go ahead and save this pickle file. And for this, I've already imported my pickle file. I'll go ahead and open this in my write byte mode, because this is a deserialized or serialized file itself. So we will be writing in the form of bytes. And this as file I've created a temporary variable. I'll just go ahead and write pickle.dump, and I will dump this entire label encoder gender inside this particular file. Okay. Similarly, you'll also be seeing that I will go ahead and open. With open, one more pickle file, I'll just go ahead and create it. That is nothing but one hot encoder underscore geo dot pickle file. And this will also get opened in my write byte mode, okay, WB mode. And here I can see as file, okay. And this also, we will go ahead and dump it. So I'll say pickle dot dump. And here also I'm going to use my one hot encoder underscore geo. And finally, I'm just going to convert this into my file, okay. So let's go ahead and open it. So I'll save it. Open. Oh, okay. This shoe file right now. I'll save it. So once I save it, you can see this is my pickle file that I got created. So till here, the basic transformation that I have actually done, right? That all has been completed. And we have almost done this kind of transformation and we have saved it. Okay. Now let's do one thing. Okay. So you have done the transformation. Now let's quickly divide our data. Divide the data set into independent and dependent features. Now you know that my data.head, if I just go ahead and execute it, right? So this is data.head. Here, exit is my column, which I will be keeping as my dependent feature, and remaining all this particular column I will keep it in my independent features, right? So quickly, let's go ahead and do that. So I will just try to go ahead and divide my data set into independent and dependent features. So I'll say data.drop, and here I will go ahead and write exited, comma axis is equal to 1, okay, y is equal to data, and here I will just go ahead and say exited, right? So this will basically be my dependent, y will be my dependent, x will be my independent feature. Then we'll split the data in training and testing sets, okay? Now let me just go ahead and write xtrain, comma xtest, comma ytrain, comma ytest quickly. And then this is very much common because we are using it from machine learning, x, comma y. Let's go ahead and use some test size. So test size will be 0.2 and some random underscore state will be 42. So here we have, also we need to do one more thing, guys. We'll scale down these features, okay? Scale these features, and the scaling of this, all the features also we will be specifically doing, okay? Now scaling, we will use the standard scalar, okay? And once we'll go ahead and initialize it, here I'm just going to write xtrain is equal to scalar.fit transform on my the entire xtrain data. And for my xtest underscore data, x underscore test data, I'm just going to use scalar.transform. And here I'm just going to go ahead and write x underscore test. So this transformation is specifically required. I will quickly go ahead and execute it. So, okay, x comma y, okay, perfect. So let's go ahead and execute this. So here you'll be able to see this will be my xtrain data, which will be the it'll be basically scaling is getting applied with the help of standard scalar, and similarly I have my xtest. So once this is done, we'll also go ahead and save this scalar file with the help of in the form of a pickle format. Okay, we will be requiring all this pickle format. So with open, I will say, hey, go ahead and use my scalar.pickle, and it'll be in the write byte mode. Okay, write byte mode. Now once we're using this write byte mode, I will just go ahead and create my context over here as file, and we'll go ahead and dump this scalar comma file. Okay, whatever scalar value is there. So let's go ahead and execute it. So here you have each and everything. Here you have label encoded pickle, you have one hot encoded pickle, you have scalar pickle. This is perfect. So in short, in this video, what I've done is that I've just cleaned some data set. I've applied all type of feature engineering that I want to do. Okay, I have divided this into dependent and independent features. So what all main feature engineering methods that we have applied is nothing but we have applied both our standard scalar, we have applied, we have converted categorical features into numerical features using label encoder, one hot encoder, everything we have specifically done. So now my data is specifically ready. Okay, this is my data. Now on this particular data, I'm going to just go ahead and train my artificial neural network, and that is what I'm actually going to show you in the next video. So I hope you like this particular video. I will see you in the next video. Thank you. So guys, now we are going to continue discussion with respect to this particular project. Already in our previous video, we have actually created 3 pickle files. One is the scalar pickle file, label encoder, gender pickle file, and one hot encoder for geography pickle file, right? Now we'll go ahead and train an artificial neural network, and that is what we are going to see, how we are going to train this and all. We'll be discussing about that, okay? So first of all, we will go ahead and import TensorFlow, okay, since we are going to just use TensorFlow as TF. Okay, so TF is an alias which we will be specifically using. Now, before I go ahead, let me just give you a brief idea, like how does a neural network basically gets created with the help of TensorFlow keras, okay? So, as I said, with respect to ANN, right? In ANN, you have an input layer, then you have a hidden layer. You can have multiple layers, like hidden layer, like you can have HL1, HL2, any number of hidden layers, right? But just to give you a basic idea, basic ANN looks like it'll be having one input layer, it can have one hidden layer, two hidden layers, and finally it has an output layer, okay? When we probably take this entire neural network, like a specific ANN, let's say in this input I have like this, hidden layer I have some 3 nodes, one more hidden layer I have 2 nodes, and finally I have one output node, right? This neural network, here we are going to perform the forward propagation and backward propagation. So in TensorFlow, we basically call it as a sequential model, okay? What do we call ANN as? It is nothing but it is a sequential model, right? And this sequential model here, you'll be able to see that we will be doing forward propagation, we'll be doing backward propagation, and all these nodes will be interconnected, right? This input will be interconnected to this, then this will be interconnected to this, similarly this will be interconnected to this will be interconnected to this, right? And this will also be interconnected, and finally you'll be interconnected to the output. So this is my input, this is my hidden layer 1, this is my hidden layer 2. All these interconnected lines that you have are nothing but these are weights, W1, W2, W3, like W4, W5, W6, like this, right? Now, in order to give you a brief idea, since I have, let's consider this, right? I have 2 inputs, I have three nodes, hidden nodes in this hidden layer, right? So here the number of weights that will be, it will be nothing but 2 cross 3 weights, right? And 2 cross 3 is nothing but 6 weights. Why 2 cross 3? That's very simple. 2 inputs, and it is getting connected to 3 weights, 3 hidden neurons in a hidden layer, right? Along with this, here also you'll be having a bias B1, you'll be adding bias B2 and B3. So along with the 6 weights, there are 3 bias in this first hidden layer, okay? In the second hidden layer, again, here you have 3 hidden neurons. This is getting connected to 2 hidden neurons. So over here, you'll be able to see that the weight matrix will be 3 cross 2, right? So again, you will be having one more additional 6 weights, right? And here also, bias will be added. So this will be my B4, this will be my B5. So here, 6 weights and 2 bias will be there, okay? So this is with respect to the hidden layer 1. Hidden layer 2, and this is with respect to hidden layer 1. And finally, you have this output layer. Here also your weights will be connected. So here some weights will be there. So here also, how many weights will be there? 2 cross 1, which is 2 weights, right? And here also one bias will get added, so one bias. And after this, you can probably apply a sigmoid activation function if it is a classification. If it is a multi-class classification, you can apply softmax, right? So total number of parameters that you see, right? If I say how many trainable parameters are there in this neural network, it's very simple. You'll just say, hey, 6 plus 3, this is 9, then 9 plus 6, 15, 15 plus 2, 17, 17 plus 2, 19, 19 plus 1, 20. So with the help of 20 trainable parameters, we will be doing the forward propagation and backward propagation. Now, similarly, this input is basically defined by the number of inputs that we have in our CSV file or in our data set, right? In our data set, how many inputs we have? In data set, how many inputs we have? If you have 2, so it'll be 2. If you have 3, it'll be 3 nodes, right? If you have 4, 11, 10, any number of nodes. So in this way only, we will be going and created our ANN, which is a sequential network. Sequential network basically means it will be interconnected, right? Now, there is also one more important part. If we really want to just create this hidden neurons, so in Keras, there is a library which is called as dense. Okay, there's a class which is called as dense. Okay, so let me again repeat what are the key parameters that we will be specifically using. First, when we start creating our ANN, we have to initialize a sequential network. Okay, sequential network. The second thing is that whenever we need to create a hidden neuron, right? Hidden neuron, I'm not talking about hidden layer. If we need to create a hidden neuron, we will specifically using dense. Okay, so if I say, hey, dense, I want 64 nodes. So in that particular hidden layer, I will be having 64 hidden neurons. Okay, something like this. So we will be using dense. Okay, along with this, you know that in every node we apply an activation function, right? So here we'll also be using activation function. Activation function can be sigmoid, it can be tanh, right? It can be relu, it can be leaky relu, right? It can be any number of others, right? But always it's a good idea that in the hidden layer you try to use relu, in the output layer you can use sigmoid or softmax, which I've actually discussed about it. Now this is my third important parameter. The fourth parameter that we will be using is something called as optimizer. Now this optimizer can be any kind of optimizers that we have. I'll show you how you can initialize this particular optimizer also. Optimizer is useful in backpropagation because these are responsible in updating the weights. Okay, updating the weights. Very important. Okay, and the fifth one that we are specifically going to use is nothing but our loss function. And our main aim is that what loss function we'll be using, and based on this loss function we'll be having a gradient descent and all. We'll try to reduce this. Okay, and the sixth and the final thing is something called as metrics. Usually in a classification problem, your metrics is like accuracy. In a regression problem, you have MSE, mean squared error, mean absolute error, and all of that. Okay, so all these things we'll try to implement. And my training information also, what I will do, my entire training information, I will store the logs in some folder. Okay, so that I will be able to use TensorBoard. And the main aim of the TensorBoard library is to display these logs in a way that we will be able to understand. Some visualization graphs will be used in order to display it. Okay, so these are the steps that we are going to first of all focus. We are going to just go ahead and create a sequential neural network. Whenever we really want to create any hidden neurons, this hidden neuron, this hidden neuron, or even in the input, I will be specifically using dense. Okay, so all these things we are going to go ahead and discuss. So let me quickly open this now. I will go back to my code. Okay, and here you will be able to see that I will just go ahead and import TensorFlow. Okay, so I'm going to import TensorFlow STF. I told you I'm going to use sequential model. So how do I import it? So I'll go ahead and say, hey, from TensorFlow dot Keras dot models, we are going to import this sequential model. Sequential. Okay, from TensorFlow dot Keras dot model. Okay, similarly, I will go ahead and write from TensorFlow dot Keras dot. As I said, whenever I need to create a node, it is nothing but using dense. Okay, dense will be that library that we'll be using, and this entire thing will be present inside layers. Okay, so I'm just going to import dense. So this is one more library. Along with this, I will be showing you one very important property we'll discuss about, which is called as TensorFlow.Keras.callbacks. Okay, and we're just going to import something called as early stopping. We'll discuss about this early stopping, what exactly it is. Okay, and finally we have this TensorBoard. Okay, now TensorBoard, we have implemented this, and finally I'm also going to import date type because I'm going to use this date time also. So I have executed or imported all these libraries which we are going to use. One is sequential, one is dense, one is early stopping, and one is TensorBoard. Okay, now let's go ahead and build our model. Build our ANN model. Okay. Now to build the ANN model, what all things we are specifically going to do? As I said, I'm going to create first of all a sequential model. So I will go ahead and initialize, and let me just go ahead and initialize sequential. Okay. Now inside the sequential, it is important. Please try to understand this. Okay. Inside the sequential, I'm going to use some layers, dense layers and all. Okay. So here, if I go back to my diagram, okay, let's go back to my diagram over here. First of all, let's go ahead and understand how many number of inputs that I have. Okay. So first, this is my entire sequential model. Okay. This is my entire sequential model. Now inside the sequential model, how many inputs I need to probably consider? So if I go ahead and see my X train dot shape, and from this, if I just try to find out how many columns are there, that will actually help us to decide how many inputs will be there, right? How many inputs will be there. So I have to probably use this entire inputs, okay, over here. And let's say that I will be using the sequential, and I'll say, hey, initially I'll take this 11 inputs, and then I will go ahead and create my dense. I'll use this dense library and create my hidden layer. Let's say that I'm going to use 64 nodes, any number of nodes in this hidden layer, right? And when I'm creating this dense, I will also give my input shape, like how many elements are coming from this input data. So let's say from this, I'm getting this X train dot shape of 1. If I go ahead and write like this, it says that what is the input that is probably coming from my X train data. That input will get corrected over here. Okay. So we are initializing our input over here along with the dense layer. So this is what we're going to first of all do. Okay. So quickly I'll go back over here and now see, focus on this. Okay. I need to give my input and my hidden layer 1 first. I'll use this dense. Let's say in my hidden layer 1, I'm going to say, hey, we are just going to use 64 neurons. I'm just considering, hey, let's go ahead and use 64 neurons. Now in all these neurons, I also need to apply an activation function. So I will go ahead and apply an activation function. Okay. Now once I apply the activation function, I will just go ahead and apply ReLU activation function. Okay. It is up to you, whatever activation functions that you really want to apply. Now, to this hidden layer, what will be the input that will be coming? So here you will be having this particular parameter which is called as input underscore shape. And this is only for the first hidden layer that you really need to write because it is getting connected to some inputs over there, right? In the second hidden layer and all, we don't need to write this input underscore shape. But always for the first hidden layer, we need to write this. So my input underscore shape will be nothing but it will, I can just go ahead and write something like this, right? So it will be X underscore train dot shape because this shape of 1, if I probably consider, it is just going to take that particular value and it is going to consider that many number of inputs are there. So if I just go ahead and execute this over here, what is my X underscore train dot shape of 1? Okay, I'll be okay. Tuple. So here it says okay. I have to use this. I have to use this index. Okay, so shape of 1. Okay, so here you can see that there are 12 elements. Okay, in my X underscore train dot shape of 1. Right now, if I'm giving input underscore shape of this value comma blank, if I just give comma blank like this in a tuple, So I'm just saying that, hey, it is a single dimension and it has 12 inputs. Okay. And that is how I'm also giving over here as my input shape. Clear? Very much simple. Now this is my first hidden layer. So I'll write down the comment over here, first hidden layer, and it is connected with input layer. Okay, connected with input layer. This is perfect. Okay. Now in my second layer, again, let's go ahead and use the dense. I will use 32 neurons over here, and I have to just go ahead and apply my activation function. Now after I apply my activation function, I don't even have to give any input shape over here because now we know, since we have used sequential, it knows that it will be connected. Right? All these layers will be specifically connected. Okay. Now finally, you'll also be able to see that I'll go ahead and apply one dense one. Okay. And then I will say, hey, go ahead and apply another activation function. And the reason I'm saying that another activation function, this is my hidden layer 2, HL2. Okay. And here you'll be able to see that this is nothing but this is my output layer. Output layer, how many outputs I need to find out? Only one, right? It's a binary output, right? So I'll say, hey, let's go ahead and use this sigmoid over here. Okay. So once I execute this, so this actually becomes my entire model. Okay, my entire model over here. Okay. So if I go ahead and execute this, this is my entire model. Very simple, I guess, right? Now just imagine how many parameters will be there. So what I've actually done over here, let me just go ahead and talk about it. Okay. So here I created an input layer. So this is my input layer. This input layer has inputs of 12 inputs, right? 12 inputs, 12 comma some. Let's consider 12. Then I have a hidden layer. This hidden layer is basically having 64 hidden neurons, right? 64 hidden neurons. Then I have one more hidden layer, which has 32 hidden neurons. And finally, this is my output layer, which is having one output, right? One neuron. And this all will be interconnected. And this is what we have actually created, right? And now we have to probably do the forward and the backward propagation. Now, let me just go back to the code. Now, let's go ahead and write model.summary. And with the help of model.summary, you'll be able to see that I'll be able to see how many total number of parameters are there. So they are around 2, 9, 4, 5 parameters. Okay. So here you can probably see in my dense, initially you have the 64, then you have this 32, then you have this one. Okay. Parameters, this is nothing but it is a combination of all the weights and bias. And that is the reason the total number of parameters will be 2, 9, 4, 5. Okay. So this is the entire model, and I'm actually going to do the forward and backward propagation with respect to this. Now, in order to do the forward and backward propagation, we need to compile this model. So let me just go ahead and write compile the model. Okay. Now with respect to the compile the model, I'll just go ahead and write model.compile. And here, I'm just going to use some parameters. One is optimizer. Okay. Right now, let's keep it blank. I will initialize some optimizer over here. Then you have loss. In this loss, I'm just going to use binary cross entropy. If it's a multi-classification, you can use sparse cross entropy. Okay, so there is different values. With respect to multi-classification, you'll be seeing a parameter which is called as sparse cross entropy. Again, you can go ahead and check with respect to Keras API. And here, we will also go ahead and use one metrics parameter. And this will be nothing but it will be accuracy. It is given in the form of list because you can add multiple values also. Now, quickly, one more thing that I really want to show that over here, is this the only way to probably put any values, or can I probably go ahead and use some other way of applying optimizers and all? Okay, so let me just show you one more way. Okay, so here I'll say OPT optimizer is nothing but TensorFlow dot. Okay, there's a function which is called as optimizers. TensorFlow optimizers. Okay, sorry, TensorFlow dot Keras. Okay, dot Keras dot optimizer. Okay, and here we have something called as Adam optimizer. I think so. It should be working fine. And let's use my learning underscore rate is equal to 0.01. Okay. Okay, TensorFlow is not defined, so that is the reason we could not see it. Okay. Okay. So now what we have actually done is that, see, over here, when we go ahead and give one optimizer, let's say that I want to go ahead and give one optimizer over here, and the optimizer name is Adam. Okay. This is the keyword that we can specifically use. Again, in Keras API documentation, if you go and see, I'm actually applying Adam over here. Okay. But this Adam has a fixed learning rate. Okay. Over here, it has a learning rate, but you need to provide your own learning rate. So what you can do, you can just import TensorFlow, and you can write, hey, TensorFlow.Keras.optimizer Adam, and not only Adam. See, there are a lot of other optimizers also. Let me just show you. So here I'll just go ahead and write optimizers dot Adam. So instead of using Adam, you have Ada Delta, Ada Factor, Ada Grad, Adam W, Adam Max. I think most of them I have already discussed. We have discussed Adam, we have discussed Ada Delta, all these things, right? Ada Grad also we have discussed, right? So let's consider right now, we'll just go ahead and use Adam. And here there will be a parameter which is called as a learning rate, which we can actually define. Okay. So here I've actually defined 0.01. Similarly, what you can do is that you can also go ahead and write TensorFlow dot Keras, and you can also set your loss, okay, losses, and dot different losses will be also there, I guess. Let's see. See, over here you have binary cross entropy. Then you have categorical cross entropy. You can use all the specific losses if you want. Let's say if I want to directly use binary cross entropy, I can also use this, okay? And I can store this in one variable, like one loss, and I can use this particular loss over here. Like, see, if I use this op, I'll be using this over here. Copy and paste it, right? So I'm showing you both the ways how you can actually do it. Directly, you can also use this particular keyword, or you can also go ahead and initialize this. Okay, so if I go ahead and initialize this, so I will be able to see that, hey, this is my loss, which looks like, right? But both this way, so what I'll do, I'll take this optimizer, I'll put it over here, and similarly, I'll use this particular loss, and we'll go ahead and do the compilation. Okay. Now, when we are doing the compilation, this is the compiling the model over here. So, okay, there's an error. Metric, please. Okay, let's see what it says. Including this metric. Metrics. It should be something like metrics. Okay, so this is the keyword that is used. So again, this kind of error will come. I'm making sure that I don't delete any of the error. Okay. Now the next thing what I will do, I will go ahead and set up the tensor board because we have still not started the training, right? We have still not started the training, and training will be set up, as soon as I probably start. Once the training gets completed, we will also be able to capture that logs and we'll be able to visualize that log. So that is the reason we set up this tensor board. So I will create a directory which is called as log underscore directory, and here I will say, hey, make this folder. Okay. So first of all, logs/fit. I will probably make this folder over here. Okay. And I'll say, hey, go ahead and make this and use some date type. Use some datetime format so that you'll be able to see this, and then I will go ahead and write datetime. Okay, dot now. Okay, I'm using this datetime, and let me use some time format. So I'll go ahead and write str of time, and I will just use this particular time format to capture my logs. Okay, so let me just copy and paste it over here. Okay, so this is my time format that I'm actually going to use. Okay, it will basically go ahead and create this entire directory in short. Okay, now. Quickly, let's do one more thing over here is that I'm also going to, okay, for right now, let me just go ahead and create this logs directory, and it is going to make sure that whenever we train our model, it will go ahead and it will store all the logs over here. Okay, perfect. Till here, I think everybody is good enough. Now, let me do one more thing. Let me just go ahead and create my TensorFlow callback. Okay, so I'm going to probably create this particular variable. And what is the meaning of this? We will just go ahead and say, hey, use this tensor board, what we are trying to import. Now, this tensor board, we need to import it. Okay, so in order to import it, I will be importing two libraries. Since I'm going to import two important things, one is import TensorFlow dot keras dot callsback. Okay, I'll be talking about what is the importance of this callsback just in some time. So I'll go ahead and write, hey, import early stopping. Along with this, I'm just going to import TensorBoard. I will talk about both early stopping and TensorBoard, but right now you just understand that TensorBoard is just to visualize all your logs that you have while training your entire model. Okay, you can also do it manually with the help of Matplotlib, but I feel TensorBoard will be a good one. Okay, so here I've initialized TensorBoard. I'm saying, hey, let's give this as my log directory over here. Log directory is equal to, I'm just going to give my log directory, whichever log directory I've actually created. The next thing that I will be using is some histogram frequency as well to just see that some of the histogram diagrams is also created from here. Okay, so once this is done, I'll go ahead and execute it. Invalid syntax. Okay, from I have to use over here as from. Okay, so perfect. This works absolutely fine. Okay, now we will also go ahead and set up something called as early stopping. Now, why exactly is this early stopping? See guys, when we are training a neural network, we can train it for any number of epochs. Okay, we can train it for multiple epochs, 100 epochs. We can create different batch sizes and we can do forward and backward propagation. But it may happen in such a way that even we run for 5 to 6 epochs continuously. There, let's say I'm trying to run it for 100 epochs. Okay, well, if we see such a scenario where in 20 epochs only my model has trained at its best level, and after that it is just varying by 1 or 2%, right? Then it is not necessary that you need to probably train that particular model for 100 epochs, right? Whenever we train our model, we have to probably continuously monitor our loss value. If that loss value is decreasing, then it is fine. We can train it continuously. But let's say that after a certain number of epochs, that particular loss value is not decreasing. So what do we do at that point in time? We don't need to probably run the entire 100 epochs. Since what we can do, we can say, hey, go ahead and apply this early stopping, where go ahead and see only the loss value. If it is not decreasing, let's say for the 5 epochs itself, then you can stop the training there itself. So that is the reason why we use early stopping. So here I'm just going to create my early stopping callback. Okay, so this is just like a callback that we use. And here we will go ahead and write early stopping. We will go ahead and monitor one very important parameter while we are training, right, which is called as validation loss. Val underscore loss. I will talk about what all keys is also getting created. Okay, like you'll be able to see multiple keys. You'll have validation loss, you'll have training loss and all. But right now I'm just going to monitor this validation loss. And let's say I'm saying, hey, be patient for at least 5 epochs. Okay, before taking that particular decision. If till the 5 epochs you see there is no improvement, then you can stop it over there. Okay, and then one more parameter that I'm actually going to say, hey, restore the best weights. So when you're going through the forward and the backward propagation, at which epoch you find out the best weight, you can probably consider that and you can reload it when you stop the early stopping. Okay, so I'm just going to use all these parameters and do the early stopping. Right, very important. So this will be my early stopping that I'll use. Now finally, now this is the stage of training the model. Okay, I've created my step by step what I've actually done. I have created my entire model. I've said, hey, which optimizers I'm going to use, which loss I'm going to use, and I've assigned that entire optimizer and loss to my model along with my metrics. Okay, then I'm saying, hey, go ahead and set up the TensorBoard. You have to probably create all the logs while training. So this is the logs, and from this particular logs only we will try to visualize some of the data. Now here I've created TensorFlow callback, and here I've actually created early stopping callback, and I've told you what is the importance of early stopping callback. Now for training the model, I will just go ahead and say, hey, history is equal to nothing but model.fit. Okay, and here I'm going to give my x train, comma y train. Okay, comma along with this I'm also going to give my validation underscore data. Validation underscore data will be the combination of x test, comma y test. Understand this y test data will be used for comparison with respect to the accuracy. Then I'm going to say, hey, run it for 100 epochs. Let's say I'm saying go ahead and run it for 100 epochs. And finally, I'm also going to apply my callbacks. So this callbacks is nothing but 2 callbacks I'm going to apply. One is TensorFlow callback, and the other one is specifically my other callback, which I'm going to use, which is nothing but early stopping callback. Okay, so this 2 callback I'm going to basically see, and then after we train this entire model, we will load our entire TensorBoard that I will show you how it is basically done. But over here you'll be able to see my logs file will start getting created. Okay, so let's quickly go ahead and execute this, and I hope everything should work fine. So I'll just go ahead and hit execution. Now here you can see my epochs has started. Right, initially I'm getting the accuracy over here, validation accuracy is over here, and you can see. I told it to run it for 100 epochs, but this has just stopped at 7. Okay, let me do one thing. Let me increase this patience level to 10. Okay, I'm saying, hey, try to just see till 10 epochs. Now let's go ahead and execute it. So here you can see accuracy is 85, validation this one. I think we are getting the best validation loss still here. Okay, it will wait for a 10. Now in the 16, 17th epoch it has stopped. Right, and this is all the values that I get. I get my loss. So till 87% I'm able to get it. Validation loss I'm able to get this much. Validation accuracy I'm able to get 0.85. Right, so these are all the information that you will be seeing over here that we are able to get it. Right, which is amazing. And here you can see that I'm able to train the neural network quickly as possible. Right. Let's do one thing. Let's save this entire model file. So I'll say, hey, go ahead and save this model.save, and I'm going to probably create one h5 file. So h5 file will be compatible with Keras, so that is the reason I'm actually creating it. So here you can also see model.h5 file. Okay, let's do one thing. Let's load TensorBoard extension. Okay, so let's load this. So for loading, I will just go ahead and write load underscore extension, and here I'm just going to use TensorBoard. Now this extension also we need to install in our so here you can see line magic function load underscore extension not found. I think the spelling is wrong over here. I just need to write like this. So here you can see I've launched my TensorBoard session. It looks something like this. Then what I will do, I will just go ahead and say, hey, take this TensorBoard, my magic function, okay, and along with this use this log directory, and inside that log directory I have my logs/fit folder. Okay, so this is how you load this entire TensorBoard. Now if you see inside this logs, this is nothing but it has your entire information with respect to training and with respect to validation. Okay, and it is just going to load this, and it is going to show us in this visualized format. Let's see this. Okay, so here you will be able to see it. I think it is getting loaded. Let's see whether it is getting loaded or not. So quickly, I think it should get loaded. Yes. So it says, hey, so it says, hey, no dashboards are active for the current data. The problem may be, let's go ahead and launch this. Sorry, let's go. Okay, see what you have to do is that. Let me click it over here. Click over here, right? Launch TensorBoard session. Okay. Now in this TensorBoard session, just click and launch. Over here, you'll be able to see use current working directory or select another folder. I'll go ahead and select another folder. And let me just go ahead and click this. And let me just go ahead and cite this particular folder. And let's go ahead and select this train folder. Okay. I'll say, hey, just go ahead and load this train folder. Let's see whether it will load or not. I think it is not able to find out this log fit directory, which is already there. Okay, that is the problem. See. Okay, I got it now. Okay, the problem is what, right? It is trying to find out this log/fit folder, but this is the folder name that I'm actually getting. So let me just go ahead and write log fit folder. Okay. let's see, I think it should replace the name, or I can just give that particular folder name over here. Even though if I execute it here, you'll be able to see that I'll not be able to get it because this is getting renamed. Okay, so let me quickly rename this. So I'll say, hey, reveal in the file explorer, inside this logs folder, this is the folder name, and here is my events. That is the information that is coming up. Okay, so quickly let me do one thing. Let me rename it from here. That would be a little bit faster. I think it will not allow because the file may be getting used somewhere. Okay, so let me do one thing. Let me quickly rename this. Instead of rename, right, I will just go ahead and take this name entirely. Okay, and now I will go back over here and say instead of fit, you just go ahead and use this entire name. Okay, so now I think it should be able to load it because I've given the correct loading directory. See, I'm not going to edit all these things. Whatever error that I'm actually facing, I will be showing you so that you will be able to execute it. Okay, that is my main name. Okay, I don't know why we have to probably execute 2 times. It was getting loaded. Now here you can see beautiful. You're getting all these diagrams. See. So here, based on epoch accuracy, let's go ahead and see this. Let's say I will just uncheck it, and here I will just go ahead and write epoch accuracy. Now with respect to this epoch accuracy, you'll be able to see. Let me do one thing. Let me just uncheck this. Okay. So this is my epoch accuracy. This is my epoch loss. Okay. Now see, with respect to this epoch loss, you'll be able to see my loss is decreasing. This is good, right? If I close this over here also, you'll be able to see. Let's go ahead and use this. In epoch accuracy, you'll be able to see this graph. See, it is increasing from 0.855 to 0.8655. So this is good. It's going in this direction, right? And you can see what relative step, what value, what accuracy you have actually got. Every information is basically getting stored over here. You can also change this value with respect to smoothing, and here you'll be able to see how the accuracy changes, right? See, these are some of the parameters. This is also something very important, the dense underscore 3, right? This, it just looks like a, if you have seen this histogram, it just looks like a gradient descent in opposite manner, right? This is the maximum top pick, and this is the minimum loss we are able to get, right? Which looks like this over here. So here also you can probably observe each and every this. But the main thing is epoch accuracy and epoch loss, which you are able to see over here. Not only that, let's do one thing. Let's, instead of taking train, let's go ahead and see validation. Now in validation, you have this epoch accuracy. So here, again, there's some up and down, but at least you are able to get it to 0.855. Then you also have this epoch loss, epoch accuracy versus iteration, epoch loss versus iteration. So please go ahead and check this out entirely. I've already shown you how to do it. First of all, you need to set this entire logs. Whatever folder name you're probably getting, you have to probably use that, okay? But still need to think why that folder came in that way, okay? Okay, I was using this plus, right, some date sign over here. And automatically with the help of date sign, you could see that instead of writing like this, right, I could have written something like this. I'll keep this code like this, okay? It'll be slash, and inside that any date format will be created, okay? Perfect. Till here, I think everything looks good. But always make sure that if I am using this folder wise over here, let me just show you again. Please make this change. So I'm saying, hey, inside the fit folder, you have to probably create it every time date timestamp, and then you have to probably go ahead and create your logs. So in this case, you don't even have to use this, right? You'll be able to get it. Perfect. So this was about this one. We have also saved the pickle file. We have done almost each and everything. And this is how a ANN neural network is basically created. Let me just show you how do we load the pickle file, because we need to do the prediction, right? So how do we load the pickle file? That is very much important to show, because at the end of the day, when we create a end-to-end Streamlit project, so we definitely require all the pickle files. So in order to load the pickle files, so first of all, what I have to do, because see, here I now have the pickle files, I have all my model trained, and I have to make sure that I load that particular pickle file and I do the prediction, right? That is what I have to actually do. If I don't do that, then it will not work out, right? So let me quickly go ahead and import all the libraries again. So let's say that I'm doing it in my new file, okay? Or let's consider a new file. So here I will say prediction.ipynb, okay? Here, the first thing first, I will go ahead and import this. Select the kernel. Okay. So here you'll be able to see that I'm going to execute this. Okay. Now we are going to load all the train model, right? So how many train model we have? So load the ANN train model, then scalar pickle file, and one hot encoding pickle file also, right? One hot encoding. So we'll load this. So I'll go ahead and write model is equal to load underscore model. So here is what we have imported. See from TensorFlow.keras.models, import load underscore model. So here I'm going to write load underscore model, and here I'm going to take my model.h5 file. Okay. When I probably go ahead and use this, here you'll be able to see I will also go ahead and load the encoders and scalar. Now in order to load this, I'll go ahead and use with open. Quickly, let's go ahead and write label underscore encoder underscore geo dot pickle file. So this will be my pickle file. We'll be reading this time in the read byte mode as file. Because picking is nothing but it is a deserialized format, right? We can serialize it, we can deserialize it. So here I'm going to basically go ahead and use this label underscore geo is nothing but pickle dot load this specific file name. Okay. So here is what I get this particular pickle file over here. Okay. And similarly, I will go ahead and do the same thing for the gender and for the scalar. Okay. So here I have my gender and for my scalar. Now let's take some input data. So I will take some input data. So this I will go ahead and execute it. Label encoder underscore geo. What is the name that I've given? Label encoder underscore gender. Oh, sorry, it should be gender, not geo. Okay. Oh no, this pickle file should be my geo pickle file is what? One hot encoder geo, right? Not label encoder. So here I'll go ahead and write one hot. Let me rename this and let me copy this entire pickle file. Okay. So here I'm just going to go ahead and write one underscore hot encoder underscore geo dot pickle file. Now let me go ahead and execute it. Now it works absolutely fine, right? Now I'm going to take some example input data because based on this input data, I'm going to do the prediction. So here I've written credit score is equal to 600, geography, France, male, gender, male, age 40, tenure 30, this, there. Now when I'm giving this particular data, the first thing that I need to think is that how do I convert this particular value into numerical and this particular value into numerical, right? So and then after that, take all the numerical value and convert that into scale down that particular value using standard scalar. That is the reason I stored this in the form of pickle file. Okay. Now let's quickly go ahead and do this. First of all, I would like to see just think over it. Okay, you just try to think like how do we probably go ahead and apply one hot encoding in this. Okay, now you really need to think, guys. You cannot just think over it. Okay, I'll give you 5 minutes. Just pause the video. But what task you really need to do? Okay, this is my new input data I'm actually getting. And now with respect to this new input data, you need to think how can I probably take this particular data and perform or convert categorical features into numerical features. That is what you really need to think first of all. The second thing is how do you apply standard scaling, right? And then how do you do the prediction with respect to the model? Okay, that is what we are going to probably see. Okay, so first of all, pause the video and do it. Till then, I will start copying and pasting the code over here. The reason is very simple because I've already told you all these things. Okay, so here one hot. So let me just go ahead and write this label encoder geo. So I'll take this label encoder geo dot transform. Okay, and here you'll be able to see that I am getting some values over here, right? Key value pairs, right? Key value pairs over here. Now, when I get this key value pairs, I need to take out the information of this particular geography. So what I will do, I will say, hey, label underscore geo underscore encoder geo dot transform, and here I'm just going to use my input underscore data. Okay, I think it is input underscore data of geography column. Okay, and then this geography is basically my key. So let me just go ahead and copy and paste it over here with respect to this. So I will be able to get my key. Okay, and then finally I get it. I convert this into an array. Okay. Now, once you do this, again, I'll be using this label underscore geo, okay, dot get feature names out of geography, and this is what in my geo encoded that I'm actually giving, okay. So, if you see, this is for my new data that I'm actually able to get this, right? So, here it says reshape 1,1, okay. Let's see this, okay. Here, I'll just go ahead and use this as like this, then it should work, okay. Expected 2D array got 1D array instead, okay. So, array of France, I have given over here. I'm using this transform, okay. This is okay. I have to use one more brackets, because that is the reason how we got it, right? Now it should work. So here you can see geography underscore France, geography underscore Germany, geography underscore Spain. Guys, you may be thinking, how did I get to know that I have to use double brackets? See over here, if you go ahead and see with respect to the transformation that we did with the help of one hot encoding, right? So here, when we use this one hot encoding, here you can see that let's see where it is. Okay, here you can see I'm actually giving this one hot encoding over here, and I'm giving a list of features, right? List of features. And similarly, I also have to give a list of features over here. That is the reason this is one of my features over here, and I'm giving it as a list of features, right? So that is the reason I'm able to get it. Okay. So once I do this, then I will go ahead and combine this entire data, this data, with my input data. So I'll say input data dot reset index drop is equal to true, because if I do the reset index, I'm actually going to get that default index value, row index value. And I'm saying drop is equal to true, and then I'm adding this geo underscore encoded underscore df. Okay. So if I go ahead and see my input data now, input data, see. So guys, here you can actually see that I'm getting this particular error. Dictionary object has no attribute reset index because I just made one simple mistake after this particular code. See, the input data right now is in the form of key value pairs, right? I need to convert this into a data frame. So in order to convert this into a data frame, we will go ahead and write pd dot data frame. Let me quickly go ahead and use this input underscore data. Okay. And once I get this, this will basically be my input underscore df. And let's go ahead and execute this. So here is my input underscore df, and this is what is my entire row, right? Now this row only I have to pass it over there, right? Now for this particular row, what I really need to do, first of all, I need to do the concatenation, right? So this is my input underscore df, and I after converting this into my data frame, I should probably concatenate my geography column, right? So I'll do that concatenation right now. Okay, I've actually changed all the values with respect to the geography column over here, right? So it is basically into two array. We have actually done this, and I've actually got this geo underscore encoded underscore df. Now let's quickly encode my categorical variables. Okay. Now I will say, hey, let's take this input underscore df and let's convert first of all this gender, because gender also needs to be replaced with some label encoded value. So I'm just going to use this label encoder underscore gender. I'll say, hey, go ahead and do this transform operation on my input underscore df on which column? On the gender column. So this basically becomes my input underscore df. So if you go ahead and see my input underscore df now, the gender column will either have zeros or ones. So right now it is one, right? So this particular value may be a male before. Now it has basically got one. Okay? So this is perfect till here. We are able to get it. Okay. I've already done the one hot encoding for geography column. So I have this geo underscore encoded underscore df. Now what I will do is that I will quickly go ahead and do the concatenation. Now finally, let's do the concatenation with one hot encoded data. And along with this we also need to add the no need to add the gender data because it was already done the changes in input underscore df. Now what we'll do is that whatever encoding we have done for the geography column, right, we need to append all those columns inside this, and we need to drop this column. So here I will just go ahead and quickly write input underscore df is equal to pd dot concatenation. Let's concatenate our input underscore df. And from this, I'm just going to drop my geography column. Same thing, what we have actually done over there, right? So geography column, and this drop will be done with respect to axis equal to 1. And here, I'm just going to go ahead and write geo underscore encoded underscore df, right? So geo underscore encoded underscore df is nothing but this particular value, which has this one hot encoding of this particular feature. Okay, that is what we are basically going to do over here. And I have to also make sure that I put with axis equal to 1, otherwise it will become row-wise concatenation instead column-wise concatenation. Now, if I go ahead and write input underscore df, you'll be able to see that gender has got converted from male to 1, and here you'll be also able to see that my 3 features have got added on geography, France, Germany, and Spain. Okay. Now one more transformation is left. That is nothing but scaling the data. Scaling the input data. Now, in order to do the scaling part, so I will be using scalar dot transform, and here let's go ahead and write input underscore df. Okay, so this will basically be my input underscore scaled. Done. Okay. Now, if you go ahead and see this input underscore scaled, I will basically get all the data in the form of array, and all these values has basically got scaled. Okay. Now, finally, we need to just predict and see whether the person is going to leave the bank or not. So I'll go ahead and write prediction. In order to do the prediction, I'll just go ahead and write model dot predict. Here, give all the values over here like input underscore scaled. Okay. Get my prediction. So I will just go ahead and print my prediction quickly. So here you can see that I'm getting this particular value 0.029766 so and so, right? I can just go ahead and get my prediction probability also. So if I just go ahead and write like this, prediction of 0 of 0, I'll be able to see that I'm okay right now. Let's see this. I'll just go ahead and write prediction score probability. So here you'll be able to see 0.297, it is there. I'll go ahead and say this particular condition, if the prediction probability is greater than 0.5, the customer is likely to churn, otherwise the customer is not likely to churn. Okay, because this is the binary output and I'm just going to keep the binary output with respect to 0.5, but here I'm actually getting 0.029, so the customer is not likely to churn. So in this video entirely, right, how to do the specific prediction, I'm actually done it. Again, first of all, we have loaded all the pickle files. Then whenever we get any input data, first of all, we converted that into a data frame. Then we did a one-hot encoding of geography. Then we did label encoding for gender. Then we combined all those things. Then we created our entire data frame. Then we did the scaling, right? Again, we used the transform feature. Then we did the prediction. Then finally we got the probability. And then we finally checked whether the person is likely to churn or not, right? So yes, this was it. Now in my next video, what I'm actually going to do is that I'm going to deploy this entire content with the help of Streamlit in the Streamlit platform itself, right? So I will see you all in the next video. Thank you. So guys, till here now we have seen each and everything. We have trained our entire ANN, artificial neural network. We got the loss. The loss was also very less. We saw the loss in our tensor board. Visualized the entire diagram. We saw various parameters. Then we went ahead and did the prediction. We saved all the pickle file. We loaded all the pickle file, and we could also see the prediction was also happening. Everything we did it. Now it's time that we create one app.py file, and this is what I'm going to specifically use as my Streamlit web app. I'm going to probably create an end-to-end web app where I will be able to give the inputs and do the prediction from there. So let's go ahead, and here is my app.py. So first of all, I need to import all the libraries that I really require. So one is Streamlit, as a NumPy, TensorFlow, SQL.preprocessing. I'm going to use standard scalar, label encoder, one-hot encoder. So whatever things we specifically did in the prediction.ipy and file, we'll be doing it. Okay. So the first step is loading the train model. So I'll go ahead and write here .keras.models .load underscore model, and I will be giving my model.h5 file name. Then what we will do is that we will go ahead and load all our encoder, scalar, one-hot encoder, all the files itself. So here you have one-hot encoder geo.pickle file. Then I'm encoding this. So here you can see one-hot encoder underscore geo.pickle. I am loading this in the read byte mode. Then I have this pickle.load. Then I'm also loading this scalar, right? So all this pickle is specifically getting loaded, right? Now let's quickly start with the Streamlit app. So here I'm going to use a Streamlit app because I don't have to worry about HTML and all. So that is the reason I'm using this. So I'll go ahead and write st.title. Let me go ahead and write customer churn prediction. Okay. So customer churn prediction I'm going to use over here. Customer churn prediction. So this will basically be my title of the Streamlit app. Now, see, you know that how many types of inputs you're specifically giving. You're giving geography, gender, age, balance, credit score, estimated salary, tenure, number of products, has credit card, or number of products already mentioned, right? Is active member. So these are some of the features. So based on these features, I need to provide my input from the Streamlit web page. So for this, we will go ahead and create all these inputs. So for geography, I'll be using a dropdown, which will be specifically using all the categories. So categories of 0, whichever is the categories of 0, by default, it will get loaded over here. It can be 0, 1, 2, or any name that we're going to give over here. Then you have this st.select box, whatever values or with respect to the classes that I have, I'm actually able to get it over here. Then you'll also be able to see st.slider. I'm using a slider for age. I'm using a input for balance, credit score, st underscore number, credit score, estimated salaries again, number underscore input. Then for tenure again, I'm using a st.slider between 0 to 10. I'm also using a slider for number of products, and similarly has credit card and is active number. Okay, so this is what is the input data I will be giving from my user input. Then I will prepare this input data by taking it in some kind of dictionary, right? So we will go ahead and prepare this dictionary. So here I have my credit score. I'll take this data. Gender, I'm going to use this label encoder gender and use transform, and probably get the 0th value. Then age is here, tenure is here, balance is here, number is here, and each and everything, all the information are specifically here. Okay. Now one more information that is missing is basically our one-hot encoder, which is my geography column. So for geography, I will try to encode it in a different way, like how I did it in my prediction.ipy file. So I will just go ahead and encode this geography. So here is my geo encoded. I'll take this geography value, which is from here, right? This geography value. I will take this in the form of list. I'll convert this into an array by using one-hot encoder underscore geo.transform. Then I'm converting back into a data frame by taking the feature names over here, right? So this is what I'm actually specifically getting for all my values. Now I will combine this one-hot encoded with my input data. Right, so for that again, we'll go ahead and pd.concat. I'm saying input data reset index top is equal to true. Then take the geo underscore coded underscore df with access equal to 1. Same thing. What we did in the prediction.ipy file, right? Nothing is different. Then we're going to take this entire data and we're going to scale it also. Okay, so here I'm going to probably go ahead and scale it. Okay, then let's go ahead and do the churn. And with respect to the churn, I will just go ahead and write like this: if prediction churn, whatever prediction probability I'll get, I will just go ahead and compare and say, hey, if this is greater than 0.5, I'll go ahead and write it in my Streamlit app. Otherwise, I'll go ahead over here and say that hey, it is not likely to churn. Okay. So yes, this was it. I think everything was discussed already in the prediction.ipy file. So let me quickly go ahead and run it. Okay. So now this is the first time in order to run a Streamlit file, I'll just go ahead and write Streamlit run app.py. Okay, Streamlit. Okay, Streamlit. So once I execute it, I will just say allow access and let's load it. So my file is getting loaded. Let's see, I should not be getting any error. Now, right now here you can see the customer is not likely to churn. It is coming up over here. Let me print this particular value also over here, right? What probability we are getting. So I'll say, hey, go ahead and just print this. So tell here what I will do. I will just go ahead. Once I get the probability, right, I'm just going to go ahead and print it over here. So now let's go ahead and see. And let's reload it. Okay. So here you can see churn probability is 0, 0. So if I keep on increasing age, is this increasing? See, churn probability is increasing. Now you can add up any values. You want to select Germany, go ahead and select it, add any balance like 10,000, go ahead and add it. Here you can see churn probability. Automatically the calculation will happen. If I go ahead and add one credit card, one active member, so see, this value is also decreasing. So on the runway, it is probably predicting, my model is entirely predicting it, right? Now, this was a very simple end-to-end project where I've used customer churn prediction. And what you can do is I can select different values and do the prediction. Automatically this will do the prediction. Now quickly, I will go ahead and open my GitHub. Okay. And with respect to GitHub, I have to probably go and see the deployment, right? So what I'm actually going to do is that first of all, I'll go ahead and check in the code. You know how to do the checking with respect to the code. You can also use Git in it, but this project, I will just try to quickly upload it in my GitHub repository. So I'll just go ahead and create my GitHub repository. Let's say I'll go ahead and write ANN classification, okay, churn, and here I will just go ahead and create this, add a README file, general public license, go ahead and create a repository, okay? So once this is created, now in my next step, what I'll do, I will go ahead and upload all the code over here, and then we will go ahead and see how we will be doing the deployment this into a Streamlit app, okay? Streamlit cloud. That is what we're going to see in the next video. So I hope you like this particular video. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to the CNN end-to-end project. Now in this video, we are going to see how we are going to deploy this entire project in the Streamlit app. So Streamlit is a faster way to build and share data apps. I've already taken a module regarding Streamlit, which you'll be able to find out in this course. So let's go ahead and first of all sign in over here. Once I sign in, I'll be getting this share.streamlit.io. And here you can probably go ahead and create your own app, right? But before that, I will go ahead and upload all my code in my GitHub, right? So here, let me do one thing. Let me go over here. Let me reveal in the file explorer. Okay, so this is the file. I will quickly go ahead and deploy some of the files, right? So I will take this, okay, this, all the pickle file along with the requirement.txt. So you can even commit it directly from the GitHub using the command line, but I'll just directly copy and paste it over here. And I hope everybody knows how to do it, right? Because already GitHub session is already spoken about it, right? We have discussed about it, right? So I'm uploading all these files quickly. And here I also have my requirement.txt. So let's go ahead and put this requirement.txt over here. Okay. So yes, this commit, we will be doing it. Okay, I have to just go ahead and reload it. Just a second. Okay. So here you can see processing your files and all the files is over here. You have your readme file, app.py, pickle file, everything. Now let me go over here. So here you can see that you have your share.streamlit.io. Now Streamlit allows you to probably create your free apps just by integrating with the GitHub. So I will just go ahead and click on create app. It is asking me, do you already have an app? So I'll say yes, I have an app. It is in GitHub repository. So I will just go and search for this GitHub URL and I'll paste it over here. Okay. Once I paste it, so the branch is main. Let me just go ahead and say main file path. It should be app.py. And this is the URL that is basically creating. Okay. So step by step, you're doing it. Okay. ANN classification churn this particular .streamlit.app. So I'll go ahead and deploy it. So there is also something called an advanced token. If please provide environment variable and other secret key to your app using TOML file format, the information is encrypted and serves security during your runtime. Learn more secrets and changes. If you have any secret key, you can probably mention it over here and save it. Okay. That also we will be seeing as we go ahead. Okay. How to probably use some secret keys. Now I'll go ahead and click on deploy. Now, once I do the deployment, automatically see requirement.txt, all the files is there. This will actually do the deployment, do all the installation that is required, and to create the entire environment over here. And my entire platform will be ready just in another 30 seconds to 45 seconds, and then we are good to go to probably check out our application. So let's wait for some time. The reason why we really need to wait for some time is that because it will be doing the pip install requirement.txt, all those things. I'll also show you an example how to probably do it with the environment variables. But right now, let's focus on this and let's see how quickly we'll be able to do it. Okay. So it shows your app is in the oven, so it's getting warm. In short, your entire server is getting warm. So we'll wait for some time till this installation takes place, and our platform is once ready. And this is the URL which you can also use it and you can also access it. So I think now my app is ready, and here you can see it's running, stop share, everything is probably displayed over here. I think it should be displayed in short over here. So let's see. Yes, perfect. This is my entire app, and right now it is in the cloud of Streamlit. Now, if I go ahead and select any value that I want, it should be able to directly compute things, right? Directly, just by selecting values, it should be able to compute. And this entire thing is working with the help of ANN. Okay, you can select any of the values, and then you'll be able to get the answer. And this is with respect to just a runtime, right? So I hope you like this part of the video. This was it, and this was one amazing end-to-end project using ANN. I'll see you all in the next video. Have a great day. Thank you. Take care. Bye bye. So now let's go ahead and probably implement this regression problem statement. So what I will do, I will go ahead and write over here. And inside this folder only, I will be creating this because we are going to follow the same steps. So I'll go ahead and write I regression, IPY and B. I'll say churn regression, or I'll say salary regression. Okay. So this will be my file. I will go ahead and quickly select my kernel. Okay. Now, first of all, what are the steps that we will do? So initially, we will go ahead and import all the necessary modules that is required, like train, test, plate, standard scalar, label encoder, one-hot encoder, and pickle. Okay. So we'll go with the first step over here. Then after this, we will be reading our CSV file. So I'll go ahead and write read_CSV. And let me just go ahead and write this as churn modeling, churn_modeling.csv file. Okay. Now, if I go ahead and write data.head, I will be able to get my input over here. And this is my entire data set, right? As I said, estimated salary will be my output feature, and remaining all will be my independent feature. Okay. And that is the reason the output feature is a continuous value over here. So we are considering this as a regression problem statement. Now, after this, the next state that what I will do is that I will delete this row, number, customer ID, and surname. Whatever things we did in the classification problem, almost the same way we have to probably do this. Okay. So I've executed this. Then we will go ahead and convert this gender from female male to zeros and ones, because this here I'm going to use my label encoder. So for that, I will go ahead and create my variable label encoder gender. I will initialize to label encoder, and then I will go ahead and write data of gender is equal to label encoder dot fit underscore transform. Okay. Similarly, I will go ahead and do it for the geography column also, where I'm going to use one-hot encoder. Again, I'll use fit underscore transform. I'll convert this into arrays. I will get all my values. I'll convert this into my data frame along with my features. Okay. So if you go ahead and see your geo underscore encoded underscore ds, you'll be able to see, hey, I'm getting these 3 features. Okay. Then we are going to combine this one-hot encoded columns with my original data. Step by step, we're going to do this. So finally, you'll be able to see data.head, and we're also dropping the geography column. Now I don't have my geography column, and if you probably go ahead and see, my these 3 columns have got added. Perfect. Now we are going to split our data into features, into our independent features and target feature, right? Dependent features. So I'm dropping estimated salary from this, and all the remaining features will go in x-axis, and my estimated salary will go in the y-axis. Okay. So this is done. A bit of processing. Now I will save all the pickle file specifically for transformation, like label encoder.pickle. Then you have one-hot encoder.pickle. Then one more pickle that we are going to probably create is scalar.pickle. But the scalar.pickle we will specifically use only when we try to do the train test split. So let's go ahead and do the train test split also. So here I will take this code quickly. I'll just copy and paste it so that I don't have to waste more time on this writing the entire thing, because we're doing the same thing. If I was doing something else, then I could have probably done that. Okay. So here I'll go back to my salary regression. Quickly, I will go ahead and write code. Now quickly I'll paste it over here. Okay, train test split. And now I will go ahead and apply my standard scalar. Scale this feature. Quickly, salary. Okay. And here I will go ahead and do this. And this is done. Right. Okay, I'm getting an error. Do not convert string to me. Why? Because let's see my x value. Okay, gender is still male and female. Why? Because data of gender it is. Okay, fine. Data of gender. So if I replace this, what is my data over here? if you see the data, or let's me execute this once again. I think I missed something. So I'll quickly execute this. I'll remove this tree. I'll see this. Now let's go ahead and check my data. So my data is basically having zeros and ones. I think I missed one line of code in executing it. Then I'll do the concatenation, and finally I will do the concatenation. This is got executed. I have gender 0 and 1, x1, y. I get it, and I'm doing the train test split. And now it should do the scaling. Okay, so I missed one code, so that is the reason that was the issue. Now we'll go ahead and save all the pickle files. Scalar.pickle file, one hot encoder geo, and label encoder gender pickle file. Okay. Now it's the time to train our ANN with regression problem statement, right? How to train our ANN. Over here, that is what we are basically going to discuss. And this is the important thing. Remaining thing are almost same. I did not have to make any changes. Okay. Now let's go ahead and quickly do this. So first of all, again, I will import TensorFlow as keras. Okay. And then we are importing sequential and dense. So first of all, we'll go ahead and import this. So once this is imported, we are good to go and work with sequential and dense. And we are good to work with our entire neural network. Okay. So here we are executing this. Then quickly, let's go ahead and do this. Okay. So we will go ahead and build our model. Again, to build our model, we will use the same technique. Like first of all, I will say, hey, go ahead and take this exchange.shape of 1 as input here. This will be my input layer. Then we are going to apply an activation function. The first hidden layer will have 64 neurons. The second hidden layer will be having 32 neurons, and the activation function will be value. And the dense will basically have 1. Okay. Now when we are using 1, here we are not applying any activation function. When we don't apply any activation function, the default activation function that will be applied is called as linear activation function. Now linear activation function is specifically for regression. That basically means I'm not doing anything. Instead, I'm getting whatever output I'm getting, I'm using that. Okay. Now after this, we will go ahead and compile this model. Okay. So we will go ahead and write compile the model. Now for compiling the model, I'll go ahead and write compile model.compile. And here, first of all, I'll go ahead and write my optimizer. Let's say the optimizer is Adam for this case. You can also go ahead and initialize it from TensorFlow.keras, but I'm directly writing the keyword. Then my loss. Now this is what is the main thing that actually changes in regression. In loss, we will basically use mean absolute error. Okay. You can also use mean squared error, but here we are just going to use mean absolute error. It is up to you. And here the metrics that we are specifically going to use is nothing but it will be ME. Okay. Again, you can see the keras documentation. What all loss will specifically be happening over here. So if I go ahead and open Google, right, and if I just search for keras loss functions. Okay. So if I just go ahead and click on this, so it shows so many different classification problems. You have binary cross entropy, binary focus cross entropy, categorical cross entropy. Then you have binary cross entropy functions. All these things, right? For regression, you have mean squared class. See, this is what I've used, right? Means absolute error, right? Function. You can also use mean squared error, right? And already I've spoken about this even in machine learning. If you know machine learning, I think there all these things will be probably covered up. So you need to have that basic knowledge with respect to all using this kind of loss function. Okay. So now what I will do, I will use the metrics as ME, and then finally let's go ahead and display the summary. So I'll just go ahead and write model.summary. And when I display the model.summary, then here you can see this is my input. This is my input. So the total number of weights and bias are nothing but 2945. These are the trainable parameters that we have, right? Then I have dense 1, dense 2, and finally my output is over here. Okay. Now let's go ahead and train this particular model. Again, for training this model, I will go ahead and set my logs. Okay. So here are some of the logs. I'll say this is my regression logs. I'm using early stopping and TensorBoard, as you all know. So we are going to use both of them so that this folder will get, it will just try to, whatever logs is basically coming during the training, it will be coming over here. Then we are going to set it to early stopping also. So in the case of early stopping, I will be using validation loss. Like whenever we are training our neural network, you'll be getting training loss, training accuracy. You'll having training loss, then you'll also have validation accuracy and validation loss. But I really need to monitor the validation loss. And I'll keep the patient's value to 10. That basically means I'm going to see it for 10 epochs. Okay. And finally, we'll go ahead and train the model. Now, in order to train the model, I need to use this callbacks. So early stopping and TensorBoard callback. I'm giving extend my train. My epochs will be 100 and all, everything is there. Right. So let's go ahead and train this. And let's see how much will be the answer that I'll be getting. So epoch 1, here you can see ME. These all values are there. Validation loss, here also values are coming. Right. And these are keep on decreasing. Unless and until it keeps on decreasing, this epochs will be going on. Right. So the validation loss also you'll be able to see that it is decreasing. Okay. See, validation ME, validation loss. Unless and until it is not decreasing, right? If it is maintained in a similar manner, hardly there is not much difference, then it will stop. So here you can see in epoch 47 it has stopped because till here the loss was going down, but after this it was almost similar, right? So now my model is almost trained. Again, this is I'm actually doing it in my local machine. Again, I have a powerful CPU, so I'll be able to do it very much fast. Now let's go ahead and evaluate the model. Okay. Now before that, let me just go ahead and load my load extension TensorBoard. Okay. So I'll just go ahead and execute it. Then I will say, hey, go ahead and take this TensorBoard, and my directory will be regression logs slash. Let's see this particular folder. So here you have regression logs slash fit. Okay. So slash fit will be my. So once I execute it, here you'll be able to see that we'll be able to load the TensorBoard. Now in this TensorBoard, all the information regarding how the training has happened and all. So I'm getting some error. So this should be directory, I guess. Let's see over here. Okay. Again, you don't need to by heart it. You can see the documentation and you should be able to see this. Okay. You may be thinking that you don't know all these things. I'll definitely not by heart it. So you should also not do that. Okay. So this should be the log directory. And here should be my folder. Okay. Now I think it should get executed. Now we are launching the TensorBoard. Now this is good enough. It will take all the events from inside this and it will display it to you. Okay. And let's see, it is taking some time to load it. Quickly let it get loaded. I think for the first time I have to execute 2 times, but it does not happen in Google Colab. In Google Colab, in the first instance only, you'll be able to run it. Okay. So this is really, really good. So here I have got my entire information, which is amazing in the TensorBoard. Now see this entire things, right? Now if I go ahead and see with respect to regression, epoch versus loss. Wow, this graph looks amazing. See, it is going down completely, right? So loss is coming down. If you see mean absolute error, this is also coming down. I think this is an amazing graph. And this looks good. That basically means your epoch is going down. That the model is really performing well. Then here you have evaluation loss versus iteration. Iteration by iteration, how much it is basically getting reduced. Then you also have ME versus iteration. This also you can actually check it out, right? If you just want to see the validation has this epic loss and all. So epoch loss and all. So here you have your ME. You can probably zoom in and zoom out, and based on this you can check. You can also do something like this and check it out, right? So all this information from the logs you are able to see it. Okay. Now let's do one thing. So if you see ME and all, we will also try to evaluate this model for our test data. So let's go ahead and evaluate model on the test data. We're just going to check the accuracy, how good it is. So I will just go ahead and compute my test underscore loss and test underscore EME. ME, mean absolute error. I'm just going to write model dot evaluate x underscore test, y underscore test. Perfect. So now I'll just go ahead and print and I'll use a string and I'll say, hey, this is my test MAE, which is nothing but it'll be test underscore ME. So here you can see 5016 and more near to 0. If it is going on, we can probably say that our model is pretty trained in an amazing way. Okay, and this is done. And what you can also do is that along with this, I can also go ahead and save my regression.py file. So I'll say, hey, go ahead and save this as my regression model .h5 file. Okay. So once I do this, this entire model will get saved, and I have my regression model.h5 file, right? So almost we've done each and everything, right? Now, if you want to deploy this, you have all the h5 files, you have all the training that has been done. Now you can also go ahead and deploy it. So for deployment purpose, what I'm doing is that I'll give you the entire code. Again, with the help of Streamlit, you can deploy it. Let me just go ahead and create a file over here. Let me say Streamlit underscore regression.py. Okay. So I'll give you the code over here so that you can go ahead and do the deployment, and it's very simple. It's almost like this only. So here you can see all the things, and estimated salary can basically go ahead and compute it. Okay. See, we are loading it. We are creating some user input box. We are converting this into a data frame. We are doing the encoding. Then we are predicting the salary. Okay. You can do this entire thing. Okay. Let me see one more model, regression underscore model.h5 file. Okay, perfect. So I hope you understood this particular video. Again, it's more about how much you practice and how easy it was probably to train the entire ANN, that is artificial neural network, for classification and for regression. Now, one of the most common questions that has been asked is how do you decide how many hidden layers or hidden neurons you need to take? We need to discuss about that also because that is something very important. So in this case, it is very, very much difficult to just say that, hey, you probably need to just use this many number of hidden layers or this many number of hidden neurons. That is not possible. So what we do is that we basically apply a lot of hyperparameter tuning, like with respect to the number of hidden layers and with respect to the number of hidden neurons. And that is what I will be showing you in the next video, like how you can also come to a conclusion. And I'll show you one type of hyperparameter tuning, how we can specifically do. So yes, this was it from my side. I hope you like this particular video. I'll see you in the next video. Hello guys, so we are going to continue the discussion with respect to ANN. Now finally, we are going to discuss about a very important problem statement or question that comes in everybody's mind whenever you are implementing any application with deep learning neural networks. That is determining the optimal number of hidden layers and neurons for an artificial neural network. Okay. Now this can be really challenging and it often requires experimentation. However, there are some guidelines and methods that you can help in making an informed decision, right? So here are some pointers in order to probably come to a conclusion that how many optimal number of hidden layers and neurons you should probably use for an ANN. So the first point over here, it says that please go ahead and start simple, begin with a simple architecture and gradually increase complexity if needed. Okay. The second thing is that you can also perform grid search or random search. I hope everybody knows about this hyperparameter tuning. Using grid search or random search to try different architectures. So you can make different architectures and with the help of grid search or random search you can actually do it. Then you also have cross validation. Use cross validation to evaluate the performance of different architecture, like how we used to do in machine learning. And here is one more approach which is called as heuristics and rules of thumb. Some heuristics and empirical rules can provide starting points, such as the number of neurons in the hidden layer should be between the size of the input layer and the size of the output layer, right? Between that particular size, that many number of hidden neurons can be there in the hidden layer. Okay? And the common practice is to start with 1 to hidden layer. So obviously there are so many statements that I've discussed about, but we will try one approach where we'll also perform hyperparameter tuning. The hyperparameter tuning will be done in such a way that I will take various number of neurons, various number of hidden layers, and then we will try each and every architecture and try to see that which is the best model, which is probably coming out of it. Okay. So first of all, what I am actually going to do for this, I'll be using one very important library which is called as Keras. Okay. So here instead of TensorFlow, I'll also use one more library which is called as Keras, because in this Keras there is one very important module which is called as Keras classifier. Okay. And that actually helps you to perform this entire hyperparameter tuning. Just to find out which is the best model. So I'll quickly go ahead and install this library. Okay, so I'll go ahead and write pip install -r requirement dot. Oops, that is 5 it went ahead. So requirement dot txt. So let me just go ahead and do this, and I hope I should be able to get the installation of Keras. Let's see. Right now it has not given me anything, but let's go ahead and import things. So here I will be importing some very important libraries. One is grid search CV. See, one more additional library that we're going to use is grid search CV. Standard scalar label encoder, one hot encoder is done. We're also going to import pipeline. Then we're going ahead with Keras classifier, which is present in keras.wrapper.scikit-learn. Along with that, we're going to import TensorFlow Keras model for sequential, dense, and early stopping. Okay, so this is almost same. Nothing changes over here, but I think I'll be getting an error over here. Let's see if the installation is not taken place. Okay, so here you can see module not found, no module keras.wrapper. So let me go ahead and see in the Keras whether we have this wrappers or not. Okay, I don't know. We need to probably check it out. Okay, pip install -r requirement.txt. Okay, keras.wrapper. So let me just go ahead in Google and search for it. So pip install keras.wrappers or scikit-learn. So for this here, you have this particular module. Okay, so I will go ahead and use this module. So always remember, whenever you find this kind of errors, please make sure that you have a good sense wherein you will be able to find out which library we are talking about. So let's see Sky Keras. I think if this is the library that we are searching for, I think it should work. Okay, but if it does not work, then again we'll look for a solution. But we'll look for a solution together. Okay, so here you can see it has been successfully installed. Now I think it should work. Okay, let me restart the kernel. Okay, so let me see. I think we should not be getting an error now. Okay, we are still getting an error. So let's search for this itself, right? Let's search for this. So here, what I will do, I will go ahead and open my browser. I'll search for no modules keras.wrapper. Okay. So here it says this works for me. Another approach you can try. Okay, it comes with TensorFlow 2.12. Okay. From SkyPy. Okay, I can also use this. Let's see. I've also installed this, right? Instead of using this, I will use this. But I think now this should work. Okay. So I've used Sky Keras, and there I've actually done this installation. Okay. Now this is done. Now the next thing will be that I will go ahead and quickly import our pandas, use pandas, and read our CSV file. And here I'm actually going to write my John underscore modeling.csv. Here you'll be seeing how I specifically experiment with things. Okay, so here I'm actually going to get my data. Okay, then you know what all things you really need to do. Okay, so I will just try to copy and paste it over here, and I hope I don't have to make you understand. We're going to apply labeling encoder, one hot encoder. Then this is my entire data frame. Then we're concatenating. We are getting the independent features, and after this we're also going to do the train test split. Okay, because this is not that important because this all things we have repeated again and again. Okay, and then finally we are dumping all the pickle file, or we are saving all the pickle file. So quickly I will copy and paste it over here. Let me go ahead and write import pickle because I will also be requiring import pickle. Okay, done. So let's go ahead and execute this. Now here you'll be able to see my pickle file will get created. So this has got executed. Now we are going to create a function. Now see, here is where I will write my coding completely from scratch. So define a function to create a model, okay, and try different parameters. Try different parameters, okay. And here we are specifically going to use Keras classify. Okay. So I'll go ahead and write definition create underscore model. Okay. Here, what I'm actually going to do is that by default, I will be providing two parameters whenever we create a model. One is how many number of neurons I require. Let's say by default I'm giving 32 neurons if I'm not passing any value, and how many layers I want with respect to the hidden layer. By default, I'll give one hidden layer. Okay. So I'll create this function and I'll say, hey, go ahead and create my model is equal to sequential model. Okay. And then what I can do on top of this particular model, I can go ahead and add one dense layer. So I'll say, hey, go ahead and add a dense layer, and dense layer by default will be this entire neurons. Okay. And along with this, I'll say, hey, go ahead and apply my activation function, which is nothing but relu. Then here you'll be able to see that I'm also going to use my input underscore shape is equal to x underscore train dot shape. Please observe very carefully what I'm actually doing over here. Okay, so this is my input shape. So in the first layer, I'm basically adding this, right? Now I need to probably check, do I need to add more layers or not? Okay, if I give 2 to 3 layers, then we should also add it, right? So based on this parameter, I'll write a generic code, right? I'll say, hey, if I'm giving 2 to 3 layers, if I'm giving 3 layers also, along with this first layer hidden layer will be there. Okay, and here you'll also be seeing that at least this will be there with respect to the number of neurons that we have. Okay, then a generic representation, I'll say, hey, for dash in range of layers minus 1, because I have to probably create that many number of hidden layers now. Remaining hidden layers is layer minus 1. I'll go ahead and write, hey, go ahead and add model dot add and use the dense, and here use the neurons. The neurons will be same what I've actually passed over there, and the activation function will be nothing but it will be relu. Okay, so this is just my for loop. We will be keep on adding this particular layers. Finally, our output layer, I'll go ahead and write model dot add. Here we're going to use my dense, and here I'll use 1 comma activation is nothing but it will be my sigmoid. Okay, so I'm basically going to add this. And finally, I'll go ahead and write model dot compile, and let me just go ahead and use my optimizer, which is nothing but Adam. Okay, loss, since it is a binary loss, so I'll go ahead and use binary underscore cross entropy. And finally, you'll also be seeing that I'll be able to add matrix. And the matrix is nothing but it will be accuracy. Okay. And finally, I return the model. This is what we are doing inside this function. Okay. So whenever I usually call this particular function, I'm just going to give this parameters, neurons and layers, and based on that, I need to add how many number of hidden layers and all. First layer is added by default. We have also added output layer by default. We have also added which optimizer and loss we are specifically going to use. Okay. Now we will go ahead and create a Keras classifier. Okay. So I'll go ahead and write, hey, model is equal to Keras classifier. Let's go ahead and call this function. Now this Keras classifier is responsible in creating the entire neural network. ANN. So I'll say, hey, go ahead and call this create model function. I will say, hey, go ahead and pass epochs as 50. I'll say, let's pass the batch size is equal to 10. And here I'm specifically going to use verbose is equal to 0. Some information with respect to this. Now this is fine with respect to my model. My model is a Keras classifier, which is going to probably call this function and create an entire model. And then you need to run, the model needs to be run for 50 epochs, batch size is 10, and all the information. Now is very much important thing. So here I will go ahead and define my grid search parameters in the key value pair. So this will be neurons, like neurons, which how many neurons I want to play with every layer. It can be 16, 32, 64, 128 layers. I'll go ahead with 1, 2, 3. If you want to add more, you can go ahead. And I'll keep on playing with each and every parameter over here. So let's go ahead and let's remove the batch size because I just want to play with one batch size that is 10. Okay, so that I don't have to probably play with more things. And my training will also happen fast. This is just to show you. And epochs I'll play with 50 and 100. Right now, grid search CV is going to probably take this entire model. It is going to take this entire parameter grid, and it is just going to perform this cross validation that we are giving. And once we write grid.fit, I'm probably going to get the best number of parameters. So I'll probably, after the fit operation happens, we can just go ahead and print it. I can write grid underscore result dot best underscore score and best underscore parameter. Parameter will be like how many neurons, layers, or epochs I need to probably take this. Okay. So here our training will start. And grid search what it does. Every combination it will probably take. It will go ahead and see what loss is there, and whichever has the highest accuracy will take that particular parameter. So let's go ahead and execute this. So it is going to take time. That fast it is not going to happen. All these things because here now the combination is many, right? Okay. I did not. Okay, I had to probably print it. At least we'll not be able to see it. Okay, over here. So that is the reason it is just showing all these things. Okay, I'm getting some error. So guys, the error that we got, right? So what I will be doing is that along with this parameters, I will also be adding this layers equal to 1 and neurons equal to 32 because in this create model, I'm actually passing this particular values, right? Neurons 32 and layer 1, right? So that parameters also I'll be passing in my Keras classifier. Along with this, I also saw one more issue that is with respect to, let me just go ahead and have a look where it is regarding binary cross entropy. So how many time I have basically written this, okay? So I think now it should work fine. Let's run this. And finally, I'll also run this, okay? Now, the entire fitting will specifically happen, and here you can see 3 folds for each of 16 candidates, totally 48 fits that is basically going to happen. And now the training has already started. I think once the epoch starts with respect to this, we should be able to see more information. But just by using this verbose is equal to 1, we'll be able to see some information. Otherwise, and right now when I wrote this n underscore jobs is equal to -1, right? It is probably going to use all the cores out there, okay, of my system. But again, if you're trying to do this in your local, and if your local is not a good system, then it may take some amount of time, okay. Otherwise, please go ahead and do it in Google Colab. Google Colab is any point of time you will have some kind of GPUs that will be available. So what we'll do, we'll wait for some time, and then we will continue the discussion. So here you can see, oh, perfect, the epoch has started and it's running like anything. See, quickly. This is the power of a powerful workstation, right? I have a powerful workstation. I have GPUs. I have all these things done as a setup over here, and this is mainly to show you like how things work over here. So here you can see accuracy is there, loss is there, and finally the best accuracy that you got is nothing but 85% using epochs 100 layer 1 and neuron 16. So it's saying that hey, just go ahead and use one hidden layer and go ahead and use 16 neurons and just try to do it and try to find it, right? So when you use this, now you can go ahead and create your own custom your entire ANN with this many number of layers, and by this you'll be able to find out the best parameter. So I hope you were able to understand this. Once you get this information, then constructing an ANN becomes very much easy, right? So this is what we have actually discussed about determining the optimal number of hidden layers and neurons for an artificial neural network. Again, you can try out with different parameters, but we can use Keras classifier with respect to this. So yes, this was it from my side. I'll see you all in the next video. Thank you. Hello guys, so in this video I'm going to talk about NLP and deep learning. Till now, if I talk about machine learning with respect to NLP, we have discussed about various topics, and all these topics were involved wherein we were specifically working with text data, right? And with respect to this particular text data, if we really wanted to convert this into some vectors, which is some numerical representation, right? Numerical representation, we used various techniques. The first technique, if you remember, in NLP machine learning, we discussed about one-hot encoding, right? Then we went up with bag of words. Then the third topic that we discussed was with respect to TF, IDF, right? Coming to the fourth one, we discussed about word to vec. Along with this, we also saw about average word to vec. And we saw a lot of practical application. We took a specific data set and we tried to solve problems like sentiment analysis, and text classification, right? We did this kind of task, text classification in practicals, okay? Now, when we move one step ahead, that is nothing but NLP in deep learning. Now, as you all know, this text data are nothing but these are sequential data. And if I just give you a brief information about ANN, we learned about artificial neural network. And this artificial neural network, let me just go ahead and write it down again. This artificial neural network was used to solve various problem statements, specifically supervised problem statements like classification and regression, right? It was used to solve classification and regression. Now, when we use this classification or regression, here you can consider that I had some kind of data, and this data was nothing but it was a tabular data. What do I mean by tabular data? So this was nothing but it was a kind of tabular data. Now, when I say tabular data, let's consider an example. Suppose I have a house price prediction data set. Okay. In this specific data set, you will be seeing that I may have some features like what is my house size, what is my number of rooms in the house, and what is the price of the house. So when we have this kind of tabular data, okay, I'll be having a lot of key points over here. I will be considering this as my output variable, my dependent variable, and then I can probably go ahead and solve a regression problem statement for this because price is a continuous value. If my output feature is a categorical value, then I can probably solve it with the help of classification. Over here, all these features that you will be seeing, right? If I probably change the order of this particular feature, let's say, and for this, right, if I really want to solve with the help of artificial neural network, since I have two inputs over here, I may go ahead and create this kind of ANN, right? So let's say this is my input layer where I will be giving my two features. Let's consider this is my F1, this is my F2, and this is my Y, right? So here I will be giving my F1 feature, I'll give my F2 feature, and then along with this, I may have some hidden layers. Let's say this is my first hidden layer, and as discussed, all this input feature will be connected to this particular hidden layer over here, and over here, right? And let's say this is my output feature, and this will also get connected, right? And finally, I get my Y hat. So in the ANN, what we do is that we give this feature F1 and F2, and then we initialize some weights. Let's say this is W1, W2, W3, W4, W5, W6 weights, and here also we have W7, W8, W9, right? So based on these particular weights, we do forward propagation, okay, and then we do backward propagation. Now in the forward propagation, what we do, we basically take the input, multiply the weights, and then along with this, we also add a bias. So let's say this is B1, this is B2, and this is B3, and then we apply an activation function. And similarly, we do all the steps in all the nodes, and finally we get the Y hat. Then we calculate our loss. Loss is nothing but y minus y hat. Let's consider this as an example, y of I minus y of I hat. And then based on this particular loss, our main aim is to reduce this loss. So in order to reduce this loss, we need to change all these weights, and that usually happens in the back propagation. And that is how we basically solve this problem. Now, one very important point in ANN is that if I interchange this feature, let's say that if I change the order of this feature, let's say that if I initially I had this F1, F2, and Y, let's say my first feature was house price, and the second feature was number of room. Even though I make this feature as F2, F1, then also we will be able to train this particular model with the help of ANN. Now, one very important information about tabular data is that here, tabular data, you have features, you have some values, like how we have our data in our CSV format and all. And the second thing is that over here, your sequence of data does not matter. Okay, so this is very much important point. Your sequence of data does not matter. That basically means you can change the sequence, right, while training it. You can keep F2 first, F1 first. Let's say if you have F3 feature, I can keep F3 first. Because at a time, this entire row will be sent for training, right? So here we are giving all F1 and F2. So this will be for my first row. Then for my second row, right? Based on the batch size, we will be giving this entire data and doing the forward and the backward propagation. Now this is fine, right? And this is with respect to ANN. Now if I consider the second example that we have seen already in our session, that is nothing but it is about CNN. CNN basically means convolutional neural network. Okay? And here with respect to convolutional neural network, you use this for, so basically over here your data will be in the form of images. It can be in the form of images, it can be in the form of video frames, right? And here, most of the tasks that you specifically do, right? Some of the examples are like image classification, right? You have image classification. Let's say you want to do object detection. So you use some higher variants of CNN, like RCNN, you have YOLO, all these kind of algorithms you have, right? So this is kind of task you'll be able to do with the help of CNN, okay? Now this is fine, and this is also fine over here. Now let's talk about the third thing, and that is where we're going to come up with. That is nothing but NLP and deep learning. The third thing that we will be specifically talking about is for a data that is of sequential type. Sequential type. Or I can also say this is nothing but this is my sequential data. Now, what exactly is sequential data? Some of the examples that I will be considering over here. Let's say this is one of the examples that I will say. I have a data set which involves some kind of text, okay? And or let me just take one example over here. I'll just go ahead and write it down. So let's take this example, text generation. Now, text generation is a kind of application where I will be having some kind of input, right? Let's say if I say, hey, how are, or I say, this is a apple juice, right? Now, juice, I'm not giving the word, right? So what my model should be able to do is that it should be able to generate this specific word. It can say, hey, it is an apple juice, or it is an apple pudding, something, right? So it should be able to generate this particular output. Now, in this kind of scenario, the data that you specifically have is a sequential data. The sequence is very much important to understand context of this sentence, right? So this kind of data is basically called as sequential data. Let's take one more example. The second example that I will be probably taking is nothing but your chatbot conversation. Now, in your chatbot conversation, what you do is that you basically have a Q&A chatbot, right? Now, in Q&A chatbot, let's say if a user is asking any question, and based on this question, the chatbot should be able to give an answer. So here, both on this question and answer, the sequence of information is very much important. The sequence of text is very much important. And based on the question, since the chatbot is answering, the context of the question is also very much important. Okay, so that is where you can consider this as a chatbot conversation. Is another one example where our data set will be a sequential data itself, right? Because see, what is a sequential data? I'll just give you a basic definition. Okay, sequential data. A sequential data is something like this. If I take one example, I go ahead and say, hey, the food is good, right? Now, when I see this data, right here, the sequence of this data is very much important because based on the sequence, the sentence is making some meaningful meaning over here, right? If I change the order, if I just go ahead and say, hey, good, the food is. If I go ahead and write this kind of conversation, if I probably see the sentence over here, right? Over here, based on the sequence of these words, the meaning may change, right? The meaning may change, right? So this is just one example of sequential data where ordering of this word is very much important because it makes sense of the entire sentence itself, okay? So if I probably consider one more example with respect to the sequential data, one more application, let's go ahead and see. This is nothing but, this is called as language translation. Language translation. Now see, in language translation, what do we exactly do? Let's say I have a text in English. I want to convert this into French. Okay. I want to convert this into French. And I hope everybody is in Google Translation. As soon as I keep on writing the word in English, automatically you'll be able to see that it'll be able to generate the sentence in French. So over here also, sequence of information is very much necessary. Okay. One more example. I'll be giving you tons of examples now. This is nothing but auto suggestion. I hope everybody has been using LinkedIn, has been using Gmail, right? Over there, whenever you're writing a mail, whenever you're writing a message, you will be able to get auto suggestion with respect to the sentences, with respect to the mistakes that you do. Okay. So this is also one very good example. The fifth kind of example that I'm actually going to take, let's consider my sales data. Now, what is so amazing about this sales data? Your sales data is based on date time, right? So if I go ahead and plot this entire data, let's say this is my date and this is my sales, right? So I may have this kind of graph, right? It may be increasing or it may be decreasing, right? So this is basically my sales data, right? And over here also, this is a sequence of information, right? Why I'm saying you, because one of the use cases that you'll be seeing is something called as sales forecasting. And probably we can solve this particular use case by just taking the previous timestamp and we need to predict the future date, what will be the sales, right? So that kind of forecasting can also be done, okay? So in short, I've given you so many different examples to just make you understand about sequential data. Now, in order to work with a neural network, and in order to work with this kind of sequential data and probably use a neural network, we cannot directly use, okay, here I'll write, can we use ANN to solve this problem? Okay, can we use ANN to solve this problem, right? This is what I'm going to discuss in my next video. But I hope in this particular video, you have understood, right? Since we're discussing about NLP in machine learning, okay, sorry, NLP in deep learning, I have to give you a brief idea about what does exactly ANN do, CNN do, and then we discuss about sequential data. Now my next question is that, can we use ANN to solve this problem which has sequential data? And this is what I am going to probably discuss about in my next video. While we are discussing this, I'll also give you a brief idea, like what all things we really need to learn in NLP in deep learning, okay? So just to give you an idea, what all things to learn over here. So NLP in deep learning involves a lot of amazing topics, right? A lot of amazing topics. And this will turn lead to right now, generative AI is in trend, right? Generative AI is in trend, LLMs are in trend, right? Multimodals are in trend, right? If you really want to learn this, right, this is the prerequisite. You really need to know each and every architecture with respect to all the neural networks that we specifically use for NLP techniques in deep learning, okay? So first topic that we will be learning in NLP in deep learning is nothing but it will be about simple RNN, right? After learning simple RNN, we will be seeing what is LSTM and GRU RNN, okay? So this will be my next RNN that we'll be discussing. Then after this, you will be seeing that we'll also be learning about bidirectional RNN. Then once we complete this, the next step will be that we will go ahead one step more, and then we will be discussing about something called as encoders and decoders, right? Encoder and decoder. And finally, after doing this, we'll be seeing about what is self-attention. And then we'll also be seeing transformers, right? Now, after we see all these things, right now, most of the variants of LLM models that you will currently see in the generative AI field, specifically of different types of transformers, right? And that is where you'll get a brief idea about how to work in generative AI, right? Specifically with the help of LLM models, like you know about OpenAI LLM models, right? So we'll be discussing this step by step. We'll be understanding the architecture, we'll be solving some problem statements, and we'll be learning this, okay? So this was a brief idea about NLP in deep learning. And trust me, guys, these are like a prerequisite to probably enter into the generative AI field and work with LLM models. Even in interviews, they still focus on all these kind of questions. So we will be solving step by step. Each and everything we'll be discussing. We'll be understanding theoretical intuition, and we'll also be understanding the practical implementation. So yes, now in our next video, we'll try to answer this question: can we use ANN to solve this problem statement with sequential data, right? So yes, this was it for my side. I will see you in the next video. Thank you. Hello guys, so we are going to continue a discussion with respect to NLP in deep learning. In my previous video, I was asking you a question: can we use ANN to solve this problem with respect to the sequential data, right? Now, when I said that, I know you may have got confused, like what kind of problem statement we are solving. So let us go ahead and let us see the problem statement, okay? So let's consider that I have a data set, and this is my data set over here. And with respect to this particular data set, let's say I have something called as text, and this is my output, okay? The problem statement that we are solving is something called as sentiment analysis, okay? Sentiment analysis. Let's say one of the data set is like, the sentence is something like this: the food is good, okay? And let's say here I have one. The next statement that I have, or next sentence in my data set I'm writing, the food is bad, and here I have 0. 1 basically means good, 0 basically means bad, okay? And then third one that I have is nothing but the food is not good. I have 0 over here. Let's say that in my training data set, I have this all sentence, okay? Now, how do I solve this with the help of ANN? Yes, can we solve it with the help of artificial neural network, right? So let's consider that over here. First of all, we will go ahead and see. And again, first step in this is that regarding your text pre-processing, if I really want to solve it with the help of ANN. So in a text pre-processing, what we do is that we have to convert our text into vectors. And we have seen a lot of various ways, like bag of word, one-hot encoding, TF, IDF, and all, right? So let's consider that I take this particular data set, okay, and I will first of all go ahead and design my neural network also, okay, ANN, that is artificial neural network. But before that, let's see that how many unique words I have in this. Let's say I have 1 unique word, 2, 3, 4, 5, and 6, okay? I have 6 unique words, okay? And in this, I will not consider is because I consider this as a stop word, okay? So I'm not just going to consider is. So over here, the number of unique words is 1, 2, 3, 4, 5. I'll also not consider the because this is a stop word, okay? So let me just go ahead and use this all remaining words. 1, 2, 3, 4, okay? So 4 words I have, so that basically means my vocabulary size vocabulary in this particular case is 4 vocabulary size. Okay. Now in this vocabulary size I have 4. That basically means my entire corpus, word corpus, is nothing but 4. Okay. So as you all know, if I want to convert sentence by sentence from text to vectors, so you have something like bag of words, right? In bag of words, what we actually do, right? We basically try to convert every sentence into a vector, right? How do we convert it? Let's say over here I have all these words, so I'll take this food, good, right? So I'll say food, good, bad, and not. Okay, bad and not. And with respect to sentence 1, what we do is that wherever food is present, right, in this particular sentence, I will make that as 1 and remaining all as 0. So food and good, where it is present, that will be 1, 1 and remaining all will be 0. So here for sentence 1, if I convert this into vectors, it will be 1, 1, 0, 0. Okay. Then in the sentence 2, you'll be able to see over here the food is there, bad is there. So this will basically become 1, remaining all will become 0, and this will become 1, and this will be 0. Okay. I'm just using the technique of bag of words to convert text into vectors. Similarly, the third one is saying that the food is not good, right? So food is not good with respect to sentence 3. So I have this one, not is there, and good is there. So this 3 will basically be having 1. So this is just a simple way of converting a word into vectors, right? And here you can see that I have some fixed vector size, right? I have this fixed vector size. So this is one way. Okay. Now, one very important information that we can see from this particular sentences and the text that we have converted that into vectors. Okay. One is like when I probably create my artificial neural network. Okay. Here you'll be able to see these are my inputs that I have to give to my neural network, right? These are my inputs that I give to my neural network. And since these all are text data, text data basically means the sequence information is important. Sequence information is important. Again, I'm stressing on this. But here, do you think this all words are in sequence? No, food is coming first based on the frequency. Food is over here, maximum number of time food is present, right? So food is basically written first, then good you have, then bad you have, then not you have. So these words are exactly not in sequence, right? And when we use this particular technique and when we try to train it with the artificial neural network, first of all, we are losing that sequence over here. When we lose the sequence, that basically means the meaning of the sentence is lost. Meaning of the sentence is lost because the context information is lost, right? So that is the reason why I say the sequential information is super important, and we are not able to manage this. This is the major one problem. Here, if I go ahead and even use TF-IDF, right? In TF-IDF, I may do the calculation and I may get different values, right? Even in word2vec, if I use word2vec, I may be able to fix this into some dimensions, right? Just by considering every word will be converted into one dimensions, right? The dimension size may be 300, it may be different sizes. But at the end of the day, we are losing some sequence information, right? Over here. Now, very much important thing. If I'm training my neural network, right? Let's say this is my ANN. Let's say over here, I can see that the maximum number of words are 4. So I'll give my input sizes 1, 2, 3, 4, right? I go ahead and create my neural network. Let's say in my neural network hidden layer, I have 3 neurons. And finally, since I have just one output, this basically is connected. This input layer is connected to all the hidden neurons. This is basically connected to this particular output layer, right? And this is also connected to every hidden neurons. This is also connected to every hidden neurons, right? So this here you can see that, hey, fine, this is how my artificial neural network looks like. The first problem you have already discussed, that sequence information is getting lost. Okay, now second problem. Here, with respect to the text, right, the food is good. Yeah, I will be sending all this information. Like let's say my first sentence is basically 1, 1, 0, 0. So I'll be sending my 1, 1, 0, 0 over here, right? This is what is the entire information that I'll be sending over here, right? While training. This will be my input. Okay. Just a second. So this will be my input that is basically getting sent. Okay. And here you can see this is my input layer. And this is my hidden layer 1, and this is my output layer. And finally, I get my y hat. Now, what is one problem over here that you see? In case of whenever we work with text data, it is always a good idea that whenever I have sequence of information, let's say over here, I go ahead and write the food is good. To solve any use cases, we have to give one word at a time. So let's say during timestamp 1, I just give this the word, then forward propagation should happen and backward propagation should happen. Then in my second timestamp, the next word is food. I have to give that. In my third timestamp, the next word is. Then in the next timestamp, my next word is good. So it is always a good idea that whenever you have sequential data, you really need to give based on a specific timestamp, not all at once. Now in this particular scenario, I'm giving this entire sentence 1, all the words all at once as my input. So here also input is going, here also input is going, here also input is going, here also input is going. And by this, the sequence information will also not be maintained, right? And that is the reason the neural network will not be able to efficiently train themselves, right? In case of sequence of data, sequential data, it is always a good idea that we pass one word at a time to our neural network, right? And this is a major problem, right? Because just by using ANN, what we are doing, we are just directly giving all the information, then we do forward propagation, then we do backward propagation. And why I'm saying you should not give all the words at all at once? Because let's say that if I want to solve a problem of language translation, now in the case of language translation, I have to give one word by one, right? If you know about Google Translation, right? If you have used Google Translation, then let's say I want to convert from Hindi to English, or let's say English to French. Now, as soon as I give one word, right? Let's say I say the, then it should automatically give you that French the word, right? Then if I keep on adding words, then it should similarly go ahead and translate in that way. So it is always necessary that you provide this information in a sequential way based on the timestamp, not all at once. So this is one more major problem, and that is the reason we cannot just directly use ANN. Two important information. First of all, it is not able to maintain the entire sequence. And the second thing is that it is giving all the words to the neural network all at once for a specific sentence. Okay, and that is where we will be using a new kind of neural network, which was proposed by the researcher. That is nothing but a simple RNN. So simple RNN will basically be used, and if you don't know the full form of RNN, it is nothing but recurrent neural network. So we will be using recurrent neural network to solve this problem. So here, in the case of neural network, our data will be sequential. Now, just to give you a brief idea, how does a recurrent neural network look like? Okay. So first of all, I will go ahead and take ANN. So in the case of ANN, I will be having an input. So let's say this is my input, and this will get as an output. Okay. So this is my hidden layer. This is my hidden layer. Okay. Now with respect to this, I'm giving my input. Over here, some processing will happen in the hidden layer, and finally I'll get the output. If I want to expand this, let's say in my input layer, I have two inputs. Let's say this is my two inputs. Let's say in my hidden layer, this is my three neurons in my hidden layer, and finally I have my output layer. So I can also represent this in this way. So this will be connected over here to all the neurons. This will be connected to all the neurons over here, right? And finally this will be connected to my output layer. Okay, so this is my output layer, and this is my input layer. This is my input layer. So here, this representation that I've actually shown is nothing but this only. I have my input, I have my output, and in middle, I have this hidden layers with hidden neurons. That is how an ANN looks like. Okay. Now, in the case of RNN, how it is different from ANN and why it is suitable for, you can just consider for a sequential data, because if I go ahead and see the neural network now, the neural network looks something like this. So initially, I will be having my input layer, then I have my hidden layer, and then I have my output layer. This is perfectly fine. But along with this, we also have a feedback loop. Okay. Now, what does this feedback loop basically say is that whatever output I am getting from my hidden layer neurons, it will be sent to that particular neuron and to all the other neurons in that hidden layer. Okay. So if I go ahead and expand this, now see the magic. Okay. Now if I go ahead and expand this will look something like this. Let's say I have two inputs, then I have three neurons in my hidden layer, and finally I have one output, right? Because to solve this problem also, I'll be requiring this neural network itself to solve this kind of data set problem, right? Because here I have this output as 100. Okay. So here you'll be able to see that I will be having one final output over here. Okay. Let's say we go ahead and connect this. Okay. We go ahead and connect this. Now this is important, okay? Because I'm expanding it. Okay. So this is very simple. Expanding from input till the hidden layer is very simple, and connecting hidden to the output also is very simple. This is nothing but this is my ANN only. Okay. This is my ANN only. Now see the magic. Okay. Now see the magic. I will just go ahead and connect this. I will just go ahead and connect this. Okay, so let's connect this. So this is my input 1, input 2. This is my hidden layer. Now, obviously, ANN is looking similar like RNN. Now, we have to think about this feedback loop. Now, this feedback loop will be like this hidden layer will be sending its output back to its node. Okay. Not only that, this hidden layer will also send the feedback to this particular node. Along with this hidden layer will also send the feedback to this particular node. Okay. That is what it is saying. Sending the information, sending the output back to itself, right? To all the hidden layer it will be sending. Okay. Similarly, you'll be able to see that the second hidden layer, the second neuron in the hidden layer, will also sending in the loop, and it will also send to this hidden layer, to this hidden neuron, along with this to this hidden neuron. So you're just passing the information to each and every hidden neuron. And finally, here also you have in this neuron, here you have the self loop, feedback loop, and then this information will also be sent to this, and it will also be sent to this. So in short, whatever output we are getting after we probably take the inputs along with the weights that are initialized, then we add a bias, then we add an activation function. Whatever output is basically coming, we also share it with all the other hidden layers. Okay, all the other hidden neurons in the hidden layer. Okay, and with respect to this particular neural network, all the inputs that is passed. Let's say this is my input. The food is good. The food is good. Here we will be doing some kind of numbering based on sentence. Okay, sentence and words. Let's say this is my first sentence. So I will go ahead and note this as x11. x11 basically means first sentence and first word. Then you have x12, first sentence and second word. Then you have the first sentence and third word, and first sentence and fourth word. In the case of RNN, we pass an input at each timestamp. That basically means at t is equal to 1, we will be passing the input as x11. So here we'll be seeing at t is equal to 1, we will be passing x11. Then as t is equal to 2, we will be passing x12. That basically means when x11 is basically passed, okay, whichever information it has with respect to the word that we are having, right? When it is passed, right, it goes to all these hidden neurons, it does the calculation, and whatever output is there, it will be shared with all the other hidden neurons that are present in the hidden layer. Then in the t2 step, what we do is that we basically go ahead and write we go and pass this next word, that is food. Okay, so here we initially pass the, then food will be basically passed, all the operation will take place. Then t3 is equal to 3, x13 will be passed, t is equal to 4, x1 will be passed, right? That is how each and every words are passed from a specific sentence based on timestamp. In ANN, we used to pass each and everything at the initial stage while doing the forward propagation, but in case of RNN, we just pass one word at a time. Okay. Now in my next video, here I've just shown you the basic example of, just to make you understand the difference between ANN and RNN. Okay, and if I want to probably expand this, this will also look something like this. Okay, I'll just give you one more brief unfolding technique that we specifically use. It looks something like this. So this is my neuron. Okay, this is my hidden layer. So now, what happens in RNN? We create a self loop. Okay, sorry. So this is nothing but this is a self loop. Okay, here also we pass some information. Okay, now if we unfold this with respect to timestamp, understand this is my hidden layer. Okay, so here I will just go ahead and write like this. So this will be my input, this will be my output, and then I have this, and then this output will go to the next timestamp. Okay. Then again you have this and you have this. So that basically means during timestamp t is equal to 1. Here I'm going to pass my x11 word of my sentence 1. See, my sentence 1 is something like this and my output is 0 or 1, right? Let's say this is 1. So what I will do in my t is equal to 1, I'll be passing x11. And then at t is equal to 2, I will be passing x12. At t is equal to 3, I will again be passing x13. Okay, at t is equal to 3. And finally, at t is equal to 4, I will be passing my last word. So based on the number of timestamps, you'll be seeing that each and every word will be passed. Okay. Now what operation is going to happen, that we'll discuss, right? But here you can see that whatever output is coming, it is also being shared with all the hidden neuron. But at t is equal to 2, I will be sending my second word, and it will also have the first word context, right? The entire RNN will have the first word context also, and that is how the previous context information will also be retained by the RNN, right? Please observe this, right? At t is equal to 1, I'm passing x11, right? So when we pass the first word, all this propagation will happen. Let's consider that I'm just going to pass one neuron. So this will be only one input, okay, not two, one input. So once I do this, everything will be happening. Once the input will be multiplied by all the weights over here, then a bias will be added. We'll talk about how the forward propagation will happen. But once I get this particular output, it needs to be shared with all the other neurons. So it is being shared with all the neurons over here, right? All this information, all this output is basically shared with this particular neuron. Now this neuron, based on the timestamp, and this neuron is the same hidden neuron, right? Based on the timestamp t is equal to 2, has the previous information of the first word, that is the, right? Now in t is equal to timestamp 2, I'm getting the second word, food. So it has the previous context, it has the current context, and again, this operation will take place. What kind of operation? I'll talk more about it as we go ahead. But this is just a brief idea to talk about how a simple RNN architecture looks like and how it is different from ANN. Okay. So in my next video, I will break down this entire diagram again, okay, and show you like how detailed it will be looking like. And along with that, we'll discuss about this architecture more in a better way. This is an important architecture, so I will be taking more couple of classes to make you explain each and everything. Okay. So yes, this was it from my side. I will see you on the next video, and we'll continue the discussion with respect to the architecture of RNN. Thank you. Hello guys, so we are going to continue the discussion with respect to simple RNN architecture, and in this video we are going to discuss about forward propagation in simple RNN, right? Already in our previous video we just saw about the entire architecture, how does a basic RNN looks like. I hope you have understood this and what is this unfolding technique, okay? Now let's take this example. The foot is good, so we will try to solve this problem with the help of simple RNN. We'll understand how does the forward propagation actually happens with the help of RNN itself. So let's consider that here I have all these words, and with respect to this particular words, first of all I'm just going to go ahead and find out how many unique words are there, okay? So let's say the number of unique words are the, food, okay, good, and I'll say bad, and I can also say not, okay? So total number of words are 1, 2, 3, 4, 5, okay? Now let's consider, initially I need to convert this words into vectors, okay? Now there are multiple ways to convert it. We can also use word to vec, we can use multiple techniques, okay? But I'll just use the most basic one, which is called as one hot encoding, okay? So we will go ahead and use this one hot encoding. Now one hot encoding, what it does is that it converts each word into vectors, okay? So let's say if I have this the word, okay? Since I have 5 words, so wherever the is available, that will become 0 and remaining all will become 0. Right? So this basically becomes my first word. Okay. Wherever the is available, so that actually becomes 1 because the number of unique words are 5. 1, 2, 3, 4, 5. Right? So wherever the is present, so that actually becomes 1, remaining all will become 0. Okay. Similarly, if I go ahead and consider with respect to food, wherever food is present, that will become 1, remaining all will become 0. Okay. So this actually is my another vector for the food word, for the word food. For my next word that I have over here is let's say good, because I'm not going to consider is because it is a stop word. So wherever there is good in the word, this third one will become 0, and then remaining all will be zeros itself. Sorry, third one will become 1 as a vector, and remaining all will be zeros. Right? And finally, you have this bad. Bad basically means let's say this is my fourth word, so this will become 1, and remaining all will become 0. And finally, when you have not, this will be 1, and this will become 0. So this exactly is the entire vector for my sentence 1. Okay. So for my sentence 1, this is how my vector looks like. Now, I need to train this entire sequential data with my neural network, that is RNN, and probably make sure that how to do the prediction. We'll probably see how to do this, how to train this particular neural network for this particular classification problem. That is nothing but text classification. Okay. So now we will go ahead and consider our RNN, right? Now in this case, as you have seen, the generic architecture of RNN is nothing but it will be something like this. So I will be having my input. This will be my hidden layer. This will be my output. Okay. So input, output. Along with this, I will be having a feedback loop. Okay. And this feedback loop is nothing but it will be sent to each and every hidden neurons in that particular hidden layer, all the information, all the output. Okay. So here, first of all, you need to understand how many inputs I need to give, right? Because at a time, I will be giving one word, right, to my neural network for the training purpose. And every word is represented by these 5 vectors. So here, I'm just going to consider this 1, 2, 3, 4, 5. So this will be my 5 inputs that I will be giving to my RNN neural network, okay? Now in my hidden layer, let's consider that I'm just going to use 3 neurons, okay? So here, I will be considering 1 neuron, 2 neuron, and 3 neuron, okay? And timestamp is equal to 1. I will be passing this word, which is nothing but x11, x12, x13. Okay, so I'll be passing this all words, right? 1, 2, 3, like that, right? All the words will be passed. So here you can see for the first word, this will be passed over here as x11. And I know what is the vector? It is nothing but 1, 0, 0, 0, 0. Okay, this is the vectors that I'm going to pass through these inputs. So this basically becomes my input layer. Okay, now this will basically get connected to all the hidden neurons, right? Over here, then you have here, then you have here. So this will basically get connected to all the hidden neurons. Okay, perfect, right? Now, this is my hidden layer, as you all know. This is my hidden layer 1. But with respect to an RNN, we need to have a self loop, right? What does this self loop basically mean? That whatever is the output, I will be passing it to itself and all the other hidden neurons. So let's consider that. I will now go ahead and use timestamp t2, and here I'm going to pass my another word that is nothing but x12. Okay. Now in this case, when my x12 is passed, 3, 4, 5, right? X12 is the word that is food, and here I have my another neuron that is with 1, 2, and 3, right? Sorry, 1, 2, 3. I will just go ahead and use the same hidden neuron over here. 1, 2, and 3, right? This needs to pass over here, right? And when I'm passing this information at t is equal to 2, as you all know, this information that we have computed at t is equal to 1. So here we'll take this input, multiply by all the weights, and whatever output I get, it will be returned back with the help of self feedback loop itself. Okay. This in short is what is basically happening is that this input will probably go over here. Sorry, this output from this will go to the next timestamp node. Then this will also go over here, and this will also go over here, right? So this is 1, right? This is what is basically happening, right? At t is equal to 1, like when we use the self loop, right, or feedback loop, what we are basically doing, whatever output is actually coming up, we are sending it to its all the hidden neurons, and that is what is basically happening at timestamp is equal to 2, right? And similarly, you'll be able to see that again. We will go ahead and pass this information to this. We'll go ahead and pass this information to this, and we'll also go ahead and pass this information to this, whatever output I'm actually getting. And finally, you'll also be seeing that this will also get passed to my third node, and this will also get passed. The output will also get passed over here. The output will also get passed over here, and here also you'll be able to see it will get passed over here. So that basically means that timestamp t is equal to 2. This hidden neurons will also have the context of this word, that is the. Over here, this word is nothing but food, right? So when this food is basically passed in the neural network, in the timestamp is equal to 2, this context, this neural network, this hidden layer will also have the context of the previous word. And similarly, at t is equal to 3, same thing is going to happen, right? This output will be passed to the next hidden layer, right? And here I'm just going to give my inputs, my next word. And similarly, when the sentence ends, this entire RNN is basically going to have the context of all the previous words from timestamp is equal to t is equal to 1, right? Now, this is basic funda. I know the diagram looks quite messy over here, but you can just understand in this way that after calculating whatever over here, whatever operation is specifically happening with respect to the forward propagation. In forward propagation, what do? We take this inputs, we multiply by the weights, and then we add a bias to this hidden neuron, and whatever output is basically coming, we are passing it to itself and the other hidden neurons at timestamp is equal to 2, so that they get the context information, right? And that is how we go ahead and do our forward propagation, right? Now, this is how you can easily do each and every step. So in a generic way, if you also want to probably go ahead and write it, it is very much simple. So I can go ahead and say, hey, let's see, this is my 5 inputs that I'm passing. This is my hidden layer, okay? This is my hidden layer with any number of neurons. Okay, so right now in this case, I've used how many? 3 neurons, right? And finally, this is my output. So this will get passed, this will get passed, this will get passed to everyone, right? Similarly, this will get passed to everyone, this will get passed to everyone, okay? All the hidden neurons. And finally, we get the output over here. It will get connected to this, it will get connected to this, it will get connected to this, but there will be an additional feedback loop that we will be using. And finally, we get our output, right? So input 1, input 2, input 3, input 4, input 5. This is based on the one hot encoding, whatever I'm actually getting with respect to the words that I have. right? Over here, whatever vectors I basically get, that I will be passing it over here, right? So if I want to probably see how many weight metrics will be there, how many weights, how many bias will be there, here you can see that I have 5 inputs, and here I have 3 hidden neurons in the hidden layer, right? So this basically becomes 5 cross 3. So let's go ahead and calculate how many weights will be there. So here it will become 5 cross 3, that is nothing but 15 weights, right? Then over here you'll be able to see that since I'm passing 1 cross 5 and the weights will be 5 cross 3, right? 1 cross 5, 1 cross 5 and 5 cross 3. 1 cross 5 why? Because one input with 5 with one row with 5 inputs. When we do the dot operation between them, right? Weights multiplied by the bias. Then in short we are going to get 1 dot 3, 1 cross 3. So for every neuron over here I'll get 1 cross 3, here also I'll get 1 cross 3, here also I'll get 1 cross 3. So this in total for this entire hidden layer will be 3 cross 3. So 3 cross 3 is nothing but 9 weights. Okay, and then finally you'll be also able to see that this will be my 3 cross 1, which will be nothing but 3 weights, because here also we initialize weights, right? So total number of weights that you'll be able to see 15 plus 9, 24, 24 plus 3, right? 3 weights, 27. But here we are also going to use bias. So here I'll be getting 3 bias, and here I'll be getting 1 bias. So 27 plus 4 will be 31. So 31 number of total trainable parameters will be there. Trainable parameters will be there. Okay. So this is how it specifically happens with respect to the forward propagation. Okay. But again, we need to understand in forward propagation what all operation specifically happens. Okay. So I'm going to take this entire example for the forward propagation. I'll copy this. I'll paste it over here. Okay. Now, in order to understand forward propagation with time, so here I'm going to go ahead and write forward propagation. Forward propagation with time. So now let's go ahead and discuss about the forward propagation. Okay. Let's say that I have my input over here. That is nothing but, so let's say my data set is present over here. The data set is nothing but, I will go ahead and write the food is good. Okay. So as I said, and finally my output that sees over here is 1. Let's consider it. Okay. So let's say this is my x11, x12, x13, and x14. Okay. At timestamp t is equal to 1, I will be giving x11. This x11 will be in the form of vectors. Right? Let's say that I've converted by one hot encoding and I got 5 characters over here and I'm sending this to x11. Okay. Now this, initially we need to convert this word into vectors first of all. Okay. Now when this passes through the hidden layer, so this is my hidden layer. Here some weights will be initialized. Okay. So here my first weights will be initialized. Then this input will be multiplied by the weights. Okay. Here a bias will be added. So at every node there will be bias. Here also bias will be there. Bias and bias. Okay. Based on the number of hidden neurons. So once we use this x1 along with this weights, I will be specifically getting my output 1 over here, O1. Okay. Now this O1, when it is getting transferred back to the to its particular hidden nodes, right? Then here also this weights will be assigned in this. So let's consider this weight as W dash. Okay. Then again at timestamp is equal to 2. So we'll first of all discuss about this particular operation, what exactly happens. So if I go ahead and see or calculate with respect to forward propagation, please focus on this. Okay. Forward propagation. So with respect to forward propagation, here you'll be able to see my O1 will be nothing but it will be a function basically means an activation function, because in every hidden neuron we also apply an activation function. Okay. A function of, here we'll go ahead and multiply x11 multiplied by W, okay, this W, and then we will go ahead and add a bias. Okay, it can be B1, it can be anything. I'll just go ahead and write B1. Okay, this F is nothing but it is an activation function. So F is nothing but over here as an activation function. So this is with respect to timestamp t is equal to 1. Okay, now t is equal to 2. What will happen at t is equal to 2? I'll be sending my next word, that is x12, and here I'll be having my words weights W dash, W, and here we will go ahead and compute our O2. Now while we are computing O2, this O1 will also get multiplied by the weights W dash, because here also we are having some different weights. So next time, if I really want to go ahead and calculate my O2, so again here we'll be using a function F, and here I'll go ahead and write x12 multiplied by W. Okay, x12 multiplied by W. Let me write it in white color. So here I'll be using a function. Okay, so first thing first, over here you'll be able to see x12, which is my vector, will be multiplied by W, plus I have to also use O1 multiplied by W dash, right? So O1 multiplied by W dash. Now along with this, I also need to add bias. So here I will go ahead and add bias, that is B1, right? And then we go ahead and apply the activation function, right? This is very much simple. Then again, if I want to go ahead and compute my O3, now O3 will be nothing but over here, right? This will be my O3, right? Now in order to calculate O3, again I have W over here, and this will be my W dash, this will be also my W dash, right? This weights will not get updated during forward propagation. All these weights will be getting updated with respect to time during backward propagation. I'm just showing you in forward propagation what all operation is going to specifically happen, right? So here you'll be able to see that if I go ahead and show you with respect to O3, now O3 is nothing but my function of. So O3 when I'm sending, O3 is nothing but, I want to calculate this. So I have to use x13 multiplied by W. Let me quickly go ahead and write x13 multiplied by W plus, on the left hand side you have O2 multiplied by W dash. O2 multiplied by W dash plus another bias, right? And that is how you basically get O3, right? And finally, when you get O4, again by doing the same operation, O4, since this is a classification problem, right? It is a binary classification problem. Then here we are going to use, so let's say that here I go ahead and probably calculate my O4. This will forward, we will use this output. If it is a binary classification problem, we will go ahead and apply something called as softmax. Softmax is basically, not softmax, sorry. We will go ahead and apply sigmoid, okay? So sigmoid activation function for a binary classification over here. So this will basically give my binary output. Okay, 0 and 1. If I have multiclass, then instead of using sigmoid, I may go ahead and use softmax. Softmax activation function. And finally, I get my y hat. Here, I may get my y hat, right? Once I get my y hat, then what will happen? Whatever will be my y hat, we will go ahead and compute the loss, and we will try to reduce this loss by doing backpropagation. So backpropagation, I'll be discussing how it happens in my next video, but forward propagation, you saw this. This is how the entire operation will happen with respect to each and every word, right? In a specific sentence. And that is how the forward propagation with time actually happens. And this function is a kind of activation function. For every word, we will go ahead and use, we go ahead and multiply each and everything as we go ahead till the end of the sentence. Okay. So I hope you got an idea about forward propagation. That is how it actually happens. But here also you got an idea with respect to weights, how many bias will specifically be there. Initially, this inputs will be 1 cross 5, then 5 cross 3 weights are basically getting applied. When we do dot operation, I'm going to get 1 cross 3. So 1 cross 3 will be with respect to every node. There are 3 nodes, so it will be 3 cross 3, total 9 weights. Since it is getting passed to each and every each and every hidden node. So that is the reason I'm basically using 3 weights. And here you'll be, sorry, 3 plus 3 it will become, right? And then finally here you can see again another 3 plus 1 is there. And when we try to multiply this, again 3 plus 1, I will be getting 3 weights, and here will be 1 bias. And this is how the forward propagation basically happens. So in short, here it took so much time, because if you understand this architecture, right? Trust me, it will be very much easy to understand all the upcoming architectures like LSTM or GRU and all, right? But here I hope you got an idea. I broke down completely to make you understand about RNN, right? So yes, this was it from my side. I hope you like this particular video. I will see you all in the next video where we'll be discussing about backward propagation. Thank you. Hello guys, so we are going to continue discussion with respect to RNN, and in this video we are going to talk about RNN backpropagation with time. Already in our previous video we have seen how the forward propagation with time happens in RNN, in a simple RNN. We have also seen about the basic architecture of a simple RNN. Now with respect to this particular forward propagation, once we go at the end, once we calculate the loss function, our main aim is to reduce this particular loss function. Now in order to reduce this particular loss function, we have to do a backpropagation, and we have to update all these weights that are available over here, right? So in this video we'll be understanding how the backpropagation will happen and how the weights will get updated in a simple RNN. Now before I go ahead, what I will do is that I will again quickly revise our forward propagation. So let's say this is the basic architecture of a simple RNN, and here you know that we use a self-feedback loop. And here also we pass some kind of input. So here also some weights will be involved. Okay. But when we unfold this with respect to time, okay, and let's consider I'm going to take my sentence 1. It has this x11, x12, x13. Let's say that my sentence 1 has this 3 words, and this is my output. It can be 1 and 0. Okay. Similarly, my sentence 2 may have another one like x21, x22, x23, right? And let's say this is the output 0. And similarly, my sentence 3 may have something called x31, x32, x33. Okay. I'm just considering 3 words at a time. Okay, you can have any number of words, that is up to you. And this word may also vary, because at the end of the day, we'll be converting these words into some kind of vectors by using one-hot encoding, by using word to vec. It is up to us. Okay, and we'll be passing every input one at a time based on the timestamp. But if I really want to give this generic format, so here I can go ahead and write something like this. I'll make this sentence 1 as generic. I'll say, hey, this will be xi of 1, then this will be xi of 2, and this will be xi of 3. Okay, so here I is nothing but it will be the sentence number. Okay, sentence number. Perfect. So I'm just giving some basic information over here. Now let's do one thing. Let's unfold this entire RNN, simple RNN, with respect to time. Now, you know, with respect to time, when my t is equal to 1, I will be passing my first input, right? So I will be going and passing my first word. So let me just go ahead and define this. And this will basically be my first word. Okay. So at t is equal to 1, I am going to pass x of I1. Okay. Now, initially, I will also pass some kind of weights over here. Let's say this is my hidden weights. By default, some weights will be getting assigned. And initially, I'll not put this. Okay. Let this be empty for now. Okay. I will just go ahead and unfold this entire network over here. So we are just going to unfold it. Now, once we give an input at a time step t1, t is equal to 1, here some weights will get assigned. So let me just go ahead and write this as w of I. Okay. Now, you know that what will happen in forward propagation, we multiply with the specific weights, then we add a bias, and after this we get a output. So this will be my output, right? And this output will be nothing but O1. Let's consider O1. So this will be my O1 output. Now you know that my output, I need to send it back to this particular RNN, right? To this particular hidden layer and all the other hidden neurons in that layer. So this will be sent to my hidden neuron. Okay, the same output will also be sent to my hidden neuron. But at time step t is equal to 2, I will be passing my next input. So here it will be writing, right, xi2. Okay, that basically means we are just passing the second input with t is equal to 2. Again, the same weights will get initialized over here. Along with this, we will go ahead and initialize one more weight over here, w of h. Okay, so this is nothing but this is a hidden neurons weight, right? If you remember, over here in this hidden neurons, I told you, right, we are also going to assign dissolve weights, right? Dissolve weights will be also getting assigned, right? And the next step will be that we will multiply with this, and we'll add O1 with WH. And finally, when we combine both of them, you'll be able to see that we will be getting our next output, that is nothing but O2. Now, with respect to this particular O2, again, I will go ahead and use my, the weights will get assigned in this. And here I'm actually going to get my next input. Again, at t is equal to 3, I'm going to pass x of I3. Okay. And finally, I will get my output, which is called as O4. Okay. Now, with respect to this particular output of O4, okay, again, I will go ahead and pass this to my sigmoid if it is a binary classification. right? And finally, I get my output over here, which is my y hat. Okay, so this is how I had also written it over here earlier when you saw this entire steps. Let me just show you once again. So here, right, we were getting this OFO, we send it to the sigmoid, and finally, if it is a binary output, we use sigmoid. Otherwise, we use softmax. If it is a multi-class classification, we specifically use something called as softmax. And here also, you know that with respect to this OFO, I will also assign some weights with respect to this. So let's say here also we go ahead and use W of h. Okay, now. And here there will be a weight of I that will get initialized over here. Now with respect to the forward propagation, so quickly let me just go ahead and write. So here is my forward propagation. And forward propagation, what happens? Okay, one more important thing is that, guys, initially I did not pass any input, right? Because when we are starting this, we will also initialize some kind of input weights. And here, when I'm initializing some kind of input weights, obviously I will also initialize some WH over here. Okay, this will be my WH. Along with that, you'll be seeing that since every layer has some kind of output, here also we need to make some kind of output, right? We need to probably initialize some kind of output. So here I will be getting my O0. This O0 can be initialized as zeros, you know, it can be initialized any values as such, right? But randomly it can also be initialized. So here we can also initialize at zeros, or here also randomly any values can be initialized based on some initialization factor, right? The initial output. And again, here also you'll be having this hidden weight. Okay. Now in forward propagation, what happens is that whenever we go with the forward propagation, the first thing that we need to compute is O1, right? So O1 needs to be computed over here. Now in order to compute O1, what I will do is that I will just go ahead and in every hidden neuron, I apply some kind of activation function. So let's go ahead and apply this activation function F. Let's say the activation function in this particular case is tan h, right? So I will go ahead and multiply x of I1 multiplied by W of I plus, then you can see O0 is also there. This O0 is nothing but it is zeros only, right? I'll be just considering that we have initialized all the values 0. So 0 multiplied by this hidden weight will be 0 only. So that entire thing, right, it will be 0 because we need to sum this up. Then we have a bias. Let's consider a bias over here. In every hidden neuron, we will be having a bias, right? So let's consider this as a bias. Okay. Now this is my first operation with respect to this thing, right? And one more important thing over here is that I will just go ahead and write this also so that you will not get confused. So I'll say, hey, my O0 multiplied by WH plus bias, okay, B1. And then we basically go ahead and apply an activation function. Okay. Now coming to my next output, O2. Okay. Now this is how the forward propagation will happen. Now in forward propagation of O2, my next word is basically sent. So this will nothing be, but it will be a function of x of I2 multiplied by W of I plus, now O1 and WH is also there. So I'll go ahead and multiply O1 multiplied by WH plus, there will again be a bias over here. Let's consider this bias as B, and here I'm going to use another activation function. This is how we go ahead and calculate O2. Right? Now similarly, when I go ahead and send my third word, that is to calculate O3, it will be nothing but x13 multiplied by W of I plus O2 multiplied by W of H plus B. Bias, right? O2 multiplied by W of H. W of H is nothing but my hidden weights. Okay, so everything looks perfectly fine over here. Now finally, when we get our output, right, we send this output to a sigmoid activation function, and then only we'll be able to get my y hat. So in order to get the y hat, let's say the sigmoid activation function I'm going to apply over there, it will be nothing but O3 multiplied by. So here you can see O3. Oh, sorry, I did not write. I wrote O4 over here. So it should be O3. This is my output, O3 multiplied by W of H, right? And then we send it to the sigmoid to get my output, right? So here what we're doing, we're just going to multiply O3 with W of H. So once I probably do all these things over here, see O3, W of H, instead of writing W of H here, I'll not use hidden weights because this will be my output weights. So let me just go ahead and write W of 0, okay? So this will basically be my W of 0. Perfect, right? So this is how the forward propagation usually happens. And finally, when we pass it to sigmoid or softmax, I'm going to get my y hat. Okay, O3 multiplied by W of 0. So here we are specifically going to apply W of 0 because this is my output weights, right? And finally, this is my output node where I'm getting my output. Okay. Now this is fine. This is perfectly till here. Everything I think we have discussed this in a previous video also. Now the time comes is that after we calculate y hat. Now once we calculate y hat, what will happen? We will take y minus y hat and we will calculate the loss. Right? There will be some loss value. Now our main aim is to reduce this loss. And how will we be able to reduce this loss? Only when we update all the weights. Now what are the weights that are available over here? As I probably see, there are three weights that will be involved over here. One is W of I, the next one is W of H, and W of H, W of I, and one more weight is W of 0. Okay, so these three weights needs to keep on getting updated during the back propagation. Right? This is the most important thing, that if we really need to update W of I, W of H, and W of 0, right, I need to probably update this weights itself and probably do the backward propagation and then continuously do the forward and the backward propagation in similar way. And we'll be doing unless and until this, till when? Till our entire convergence will happen in this gradient descent. We'll reach this global minima. Or when my loss will be really less. This is equivalent to when my loss will be really, little bit less, right? Now, let me just go ahead and quickly show you with respect to the back propagation. How does back propagation actually happen? So I will just go ahead and create one more cell over here. Okay, so this is my forward propagation. Now, in the backward propagation with respect to time. Backward propagation with time. Now, see, at the end, over here, when we do the forward propagation, we finally go ahead and calculate our loss, right? So this is our loss. So we go ahead and calculate our loss, okay? Now, once we calculate this loss, okay, please focus on this, okay? Once we calculate this loss, the first output, so first weight that we need to update is WO. Now, in order to update W, and as I said, we have to update, which all weights? We have to update W of I, W of H, and W of O, okay? We need to update these three weights. Now, in the backward propagation, the first weight will get updated based on your timestamp. So let's say timestamp is equal to 3, the first weight that is coming is W4. So in order to update W4, how do I do it? So here, I will be using a weight updation formula. And I hope everybody remembers this. What is the weight updation formula? It is nothing but, you'll be able to see that weight of new is equal to weight of old minus some learning rate, derivative of loss with respect to derivative of W old. Okay. Now, this formula, I hope you are very much familiar because we have also discussed this in ANN. But out of it, this is the most important one. Okay. Because of this here, when we are doing this is basically my derivative. And why we are doing it? Because we need to calculate the slope of gradient descent. We need to go ahead and calculate this. Slope of gradient descent. Okay. Now, my question is that, our question is that, how do we solve this? Now, see, first is derivative of loss with respect to derivative of W old. So first weight, that is WO. So first thing that we really need to calculate over here is that derivative of loss with respect to derivative of W old. This is what I really need to calculate, right? if I calculate this, then only, see, this weight is nothing but derivative of loss with respect to derivative of WO, right? And if I talk with respect to the weight updation formula, this will be nothing but derivative of O is equal to derivative of O old, or I'll write like this, derivative of O new, sorry, W of O new is equal to W of O old minus learning rate derivative of loss with respect to derivative of WO old. Okay, so this will be old. So this is my entire weight updation formula for WO, right? But here I need to calculate this. This is fine. I'll be getting the old value. Now in order to get the new value, I have the learning rate. Learning rate will be a small value. So let's consider learning rate will be something like 0.001. Okay, but I need to compute this. So in order to compute this derivative of loss with respect to derivative of WO old, how do I probably write this entire, or how do I find this? Okay, now it is important for you all to understand is that here WO is directly dependent on y hat, and y hat is also dependent on loss, because at the end of the day we are calculating the loss. So here you can see there is a direct relationship. The loss is dependent on y hat and y hat is dependent on W, right? So if I want to probably expand this equation based on chain rule, so this based on chain rule of derivative, if you remember this, we have already discussed. So based on chain rule of derivative, you'll be able to see that I'll be having derivative of loss with respect to derivative of WO old. Instead of writing WO old, I know loss is dependent on y hat. So I'll go ahead and write derivative of loss with respect to derivative of y hat. And similarly, I will go ahead and say derivative of y hat is dependent on, now I can go ahead and write derivative of y hat is dependent on what? WO old, right? Now once we do this, we will be able to get this value. And this is nothing but this is a chain rule of derivative, right? And through this, you'll be able to see that we will be able to calculate, or we'll be able to update the weights of WO new. Okay, this is perfect. So our first main thing is that how do we update W0? That has been very much clear. Okay, because there are three types of weight. One is W0, one is W of H, and one is W of I. So here with respect to timestamp, here you can see that I have updated my W0. Now coming to the second important case, we need to update W of H, and this is nothing but this is my hidden weights, right? Hidden layer weights. Now these weights are important because this weight is used in all timestamps. Right? T is equal to 1, T is equal to 2, T is equal to 3, T is equal to 4. So we have used this in each and every timestamp. Now how do we do that? Okay, so here you can see. Now what we are going to basically do while updating this is that it's very much simple. Okay, and first of all, let me just go ahead and write the weight updation formula here. So I'll say, hey, W of H new is equal to W of H old minus learning rate derivative of loss with respect to derivative of WH old. So this is the formula, the weight updation formula. And out of this formula, the main thing that I have to compute is nothing but derivative of loss with respect to derivative of WH old. Okay, this we need to compute. So in order to compute this, how do I write now? Derivative of loss with respect to derivative of WH old. How do I compute it? I have to make sure that how many timestamps are there in my entire RNN is equal to 1, 2, 3. So I have to make sure that I have to find this based on my timestamp t is equal to 1, 2, and 3. Now how do I do it? Okay, first of all, let's in the back propagation, my first timestamp is 3. Now I need to update which weight over here. I need to update this W of H, right? I need to specifically update my W of H weights. Okay. Okay, perfect. So let's go ahead and do that. Okay, and here you can see there is W of H and there is W of I. Okay, so I will just try to show you how we will update this W of H. So W of O, we saw it how we can update it. Now let's go ahead and see with respect to W of H. Now this hidden weight, you know that this is dependent on O3. See, just try to always make a rule like this is dependent on O3. O3 is dependent on Y hat, and Y hat is further dependent on loss. Okay, so here you can clearly see this. First of all, loss. Like if I go from this particular, because I'm searching with respect to time is equal to 3, right? And time is equal to 3, I have WH over here. Now first of all, this is dependent on O3. O3 is further dependent on Y hat, right? And y hat is further dependent on loss, right? So there is a kind of dependency, right? And vice versa also I can say, right? I'll not say, okay, WH is dependent on O3 and all. I'll say O3 is dependent on WH. Or you can also think in this way. Let me reframe it, okay? So I have my loss. Loss is dependent on y hat is dependent on O3, and O3 is dependent on WH. Now in order to update this, I have to follow this chain, okay? I have to follow this chain, okay? So let me just go ahead and write it and how it will look like. So first of all, I'll go ahead and write derivative of loss. Let me go ahead and write this. So here I'll go ahead and write derivative of loss with respect to derivative of y hat, because this is the first dependency. Then derivative of y hat will be dependent on what? Derivative of O. Let me just see this weight. Okay, W4. Okay, so derivative of W4, or instead of writing derivative of W4, I know this will be dependent on derivative of O3, because O3 is the output over here, right? O3 is the output. Then similarly, this O3 will be further dependent on derivative of O2, right? Now I know that in timestamp t is equal to 3, I have to first of all update this weight. So what I will do, instead of writing O2, I will go ahead and write derivative of derivative of WH. Okay. Now this is very much important because when t is equal to 3, I'm doing the back propagation and I'm finding out this particular derivative of this value in this way. Okay. Now I will take this as 1. Okay, one entire thing, and we'll update this. We'll calculate it. Okay. Now we will go ahead and write plus. Why? Because at timestamp t is equal to 2, I still have W of H over here. Okay. Now what kind of rule we will follow, or what kind of chain we'll follow? So here you can see loss is dependent on y hat. Y hat is dependent on O3. O3 is now dependent on O2, and O2 is now dependent on WH. Now in order to update this W of H, please see this. Okay. In order to update this W of H, I have to follow this chain rule. Okay. So here what I will go ahead and write again. Derivative. So I will start from here. Okay. I will go ahead and write at timestamp t is equal to 2. How I will update this? First of all, I will go ahead and write derivative of L with respect to derivative of y hat. Then I will multiply derivative of y hat. Derivative of y hat with respect to derivative of O3. Then I have derivative of O3 with respect to derivative of O2, because there is also a dependency over there. And then with respect to derivative of O2, I will be calculating the derivative of WH. So this will be my, for timestamp t is equal to 2, how I will go ahead and calculate my W of H, right? This is how, based on the chain rule, it will happen. Again, let me repeat it. Loss is dependent on y hat is dependent on O3 is dependent on O2 is dependent on WH. And that is how I've actually calculated my derivative. Now comes to the next point. And the next point is nothing but with timestamp t is equal to 1. Now how do I calculate it? So here, what I'm actually going to do, I'm going to probably create this chain. Now I need to update this particular value, that is W of H. Right? Now how do I calculate it? Now you can see there'll be a dependency. Now from here I'll say O2 is dependent on O1, O1 is dependent on WH. Right? So first we'll say loss is dependent on y hat is dependent on O3 is dependent on O2 is dependent on O1, and finally O1 is dependent on WH. And that is how this chain rule will be working. Okay. Now if I really want to write this again, so it will be nothing but here I'm going to write derivative of loss with respect to derivative of y hat multiplied by derivative of y hat multiplied by derivative of O3 based on the chain rule, derivative of O3 divided by derivative of O2, O2. Then again I will go ahead and calculate derivative of O2 divided by derivative of O1. I think it is O1, right? O1. Then O1 is derivative of then O1 is dependent on W of H, derivative of W of H. So here I have my next one. And once we add up all these particular values that we are going to get, that is when we are going to get this entire value. And we'll go ahead and update it. And our WH new will be the value with respect to this old minus learning rate multiplied by this, whatever value we specifically get. And that is how, in one back propagation, all the hidden weights gets updated. Okay, this is perfect, right? So I hope you're able to get how to update WH, which is my hidden layer weight based on timestamp. Now coming to the third and the very most important thing, that is W of I. Okay, so third is nothing but updating weights, W of I. Now let's go ahead and discuss about this. So guys, now we are going to probably see how we can update weights W of I again based on timestamp. Okay, because at t is equal to 3, I'm sending one word. At t is equal to 2, I'm sending one word. And at t is equal to 1, I'm sending one word. So we are just talking about these weights, right? So this weights we also have to update in the back propagation. So let's go ahead and see step by step. Okay. Now first of all, for this, what kind of chain rule I'll go ahead and apply. So here you can see that first I have loss. Loss is dependent on y hat. Y hat is dependent on O3. O3 is dependent on W of I, right? So again for this, the weight updation formula will look something like this. So here I will go ahead and write W of I new is equal to W of I old minus learning rate of derivative of loss with respect to derivative of W of I old. Okay. Now as you know, we have to go ahead and compute this. Okay. And this will be with respect to time. Now quickly, derivative of loss with respect to derivative of W I old is equal to, I know first of all loss, this derivative of loss. So this will be with respect to timestamp t is equal to 3. Okay, we have to do the back propagation. So here you can see derivative of loss with respect to derivative of W. Here you know that loss is dependent on y hat. Okay, then I have y hat, which is on turn dependent on. So y hat is dependent on what? Y hat is dependent on O3. So I'll just go ahead and compute O3. Then O3 is dependent on W of I, right? And when I say W of I, this is nothing but W of I old. Okay, so this is with respect to my timestamp t is equal to 3. Okay, similarly we'll go ahead and write plus. Now let's go with respect to timestamp 2. Now with respect to timestamp 2, you know that how we are going to go. Y is dependent on y hat is dependent on O3, O3 is dependent on O2, O2 is dependent on W of I, right? So we will go in this rule. So first of all, I will say, hey, let's go this. So this you have one dependency loss with this, then O3 from O3 to O2, and O2 to this W of I. Okay, so we'll go ahead and write this. So quickly, let's go ahead and do this. So here I'll be writing derivative of loss with respect to derivative of y hat multiplied by derivative of y hat multiplied by derivative of O3. Then you have derivative of O3 divided by derivative of O2, and finally you have derivative of O2 divided by derivative of W of I old. So here is my total thing, right? So O3 to O2. See, I'll see O3 to O2, O2 to W of I. So O2 to W of I, right? And finally, you'll also be seeing that we will go ahead and write my final and this is for t is equal to 2. Now let's go ahead and write it for t is equal to 1. T is equal to 1 is very simple. Derivative of W of y hat multiplied by derivative of y hat with respect to O3, derivative of O3 with respect to derivative of O2, then O2 to O1, and finally O1 to W of I old. Once we calculate this all values, you'll be able to see that I'll be getting this entire value over here, and this will be replaced over here, right? And finally, we update W of I weights in the back propagation. And this usually happens in one back propagation with respect to time. So finally, when we are using this weight updation formula, what exactly is happening, right? And I hope everybody knows about gradient descent, okay? Our main aim is to probably come to this global minima, right? And there are different weights. One is W of H, there is W of I, and there is something called as W of O, right? My main aim is that whenever this conversion basically happens, we have to probably come towards this global minima, right? If you're coming towards this global minima, that basically means our loss will be very much near to 0, or our loss will keep on decreasing, right? And this is what we had already discussed in ANN regarding gradient descent. So I hope you like this particular video. This was it from my side. Here in this video, we have discussed about RNN, simple RNN, we have discussed about forward propagation, we have discussed about backward propagation with all the equations and all, right? So yes, this was it from my side. I will see you in the next video. Thank you. Hello, so we are going to continue the discussion with respect to RNN. Already we have seen about forward propagation in RNN, we have seen about backward propagation in RNN. Now we're going to understand what are some of the problems with RNN, okay? And because of this, the next neural network after RNN, which we are specifically going to discuss about is LSTM RNN and GRU RNN, right? Why we require this variance of RNN when we already have a simple RNN, okay? So we'll be discussing about that. And in the upcoming videos, we will be discussing about LSTM RNN and GRU RNN. So let me just go back and probably revise some of the concepts with respect to RNN. So here is what my RNN looks like, right? A simple RNN. I have a feedback loop. And then when we unfold this, you will be able to see that I will be getting something like this. And this will basically be the output will go to my hidden layer again with respect to the specific neuron. This is my input. This is my input. Again, it will go like this. And I will keep on going to the next stage till we get the last word with respect to the timestamp, right? And once we get this, what happens? Once we get the output here, we are just going to apply a sigmoid or softmax activation function. Let's say soft or sigmoid. And finally, we will be getting a y hat. And later on, we go ahead and calculate our loss, y minus y hat. And our main aim is to reduce this loss. So what we do, we basically do the back propagation. And if I just talk about over here, I will be having W of I. Here I will be having W of H. Okay, this will also be W of H. And here I will be having one input, which will be like initialized to 0 initially. And similarly, this will also be W of H. Here I will be getting W of I, W of I, W of H. Similarly, W of I. And here finally we get W of 0. And with respect to this particular output, here you'll be seeing that I'll be having O1, O2, O3, like this up to ON, right? So we discussed about this entire process and we have discussed about forward and backward propagation. Now let's understand what is the problem with RNN, okay? And I hope in ANN, when we were discussing, we discussed about a very important topic, which is called as vanishing gradient problem. Vanishing gradient problem, okay? So let's go ahead and discuss about this again. And here also, in our simple RNN, we may face this problem. Now the thing is that you really need to understand how do we face this particular problem, okay? Now let's consider in my data set, I have some text. I have some output. Okay. Till now we just saw smaller sentences. Let's say I have 4 words like the food is good, right? So my output will be 1. The food is bad. So the output is 0. Okay. When we're using this all kind of words, right? Or this all kind of extra sentences, this sentences was small. This sentences was specifically small, right? And instead of taking this particular use case, let's consider one more use case which is called as text generation. Okay. Let's say some of the example with respect to text generation. I'll go ahead and write, hey, I'll take a very simple example. I like to play dash. Okay. So here I need to probably go ahead and predict my next word. It can be cricket, it can be football, it can be anything, right? And over here, this word will be predicted based on the context or based on the previous words that we have, right? For this particular sentence, if I have this sentence as 1, over here you can see this word may be actually dependent on this word, or it can be on this word, or it can be on this word, or it can be on this word, right? If I consider and if I try to train my neural network, right? Here you can basically consider that this has a kind of short-term dependencies. Now, when I say short-term dependency, what does this basically mean, right? Let's understand this with a very simple example right now. Here I have specifically written that I like to play. I need to predict the next word. Now this word may be dependent on this word, or this word, or this word, or this word. Okay. So here you can see based on the length of this entire sentence, right? Based on this length of this entire sentence, there are hardly 4 words, right? So I have a dependency within this shorter sentence. Okay, but let's say I will go ahead and write a new sentence. Let's say I'll write, hey, my name is Krish, and I like sports like cricket, volleyball. Okay, and I like, let's say I'll go ahead and write, and also like to make, and this will be dash over here. I need to predict this particular word. Now this word can be videos, I like to make food, it can be different words. Now here, in order to determine this specific output, now the dependency is on this word, right? It may be on this word, it may be on this, or it may also be on other words. But here you can see this sentence is long, is really long, right? Now when this kind of sentence is long, just imagine if I am passing through my RNN. So how many timestamps I will be requiring? I'll be requiring t is equal to 1, I may require t is equal to 3, 4, like this. If I keep on counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So at t16, I will be sending this word for my forward propagation. Okay. Now similarly, this is just a smaller, this is still, I'll say a sentence with a good length, but let's say if I have a sentence which may have 100 words, So at t is equal to 100, I will be sending my last word for the forward and the backward propagation, right, to calculate the loss. Now what will happen as the sentence keeps on getting longer and longer, right? The final output that I really want to get, right? This may be dependent on some words that may have started earlier, right? That may have come up in time stamp t is equal to 4, 3, 2. And this dependency cannot be captured by simple RNN. Okay, so let me just go ahead and write it down. Why it cannot be captured? I will be explaining about it, right? The long-term dependency cannot be captured by RNN. And hence, RNN cannot provide a better accuracy in this kind of use cases where it has this kind of dependency. Where it has this kind of dependency. Now you may be thinking, Krish, whatever things you are actually explaining over here, it hardly makes sense. Please try to give some example. Obviously, I'm not going to stop over here, right? Now let's take one example. Let's say I'm going to use this entire neural network again. Okay, I will just go ahead and copy this. I will go ahead and copy this. And let's paste it over here. Okay. Let's go ahead and do this. Okay. Let's say for the first instance, I give my xi1, xi2, xi3. Okay. So in one of the sentences, I just had 4 words, right? Or I just had 3 words. And after that, I got my output. I passed this to my sigmoid. So if I really want to show you with respect to, let's say, in one of the sentences, I just had 3 words. So my unfolding will basically happen like this. So at t is equal to 1, I will be giving my x11. As t is equal to 2, I'll be giving x12, then my x13. And finally, when I get my output, this will be passed. This will be my output. Here, instead of writing hidden, I will be writing something like this. I will be sending it to my, let's consider this as sigmoid, okay? So I'll be sending it to my sigmoid. Let me just draw this properly, okay? So here, I'll be sending it to my sigmoid to perform to capture or to calculate the y hat, okay? So this is pretty much easy. And here I will be saying that this will be my W0, okay? Now in this case, when I try to find out the weights, right, I need to update weights over here as W or H, W of I, and W of 0. Now, in order to calculate this weights, again, the generic formula is nothing but W new is equal to W old minus learning rate of derivative of loss with respect to derivative of W old, right? And out of this, what is the main thing that I really need to calculate is this particular value, right? This. And this value needs to get calculated for, first of all, I'll go ahead and write W of 0, right? This loss with respect to 0. Here, I will go ahead and calculate my loss, Y minus Y hat, okay? Now, when I calculate derivative of loss with respect to derivative of W0, so here you'll be able to see the equation will be very much simple. So I will go ahead and write derivative of loss with respect to derivative of y hat, derivative of y hat with respect to derivative of WH. Okay. So for this, the calculation will be very much easier. But now let's go ahead and consider one of the examples. Let's say I want to update this hidden weight. Okay, this WH. Okay. So let's go ahead and update this hidden weight. Okay. I'll take this example. So for this, I will go ahead and write derivative of L with respect to derivative of H old. Now you know that my loss which is getting calculated is dependent on, in this particular case, it is dependent on O3. O3 is dependent on O2, and O2 is finally dependent on WH. Okay. So here what I'll write simply like derivative of loss with respect to derivative of y hat. Sorry, loss is dependent on y hat. Y hat is dependent on is probably dependent on O3. Okay. So now I will go ahead and write derivative of y hat with respect to derivative of O3. Okay. And this is a simple chain rule that we have actually discussed. Derivative of O3. Okay. Then we'll go and write derivative of O3 to O2. Then we'll go and write derivative of O2 to derivative of WH old. Now remember one thing. Here we are calculating with timestamp is equal to t is equal to 1, right? if I really want to calculate all the derivatives, I need to keep on adding. For t is equal to 2, I need to add. So I can go ahead and take this entire value. Okay, so at t is equal to 2, I can go ahead and add that. So at t is equal to 2, let's say I want to go ahead and do this. So I will be having a different derivative, or I'll be having this different separate chain rule over here. I'll be able to get it. Then at t is equal to 3, I'll be able to get it a different chain rule. Okay, but I just want to focus over here right now in this. Right now, here when you're seeing this is a specific chain rule that I have. Okay. And here you can see that with respect to t is equal to 1, when my total number of words was just 3, when t is equal to 1, I was able to get this big chain rule of derivatives. Okay? Now, if I go ahead and consider if my length of one of my sentence, if my length of one of the sentence is having 50 words, now in the case of 50 words, now just imagine what will happen to this particular w of, like if I go ahead and try to calculate derivative of loss with respect to derivative of w hidden. Please focus on this. Okay? If my length of the word is 50 words, so at t is equal to 1, how my equation will look? So I will go ahead and write like this. So at t is equal to 50. Oh, sorry, at t is equal to, like, total number of timestamps will be 50. And I want to find out derivative of loss with respect to derivative of w old with respect to t is equal to 1. Right? Now this same equation will come, right? And here what it will become? See, now my derivative of loss will be dependent on derivative of y hat. Next step will be that derivative of y hat will be dependent on what? Derivative of o, whether it will be 3 or whether it will be 50. So now I'll go ahead and write 50 because I'm going to go ahead with till t is equal to 50. So my last step over here will basically be o50. The output 50 that we'll be calculating, right? Then similarly, we will go ahead and calculate derivative of o50 with respect to derivative of o49. Similarly, we'll go ahead and write derivative of o49 with respect to derivative of o48. And similarly, like this, we'll keep on going till what step will be going? Till we get this one, right? Till we get derivative of O2 with respect to derivative of WH old, right? So at t is equal to 1, this will be my first step, right? At t is equal to 1, this will be the value that I really need to compute. Then again at t is equal to 2, I'll keep on writing it, right? And again over there, hardly from 49 it will start. From 49 it will start and it will end till here. Then for t is equal to 3, it will start from 48 and then it will end till here, right? Same thing will basically be happening along with this, right? Now let's focus on these important things, right? Let's focus on these values, okay? Let's focus on these values. These are very important values. And we'll take this up. Okay, let's consider one of the equation like, out of all this, I will go ahead and take one more over here. Derivative of O3 with respect to derivative of O2 plus, multiplied by this last one, okay? So what I'm saying is that if I keep on doing this, right? If I keep on going this, like this, it will continue till this particular value, right? And before this value, I also have something like derivative of O3 divided by derivative of O2. Now let's go ahead and calculate this, okay? We will just go ahead and calculate it. Now derivative of O3, what is O3 over here? O3 is nothing but, it is very much simple. We basically take this W of H. See, let's go ahead and see what exactly is O3, okay? O3 is nothing but derivative of, let's say I'm going to apply a sigmoid activation function on this node, okay? Let's consider this. For O3, I'm just considering, okay? Just taking an example. So O3 is nothing but, first of all, I'll just go ahead and write about O3, okay? What is O3 over here? O3 is nothing but, it is, how we are getting this particular output? It is very much simple. First of all, I will go ahead and multiply x of I3 multiplied by w of I, right? So let me just go ahead and write it down over here. X of I3 multiplied by w of I plus, okay, plus we are multiplying with w of H multiplied by O2, right? So here I'll go ahead and say O2 multiplied by w of H, right? So this is my derivative of this O3 value, okay, divided by derivative of O2, divided by derivative of O2. Now once we perform this derivative, since we are doing it with respect to O2, this will become 1, okay? This will become 1, so I will be getting this WH, and this will be considered as a constant. But before this, you'll be able to see that when I am applying derivative over here, on top of it, I also have to perform a sigmoid activation function. On this node, I have to perform, on top of it, I also need to perform sigmoid activation function because there will be a sigmoid activation function over here. Along with this, you'll also be seeing that I will also have one bias parameter. So this will be plus bias. Okay. Now this will how the equation look like. So I'm saying here derivative of sigmoid of this x of I 3 multiplied by w of I plus O2 multiplied by w of H plus 1 plus b. Okay. And this is entirely my O3. Right. This is what I have replaced O3 by. Right. So O3 over here means what? O3 is nothing but it is sigmoid of xi3 multiplied by w of I plus O2 multiplied by w of H plus b. Right. Now if I go ahead and find out the derivative, how it will work? Derivative, if you know, I will get this is sigma dash, I will write because this is the derivative. Now further going ahead, you'll be able to see that it's like if you use the derivative for this entire thing, okay? If you probably use this entirely, this particular derivative, this will be nothing but here you can specifically write 1 multiplied by w of H, okay? 1 multiplied by w of H because this will be a constant, this will be a constant, this will become 0, this will become 0, okay? So I have something called as 1 multiplied by w of H, that's it, okay? So here is what I'm actually going to get, okay? So this is nothing but derivative of sigmoid, and here I'm just going to get 1 multiplied by w of H. Now this will be nothing but whenever we try to find out the derivative of sigmoid. So I have actually explained this in my activation function. So derivative of sigmoid ranges between 0 to 0.25. The output of the sigmoid ranges between 0 to 1, but whenever I try to find out the derivative, it will be ranging between 0 to 0.25. So this value that you are going to get is nothing but 0 to 0.25. In between this values you'll be getting. Now here you can see that you observe one thing, right? One of the value that I calculated in this multiplication, which was this one, okay, this one, was ranging between 0 to 0.25, okay? Now as we go ahead, right? Now this is a decimal. Let's say that we went and calculated here, we got a decimal as 0.015, okay? I just calculated it randomly. Now let's say for this I got 0.02, right? For this I got 0.25, right? For this I got not for this. For one of the internal one I got 0.01. Now when I keep on doing this multiplication, you'll be seeing that after some point this will become a very small value and it will be approximately equal to 0. Now when this is approximately equal to 0, that basically means what? At t is equal to 1, where I had this first word that I'm actually giving, it is not participating much to update the weight value, right? So what is happening over here? The t is equal to 1, the word is not participating to update the weights value. Do you agree or not? Just see this. Why it is not participating? Because this entire operation will be approximately equal to 0 because we are just multiplying with these numbers, right? These numbers. And as you know that if you keep on multiplying with decimal numbers, you'll be seeing that, hey, we'll be getting a value which will be approximately equal to 0. It will become smaller value, a very, very small value. Now, since this entire value is becoming 0, you'll be able to see that when I will try to add this number, or when I'll try to add this with my next timestamp, it is not probably going to impact the weights, right? It's not going to change this specific value, right? You will be seeing, so what is basically happening over here? Here, in short, it is saying that the word that you initially gave in our simple RNN, when compared to the last word, this word is not playing a good or amazing impact in the simple RNN to probably predict the outcome or the output. right? It is very much simple over here, right? Whichever will be the nearest value with respect to the timestamp, that may create a bigger impact. The reason is very much simple. Why? Because when you perform the operation will be very smaller. So here, when I am trying to calculate, let's calculate for O3, right? Just for this last timestamp. If I'm trying to find out O3, loss is dependent on y hat is dependent on O3, right? Or loss is dependent on y hat is dependent on WO, and WO is further dependent on W5. If I want to update this, the chain rule will become very smaller. But in this case, the chain rule is big. Now, when the chain rule is big, right? Big basically means the chain is very big over here, right? Over here you can see that whichever is our first word, that will not play a very bigger impact to finally predict the last output, right? And that is what we will be seeing, because here we have a long-term dependency. Long-term dependency, why? Because in this case I took 50 words. This was my first word. This was my first word that I passed with respect to timestamp. And if I'm updating this weight, it's hardly zero, and it is not creating any impact for my final weight, right? So this is the major problem. And whenever we face this kind of problem, right, this is basically called as vanishing gradient problem. Okay, vanishing gradient problem, right? So this is very much important. Let's consider at t is equal to 50 what is going to happen. Okay, so at t is equal to 50, you'll be seeing if I go ahead and calculate my derivative of loss with respect to derivative of WH old. Now first, I know my derivative of loss will be dependent on derivative of y hat. Then I have derivative of y hat. It will be dependent on what? If I really want to just play with the last WH50, right? So this will basically be dependent on derivative of y hat will be dependent on my final output. My final output will be O50, and derivative of O50 will be dependent on derivative of WH old. Right? This is what is going to happen at t is equal to 50. Now here you can see this is the right. So this is basically t is equal to 50, right? This is what I'm actually going to add at t is equal to 50, right? So this here you can see my chain rule is very small, and here I may be getting some value because the chain rule is small. I don't have to probably do so much of calculation, so much of multiplication like when we did it for t is equal to 1. So similarly, I'll go ahead and add with t is equal to 449, then we'll have t is equal to 50, and we'll keep on adding it till t is equal to 1. Finally, we'll be having t is equal to 1. Here you could see that almost my value was approximately equal to 0, right? And as we keep on going towards this timestamp, which is the last timestamp, you'll be seeing that these words will play a very important role while predicting the next output. Right? So here you'll be able to see that these all values will never be equal to 0, right? It will have some value because this will be creating an impact on this, and this nearest words with respect to the timestamp will be responsible in updating the weights. But some of the weights that are present in t is equal to 1, t is equal to 2, these all values will be approximately equal to 0, and that is what vanishing gradient says. And this is the problem in simple RNN. It is just having a dependency in this entire chain rule. It is having a dependency on the nearest word, not on the farthest word that is available in that entire sentence, right? And this is a major problem. Now, how do we solve this problem? See, instead, I told here we are using sigmoid. The derivative of sigmoid is 0.25. We can also change this to tanh activation function. But again, in tanh you'll be getting a derivative between 0 to 1. But as the chain rule keeps on increasing, the multiplication will keep on happening, and you'll get a smaller value. Okay. So, in order to solve this, you can use other activation functions like ReLU, okay, or leaky ReLU. So this here it makes sure that the derivative is always near to 1. Okay. The other case is that researcher came up with an amazing one more network which is called as LSTM-RNN. Okay. Now this LSTM-RNN solves this problem of long short-term memory, and that is why it is called as long short-term memory RNN. Okay. Not only this, you'll also be seeing along with this, we'll discuss about GRU-RNN. Okay. GRU-RNN. So both this RNN will solve the problems with respect to a simple RNN, and that is what we are going to discuss about in the upcoming videos. But I hope you got an idea, right? If I have a long-term dependency with respect to the sentences, then your simple RNN will not be working well. Right? That is the major problem. And I've also explained you why. Because at time is equal to 50 steps, you could see my chain rule was so big. And when we did just one of the derivative problem statement, when we try to solve it, here you could see that, hey, I'm getting this particular value with respect to weight. So this will be nothing but this will be weight. Over here, we are multiplying with this specific weight, but we are multiplying a smaller value. Okay, smaller value. So I hope you were able to understand this particular video. This was about the problems of RNN. Yes, I'll see you all in the next video where we'll be discussing about LSTM-RNN and GRU-RNN. Thank you. Hello guys, we are going to continue discussion with respect to simple RNN. Now in this particular video, we are going to develop an end-to-end deep learning project using simple RNN. For this, the dataset that I'm actually going to take is something called as IMDb dataset, and this is nothing but it is a movie reviews dataset. Now our main task is that in our dataset you'll be able to see that we'll be having some text and some output labels. Text will be specifically the reviews, and your output label will be having something like positive or negative. Okay. So with the help of simple RNN, what we are basically going to do is that we are going to train this model, and we are going to see that how we can do this specific prediction. And we'll not stop here. We'll also do this entire deployment in the cloud. And for this, I'm also going to perform some trainings in my local machine. Okay. Now, for all those who do not have a powerful machine, you can also go ahead and execute this in Google Colab. Okay. Google Colab. You can go to the Google Colab and you can probably create your model. Okay. Basically train the model, because in Google Colab they even provide you GPUs. Okay. Free GPUs. Free GPUs. And it's not like I'm just taking a very small data set. It will be good number of data. Like over here, 50,000 records will be specifically there. Now, before I go ahead and probably create this end-to-end deep learning project, understand what we are going to do in this deep learning project. Okay. So I have my, first of all, I just draw the architecture. I have my input data. So this is my data set, the reviews data set. We will take this data. We will perform some feature engineering, and we also say it as feature transformation. After we do this, we need to keep ready for this particular data so that it will be ingested in the simple RNN for training the entire neural networks, right? So after this, we will go ahead and build our simple RNN. So we will probably take a simple RNN architecture, we will feed this data, we will train it completely. Once we train it here, we are going to get our model file, which I will be storing it in the form of .h5 file. Okay? .h5 file is nothing but a kind of format, like how in machine learning we use pickle files. Similarly, in deep learning we use, if you're using keras, you can actually convert that into a .h5 file. Okay? Then after this, we will go ahead and create a Streamlit web app, and then we will further do the deployment. Okay? We'll further do the deployment of it. Now, this is the entire fundamental things that we are specifically going to do in this particular project. Okay. Now, the best thing over here is that how do we go ahead and implementing this? Okay. Over here, dataset, feature engineering, Streamlit web app, and deployment. This we obviously have seen even in ANN. The major thing will be training the simple RNN. Now, this simple RNN will definitely have two important components. Okay. I will be talking more about it. One is something called as embedding layer. We also need to use embedding layer over here. Now, what is this embedding layer? We will just talk about in some time. And along with this, we will also use a simple RNN for training our neural network. So both of them we really need to use. Okay. Now, let me just talk more about this embedding layer. What does this exactly mean? As you know, if I just take the simple RNN, okay, you know what is the architecture of simple RNN. So this is my simple RNN over here. And if we just make sure that we unfold this with respect to time, it will look something like this, right? This we have already discussed in our theoretical session. Like this, and it will go on till my last layer. And finally, I'll have my output, and this will probably go to my sigmoid or softmax, and then we get y hat. Okay, so this is the process that we specifically use. But along with this, you know, let's consider any of my text. Let's say in my dataset I have a text, and this is my output. Let's say in this text I have some inputs like x11, x12, x13, x14, and then I have my output over here. It can be 0 or 1. Let's say it is 0. Okay. Similarly, my next sentence will be x21, x22, x23, x24, and this will be 1. And you know, whenever we are doing the forward and the backward propagation with respect to every sentence, we give words by words. Right? Initially we give x11, then in t is equal to 2 we give x12, then x13, then x14. Okay. Now this x11, x12, x13, these are words, right? And we really need to convert these words into vectors. Okay, so here you'll be seeing that we also have to convert these words into vectors with respect to some dimensions, which I will be passing it over here, right? Now, already we have discussed about this architecture. One thing that I never discussed about, specifically in deep learning, how these words are converted into vectors. Okay, and here is what your embedding layer comes into picture. Embedding layer. We have another embedding layer like this. Let's consider it like this. Okay, and this embedding layer is responsible in converting your words into vectors. This embedding layer uses something called as word embeddings. I hope you have some idea about word-to-vec. Word-to-vec is a kind of a word embedding techniques, which we can also specifically use in the embedding layer. Now, in the next video, before we start this entire project, we really need to understand about embedding layer, and that is what we are going to discuss. First of all, we will go ahead and discuss about how does embedding layer work, and then we will try to understand the mathematical intuition. Okay, we'll just try to understand the intuition. Along with this, we will also do some practical implementation, because unless and until we don't know this, right, it will be very difficult to understand the project. So both of this, I will try to cover it up, okay, for you all. So this was just an introduction video about this end-to-end project. Now in our next video, we will talk about word embeddings, embedding layer, and feature representation. What exactly is this feature representation? Okay, so let's go ahead and discuss this in the next video. Thank you. Hello guys, so let us go ahead and continue the discussion with respect to word embedding. Already I gave you an idea, right, where word embedding or embedding layer is specifically used. See, word embedding is a technique which is just converting a word into vectors, and specifically in a neural network, we have to use this as a layer, another layer, like how we have a dense layer, right? Similarly, embedding layer will also be there. And the main work of embedding layer is that it will be using some kind of word embedding technique where it will take an input and it will convert that into vectors. Okay. Now when I'm discussing about this word embedding, and it is also called as feature representation. Okay, what exactly it is? Okay, we will discuss about it, right? Let's say I have a data set, okay, and in this data set, let's say I have text, and this is my output. Now, with respect to this particular text, let's consider that I have some sentence x11, x12, x13, x14. This output is 0. Let's say again you have x21, x22, x23, x24. Then you have this output 1. Similarly, you have a lot of data like this. Okay, available. Okay. Now, as I told you, whenever I need to give any input for my neural network, the LS specifically simple RNN. This is how the representation is, right? With respect to simple RNN, right? From here also. So let's consider that this is my simple RNN. If I want to give any inputs over here, one thing that you really need to understand is that whatever with I of t, whatever I give words with respect to timestamp, I need to convert this into vectors by using some embedding layer. Okay, so I'll try to convert this into some vectors. Now, let me just go ahead and talk about one of the process which is initially it was most commonly used, which is called as one-hot encoding, right? Now, let's say, first of all, if I really want to use some word embedding, okay, it is also called as feature representation. Understand this word, okay? This I will discuss about what exactly is feature representation. Very important thing, okay? So initially, let's say I'll not use word embedding, I'll use some other techniques like one-hot encoding. Let's say we will use some other technique, and we will discuss what is the disadvantage of this particular technique, and then we will go to word embedding. So let's say with the help of first technique that we are going to use is one-hot encoding. Now in one-hot encoding, what happens is that we define a vocabulary size. Vocabulary size is basically the total number of words that you have in this vocabulary. So let's say if I go ahead and say it is 10,000. Okay, so 10,000 words I have. Okay. Now, if I consider one-hot representation, what does this basically mean is that if I have a word something like this, let's say man. In this sentence, I have a word which is called as man, or over here I'll just define man. So every word will be converted based on this one-hot representation. What does this one-hot representation basically say? This man will basically get converted to a vector of 10,000 dimensions. So over here you'll be able to see that this vector that you'll be seeing will be having 10,000 words. And let's say these are like represented somewhere like this, and somewhere like this I have dot, and here I will be having 1, then I'll be having 0, and continuously all 0. Okay. So one-hot representation basically says that in this vocabulary, in whichever index man word is present, that will be 1, and remaining all will be 0. So how we are representing man by one-hot representation, we are basically using this vector vocabulary size. That many number of vectors will be there. Every value will be 0. Only on the index where man is present. Let's say if this is 5,000 index, right? This way we will specifically make this value as 1. So man will be shown in this vector, will be represented using this vector according to one-hot representation. Okay. Similarly, let's say there is also another word which is called as boy. And let's say for boy in this index, boy index in 2000 index, let's say I'll go and write 000 like this up to 1, then 000, then like this up to 0, right? So this size will be 10,000. In the 2000 index, I'm just imagining in the 2000 index boy is present, so that is this word boy is present in this vocabulary, so this value is 1, okay? So this way, the entire one hot representation is basically done for a specific word and it is converted into a vector, right? Now just imagine you're having a word, you're converting this every word into 10,000 dimensions and you're sending it in the form of vectors, which is having zeros and ones, and only at one place there is one and remaining all are zero. So this is really a sparse matrix. This is basically called as a sparse matrix. And what is the problem with this sparse matrix? The problem with this sparse matrix is that whenever we try to use this, it leads to something called as overfitting because you have just zeros and ones. There is no much calculation as such, right? So this is really important for you all to understand how these things are basically taking place, right? So obviously we cannot use one hot representation. It is not an efficient technique, right? Because any number of zeros and ones we have based on the vocabulary size, we are making it so much big, right? Similarly, you can see boy, so many number of words are there, like so many, this one hot representation, you just have zeros and one place you just have one. So not an efficient way to use this, right? And this is what we, in order to overcome this disadvantage, we specifically use something called as word embedding. Now, if you don't know about word-to-vec, I again suggest please go ahead and revise about word-to-vec. Word-to-vec is one type of word embedding technique, and this can also be used in the embedding layer. Now, what does this basically say? Word embedding, what does it say? Okay, and please remember this word called as feature representation. Okay, it creates a feature representation for every word that is available over here in this data set. Okay, what does that basically mean? Let's say in my data set I have some words. Okay, let's say I'll just go ahead and make this like boy. I have something like girl. I have something like king. I have something like queen. Then I have something like apple. Then I have something like mango. Okay, let's consider these all words are there. And again, over here also, my vocabulary sizes, let's consider 10,000. Okay, let's say boy is present in 2000 index, girl is present in 5000 index, king is present in 6000 index. The word in this vocabulary is present in that index. 9000, queen is present, apple you have something like 1000, and mango you may have in 7000. Okay, now let's consider these words. Now I need to convert these words, right? Let's say these are some of the words that I have picked from the first sentence. I'm just considering it. Okay? Now how every word is basically converted into vectors, that we really need to understand with the help of word embedding. If you remember word-to-vec, I've already shown you how word-to-vec is basically trained, right? There is two types, scriptgram is there, CBOW is there. We have already seen how forward propagation, backward propagation will happen. Now in the case of word embedding, in the case of embedding layer, which is using some kind of word embedding, for all these words, first of all, we will go ahead and select some feature representation. Let's say for this, we will go ahead and select some feature representation. And let's say I'll say, hey, in this feature representation, I will take each and every word and I will change this into so many numbers, or I'll represent every word in some dimensions according to this feature representation. So here I will say, let's go ahead and do one thing. Let's take 300 dimension. Okay, let's take 300 dimensions of vector and represent each word in this 300 dimension. Okay, let's represent each word as 300 dimension. Okay, it is very much difficult to understand how the inner working of word-to-vec is, or this word embedding is, because we will not be able to see all the features. But here, let's go ahead and consider that I'm going to represent some features over here. I'll probably use some feature representation and I'll write some words. Okay, that will actually help you to understand. Let's say that I'm going to consider gender over here, one of the feature. Then I'm going to consider royal. Then I'm going to consider age, and then I'm going to consider food. Okay, these are some of the features that I've used. And let's say like this, there are 300 dimensions. More so many words are there till here. Okay. Now, what word embedding does is that based on these features that we have considered, how these features are basically coming up, I've already shown you that in word-to-vec training. Please go ahead and see that. Okay, we are going to train this separately, and this is what is used in the embedding layer. Right now, we're just considering this feature representation, and each word will try to find out the relation between this word and this word, this word and this word, this word and this word, and we'll assign some vectors. Okay. So this boy word will be given by this 300 dimension features or 300 dimension vectors by seeing the relationship between this particular word. Again, let me repeat it. Okay. So here what we're doing is that if we consider this word boy, this boy will be converted into vectors in such a way that we'll try to find out the relationship between all these features, right? And then we'll get one vector value. Let's say one example, I'll say boy to gender. If I write -1, okay, I'll just go ahead and write -1. I'm just assigning some value. Let's say -1. Then girl to gender will be +1 because these are opposite, right? Opposite to boy is girl. So that is the reason I've written -1 and +1. Now, if I see the relationship between royal and boy, we don't say, hey, it is a royal boy or something. So there will be hardly some relationship. So for this, let's say I'll go ahead and write one value, 0.01. Similarly, royal girl can be said royal, so I'll just go ahead and keep some value more than boys. Okay. Now, similarly, if I take king to royal, they say, hey, royal king. So obviously this value will be higher. Let's say 0.95. Okay. If I say, hey, queen to royal, yes, we obviously say queen or royal. Okay. But if I say king to gender, okay, if I see some relation, let's say it is 0.92. Queen to gender, again, I'll go ahead and write 0.92. And again, this will be opposite. Okay. Apple to gender, is there any relationship with respect to gender? So it will be 0.0. Mango to gender, okay, I'll just keep one value 0.1 because there is hardly no relationship. But do we use royal to apple? Do we say royal apple? No. Okay. So it will be 0.02, let's say. And for this, it will be 0.01. I'm putting some values over here based on the relationship, right? So like this, all these values will, with this representation, with this relation, it will be trained and it will be provided a vector. How do we train it? Please go ahead and see my word-to-vec tutorial. There you'll be able to understand it. Okay. Word-to-vec. Okay. It is necessary that you need to understand word-to-vec. Okay. Now this boy is given by these vectors. This is now important for you to understand, right? So whenever I pass boy word over here, first of all, I will give this word to my embedding layer, and my embedding layer, if it is using this 300 dimension, it is just going to convert this into a vector with respect to 300 dimension with all this relationship vector values, okay? Like -1, 0.01 and all. And once we pass this, then only our simple RNN will start getting trained, okay? Now, this is what exactly is all about. So here, there's some important parameters you should remember. One is obviously the vocabulary size. So in this case, I have taken 10,000. The second is what is the features dimension that I really need to use. So feature dimension, let's say I'm using over here as 300. So there is a word-to-vec technique from Google, and there's also a library called Glove, right? This has specifically 300 dimensions, okay? Then these two are the important parameters, and you have to remember this because in the next video, what I'm actually going to do is that I'm going to show you a practical implementation, how word embedding will work. Word embedding layer will work. And this is what we are going to discuss in the next video. And here, I'll just take some examples. and then convert that into vectors before I convert that into vectors with the help of word embedding layer. Okay. Then after that, we will start our end-to-end project. Okay. So yes, this was it from my side. I hope you like this particular video, but I hope you got an idea with respect to word embedding or what exactly is embedding layer or feature representation. I will see you all in the next video. Thank you. So guys, now we are going to continue our discussion with respect to word embedding. Now in this video, we are going to see a practical implementation that how we can use word embedding and convert your word into vectors. Again, before I go ahead, please remember this vocabulary size and feature dimensions because we are also going to use the same thing in our code. Okay, so let's quickly go ahead and open my file. So here is my entire, you can see in ANN classification, I created a folder over here. Similarly, in simple RNN, I will go ahead and create one of my file, which is called as embedding.ipynb. Okay. Now in this embedding, I will first of all go ahead and select our kernel quickly and start our code over here, right? So here you'll be able to see that first. Let me make some code cells, and this is where I'm going to write my code. Okay. Now here also we're going to use this current TensorFlow, so that is the reason in the same VM environment we are going to work. Okay. So here I will go ahead and write from TensorFlow dot keras dot pre-processing dot text. First of all, what I'm actually going to do is that I'm going to perform one hot representation for a specific word. Okay, so that is the reason I will go ahead and import one hot. Okay, so this one hot representation I've already shown you in my previous video how do we specifically do it. Now to try some of the sentences, here are my list of sentences that I'm actually going to use. Okay, so I'll go ahead and execute this particular code with respect to one hot, and these are my sentences: the glass of milk, the glass of juice, the cup of tea. I'm a good boy. I'm a good developer. Understand the meaning of words. Your videos are good. Okay, so these are my set of questions that I'm going to specifically use. So if you go ahead and execute this, now if I go ahead and probably see my sentences, here are all my sentences. Let's say as I said you that we need to define the vocabulary size, and we're going to use this word and probably convert this into vectors. Each and every word you'll be able to see that I'll be able to convert into vectors. Okay. So here my vocabulary size that I'm actually going to consider, it's 10,000. Okay, let's consider 10,000 that I'm actually going to do. Now the first thing that we're going to discuss about is one hot representation for every word. Okay. So I will just go ahead and write for word in sentence. Okay. So first of all, I will just go ahead and write. I'll say for words in sentences because when I'm running through each and every sentence, I'll get each and every sentence itself. So I'm writing words, okay. And for every words that or every sentence that I get, okay, in this specific sentence itself, I will pass it to one underscore hot. And here I'm just going to give two parameters. Okay, please focus on this. I'm going to give two parameters. The first parameter will be my words, what sentence I'm specifically giving, and the second parameter here we're going to focus on the vocabulary size. And this I will try to create as a list representation or list comprehension. Sorry, right? And this will basically give my one hot representation. Now once I write this code, let's go ahead and execute it. Okay. I will just go ahead and execute it. So here you can see vocabulary size is not defined because, okay, I did not execute this code. Okay, now it should get executed. Now if I go ahead and execute it, now see, this is very amazing. Okay, if you remember what were my sentences, if I go ahead and write my sentence, here you can see my first sentence is the glass of milk. The second sentence is the glass of juice. Third sentence is the cup of tea. Here you have I'm a good boy. Now this glass of milk has got converted into this vectors in my 10,000 vocabulary size. Okay, 10,000 vocabulary size. That basically means this the is given by the index 6186, right? Glass is given by the index 6775. Off is basically given by the index 637, right? And milk is basically given by 4895. What does this basically mean? If I expand this off into a vector of dimension, in the 638 index, I will get 1, remaining everything will be 0. Similarly for this particular word, similarly for this particular word. This is what it is basically saying. It is just giving an idea, right? For every word which index, it is just going to be 1. Okay. Now here also you can actually see, this is one hot representation I'm specifically using, but we need to use this in our embedding layer. So we are not going to use that entire vectors where only one is present and remaining all are zeros. We will try to convert all our words based on this index. So every word that you'll be seeing in the sentence is representing one index. Okay. Now once we do this, okay. Now see, observe one thing. I have written the glass of milk and also I have written the glass of juice. Okay. Now, when we write the glass of milk and the glass of juice, okay, it is very much important to see. You'll be able to see all these words are same, all these vectors are same. Only this particular vector is basically changed, right? Because over here I have milk and then I have juice. So that is the reason, and it's a vector, but the index has got changed, right? Now, this is a very important thing that I really want you all to explain, okay? So please focus over here. Now, in word embedding, if you probably see, based on these vectors, okay, based on these vectors, if I take all these vectors, okay, and if I start plotting this, let's say I apply a PCA, PCA basically means principal component analysis, and I convert this 300 dimensions into 2 dimensions. Let's say that I go ahead and do a dimensionality reduction, okay? And if I then plot all these vectors, you'll be seeing, let's say if I have man over here, okay, woman will be somewhere here again, okay, king will be somewhere here, queen will be somewhere here. So here you can actually see the vectors like man and king because they are almost similar kind of vectors. It'll be near to each other. Woman and queen, they are similar kind of vectors. It'll be very close to each other. Similarly, if I go ahead and see with respect to fruits like apple and mango, these all are fruits, right? If you go ahead and see, both these vectors will be very much nearby, right? So this is very much important. That is what it actually mentions. Whenever you have this particular vector, you will be able to find out which vector is near to which one, right? And here only your very important algorithm gets applied, which is called as cosine similarity. One of the amazing use cases that we will be seeing is something called as recommendation system, right? Recommendation system uses this based on this particular vector. If I'm watching an action movie, I should be recommended another action movie, okay? And that is what we are specifically doing. Now I told you there are some problems with respect to one-hot representation, so I'll not directly use that. Instead, I will convert all my words into this particular indexes, okay? And now I will take all these words sentence by sentence and I'll pass it to my embedding layer, and then we will try to convert this into a word embedding representation. So let's go ahead and write this word embedding representation. Very much important, okay? So quickly, let's go ahead and do this. Now in word embedding representation, as I said, right, how we use dense layer. Similarly, there will be one more addition layer, which is called as embedding. So for that, we will go ahead and import for TensorFlow dot keras dot layers. I'm just going to import embedding, okay? Then we have from TensorFlow dot keras dot pre-processing dot oops, okay, let me just go ahead and from TensorFlow dot keras. I'm also going to import one very important library which is called as dot sequence, and we are going to import pad underscore sequence. I'll talk about it why this is really important, okay? Pad underscore sequence, okay? I will talk about it, just wait. But I have imported the embedding layer over here. Along with this, we know that we are going to create a sequential model. So for this, I'll go ahead and write from TensorFlow dot keras dot models import sequential, okay? Now I'm going to use these three important libraries. So I'm actually getting one error saying that, hey, from TensorFlow.keras.processing. So now here you can see, guys, we are getting an error which is called as no module name TensorFlow.keras.preprocessing. Now previously, this preprocessing.sequence was present inside this TensorFlow.keras.processing, but now after seeing the documentation, it has changed. Okay, so I will go ahead and write from TensorFlow.keras. Okay, from TensorFlow.keras.utils. Okay, and here we are just going to go ahead and import my pad sequences. Okay, so we'll just comment this out. It was before in this, but again, whenever you see this kind of error, always refer to the documentation page. Okay, so now I'll go ahead and execute it. This has got executed perfectly. The next step that I'm actually going to probably do is that we will also go ahead and import one important library called as numpy as np. Okay, now first of all, we'll understand what this pad sequences basically mean. Now see, observe each and every sentence. Every sentence is of different number of words. Let's say, okay, first sentence is having 4 words, second sentence is having 4 words. This is also 4 words, but here you have 5 words. Here you have 5 words, and here also you have 5 words. And some of the sentences also have 6 words, 7 words, right? One very important thing is that we need to make all the sentences of equal size. Okay, otherwise we'll not be able to train it in our RNN, because at the end of the day, all the words that will be probably going, it will be going for a fixed number of timestamp based on the sentence size. Okay, so that is the reason what we do is that we import this pad sequences, and what we are going to do with this pad sequence, we will go ahead and set up one maximum sentence length. So here, let me just go ahead and write. Right now, based on our data set, I will just go ahead and set this sentence length to 8. Okay, because I know maximum number of words are 5. So considering this, all the words, all the sentences in this should have a maximum of 8 words. Okay, so I'm just keeping it. We can also keep it to 10. Okay, now I will go ahead and say use this embedded docs or create my new docs where I apply all this pad sequence, because if I want to make this sentence of 8 words, I need to add 3 zeros more, right? So pad sequences does that only. You can add 3 zeros before, or you can add 3 zeros after. So in order to make all the sentences equal. So for this sentence also, I'll say if 4 words are missing, so I'll go ahead and add either 4 zeros in the forward or 4 zeros in the backward. So that will actually become 8 sentences. Similarly, here also I'll try to make it as 8, sorry, not 8 sentences, 8 words. Similarly, I'll also try to make this as 8 words. Similarly, I'll try to see over here what is the length, 5 words. So 3 more zeros, if I add it, you'll be able to see that, okay, it will become 8 words. So that is what pad sequences basically do. Okay, so I will go ahead and use this, and I'll use the one hot representation that I've used. I'll say, hey, go ahead and apply padding, and inside this padding, I'll say, hey, go ahead and do pre-padding. Pre-padding basically means if I want to make the sentence of the same length, I will, how many words are basically remaining out there, that many number of zeros will get added forward, right? And the third parameter that we really need to give is something called as max length. So inside this max length, I'll just go ahead and give my sentence length. Okay, and now let me just go ahead and print my embedded docs. Now this will be lovely, because now you'll be able to see that all my sentences are of equal words. There are 2 ways. One is post, one is pre. So if I do post, I will be getting the zeros at last. If I go ahead and write pre, I will be getting zeros at the first. Okay, so right now I will just go ahead and use this pre. Okay, so I've used my vocabulary size. I've converted all my words into a representation wherein I'm using pad sequences along with that pre, right? And I've converted all the things based on my maximum sentence length. Okay, now is very much important. Now we will talk about feature representation. Okay, feature representation. Now in this feature representation, I'll say, hey, use the dimension 10. That basically means I want 10 features with respect to the dimensions, right? In the word embedding. Okay, over there I showed you in my theoretical intuition, I showed you the maximum example of 300 dimension, but here we're going to use this 10 dimension. Okay, I'll go ahead and execute this. Now let's go ahead and create this model that is embedding layer. So I will go ahead and write model is equal to sequential first of all, and then we will go ahead and add model.add one embedding layer. How do I add my embedding layer? I'll just say embedding. Now inside this embedding layer, there are some parameters that we need to give. One is my vocabulary size. Second is my dimension, how many dimension I want, and third is nothing but my input underscore length, which is equal to your sentence underscore length. This is just to give you the maximum length. Okay, and this is my model with respect to the embedding layer. Now along with this, I will go ahead and say, hey, I want to probably train with this entire. See, I'm showing how you can also train your entire embedding layer, right? So I'll say, hey, model.compile. I'll use the optimizer which is called as Adam. Along with this, I will go ahead and use my loss function, which is nothing but MSC. Okay, done. Now if I go ahead and execute this, okay, so this is what it has got executed. Now I'll go ahead and see my model summary. So this is my embedding model, right? I have this many number of parameters. This many number of params are there because my vocabulary size is 10,000. Okay, and then you have this 8, 10. Okay, so this is perfect. Now this is my model. Now I will just go ahead and use this model. I'm not trained it. See, I've used this embedding layer. So embedding already is a class over here. Now, if I pass any words, right, you'll be able to see that how it will be converting into a vector. So now what I will do, I will take this embedding layer. I will go ahead and write model.predict, and let's go ahead and give my embedded docs, all the embedded docs. And this is what is very amazing. Every word will be represented by how many number of dimension? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, 10 dimensions, right? And if I just get the first sentence, okay, so my first sentence, what is my first sentence if I probably see over here, right? So let's go ahead and write it this way. Then you'll be able to understand. I'll go ahead and write embedded docs of 0. So this is my first sentence. Okay. Now I will just go ahead and predict for the first sentence what my embedding layer will basically be giving me as a vector representation. Obviously it needs to be 10 dimension. So embedded docs of 0. Okay. 0 of 0. Perfect. Okay. 0 of 0 is not working because this I'm getting as an array. Then this is my first sentence. So what you can see over here, this entire sentence has got converted to this. Okay. Then my second sentence, where only the last word is changing, has got converted to this. So that basically means this 0 is got converted to this 0 is got converted to this 0 is converted to this particular vector, this 0 is converted into this vector, this index is converted into this vector. So here you can actually see all these vectors, right? And that is how your entire embedding layer works. Okay, please see this. We don't even have to train anything. I've used the embedding layer internally. I think so. It is using word to vec. Here it takes vocabulary size input, then it takes the dimension, then it takes the input length. Now this is something really important because in my next video, I'm going to start our end-to-end project, and I'm going to take a very much bigger data set, and this embedding layer will be a part of that simple RNN, right? But I hope you got an idea with respect to working with embedding layer. So yes, this was it. And you can proceed further and you can go ahead and practice with different text. You can go ahead and write more text over here. And because these all steps will follow over there, you can add any number of sentences, you can verify, right? So yes, this was it. I will see you all in the next video. Thank you. Hello guys, so we are going to continue our discussion with respect to our end-to-end deep learning project using simple RNN. So already in my previous video, I've already shown you how to actually use embedding layer Now let's go ahead step by step and see like what kind of deep learning project we are implementing with the help of simple RNN. And as I've already told you, I'm going to use the IMDb dataset and we are just going to do the text classification using simple RNN. So let's go ahead and first of all, I will quickly use the same environment. You will be able to see that over here I have my simple RNN folder with ANN classification, what requirement.txt was there, what virtual environment was there. We're going to use that same thing. Okay. So here's my ANN classification folder. Here's my simple RNN. And similarly, I'll keep on creating all the other projects as we go ahead, like LSTM RNN or GRU or any other further variants of RNN we are going to see. Everything will be creating folder wise. Okay. So first of all, I will go ahead and select my kernel. Okay. Here I'm going to import numpy as np. Okay. np. Let's execute this and see it's working fine. Then along with this, we are also going to import TensorFlow as TF. Here also we're going to use TensorFlow and Keras. Then, as you all know, this IMDb dataset is available inside the TensorFlow. For that, we can actually load that particular dataset directly from there. So let's go ahead and import that also. So if I go ahead and write from TensorFlow.keras.datasets, I'm going to import IMDb. Okay. Then I'm going to basically write from TensorFlow.keras.preprocessing. As I said that I can also use this preprocessing. Okay. Preprocessing import sequence. Okay, so I'm going to import the sequence. I'll talk about it, why we'll be using the sequence and all, but you can just imagine that this is a kind of a pre-processing technique that we really need to use. Then from TensorFlow.keras.models, I'm going to specifically import sequential. Sequential is must for any type of neural network that we're going to use. Then from TensorFlow.keras.layers, I'm going to import embedding. Along with the embedding, I'm going to use simple RNN. Okay. And then we'll also use another layer which is called as dense. Now, usually with the help of ANN, we usually use this dense layer, right, where we create the hidden layers, where we create the hidden nodes. With the help of simple RNN, we'll be creating the RNN nodes, right? And this embedding is basically for your embedding layer. So let's go ahead and import this. So this has got successfully imported. Now I'm just going to go ahead and import my IMDb, which I've actually done it over here. Now let's load the IMDb dataset. So here you'll be able to see I will be loading the IMDb dataset. So first of all, I'll just go ahead and use my max features. This max feature is just like your vocabulary size, right? So here I'll go ahead and first of all write my vocabulary size. I'm basically initializing my vocabulary size. Perfect. Then I will just go ahead and create my x_train, comma y_train values. Okay, I will talk about this particular dataset in depth. Okay, what kind of dataset is given, everything I'll be talking about. Then along with this, I will go ahead and write x_text, comma y_text. And if you go ahead and write this IMDb dot load data, okay, and I'll say based on how many number of words, what is my vocabulary size, right? So that is nothing my max features. So once I give this, I will be able to print the shape of my training and test data. Okay, so here I will just go ahead and execute it. So I'll say, hey, go ahead and print the X test shape just to make you understand how many records we are actually playing up with, right? So here you'll be able to see that it will be downloading this entire dataset, and the training data shape is 25,000 records. Okay, so this will get downloaded in your local, and it will be staying in the cache memory itself. Then here you have your testing data, which is again 25,000 records. Okay, similarly for this particular sentence, you have these labels, right? It can be positive or negative. Now let's do one thing. Let's go ahead and explore this kind of sample reviews, what is there inside it, and what kind of labels is specifically present. Okay, so we will just go ahead and inspect sample review and its label. Okay, so here I'm going to write sample review is equal to x_train of 0. Okay, so if I'm taking x_train of 0, let's see first of all what is there in my x train and what is there in my x test. Okay, so in x train you'll be able to see x train of 0. In my first sentence I have this kind of words, and you remember this kind of words, when do we get it? I have already shown you with respect to the embedding layer, right? So if you go ahead and open this, here also you could see in every sentence I was getting this kind of words, right? So in short, this is nothing but it is a one-hot representation of every word, right? When I say one-hot representation, here you are able to see the index, right? So this is one sentence, okay, and as you know my vocabulary size is 10,000, so based on that you'll be seeing different index, and each index represents one word. Okay, so this is what you can actually get it. Okay, so I'm going to take this as a sample review. Okay, and let's see y of train of 0, y_train of 0. This will basically be 0 or 1. Okay, so here you can see it is 1. Okay, it can be 0 or it can be 1. 1 basically means, says that it is a positive sentiment, 0 basically means it says a negative sentiment. Okay, so I will also go ahead and take my sample_label. Okay, and then I will go ahead and write y_train of 0. Now you might be thinking, Krish, how did we get this direct vectors, right? How do we get this indexes directly? This data set is put up in that way, but I will decode this and I'll try to show you what exactly is the real sentence also. Okay, now let's go ahead and print this. So I will go ahead and print. Okay, I'll say, hey, this is my sample review as integers. Okay, and here I'm going to specifically use this as my sample review. Okay, I'm just printing it. Similarly, we'll go ahead and print my sample label. Okay, so once I print both of them, you can see this is my sample review as integers. This is my entire sentence, and it is like very, very big, right? So that many number of sentence length is quite big, I guess. Okay, and the sample label is 1. Now let's do one thing. Okay, let's mapping of word index back to words. We need to do this. Okay, we will try to convert this just for our understanding. Okay, how do I do that? Okay, that we will try to see. So here I'm going to basically use word_index is equal to, I'll say, hey, go and use this IMDb, and I'll say, hey, get all the word index. How many word index are there? You just get it. Okay, so once I execute this, I will be able to see my word index. So this will basically be my word index. For this particular word, you'll be seeing this is the index. For this word, it is this index. For Nunari, this is this index. For Javani, all these words, I'm actually seeing the indexes. Okay, now what I will do, now as you know, this word index is an dictionary, right? It is obviously a dictionary. What I will do, I will try to reverse. See, I can also reverse this word index. Okay, I can basically write first of all index information, and then I can go ahead and write this particular value. Okay, so for this, I will just go ahead and write this code. Please focus on this, and this is where dictionary comprehension will also come into picture. So here, what I'm saying, for key comma value in word_index.iterms. Okay, and then I'm saying, hey, write like this: value colon key for key, value colon key. Right. So value. So this is basically just getting reversed. Okay. So now, in order to see the reverse word index, I can also go ahead and print it if you want. So I will go ahead and print it, and this also will be able to see it. See. Let's see, where did it go? Okay, I will just try to print in this way. Just a second. Instead of using print, I will just use this. Let me comment this out. So this is how it is reversed. Okay. Now, what we are going to do is that we are going to probably from this particular keys, or from this particular keys, I'm trying to get all my reviews. Like let's say I'll consider this particular sample review. I'll get all my words. So 1 is over here. So for 1, what will be the word? We'll try to see. Then I have 14 over here. Then for 14, what is the word I'll try to see? Okay. So when I check the documentation with respect to the TensorFlow, this was the code that is used. Okay. So here I'm saying reverse underscore word underscore get index. Okay. Over here, it is saying dot get I minus 3 comma question mark for I in sample review. See what it is doing. First of all, I'm going through each and every words in that sample review. Then it is taking this particular I. Right. So here you can see for I in sample underscore review. So first index I got whatever index. Then over here I'm writing I minus 3. Okay. I minus 3. We're trying to get that specific index value. If you're not getting that index value, it will be just replaced by question mark. Okay. Now if I go ahead and see this decoded review, you'll be able to see this. See, initially I got question mark. It was 1. 1 minus 3 is minus 2. So when we are trying to search for minus 2 index, I'm not getting any value, so it is replaced by question mark. Then it shows this frame was just brilliant. So and so all the information is over here. This frame was just brilliant. Casting location, scenery, story, direction, everyone really suited that part. They played, and you could just imagine being the robot, and all this information is specifically there. So this is nothing but this is my decoded review, right? So initially this was my entire sample review, and we had completely decoded it over here. And this is just one sentence along with the text. Okay. So this is just to give you an idea from where this exactly sentence is coming. But for our sake, this step is already done. We are able to get this particular 100 representation index. We'll directly go ahead and use it. Just for your understanding, I've actually given over here. Okay. Perfect. So this was one of the basic information. What we did is that we loaded the data, we did all the things and all. Okay. Now let me just go ahead and use this from text from TensorFlow. If you remember, we have also imported something called a sequence, right, in pre-processing. Now, why the sequence will be very much necessary? Because here we are going to do the padding sequence. Padding sequence has been done by in embedding. Also, I showed you, right, how to do the padding sequence. We can use this padding underscore sequences, right? We can use pre and post. I'll also show you one example with respect to the sequences. Let's say the maximum length of my sentence, I'm just going to take it as 500. Okay, that can be the maximum text probably that I can have in my sentences. Now I'll go ahead and write x underscore train is equal to sequence dot pad underscore sequence, and here I'm going to basically write x underscore train comma max length is nothing but it is equal to this max length. So that's it's just like we are trying to apply pre-padding, right, by using this pad sequence. Similarly for x test, I can go ahead and write something like this. Okay, sequence dot this will basically be my x test. Okay, and let's say this is my x test. Okay, and here also I can go ahead and write my max underscore length. Okay, let's go ahead and display my x train now. So x train max underscore length max. Okay, here my feature is max underscore length. Okay, again I'm getting an error. Max underscore length. Okay, this should be okay. I made one mistake. This parameter is max length. Okay, so once it is got executed, here you can see by default it is done that pre-padding. Okay, pre-padding before zeros are basically coming up. So if I go ahead and see x train of 0, x underscore train of 0, here is what I'm actually able to get. See, initially all I'm getting is zeros, and then I am specifically getting all these values at the end. So pre-padding technique is basically applied. So this step is also done. Okay, now in the next step we will go ahead and design our simple RNN. We will train our simple RNN, and this is what we are basically going to see in the next video. Till here we have kept all the transformation technique that is required, and we are ready to probably use this entire inputs for training our simple RNN. So yes, I will see you all in the next video. Thank you.